In episode 38 of the SOC Level 2 training series, we're going to begin the malware analysis module that is inside of the SOC Level 2 pathway of TryHackMe, and the very first room and the first video in this series is going to be the x86 architecture overview. And this is the full overview of the malware analysis module as we have it here. So we'll be going through x86 architecture overview, x86 assembly crash course, Windows internals, dissecting PE headers, basic static analysis, MalBuster, advanced static analysis, basic dynamic analysis, and then dynamic analysis debugging, anti-reverse engineering, and finally MalDoc static analysis. And that will be the very end of the SOC Level 2 pathway in TryHackMe. That's actually pretty much the full path itself that we have gone through for this entire training series. So when you go through this playlist, this video is going to be the part of the full playlist. When you actually go through the playlist, you're going to get to see all of the previous episodes that came prior to this one, including these modules that you see right here. And this is it. The malware analysis one is the last one. So I am very excited to actually wrap this up so that we can move on to other courses and other series of content. And I hope you're excited about it as well. I think this is going to be a really good way to wrap this whole thing up. Now, the overview of the x86 architecture is going to be obviously the introduction to what we're going to be talking about: CPU architecture overview, registers continued, memory overview, stack layout, and then there will be some conclusions, kind of like a review, final thoughts, and you will be dismissed for the day. And that's pretty much all we got for the videos outlined for today. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@hankhackshackers/join, and you'll be able to join Hackaholics Anonymous. Now, without further ado, let us jump into x86 architecture overview. The reason for this room is to understand what x86 architecture actually is so that we can understand how malware can attack it. So essentially, the point of malware is to abuse the way that systems are designed. And to be able to understand how malware works, you need to really understand how the system is actually set up, or what the architecture of the system is going to be. Now, for all disclosures in front right here, there is literally so much about x86 architecture that we can talk about, but we're not going to, because we're strictly going to be talking about this type of architecture from a malware analysis point of view, because I could make probably an entire series of videos around x86 architecture. So we're looking at it strictly from the point of view of malware analysis, and that's essentially the purpose of this entire video. So the objectives that we have are the overview of CPU architecture and the components, the different types of CPU registers and their usage, memory layout as viewed by a program, stack layout, and stack registers. And that's pretty much it. The prerequisites, in my opinion, would be everything that we did in SOC Level 1. So if you've never done SOC Level 1, you should do SOC Level 1, obviously. And everything that we've done up until this point in SOC Level 2 pretty much sets us up for this specific video and the entire module of malware analysis. So I can imagine how people kind of would jump into this video by kind of finding it randomly on YouTube or something like that. For the most part, the people that watch these specific series of videos for TryHackMe are actually trying to complete the rooms inside of TryHackMe. So if that's you, then you've already done everything up until this point, and now you're just looking to go through this. This is actually one of the free rooms as well. So you may be one of those people who actually has a free subscription with TryHackMe, and you're just trying to go through all of the free rooms that they have. And if that's the case, then most likely there's a lot of the rooms that require a subscription inside of SOC Level 2 that you have not completed because you don't have a subscription and you only have a free subscription. So that could be another category of user or viewer. But for the most part, I think the people that are here right now actually do have a paid membership to TryHackMe, and they're just trying to complete SOC level 2. In either case, no matter who you are or where you're from, what experience level you're at, welcome. Thank you so much for being here, and I sincerely hope that you actually get value out of this video. So let's jump into the CPU architecture overview. When we talk about CPU architecture, or when you hear the phrase CPU architecture, it's most widely used or derived from the von Neumann architecture. So everything that we talk about in the modern era is kind of derived from this overview or this original architecture from von Neumann. And this is what it looks like as the layout, like the visual layout is concerned. You have the CPU registers, which are connected to the arithmetic logic unit, which is connected to the control unit and the main RAM, the main memory. And then the arithmetic logic unit is also connected to the input output devices, for example, the keyboard and the mouse, etc. And this is the main overview of this thing. So what it looks like, and we can break down obviously what all of these things are going to be, but the diagram that we just saw has three components, right? It has the arithmetic logic unit and the control unit and the registers. And the CPU interacts with memory and the input output devices outside of the CPU. So this is what each one of those things are. The control unit gets instructions from the main memory, depicted here outside of the CPU. So we have the control unit, right? This piece right here. And it receives from the main memory, and it receives it from the arithmetic logic unit, which is receiving its data from the input output devices as well as the registers. The address to the next instruction to execute is stored in a register called the instruction pointer, or IP, very different from the Internet Protocol. So in 32-bit systems, this register is called the EIP, and in 64, it's called the RIP, not to be confused with rest in peace. So IP in this particular context is the instruction pointer. It's not Internet Protocol, because IP addresses would be Internet Protocol addresses. And then we have in 32 bits, also known as EIP, and then in 64 bits, they're known as XIP, and we're technically talking about the 86-bit right now. So arithmetic logic unit is the unit that executes the instruction fetched from the memory. The result of the executed instruction are then stored in either the register or the memory itself. Then the registers are the CPU's storage. They're generally much smaller than the main memory, which is outside of the CPU, and they help save time in executing instructions by placing important data in direct access to the CPU. So instead of having to pull it from the memory and then process it, it just pulls immediately from the register to be able to save time. And these are typically smaller in size. The data units that are being pulled from registers are typically smaller in size than the stuff that's being stored in main memory, and they're much more critical to the overall operation of the system instead of the things that might be in main memory that might have to do with applications or ancillary services. The stuff that's inside of registers is typically much more critical and foundational. We can call it kind of the framework or the foundation that everything else is stacked upon. Then we have the memory, also known as main memory or random access memory, which contains all the code and data for a program to run. When a user executes a program, its code and data are loaded into the memory from where the CPU accesses it one instruction at a time. And input-output devices are everything else. So these could be the keyboard, the mouse, displays, printers, mass storage devices like a hard disk or USB external devices. And when a program has to be executed, it's loaded into the memory. From there, the control unit fetches one instruction at a time using the instruction pointer register, and the arithmetic logic unit executes it. The results are stored in either the registers or the memory. So when a program is to be executed, it's loaded into the memory. From there, the control unit, the CU, fetches one instruction at a time using a specific register, meaning the instruction pointer register, and the arithmetic logic unit executes it. So once the program's been executed and it's inside of the memory, the control unit fetches the instructions and the arithmetic unit executes it. and the results are stored in either the register or the memory. So in which part of the von Neumann architecture are the code and data required for a program to run? And that would be the memory. And what part of the CPU stores small amounts of data? And that would be the registry, or registry, right? Registry, like that? No. Registry? No. What? Hold on. It's literally right here. Or registers. Registers. There we go. In which unit are arithmetic operations performed? And the arithmetic operations are done inside of our arithmetic logic unit, as the name itself implies. So arithmetic logic unit. And those are all the questions. Okay, cool. Let's jump into the registers overview. As we understood in the overall overview of the architecture, registers are the storage medium for the CPU, and the CPU can access data from the registers quicker than the other storage mediums, but it's also limited in size, meaning that whatever is inside of the register actually has to be, that space needs to be used effectively, and you can't store things that are not absolutely critical to the system's operation and the foundation of the system. The only stuff that goes in here are the foundational stuff. So they're divided into different types. You have the instruction pointer, general purpose registers, status flag registers, and segment registers. And typically the names of these things can actually tell you a lot about what their purposes are. The instruction pointer is a register that contains the address of the next instruction to be executed by the CPU. It's also called the program counter. It was originally a 16-bit register in Intel 8086, from where the term x86 originated, and it was abbreviated as IP, the instruction pointer. In 32-bit processors, the instruction pointer became a 32-bit register called the EIP, or the extended instruction pointer. And in 64-bit systems, this register became the 64-bit register called the RIP, and this stands for register instruction pointer. So earlier I was actually mistaken, so I apologize. I know the comments are going to come for me, but essentially when I was saying that x86 is an 86-bit, I was actually incorrect. x86 was the very original 16-bit, and then from there was a 32-bit, and then there was a 64-bit. So my bad. I understand that you guys are going to come for me in the comments. If you make it to this part of the video, you will see that I have corrected myself. If not, then you can just go nuts in the comment section, as you normally do. General purpose registers are, in an x86 system, there are all 32-bit registers. As the name suggests, these are used during the general execution of instructions by the CPU. In 64-bit systems, the registers are extended as 64-bit registers, and they contain the following. EAX, now this is going to be a long list of stuff that we're going to go through. So all of these things are going to be inside of that this last piece right here, which is the general purpose registers right here. So we have EAX or RAX, and this is the accumulator register. Results of arithmetic operations are often stored in this register. In 32-bit systems, a 32-bit EAX register is present, while in a 64-bit system, RAX register is present in 64s. The last 16-bit of this can be accessed by addressing the AX. Similarly, it can also be addressed in 8 bits by using the AL for the lower 8 bits and the AH for the higher 8 bits. And then you can see that here. So this is essentially what we have right here. So you have RAX, RBX. Let's see if I can zoom in a little bit for you. So you have EAX, and then you have RAX, which is the full thing right here. And this will be 8 bits right here. This would be 8 bits. So in total, we have 16. Then we have RBX, EBX, and then we have RCX, ECX, RDX, EDX. And essentially, the pattern is very similar, as you can see right here. So half is dedicated to one section. This other half is split between these 3 right here. And then we'll be discussing all the other ones as well, but just to give you kind of the visual in advance. And then we have the ESI, RSI, EDI, RDI, EBP, RBP, and then ESP, RSP. So you can see the patterns. So the first one that we talked about was the EAX and RAX. And as you can see from the visual, then you have the RAX, which is dedicated to the full piece. And then you have the EAX, which is the last 16 bits that can be addressed by using the AX, or excuse me, the last 16 bits right here are the AX right here, and then we have 16 bits right here. So the total thing would be 32 bits. Again, my bad. So the total thing right here is 32 bits. The last 16 are the AX piece right here. This section, this half right here, would be a 32-bit section, and this section would be another 32-bit section. So that's what we have over there. Then we have EBX or RBX, which is the second line that we see right here. It's also called the base register, which often is used to store the base address for referencing an offset similar to EAX, RAX. It can be addressed as a 64-bit, 32-bit EBX, and 16-bit BX, and an 8-bit BH and BL registers, which you can see right here. So full thing is 64. This half would be 32, this half would be 32, and then these last 16 bits are split between the BHBL, which is considered the BX portion of it. Then we have ECX or RCX, as you can see right here. The patterns for these ones that ends with the X are very similar. So ECX, RCX is also called the counter register, and it's often used in counting operations such as loops. Similar to the above two registers, it can be addressed in the format that we had previously. EDX, RDX is also known as the data register, and it's often used in multiplication division operations similar to the above registers. It can be addressed as 64-bit, etc., etc. And then we get to ESP, RSP, which is actually, is this even listed here? Oh, right here. So ESP, RSP is the last piece right here. So ESP RSP is the stack pointer. It points to the top of the stack and is used in conjunction with stack segment register. It's a 32-bit register called the ESP, and then a 32-bit system. Excuse me, it is a 32-bit register called ESP in a 32-bit system, and a 64-bit register called RSP in a 64-bit system. It cannot be addressed as smaller registers, as we saw previously over here. Then we have EBP, RBP, which I'm guessing it would just go, now it's going from the bottom up right here. So EBP, RBP, also known as the base pointer, it's used to access parameters passed by the stack. It's also used in conjunction with the stack segment register, which is the one right above it. It's 32-bit called EBP in a 32-bit system, and 64-bit called RBP in a 64-bit system. ESI or RSI, which is the actually, so I guess we're not going in order. So ESI, RSI would be the top one in that 4 segments at the bottom. It's called the source index register. It's used for string operations, and it's used with data segment register as an offset. It's a 32-bit register called ESI in 32-bit systems, and a 64-bit register called RSI in 64-bit systems. Then we have EDI or RDI, called the destination index register, and it's also used for string operations. It's used with the extra segment register as an offset in 32-bit systems. It's called EDI in 32-bit, and a 64-bit register is called RDI in 64-bit systems. Then we have R8 and R15, which actually are not even in this list or in this image, as we can see right here. They don't even exist over there. So R8 and R15, these 64-bit general purpose registers are not present in 32-bit systems. They were introduced in the 64-bit systems. They're also addressable in 32-bit, 16-bit, and 8-bit modes. For example, the R8 register, we can use the R8D for lower 32-bit addressing, R8W for lower 16-bit addressing, and R8B for lower 8-bit addressing. The suffix D stands for double word, W stands for word, and B stands for byte in the outline that we just saw right here. So this sounds like more recent compared to these various other types that we can see over here, and it's very specific to 64-bit systems, although it can kind of revert back to 32-bit, 16-bit, and 18-bit or 8-bit modes, excuse me. So which register holds the address to the next instruction that is to be executed? And that would be the instruction pointer, right, that we saw at the very, very top. So if it's asking for instructions, it is most likely the instruction pointer. Which register in a 32-bit system is also called the counter register. So to kind of speed up the process, we're just going to look for that. And that would be ECX or RCX. So let's go back down here and let's try, I would say any of them, right? Either of them would work great. Which register from the one discussed are not present in a 32-bit system? And that was the last one right here that we have, the R8-R15. is not present. So that would be the one that's only present in 64-bit. So let's continue with the remaining register types because we only have discussed 2 so far. Status flag registers come in when you're performing execution and indication about the status of the execution is required. This is where the status flag actually shines. It's a single 32-bit register for 32-bit systems called the E flags, which is extended to 64 bits for 64-bit systems, and is called R flags in the 64-bit system. The status flags register consists of individual single-bit flags that can be either 1 or 0. Some of the necessary flags are here. So we have the 0 flag denoted by ZF, and it indicates when the result of the last executed instruction was 0. For example, if an instruction is executed that subtracts a RAX from itself, the result will be 0. In this situation, ZF will be set to 1. So the 0 flag would be set to 1, meaning true, right? So it's actually set. So it is technically a 0 flag, but to set the flag, you would either have a 0 or a 1. And if the instruction is to be executed that subtracts something from itself, that would be the flag being set to 1. Then we have the carry flag. The carry flag is denoted by CF, and it indicates the last executed instruction resulted in a number too big or too small for the destination. So if we add this piece right here and this piece and store the result in a 32-bit register, the result will be too big for the register. In this case, CF will be set to 1. So if carry flag is set, that means that the result is too big for the register, right? Sign flag, or SF, indicates if the result of an operation is negative or the most significant bit is set to 1. If these are met, the SF is set to 1. Otherwise, it is set to 0. Trap flag, also known as TF, indicates if the processor is in debugging mode. When TF is set, the CPU will execute one instruction at a time for debugging purposes. This can be used by malware to identify if they're being run in a debugger. So if it notices that the trap flag is set, the malware can detect that it's being run in a debugging kind of a situation. So general registers, they're segment registers, status registers, and instruction pointers. So you have the general register. Its segment register would be CS, E flags, and an EIP, RIP. You are not required to memorize this. People who are extremely detail-oriented and are very, very great at memorization will probably memorize this. You will most likely use it as a cheat sheet, and I can guarantee you I am not going to memorize this because I don't plan on memorizing it. For the most part, a lot of these things are going to be done by tools for us anyways. We just need to understand the philosophies and the concepts, the principles that are making those specific tools useful as we go along with the rest of the module for malware analysis. So it's just good to know that there is something like this that does exist, and if you ever really needed to understand it, you can always go ahead and kind of take the entire contents of this particular section, go to your favorite AI and be like, hey, breaks this down for me in layman's terms and help me understand why these things are important. We are now moving on to segment registers, which are 16-bit registers that convert the flat memory space into different segments for easier addressing. There are 6 segment registers. We have the code segment, which points to the code section in the memory. Data segment points to the program's data section. Stack segment points to the program's stack in the memory. And extra segments, ES, FS, and GS, point to different data sections. These and the DS register, the data section, the data flag, I guess, divide the program's memory into 4 distinct datas. So we have the DS register, which was up here from what I remember, or maybe it was in a previous one. But I do remember that the DS was specific to data. So because it is specific to data, obviously it would deal with the extra segments that are also pointing to different data sections. So which flag is used by the program to identify if it is being run in a debugger, and that would be the trap flag. Which flag will be set when the most significant bit in an operation is set to 1, and by doing a search for significant bit, we find the sign flag. So the sign flag would be the answer for this one. which segment register contains the pointer to the code section in the memory, and that would be the code register, or the code, it's definitely the code segment, I want to say. And code segment is the answer, so it's not the code register, it's the code segment. Okay, so let's talk about memory. When a program is loaded into the memory in a Windows OS, it sees an abstracted view of the memory, meaning it only has access to the memory that is assigned to it. It's going to have access to its own memory. It's not going to have access to the full memory because it doesn't need access to the full memory. It just needs access to its own memory so that it can operate. We're not going to go through how the OS actually performs abstraction, but we will look at the memory as a program actually sees it, and that's actually more relevant to what we're talking about when it comes down to reverse engineering malware. The diagram that we're looking at is the typical memory layout for a program. Memory is divided into 4 segments: the stack, heap, code, and data. And while we have shown the 4 sections in this specific order, it can be different from how they will be at the time or all the time. The code section can be below the data section, for example. So this is what we have. We have the stack, heap, code, and data. And the stack is at the top, heap would be second, code, and then the data itself. And obviously the code is the largest portion, and then you have these various elements inside of it. So starting from the code, because it is the largest portion. So contains the program's code. Specifically, this section refers to the text section in a portable executable file, which includes instructions executed by the CPU. This section of the memory has execute permissions, excuse me, meaning that the CPU can execute the data in this section of the program memory. So this is a very important one, and for the most part, when malware is designed, it's typically, from what I understand here, I reserve the right to be wrong here, but this is the part that has execute permissions, right? So that would be the part that you would want to inject your poisonous code so that it runs because it actually has permission to run. The data section contains initialized data that is not variable and it remains constant. It refers to the data section in a portable executable file. It often contains global variables and other data that are not supposed to change during the program's execution. The heap, also known as dynamic memory, contains variables and data created and destroyed during the program's execution. So when a variable is created, the memory is allocated for that at runtime, and the variable is deleted, the memory is freed, hence dynamic. Then we have the stack. This is one of the more important parts of the memory from a malware analysis point of view. This section of the memory contains local variables, arguments passed on to the program, and return address of the parent process that called the program. Since the return address is related to the control flow of the CPU's instructions, the stack is often targeted by malware to hijack the control flow. So, as I reserved earlier the right to be wrong, the stack apparently is the main target by malware to hijack the control flow. You can look at the buffer overflows room to learn how this happens, and we'll cover more details about it. I think I've actually done a video on buffer overflows. Let's see if the room has been completed. And we can see that it has not been completed because it has a progress of 0%. So we will most likely run into this at some other points in our educational journey. I don't think it's a part of the SOC level 2 path, so we will definitely run across it some other time. But if you have access to TryHackMe, you can always go and try to find the buffer overflows room if you want to get a good idea of what this is. And it is actually a subscriber only room, so you do need a paid subscription for it. But you can always just Google or talk to GPT or Gemini or Meta AI or whatever your favorite AI is, and see what it can teach you about buffer overflows. But at some point in the future, I promise you there will be a video on buffer overflows, because I am going to create a video on every single one of the rooms inside of TryHackMe. So when a program is loaded into memory, does it have a full view of the system? And that would be no. It just has access to the memory that's assigned to the program itself. Which section of the memory contains the code? And that's the code section. Which memory section contains information related to the program's control flow? And that was the last one that we talked about right here, which is the stack section. And that's the most important one that actually ends up being manipulated by malware. Now we're going to look at stack layout, and we actually have a a site that we're going to open up to be able to pull this off. So first we're going to read through it, and then we'll open the site and see what's up. As we already discussed, the stack is the portion that is targeted by malware to hijack the control flow of the program. The stack is the part of the memory of the program that contains the arguments that are passed to it, the local variables, and the program's control flow. It's very important regarding malware analysis and reverse engineering. So we need to understand its layout and its working. The last in, first out is what the stack is for. So it's the last in, first out memory. This means that the last element that's pushed onto the stack is the first one to be popped out. So for example, if we push A, B, and C onto the stack, when we pop these things out, we will be pushing it in reverse order, C, B, and then A. So the CPU uses two registers to keep track of the stack. One is the stack pointer, the ESP or RSP, and the other is the base pointer, the EBP and the RBP. So these are the elements that are used to control or to keep track of the elements that are being pushed onto the stack. So last in, first out. Just keep that in mind, right? LIFO or LIFO, however you want to remember it. The stack pointer points to the top of the stack. When any new element is pushed on the stack, the location of the stack pointer changes to consider the new element that we pushed on the stack. Similarly, when an element is popped off the stack pointer adjusts itself to reflect the change. So it's the stack pointer itself is going to the top of the stack. The base pointer is going to the bottom of the stack, right? So whatever is left at the bottom. This is the reference address where the current program stack tracks its local variables and arguments. The old base pointer and the return address are a big piece of this as well. So let's see what this visual gives to us here. So we have the stack frame for the caller, and then the stack frame for the callee, and it has high to low, argument 1, argument 2, return address, saved EBP, local variable 1, 2, and 3, argument 1, 2, return address, same. So pretty much the same thing. This, I'm assuming, would be the top of the segment, and then this would be the bottom. So this would be the stack pointer, and everything else below this specific piece would be considered the base pointer's job. And let's see if I'm actually right. So the ESP or the EBP, RBP, so ESP or RSP is the stack pointer, and then EBP, RBP would be the base pointer. So we have ESP, which is the stack pointer right here, and then EBP, which would be the base pointer. So it's actually the reverse of what I talked about. So again, I reserve the right to be corrected throughout this whole thing. I try to make deductions based on what I've read, but then I am corrected and humbled very, very quickly. So the ESP is for the stack pointer, the EBP is for the base pointer, but the ESP is controlling the most recent thing that was added to it. Okay, so keep that in mind. It points to the top of the stack is what the stack pointer is. And this is what's confusing about it, right? So if it points to the top of the stack, why is it at the bottom of the image, right? That's the thing that kind of confused me. When any new element is pushed on it, the location of the stack pointer changes to consider the new element that was pushed on the stack. Similarly, when an element is popped off, the adjustment is made, and then the base pointer is remaining constant. And this is the reference address when the current program stack tracks its local variables and arguments. So anyways, the old base pointer and return address. So we can talk about this right here, the return address, and I would guess that this would be the old base pointer. Below the base pointer lies the old base pointer of the calling program, the program that calls the current program. And below the old base pointer lies the return address, where the instruction pointer will return once the current program execution ends. So keep this in mind. This is below, or excuse me, this technically is below this. So even though it looks like from like a normal view of a human being, argument is at the top of the thing, technically argument is at the bottom of this whole thing. This is the top of the thing, which means that the return address is below the EBP right here. So below the old base pointer lies the return address, where the instruction pointer will return once the current program's execution ends. A common technique to hijack control flow is to overflow a local variable on the stack such that it overwrites the return address with an address of the malware author's choice. This technique is called a stack buffer overflow. So this piece right here is being modified by the malware to use the attacker's address. The arguments being passed to a function are pushed to the stack before the function starts execution, these arguments are present right below the return address. So again, the arguments would be below the address, even though they look like in this visual, they're in the top of the address, right? It's just so confusing. I don't know why they did that. The function prologue and epilogue. So when a function is called, the stack is prepared for the function to execute. This means that the arguments are pushed to the stack before the start of the function execution. After that, the return address and the old base pointer are pushed onto the stack. Once these elements are pushed, the base pointer address is changed to the top of the stack, which will be the stack pointer of the caller function at the time. And the function executes, the stack pointer removes at the part of the requirements of the function and the portion of the code that pushes the arguments, which is the return address, and the base pointer onto the stack rearranges the stack, and the base pointer is called to the function prologue. So what does all of that mean? Because that's a very confusing paragraph for me. So when a function is called, the stack is prepared. This is considered a stack, right? So the function is called, the stack is prepared. This means that the arguments are pushed to the stack before the start of the function. So if this is the top and this is the bottom, these things are pushed before the start of the function even happens. So the function is called, this is prepared. The arguments would be sent first, okay? After that, the return address and the old base pointer are pushed. So return address and base pointer are pushed, or the old base pointer, which ends up calling the new base pointer. Once these elements are pushed, the base pointer address is changed to the top of the stack, which will be the stack pointer of the caller function at that time. So once the return address and old base pointer are pushed, the actual base pointer is moved to the top of the stack. So again, this is the bottom, this would be the top, and then on top of this would end up being added the local variables, right? As the function executes, the stack pointer moves as per the requirements of the function. This portion of the code pushes the arguments, the return address, and the base pointer onto the stack and rearranges the stack and base pointer is called the function prologue. The old base pointer is popped off the stack and onto the base pointer when the function exits. The return address is popped off the instruction pointer and the stack pointer is rearranged to point to the top of the stack. The part of the code that performs this action is called the function epilogue. So the prologue is when it's called. The epilogue is when it is being exiting, right? It's going into exit or shutdown. We're going to look at the view site. To launch the static site in split view, now hop on the attached static site and find the flag by arranging the stack correctly. So that's basically all we're doing, is we're going to open this thing up and then we're going to try to arrange the stack correctly. So let's zoom out a little bit so that we can actually see what's up when we do the split screen here. And let me see if I can do this right. Okay. I mean, so let's copy this just so we can see what's up. But essentially the stack portion of this is exactly as this view right here was, right? So I just did argument 1, 2, and then I did return address, the EBP, and then variables in that order. And then the only thing that they really wanted to make sure was you match up the EBP register and the ESP register correctly, which is under the registers column. And so EBP matched up with the actual portion of the called EBP, and then ESP was at the bottom of this whole thing. So let's, I'm going to go ahead and just paste the flag, but I'll do that again so you can actually see what I just did. It's also timed just to kind of give you that. Let's see if we can, I don't know if I can restart this because I already just finished this. So let's see if we can kind of restart the whole thing. Yeah, okay, so we can restart it. So there you go. You have 60 seconds to do this. As soon as you click proceed, it starts. So you're going to start with your arguments at the bottom, and then we're going to go with the return address and the EBPs, and then we'll do local variable 1 and local variable 2. So that's all of that. And if you do it wrong, it'll just bounce back. And then you want to match the EBP with the EBP, and then the ESP goes at the bottom of this whole thing. And so you get that outline over there. So very simple, pretty easy room. Easy exercise to do. Usually the free rooms don't have crazy exercises. So that's pretty much it. That's all we had for the stack layout. So let's review the conclusion and some final thoughts, and you will be dismissed for the day. So as you can tell, and as you just went through this whole thing, this was not a simple lecture. This was technically a lecture. There wasn't really much of a practical that we did, but it was not a simple lecture. Even for me, going through this, I'm like, okay, well, this is a lot. There was a lot of data in this little short video that we just made. We talked about the von Neumann CPU architecture, which is kind of like the format that all of the rest of the architectures have been built upon. x86 is technically the original 16-bit, and then it goes to a 32-bit, which is EIP, and then we have the 64-bit, which was the RIP. And so these were the different types of architecture that we covered, and everything is founded upon the von Neumann. And then there's the different components of a CPU, different types of CPU registers, memory, and the different sections, and the stack layout of a program in memory. That's basically what we talked about in this video. I do understand that it can be overwhelming for some people. For me, it was overwhelming. And I was just trying to make sense of it as I was reading through it. So hopefully it made sense to you. If not, don't trip. It's not that big of a deal. This is kind of getting into the advanced conversations. When you start analyzing malware and you need to understand how architecture works and how malware is going to attack architecture, it can be confusing for people who don't have a coding background. If you don't have really, really strong foundation in coding and operating system functions and things like that, don't trip. Like, don't worry about it. You're not supposed to be like the be all end all of something that is this detailed and this nuanced. So as long as you kind of understand what just happened, and the big piece, the big takeaway from this whole thing was that the stack is the target of malware because it controls the arguments and it has the local variables. And so that's where malware most likely will try to make modifications to change the return address, etc. So that's kind of like the big takeaway that I took from this specific room and this video. So overall, if you have any questions or comments, just drop them in the comment section below. Let us know what you think about this room in the Discord chat. This will be the Discord chat for TryHackMe and the Twitter account, now known as the X account for TryHackMe. So you can give them feedback if you want to. And I mean, I think you should. If you actually have feedback, definitely let them know because they're very open to feedback and they are very receptive. That is pretty much it. So I'm going to click complete and we will be done with this room. If you found this video useful and if you actually got value out of it, and if you would like to get notified of all of the future videos that come out from SOC Level 2's path as we wrap it up, as well as everything else for Pentest Plus and everything else we're going to do with AI and cybersecurity, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. Of course, drop a comment if you have any comments or if you have any questions that you want to ask, and I will respond to them accordingly. And if it's a really big comment and a big question, then I will go ahead and respond to your comment or your question inside of a video, which has happened before. It is not unprecedented, so you will definitely get access to customized responses through video if you actually have a really deep question, like a big question. And there have been requests that have been made that have actually resulted in playlists being generated and things like that. So that is pretty much it. So make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. I hate to point at you, but I'm pointing at you, so let me know. And that's pretty much it for today. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord servers. If not, I hope I see you in the comment section. And that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I'll see you in the next video later. In this episode 39 of the SOC Level 2 training series, we are going to go through the x86 assembly crash course room, which is inside of the malware analysis module inside of the SOC Level 2 pathway of TryHackMe. And this is the last module in SOC Level 2, and we're going to just kind of keep trucking along with this whole thing. As a part of the outline for this video, we have the intro to the assembly for these. Then we have the opcodes and operands, general instructions, flags, arithmetic and logical instructions, conditionals and branching, stack and functional calls, and a couple of practice exercises. And of course, there will be a conclusion where we review everything that we went through. We'll give you some final thoughts, and you will be dismissed for the day. So that is essentially the overview of the assembly crash course for x86 inside of malware analysis. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into the x86 assembly crash course. All right, this is going to be another one of those technical lectures that we're going to go through, so try to bear with me as we go through this thing. I will understand in advance, and I'm just going to disclose in advance that there's going to be a lot of technical jargon and a lot of things that if you are not familiar with malware, if you're not familiar with coding or compiling software or any of those things, these things may go over your head. But again, it's not that big of a deal if you don't understand all of the nuanced details, because the big thing is for you to understand the overall concept behind this, the principles behind assembly. And then once you understand that, you can see how it'll fit into malware analysis. So the assembly language is the lowest level of human readable language. It's also the highest level of language into which a binary can be compiled, or decompiled. So you can take binary and then decompile it into the assembly language. When learning malware reverse engineering, knowing the basics of assembly is essential. This is because when we get a malware sample to analyze, it's mostly a compiled binary, and we can't view the binary's C or C++ code, so any other language code that it might be as well, because it's not going to be available to us. It's going to come to us in binary. So what we can do is we can decompile the code using a disassembler or a decompiler. And the problem with that challenge, or the problem with that step, is that a lot of the information in the code is removed while it's compiled into a binary. So when it's being compiled into binary form, a lot of the written information, key information, is removed. So for example, you don't see the names of variables, you don't see names of functions, and a lot of other key information that would actually help you make sense of it. So the most reliable thing that we can actually rely on would be the assembly code. And that's, again, it's like the next step. So it comes up from binary and it goes into assembly code. And we're going to just learn the basics of assembly so that we can use it in malware analysis as we continue with the malware analysis module and try to figure out what malware does or how it works, etc. We're going to go look at opcodes and operands. We're going to look at general assembly instructions, arithmetic and logical instructions, conditionals, and branching instructions. The prerequisites would be the last video prior to this one, which is the overview of x86 architecture and the specific stack flow, which is very, very important. That was like the big takeaway that we got from the x86 architecture room and that video. So if you haven't seen that video, I highly encourage you to go through that video first, because again, there's a lot of technical stuff, there's a lot of foundational stuff that we covered in that video that's going to be crucial in this particular video. So that being said, let's go into opcodes and operands. The code for a program, as it's understood by the CPU and written onto the computer's disk, is in binary format, which means the actual code is basically a sequence of ones and zeros, which looks like this. And they're usually measured in a series of 8 bits, meaning 8 of these ones and zeros. And so the first 4 of those series is going to be translated into something, and then the next 4 will be translated into something else. So for example, this specific one would be, the first 4 would be the letter A, and then the next 4 would be the number 5, which means it would be A5 in hexadecimal code. So if you wanted to convert this from binary to hexadecimal or hex, then you would convert it into A5, and then it's written as 0 times A5 to denote that it's a hex number. The instructions that a computer is going to execute will just be a sequence of random numbers in hex, if we look at it with the naked human eye. So among these random numbers are opcodes and operands, and opcodes denote the hex for the actual operation, and operands are the registers or memory locations on which the operations are performed. Opcodes are numbers that correspond to instructions that is going to be performed by the CPU. So numbers that are corresponding to instructions. When we use a disassembler, and we're going to talk about this in a little bit, we disassemble a program, and then it reads the opcodes. It translates them into assembly instructions to make them human readable. For example, in the instruction for moving this 0x5f to the register will end up being to move EAX, and then that's what it's going to look like. So this is literally what the instruction for that specific thing is going to look like. For moving this to the EAX register is going to be move to EAX, and then you're going to remove the 0x5f. When you look at it in a disassembler, this is what you're going to see. This is going to be the line of code. And again, for most people, this is not going to make sense. This last piece might, but when you look at it in a disassembler, this specific instruction for moving that is going to look just like what you see right here. This, I'm assuming, would be the ID, so we can actually see it. So 0440,000 corresponds to the address where the instruction is located. The specific ID, or the line, we can say, inside of the overall file that we're looking at. B8 refers to the opcode of the instruction, which is move EAX. So B8 refers to this piece right here. And then 5F with all the following zeros indicates the other operand, which is this piece right here. So due to endianness, and there's little endian and big endian, so this is different conversation, but let's open it just to see what we'll get in this. Endianness, in this case, we have big endian, little endian, for conflicting ideologies. In computing, endianness is the order in which bytes within a word are transmitted over data communication or addressed by rising addresses in computer memory, counting only byte significance compared to earliness. So it's looking at the significance of the byte compared to the order in which it came in. Endianness is primarily expressed as big endian or little endian, introduced by Danny Cohen into computer science, etc. The adjective endian has its origin in the writings of 18th century, etc. So computers store information in various sizes. You're more than welcome to go ahead and just read the wiki for endianness inside of Wikipedia. But essentially, due to endianness, the operand 0x5f is written as this, which is actually this in this particular case. So remember, it's not the order in which it came in, right? It's due to the significance. And in this particular case, 5f in this series of numbers and characters, 5f is more significant than the other one. In little endian notation is what we're looking at. So there's an opcode for each instruction in the assembly language. There are references for converting opcodes into assembly instructions. Unless we are writing a disassembler, we will not need them, as a disassembler does that work pretty well. It's good to understand what's happening under the hood, and that's why literally we're doing this. So in the above operation, we had 3 parts. The instruction was move. The 2 operands were EAX and the 0x5f. And in this particular instruction, the value 0x5f is being moved into EAX. However, we can also have other kinds of operands in assembly. So type of operands would be immediate. That can also be considered constants. These are fixed values like we have in this particular example above. Then we have registers, which are the EAX in this particular case, which is the location. You can think of it like that. It's a register where the immediate operand is going to be stored in the particular operation that we just saw. It could be something else. but essentially registers in this case would be the location. And as we talked about in the previous video, registers is where a lot of the smaller sized data bits are stored for the overall processing of a computer's operations inside of the CPU. So the registers hold data, just small chunks of data. And then you have memory operands, which are a little bit bigger chunks of data. And these are denoted by square brackets, and they reference memory locations. For example, if we see this, then it will mean that the value in EAX is in the memory location instead of the registry. So again, if it's inside of these square brackets, that means inside of the memory, inside of the registers. So, and not registry, I should say, inside of registers. So I apologize for that. So now that we understand this, we can talk about common assembly instructions. So what are the hex codes that denote the assembly operations are called? And the hex codes that denote what they are called in this particular case are going to be the opcodes, I believe, or it would be operands, I want to say. I think it's opcodes. So let's try opcodes and see if that's the answer. And then which type of operand is denoted by square brackets, and that is the memory operand. So let me make sure my keyboard wakes back up. All right, cool. Now we can move on to general instructions. Instructions in general, so not general instructions, but instructions as an overall concept, they tell the CPU what to do, right? So what operation to perform. They often use operands, and they pull those operands from either registers, memory, or the immediate operands to perform an operation and then store the results in either registers or memory. So the most common instructions that we come across are going to be the general instructions that we can see, and this is what we're going to end up using or finding in reverse engineering malware. General instructions perform simple operations, like, for example, moving something from one type of storage to another. The move instruction. So if you actually have ever used the Linux command line, you will end up seeing MOV, and it moves something from one place to another place. So you would move it from the destination to its source, and usually the destination is some kind of a path. So for example, /user/hank/downloads/file.txt. That would be the full destination, and then the source would be /user/James/downloads, something like that. And that's basically what this command itself ends up doing, is that it's just moving something from one place to another, and this falls under a general instruction. It can move a fixed value to a register to another register, and a value in a memory location to a register. So this will kind of help us understand here. In this instruction, in this set right here, we're copying a fixed value to a register. In this particular case, 0x5f is being moved to EAX, right? So we're moving to this place, this thing. And it kind of doesn't make sense, because usually when you do it in the command line, you use without the comma, you would use the source first, and then you use the destination. I think I explained that incorrectly the first time that I tried to explain this, but in operands and general instructions, you can see that you have the destination. So you're going to say move to this place, comma, this thing. And then you can also say on the terminal, you can say move this to this location, and then so this would come right after move, and then there would not be a comma separated. You would just say move source destination without a comma separating them. So in this case, we're saying move to this destination, this piece right here. The value stored in EAX is being moved to EBX, for example. So move to EBX, this specific thing. And then in this case, move to EAX, this specific thing. Now, what we understood earlier is that if it's inside of square brackets, we're pulling it from a memory instead of pulling it from a register. So we use square brackets when referencing memory. Suppose that we see a register in square brackets. In that case, that will mean that the value in that register will be treated as a memory location, and the value in that memory location will be moved to the destination. This means that the example move EAX, comma, this piece, and the below example will have the same result. So move EBX, this piece right here, and move EAX, EBX, which is the contents of EBX, right? So moving into EBX, this element is going to then put this element inside of EBX. And then if I move EBX to EAX, then I have moved those contents inside of EAX, which will be exactly the same thing as this piece right here, because we're taking these contents and just moving them directly into EAX, which is what we see right here. So we can use the move instruction to perform arithmetic calculations when referencing memory addresses. For example, the below instruction calculates EP or EBP plus 4, adding an offset of 4 bytes to the memory location, and moves the value in the resulting memory address. So move into this location this specific value, which is inside of a memory location. The LEA instruction. So this is everything that we just talked about was a general instruction that is called the move instruction. And now we have the LEA instruction, which is another general instruction. And it stands for load effective address. So load the effective address. And this will be like LEA to this destination, whatever the source is. While the move instruction moves the data to the destination, the LEA instruction moves the address of the source into the destination. So the EBP value will be increased by 4 and then moved to EAX. However, if we had just used a move instruction here, we would have just moved the value itself, the data inside of it, to that location, right? So in this particular case, we're taking the address of it and putting it into EAX. We can notice that we have performed an arithmetic operation on a register and saved the result on another register using a single instruction. And what this arithmetic operation is that they're talking about is that they're adding the 4 bits at the end of it. The LEA instruction is often used by compilers, not for referencing memory, but so that an arithmetic operation is performed on a register and then saved to another using a single instruction. So you're not necessarily doing something to move locations, right? You're not using it for referencing memory locations, but so that you can actually have an arithmetic operation on the register and then save that to another location. Especially if an arithmetic operation are more complex, like adding and multiplying in a single instruction. And then we'll see that in a little bit. The NOP instruction stands for no operation, and this exchanges the value in EAX with itself, resulting in no meaningful operation. Hence, the execution moves to the next instruction without changing anything. These are used for consuming CPU cycles while waiting for an operation or other such purposes. It has no it has the particular syntax right here. You just say NOP literally. It's used by malware when redirecting execution to their shellcode. The exact location where the execution will redirect is often unknown, so the malware author uses a bunch of NOP instructions to ensure that the shellcode execution does not start from the middle. The padding of NOP instructions is called an NOP sled, and so if you can see a bunch of NOP instructions, you can assume that what's going to come next are going to be a set of instructions that will call the malware to do something. For example, redirect something to their actual shellcode. Shift instructions are used to shift each register bit to the adjacent bit. So there are 2 shift instructions for shifting either to the right or the left, and it could be shift or SHR, right? Destination and count. So shift to this destination by the following count, and SHR is to the right, and then SHL would be to the left. So shift to this destination by this count, certain number of bits, right? So the SHR is shift right and the SHL is shift left. The instruction shifts the bits to the destination operand. The count decides the number of bits to be shifted. The bits which are shifted out to the location are filled with 0. So if we have this in EAX and shift it left, it will become this whole piece right here, and we're shifting it left 1 count, right? So you can see that it just moves, and then the new placeholder right after this 0 to the right of it is just this extra 0 that we saw. So we moved it left, right? The carry flag is used, and we talked about this in the last video, is used to augment the destination and is filled by the last bit overflowing the destination. So for example, if we have this ending in 101 and shifted right by 1, it'll result in this piece in EAX, and the carry flag will be set, meaning it'll have a value of 1. So again, remember, if you haven't seen the previous video, this is directly related to what we just talked about in this paragraph. The carry flag having a value of 1 or a value of 0, because we're talking in binary. And so if this is being shifted to the right, the carry flag will be set, and then it will have a value of 1, because that extra 1 at the end seems to have fallen off, but it's actually being stored inside of the carry flag. Shift instructions are used instead of multiplication and division by 2 or more powers of 2. So 2 to the power of n, essentially, where n is the count in the shift instruction. This saves execution time by not having to manipulate values in registers before performing multiplication or division. For example, if we have this that ends in 10 and we shift it to the right by 1 bit, we get this that has the 1 at the very end, which is the same result as dividing EAX by 2. Similarly, if EAX has 1 at the very end and we shift it left by 1, the result will end up being this, which is the same as multiplying it by 2. If that went over your head, I completely understand. Re-listen to it multiple times, because no matter how I paraphrase that or I try to change the phrasing of that, it's not going to make any more sense. So that specific piece, feel free to pause the video and try to kind of wrap your head around it. Again, it's not that big of a deal, because all of this stuff that we're talking about is going to come together at the very end of this, but it's just a building block. So we have rotation instructions. So the rotate instructions, they're similar to the shift instructions, and the only difference is that the bits are rotated back to the other end of the register instead of moving the overflowing bit into the carry flag or adding zeros instead of shifted out bits. The rotate instructions would be ROR to the right or ROL to the left, and the destination, and by a number of counts. So ROR instruction rotates it to the right, ROL rotates to the left. The rest of the syntax remains the same. As an example, if we have this 10, 10, 10, 10 in AL, we can rotate it right by 1 bit and it will result in 0, 1, 0, 1, 0, 1, 0, 1, like that. Similarly, rotating the result to the left will result in 10, 10, 10, 10. So if you take this to the left again, it'll just result in 10, 10, 10, 10, right? So rotate is it's kind of I would say I want to say that it does the same thing essentially that you would do with the shift left or the right, right? They're similar to shift left or the right. Is that it's just that the bits are rotated back to the other end of it instead of actually being moved to a carry flag, right? So this is essentially just taking this last 0 and putting it here. It's being rotated. So it's taking that last 0 and putting it to the front. And if we rotate to the left, it'll take this 0 and put it back at the end again, instead of putting it inside of a flag, for example. In move EAX EBX, which register is the destination? So remember, we're moving this to this destination. So in this particular case, EAX would be the destination. Which instruction performs no action, and that is the NOP, the no operation. All right, let's talk about flags. We did talk about flags in the last video, and the flags indicate the outcome of certain operations or conditions. They are bits in a special register known as the flags register or eFlags register. Each flag represents a specific condition or result of the most recent arithmetic or logical operation, and this is our table. So we talked about a few of these. We did not talk about parity. I don't remember talking about parity or auxiliary. We did talk about the 0 flag, the sign flag, the overflow. I don't remember if we talked about a direction flag, interrupt enable. We talked about a few of them. We haven't talked about all of them. So the carry flag is set when carry out or borrow is required from the most significant bit. We already saw this. Also used for bitwise shifting operations. Parity is set if the least significant byte of the result contains an even number of 1 bits. Auxiliary, the AF, is set if carry out or borrow is required from bit 3 to bit 4 in an arithmetic operation. It's called BCD arithmetic. Again, a lot of details here. You are not required to memorize this. I don't want you to feel like you need to know exactly what all of these things are. If you can memorize them, that's amazing. But for most people, especially if you have no background in any of this stuff, this is not going to be a really easy thing to wrap your head around. So ZF, 0 flag, is set if the result is 0. Sign is if the result of the operation is negative. The most significant bit is 1. Obviously, you can't have a -0, so you could have a -1. Overflow is set if the assigned arithmetic overflow, adding two positive numbers and getting a negative result, or vice versa. Direction determines the direction for the string. So if df is 0, the string is processed forward. If df is 1, the string is processed backwards. And interrupt, if it's set, meaning if it has a value of 1, it enables maskable hardware interrupts. If it's cleared, or value of 0, interrupts are disabled. They can be used in conditional jumps and are crucial for implementing conditional branching in assembly code. For example, you might only jump to a specific address if a certain flag is set or cleared. Which flag will be set if the result of the operation is 0, and that's going to be the ZF, the 0 flag. Which flag will be set if the result of the operation is negative, and that's a sign. So think about the sign flag as the negative sign, the minus sign, and that would be the SF. So now we can move on to arithmetic and logical instructions. So far, pretty much everything that we've talked about has kind of fallen under general instructions. Arithmetic operations, and I guess technically flags can also fall under arithmetic operations, but arithmetic operations are performed using arithmetic instructions. So if you know what arithmetic means, you can kind of wrap your head around what this would be. This might be a little bit easier to understand. So addition and subtraction instructions. So the syntax for this is as follows. You can add to this destination this value. You can subtract from this destination this value. That's basically it. And then the result will be stored inside of the destination, or taken from that destination, right? So the value is subtracted from the destination, the value is added to the destination. The value can be either a fixed value or constant, fixed value, constant, or a register in its entirety. For the subtraction operation, 0 flag ZF is set if the result of the subtraction is 0. If the destination is smaller than the subtracted value, then the carry flag is set. Multiplication and division instructions, they use the EAX and EDX registers. Therefore, we will have to look at the last instruction that manipulated the register for every multiply and divide operation. To multiply, the following format would be used here. It multiplies the value with EAX and stores the result in EDX colon EAX as a 64-bit value. Two registers are required here because the result of multiplying two 32-bit values can often be higher than 32 bits. And the lower the 32-bit values are stored in the EX register, the lower of those two values, are stored in the EX register, and the higher 32 bits are stored in the EDX register. The MUL value is essentially the syntax for multiplying, and then div value would be the syntax for dividing. And the value can be another register or a constrand as an immediate operand or operand. For the division instruction, the case is the opposite. It divides the 64-bit value in EDX EAX and saves the result in EAX and the remainder in EDX. So remember this one right here, these two are exactly the same, the format that you see right here, right? So the format for this element, and that's not even something that you're going to end up doing. It's just that you need to understand what it actually is doing and which registers are being addressed for which one. And again, you can kind of refer to the last video just so you can see what all of the different registers were as we listed them, because there were a good amount of registers that we covered. Then we have increment and decrement or decrement instructions. And as the name suggests, the increment and decrement instructions increment or decrement the operand by a register of 1. And the syntax to increment EAX by 1 would be inc the EAX. And then similarly, the syntax to decrement would be dec EAX. You can kind of also think about it as increase or decrease, but you shouldn't, just for full understanding, is to increment by 1 or decrement by 1. That's basically what this is going to be doing. We have logical instructions that are used to perform logical operations, and we have the AND instruction. So it performs a bitwise AND operation on the operands, and an AND operation returns an output of 1 when both the inputs are 1. Otherwise, it returns 0. So an example would be AND AL which again, remember this is the destination, and then you have this value, and this is either coming from a register, and if it's inside of brackets, it would be coming from a memory location. In this example, 0x7c converts to 01111100 in binary. And this is just hex being converted into binary. There's nothing special about that. So suppose that AL had a value of 0xfc, which ends up being this in binary. In this case, the output of the above instruction will end up being 01111100. However, if it has the value of this, then it will be turned into this right here. So keep this in mind, right? So it's essentially doing this. It's looking at the two values, right? It's looking at, it says right here, right? If it will return an output of 1 when both of the inputs are 1, otherwise it returns 0, meaning if both of them are 1, it'll give you 1. If one of them is 0, it'll give you a 0, or if both of them are 0, it'll give you a 0. So this converts into this in binary. If it had this value, 0xfc, which is this, then the output would end up being this. So we're looking at 0, and then this one is 1, so that ends up being 0. Then this one is 1, and this one is 1, that'll give you 1, and then so on and so on. And then it gets to the last two digits, and the last two digits are also zeros, so it'll end up giving you a 0. However, if AL had a value of this, which ends up being this right here, then if we compare these two now, so if you have 1 and 0, then that'll end up being 0. If you have 0 and 1, that'll end up being 0. And then if you have 0 and 1, again, 0, 0. And so the only ones that end up coming back as 1 are the only two digits that actually have 1 right here, and then they also have 1 right here, and that'll end up being 1s, and then the rest of them will be 0s. So AND is essentially comparing the binary values of these two different data points, and then it's comparing to see if they both match as 1. If they do, it'll convert them into a 1. If either of them is 0, it'll be 0. If both of them are 0, it'll be 0. So that's basically it. The OR instruction performs a bitwise OR operation, and it returns a 1 if at least one of the operands is 1. It returns 0 if none of the operands is 1, meaning if you have two zeros, it'll return 0. If either one of them is 1, then you'll get a 1. So that's kind of the thing right here. You can pause this to look at these examples because I don't have to go back and forth for it for you to understand. But essentially, the AND one is saying both of them. So this needs to be a 1 and this needs to be a 1 in order for me to give you a 1. If both of them are not 1, then you'll get a 0. In this particular case, it's just saying if either of them is a 1, then I'll give you a 1. If both of them are 0, so if neither of them are a 1, then you get a 0, which is a little bit more inclusive. The NOT instruction takes one operand. It simply inverts the operand bits, replacing ones with zeros and vice versa. In the following example, if AL had this value, it would then turn into this value. So you don't want this, right? You don't want AL. You want the opposite of AL, which would just turn all of these into their exact opposites. The XOR instruction returns 1 if both the inputs are opposite. It returns 0 when both inputs are the same. This is performed by XOR instruction in assembly language, which performs a bitwise XOR operation on the operands, and it has the following syntax: XOR AL and then 0xfc or 7c, excuse me. If AL has this value right here, the result of the instruction will end up being 1 1 0 0 0 0, which is this. If it has a value of this, which is this piece right here, the result of the instruction will end up being this right here. If it has a value of this, the result will end up showing this. So it shows that zoring, we can call it a zor, I guess, a register with itself results in 0. Therefore, the zor instruction is often used to zero a register, which is more optimized than a move instruction. So it'll return 1 if both of the inputs are opposite, okay? So if this, right, which the result of this will end up being this or this. Similarly, I'm kind of, these digits right here are kind of messing me up, but this one actually ends up making more sense to me. So if it'll return 1 if both of them are opposite, meaning that if you have a 1 and a 0, which are opposites, then it'll return 1. If you have a 1 and a 1, which are not opposites, it'll return 0. If you have a 0 and a 0, it'll also return 0. So it's only going to return 1 if both of the inputs are opposite. That's basically how I understand it. In a subtraction operation, which flag is set if the destination is smaller than the subtracted value? And that is the carry flag. So let me see, my keyboard just times out. If I talk too much and if I don't use my keyboard, it'll just kind of go to sleep. Which instruction is used to increase the value of a register? Now, technically, it can be increment because it increases the value. But let's see if there's anything else. I want to say it's increase. Multiplication can also increase the value of it. Add can also increase the value of it. I think the answer that they're looking for would be add, although technically multiply and increase both work. So let's see if it's add that they're not looking for add. So is it increase? Yeah, they're looking for increase or increment. So do the following instructions have the same result, yay or nay? So we have XOR EAX and EAX right here. Move EAX 0. They technically should have the same result, right? But it says, because remember, if it's going to return a 1 if both of them are opposite. So if they're both the same, it won't return a 1. It'll return a 0. And in this particular case, we're moving this 0 value into EAX. So technically, it should be yay. So let's see if I'm right. And I am right. Okay, great. Because it's comparing these two, right? XOR is comparing these two. And if they are opposite, then it will give you a 1. But if they're the same, it's going to return a 0. And then if you move into this destination the value of 0, then you're getting 0 in both of these. So yes, that is the same. So let's talk about conditionals and branching now. A lot of times the CPU has to determine if two values are equal to each other, if one is greater than the other, or if one is less than the other. And to perform these things, it uses conditional instructions. And we're going to be talking about those instructions in x86 assembly language specifically. The test instruction performs a bitwise AND operation, and instead of storing the result in the destination operand as the AND usually does, it just sets the 0 flag if the result is 0. The instruction is often used to check if an operand has a null value, for example, by testing the operand against itself. This is done because it takes fewer bytes to use the test instruction than by comparing to 0. The test instruction would have this. So you want to test this destination against this source, right? So the instruction is often used to check if an operand has a null value by testing the operand against itself. And it's done because it takes fewer bytes to use the test instruction than by comparing it to the value of 0. So you're just testing these two against each other to see if they're equal to each other or if one is less than the other, etc. The CMP instruction, I would assume, is to compare, right? So based on the results, the CMP instruction compares the two operands and sets the 0 flag or the carry flag. It has the following syntax: CMP, destination against the source, and it works similarly to a subtract instruction. The only difference is that the operands are not modified. The 0 flag is set if both of them are equal, if the source operand is greater than the destination, so if this is greater than this, then the carry flag is set, and the ZF and the CF are cleared if the destination operand is greater than the source operand. So if they're both the same, right, it'll be setting the ZF flag. If this is greater than this, right, so if source is greater than destination, then carry flag is set. And if destination is greater than source, then both of the flags are cleared. So you would have 0 for this, and you would have 0 for the carry flag, which implies that this one is greater than the source. Branching. So when there's no branching, the instruction pointer goes from one instruction to the other in order that they are placed in memory. So it'll go from one place to another based on the order that they actually came in chronologically, we can say. The control flow remains in a straight line unless there is a branching operation. Branching operations change the value of the instruction pointer and change the program's control flow from linear to branching out. And again, instruction pointers were covered in the last video, so if you don't know what that means, you need to watch the last video. This is literally like a continuation from the last video. It's pretty much the same exact conversation. I mean, this whole thing is going to be about malware analysis, so technically it is the same exact conversation, but we are literally picking up where the last video left off. The jump instruction makes the control flow jump to a specified location, and it jumps to wherever the location is. The location operand will be moved to the instruction pointer, making it the address where the next instruction will be fetched for execution. And we have conditional jumps that have the if condition inside of it. If statements are used inside of coding a lot, and it says if something, then something. That's basically what it is. So in higher level languages, if they're said they help to fulfill the requirement. However, there are no if statements in the assembly language. This requirement is fulfilled using conditional jumps. Conditional jumps decide whether to jump based on the value of the flag register. Their syntax is similar to jump instruction, and the following table shows us what the condition, some examples that we have over here. So the instruction is JZ jump if the ZF flag is set, meaning if ZF is equals to 1, you jump. JNZ will jump if the ZF flag is not set, so the ZF would be equal to 0. JE will jump if it's equal, and it's often used after the comparison. JNE will jump if it's not equal, and it's often used after a comparison instruction as well. So then we have JG. If the destination is greater than the source, then you want to jump. It performs a signed comparison and is often used after a CMP comparison or instruction. JL would be jumping if the destination is lesser than the source and performs signed comparison, is often used after CMP. JGE is greater than or equal to, and it jumps if the destination is greater than, equal to, or the source, comparing to the above instructions. This LE would be lesser than or equal to. So if the operation is lesser than or equal to, if the destination is lesser than or equal to the source. JA, jump if above. So similar to JG, but performs an unassigned comparison. JB, jump if below. If you don't know what above or below means, that means you have not seen the last video. So there is an order of things that comes in when you're looking at the stack. And so either things are above or below each other. JAE, above or equal to. JBE, below or equal to. So which flag is set as a result of the test instruction being 0? And that would, of course, be the 0 flag. Which of the below operations uses subtraction to test the two values, 1 or 2. So you have compare or you have test, and if I remember correctly, test uses subtraction. Compare just compares the values to each other. Oh, I'm wrong. So compare uses subtraction to test. Yeah, I'm sorry. Yeah, my bad. That's my bad completely. I want to blame it on dyslexia, but I think it's because I fully didn't recall the data from those sets of instructions. Compare uses subtraction to test two values. Which flag is used to identify whether a jump will be taken or not after a jump 0 or jump not 0 instruction? And we have these values right here, but it is the jump flag, I want to say. So a conditional jump will end up being the thing. So would it be the jump flag? I think it is the jump flag. So something will jump if it is not. So let's see if it is the jump flag. It's not. So the 0 flag. Yeah, so it's the 0 flag. So if it is 0 or if it's not 0, that's the flag that's being used to identify whether a jump should take place. All right, so stack and function calls. Now going back to the concept of the stack based on what we talked about in the last video. In the last video, we talked about how important the stack is, and it ends up being the target for a lot of malware to operate in or to manipulate the data that's inside of the stack. We also learned about the registers that are used to reference the location of the stack, as well as the concept of the last in, first out memory, which means that the last variable that's pushed onto the stack is the first that will be popped out. And these push and pop operations are performed by following instructions in the assembly language. The push instruction is push source. So it'll push the source operand onto the stack. The value of the operand is stored at the memory location pointed to the stack pointer, the ESP, effectively becoming the new top of the stack. So when you add something to it, that's going to end up becoming the top of the stack. The stack pointer is then adjusted, which means it's decremented to reflect the updated top position of the stack. So the pointer is everything other than the stuff that's just being pushed on top of it, right? So everything. So let's say this is the top. All of this stuff ends up being the pointer, which means all of this is going to be decremented, decreased by 1, right? So it's going to be decremented, meaning it's going to move down one place so that we can add this thing to the top of it. That's what all of that actually means. The following instructions also push all of the general purpose registers to the stack. So push A, also known as push all words, it pushes all the 16-bit general purpose registers to the stack, for example, AX, BX, etc. Push AD pushes all of the double words, all the 32-bit general purpose registers to the stack. So EAX, EBX, etc. And if you don't know what that means, watch the last video. When we encounter these instructions, it's also often a sign of someone manually injecting assembly instructions to save the state of registers, and it's often the case with shellcode. The pop instruction is taking something off of the stack, right? So push puts something on the stack. Pop retrieves the value from the top of the stack and stores it in the destination operand. As a result, the stack pointer, ESP, is incremented to reflect the adjustment. So again, if you're taking this off, that means these things are now going to move up by 1. So it's going to be incremented. The following instructions also pop all the general purpose registers. So you have pop A, which will pop all words, which means all of the single words, and you have pop AD, which will take all the double words, meaning all of these things right here. The call instruction is used in the assembly language for performing a function call operation to perform a specific task, and it has the call location. So depending on the calling convention, the arguments are placed on the stack or in the registers in a function call. The function prologue, if you remember this, we talked about this in this video. The function prologue prepares the stack by adjusting the EBP ESP and pushing the return address on the stack. Similarly, when it returns the epilogue, so this is the way that the function will exit, restores the stack for the caller function, and we'll learn more about these things in upcoming videos. So in the next task, we're actually going to practice using all these things. So which instruction is used for performing a function call? And that should be the call. Which instruction is used to push all registers to the stack? And that should be, or push all registers, it would be push A. There we go. All right, let's do some practice now. All right, so we're going to apply everything that we've learned so far in this video and the last one, and it's going to be on this view side. I'm going to zoom out and put it into full screen so that it's a little bit easier for us to handle. The options on the top bar could be run the program, execute the next instruction, stop the execution, restart the program. And we have instructions that we should be doing basically. So contains the following assembly code instructions. Run these instructions and observe how they impact register, flag, etc., etc. And the following instructions demonstrate how different arithmetic instructions work. The following instructions demonstrate how the data can be moved into registers, from register to register, from memory to register, etc. And the stack, so they demonstrate two instructions, push and pop, used to push data into a stack and pop the data out. And then CMP and test instructions, and we have these available for us as well. I mean, we already know essentially what these things are going to do, so we just need to run them. So while running move, what is the value of EAX after running the fourth instruction in hex, etc., etc. So that's pretty much it. That's all we got to do. So what I'm going to do is I'm going to zoom out and click the view site button so that we can actually access the site, so that we can run the commands. And let's see if I do need to go into, let's see, would you take a guided tour to look more about, yeah, why not? So we'll take a guided tour, kind of understand what's going on, and then we will make modifications and see what the results are. So let's see what the guided tour is. We have the control buttons, run all the instructions at once, run instructions one by one, reset all memory. So run all at once, run by one, and then reset. The next one would be you can choose different sets of instructions, so arithmetic code or other general types of code. Instruction block would be the stuff that you want to do. You can see different instruction codes. The green arrow presents the running command. Then we have the registers and the flags. So you'll see the register value and checkered flags, which is what we have here. And then these are the flags that we can check. And at the bottom right here, the memory block. So with the current command memory. And then finally, we have the stack and pointers, which is right here. And I think that's pretty much all of it. So I think this should be fine to use in one window. It says that we can expand it into a new tab in a full window. And I guess this might be a little bit easier to navigate, and I can still zoom in and zoom out accordingly. So we'll just do it that way, I guess. So we'll do it like this, and then we'll try to find the answers to each one of these questions. I'll kind of zoom out of this, and then we'll be able to move into our questions. So here we go. First question says, while running the move instructions, what is the value of EAX after running the fourth instruction? And they want the hexadecimal value. So EAX under the move instructions that we have right here. So while running this, and now we can see right here. So what is the value after running the fourth instruction, which is this piece right here? What is the value of this in hexadecimal? So the first thing that we have to do is we need to change this to move instruction and come out here. And I think if we just click this, we end up seeing the values here. And so if we move down to the fourth instruction right here, so you can see move EAX 40, it says what's the value of it, which ends up being this guy right here in hexadecimal. So that should be the value. So let's go down here and see if that's indeed the case. And let's paste that and test that. Okay, cool. Yeah, that is the case. What error is displayed after running the sixth instruction from the move instruction section? So we are now on 4. Let's move to 5 and 6. And it says error, memory to memory data movement is not allowed. So that's the error. So let's go here and paste that here. Run the instructions from the stack section. What is the value of EAX after the 9th instruction in hexadecimal? So let's see if we have a stack. There we go. That's the stack section. And the 9th instruction is technically position 8 because it starts at 0, right? So what is that's what it's saying, right? Run it. I don't know what's the value of the EAX after 9 instructions. So we're just going to click this 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the value of EAX after the 9th instruction. And what we see here is as such. So let's copy that and take that. There you go. Run the instructions from the stack. What's the value of EDX after the 12th instruction? So we're technically on 9. That would be 10, 11, and 12. And the value of EDX is right there. So, I mean, I'm literally just copying these things by just clicking play one by one. I'm not doing anything crazy. So there is that. Run the instructions from the stack section. After pop ECX, what is the value left at the top of the stack? So pop ECX. We have pop ECX right here. What's that after the stack? So I'm going to reset this whole thing because I want to stop at pop ECX. So we're going to go 5, 6, 7, 8, 9, pop ECX. There we go. What's the value at the top of the stack, right? That's what it's asking in hexadecimal format. So this is the stack right here. And technically, from what I understand, the bottom is the top of the stack and the top would be the bottom of the stack. So I want to say it's this thing right here. So let's see if that's actually the answer. Hopefully that's right. Oh yeah, okay, great. Run the CMP and test instructions. Which flags are triggered after the third instruction? These abbreviations in alphabetical order with no spaces: CF, PF, SF, and ZF. So let's see, we're going to go to the CMP and test instructions, and it says use these abbreviations in alphabetical order with no spaces: CF, PF, SF, and ZF. Okay, so after the third instruction, let's go 1, 2, and 3. And it's saying which flags are triggered. Okay, so this is basically the flag. So parity and 0. So it would be PF for parity and then ZF for 0. Run the test and the CMP instructions. Which flags are triggered after the 11th instruction? So test and CMP, we're technically on number 3. So 4, 5, 6, 7, 8, 9, 10, and 11. It ends up giving us CF for carry and then SF for sign. So CF slash SF. Run the instructions from the LEA section. What's the value of EAX after running the 9th instruction? So we'll go to LEA, which is the last one. And what do we have? The value of the 9th instruction. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the value of EAX is this right here. And last but not least, run the instructions from LEA. What is the final value found in ECX register? So 1, 2, 3. The final value should be that. That should be the answer. And that's it. That was very straightforward. I was kind of nervous because I didn't know exactly what we were going to end up doing. And to be brutally honest with you, I have to review all of these contents just to remember what all of these things are. Because the biggest confusion for me are not these initial instructions. It's what EAX was and EBX and all of these things, what ECX and what EDI and all of those things were, because we talked about those in the last video. And this is my very first time being exposed to all of this content. So it was not, I didn't memorize it. As I mentioned multiple times, it's like, this is not going to be something that you're going to end up learning how to memorize immediately unless you just have amazing memory. So, but yeah, that's pretty much it. Let's do kind of a little bit of a review and we'll do a wrap up. So basically what we looked at was what the common assembly language instructions are in the x86 architecture. And obviously there's a lot of other stuff because this is not the be all and end all of this conversation. This specific topic for x86 architecture can go very, very deep, as I'm sure you can imagine, because this is, again, not something super easy to wrap your head around. We covered the ones that operations are performed in assembly languages, and as we move forward to the rest of the videos in this module, we're going to learn about some of the more instructions as per requirements. And so far, we've covered opcodes and how we can convert them into assembly language. General instructions such as move, load effective address, and shift and rotate. Arithmetic instructions like addition, subtraction, multiplication, division, and conditionals, and how we can use them for branching, stack, and with the push and pop to make sure to adjust the positions inside of the stack and function calls. You can reach out to TryHackMe inside of their Discord channel, or you can hit them up on X, formerly known as Twitter. And that is pretty much it, my dear friends. I know, again, for me, this was not something that I can understand by just going through it once. So if you are a genius when it comes down to this kind of stuff, I'm kind of jealous. But at the same time, you should have an easier time going through this information. If not, review it. If you really want to go into malware analysis as a role, you should understand these things. And I personally don't. So I'm not that excited about this kind of information, but at the very least, we have a recording of it, and I can use it in the future to remind myself of this data point. And honestly, I feel like I'm going to re-review the contents just because I want to have a little bit of a better understanding. I don't want to feel as unknowledgeable. I don't know if that's a word, but I don't want to feel this badly about this kind of information because it really, like, it was my first exposure to this. So I'm rambling at this point, but yeah, feel free to review and of course drop any questions if you have any questions, and I'll do my very best to answer them for you. All right, and that is it, my dear friends. If you got value out of this room and out of this video, and if you would like to get more videos like this one, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel, especially on SOC Level 2 as we wrap up the pathway and as we get into pen testing more and as we get into AI for cybersecurity as well. Drop any questions or comments that you have in the comment section below and let me know, and I will do my very best to respond to them. But apart from that, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section. And that's it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video later. In episode 40 of the SOC Level 2 training series, we're going to go through the Windows internals room, which is a part of the malware analysis module of the SOC Level 2 pathway of TryHackMe. And inside of the Windows internals room, we're basically going to understand the fundamentals of how Windows operates at its core, because most of the malware and most of the attacks that are done inside of the enterprise environment are done against Windows computers. And that's mainly because Windows computers are the easiest to manage when you have a large network of employees. So most enterprise environments, most companies basically use Microsoft Windows for their users because it's really easy to manage inside of Active Directory. And then they'll use Linux for the critical infrastructure, the systems, the infrastructure type systems too, because Linux is more lightweight and it doesn't really require a graphical user interface when you're dealing with some kind of a, let's say, a controller, you know what I mean, inside of a factory or something like that. So for end users, for individual employees, most likely it's Windows. Therefore, we're going to be talking about Windows. We're going to go through the introduction, the processes, threads, virtual memory, dynamic link libraries, portable executable format, interacting with the Windows internals, and of course, there's going to be a conclusion. We're going to do some final thoughts. We're going to do a review, and you will be dismissed for the day. That's pretty much it. And we do have a virtual machine that I've already launched, and it seems that the IP address has actually been assigned to us already, so we are ready to go. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into Windows internals. For the average user of a computer, they have no idea what the hell is going on behind the scenes. So operating systems have a lot of stuff that's happening in the background that most people don't see because they just see the graphical interface. They see their little mouse and then they click here and they click there. That's essentially what most people know of. Now, you obviously know that there's a lot more going on because you're literally studying cybersecurity. So you already know that there's more stuff happening behind the scenes. And this is what we're going to be talking about. This is the internal components of a Windows machine, specifically the Windows operating system, and the stuff that's actually happening behind the scenes that make the computer run and do what it is capable of doing. The objectives that we have are to understand and interact with Windows processes and their underlying technologies. We need to learn about core file formats and how they are used. And we're going to interact with Windows internals and understand how the Windows kernel operates. With Windows machines making up a majority of corporate infrastructure, because I already talked about that, red teams need to understand Windows internals and how they can be abused, right? So used, but abused. It's a very interesting way that they wrote this. I love that. The red team can abuse Windows to aid in evasion and exploitation when crafting offensive tools or exploits. So think about being on the red team, which means you are a pen tester, right? You're on the offensive security team, and you want to know how to use and, of course, abuse Windows to evade the stuff that Windows can do to detect you and ultimately exploit that Windows machine. Before beginning this, we want to make sure that we understand Windows usage basically and the functionality. The basic programming knowledge that's inside of C++ and PowerShell is also recommended, but not necessarily required. I'm actually not that great at C++. I can kind of understand it. I can make sense of it. I am pretty good at understanding PowerShell because I've done a few videos on PowerShell already, and we use a lot when we do exploitation of Windows machines. But for your intensive purposes, there's a very powerful tool called an AI, and you can use AI tools like Gemini or Meta, whichever your favorite one is, and you can copy and paste the C++ code and be like, hey, can you just help me understand what this code is trying to do? And that way you can wrap your head around what's trying to happen. And then at the same time, you kind of learn how to read C++ code as well. So I'll probably end up doing that in these segments where I can't really fully understand what's happening. This is our virtual machine information. If you want to, if you're using TryHackMe yourself and you have access to OpenVPN, you can actually remote desktop into the Windows machine instead of starting it inside of the browser. I've started it inside of the browser just to make things a little bit simpler for myself. So I'm just going to be using the browser-based version of it. This is going to be the IP address for it, which is going to die at the end of the recording of this video. So this will no longer be available. And the username and password is right here. So, if you're trying to hack into this, I promise you're not going to be able to do it because it's not going to be available by the end of this recording. It's going to be tracked down. It's going to be pulled down. So that's pretty much it. There's some really, really good stuff that's ahead of us, and I'm excited to go through it. So we're going to click complete on the intro, and we're going to move into processes. You can think about a process as the entity, right, that maintains and runs the program. Or when a program is running, you'll see in the list of processes a process name that is associated with that program. A lot of times applications actually use one or more processes, and it has a lot of different components, and it gets broken down into the storage, or it can be broken down to be stored, and you can interact with the various elements of that application or those various processes. Inside of Microsoft Docs, they break it down as this. So each process provides the resources needed to execute a program. A process has virtual address space, executable code, open handles to system objects, a security context, a unique process identifier, also known as a PID, environmental variables or environment variables, a priority class, minimum and maximum working set sizes, and at least one thread of execution. That's a lot of data to wrap your head around. Don't worry about it if you didn't understand that. Hopefully, I think by now you should know what a process is. But in case you didn't know what all that means, not that big of a deal. We're going to go into it. This information might seem intimidating, but this room aims to make everything a little bit less complex. As previously mentioned, processes are created from the execution of an application. So just keep that in mind. They are core to how Windows functions, and most functionality of Windows can be encompassed as an application and has a corresponding process. These are some examples. MSMPENG is Microsoft Defender. WinInit is keyboard and mouse, and LSAS is credential storage. LSAS is a very common one. We do LSAS dumps using something like Mimikatz or something like that. So we've used this a lot in exploitation exercises. But MSMPENG, Microsoft Defender, WinInit to initialize the keyboard and the mouse and to use the keyboard and the mouse. So attackers can target processes to evade detections and hide malware as legitimate processes. This is the smallest of potential attack vectors. So process injection, this is the ID inside of the MITRE attack framework, the attack matrix. Process hollowing, this is the ID. Process masquerading, this is the ID. So if we open this, it will most likely open up, yep, MITRE attack for us. So process injection, right? And then you can go through the description, you can see the various examples and the IDs and the names of the organizations that actually used them, and there are going to be reference sources at the bottom, as well as mitigation and detection techniques that you can use. And then, of course, these are all the references for this specific thing. So all of these have a MITRE attack page that you can go and read a bunch of data for it. And MITRE attack is one of the most powerful things that we've used thus far inside of our SOC level 2 and even SOC level 1 activities, because it's just a massive data of actual attacks that have taken place inside of the real world and the data that was pulled from it, the lessons that were learned from them. Processes have many components that can be split into key characteristics that we can use to describe processes at a high level, and the table below describes each critical component of processes and their purpose. Private virtual address space is virtual memory addresses that the process is allocated. Executable program defines the code and data stored inside of the virtual address space. Open handles defines the handles to system resources accessible to the process. Security context is the access token defining the user, the security group, the privileges, and other security information. The process ID is the unique numerical identifier, and the threads are the sections of a process scheduled for execution. So these things are actually all feed into each other, right? So starts up here and it just works its way downwards. We can also explain the process at a lower level as it resides in the virtual address space. And this is what that breaks down to. So the code is the code to be executed. The global variables are stored variables globally, meaning across the entire system. Process heap defines the heap where the data is stored. Process resources defines further resources of the process. And environmental block data structure to define process information. Process resources can also be considered the dependencies or requirements. These are the further resources of the process that it's using or it provides for use for other things, and the data structure to define the process information. So we have an image right here. You have the full job, right? And then within the job, there's all these individual processes, or the elements of the process, I should say. So code, global variables, process heap, process resources, open files and heaps, environmental block, and then thread 1 through thread however many. This information is excellent to have when we get deeper into exploiting and abusing the underlying technologies, but they are still very abstract. We can make the process tangible by observing them in the Windows Task Manager. And a task manager can report on many components and information about a process. Below is a table. So it'll give you the name, it'll give you the PID, the status of it, and the username that's actually running it. So for example, conhost would be the name of the executable that's running. 7408 would be its process ID. It is currently running, and the owner is the system. The username that's actually running it is the system. And if it's running on a system level, that means it has system permissions. So keep that in mind, right? So if you can actually manipulate this specific executable, that means it's going to continue to run with system permissions. Keep that in mind. They're what you would interact with the most as an end user or manipulate as an attacker. There are multiple utilities available that make observing processes easier, including the Process Hacker 2, Process Explorer, and ProcMon, Process Monitor. These are all things that are available. I think these are the connections to the rooms. Oh no, these are the GitHub repositories for these things. So System Informer under Winsiders, I think that's how you pronounce that. So we have System Informer, Process Explorer. And this is on Microsoft's official website, because this is a Microsoft official software application that's available. And ProcMon should also go to Microsoft, yeah, because this is also a Microsoft unique application that's available for us. The process at the core of Windows internal components and Windows tasks will extend the information about processes, and we will go through them. The following tasks, we will go through them. Open the provided file, log file PML in ProcMon, and answer the questions below. So let's go ahead and do that. So what I'm going to do to make our life a little bit easier, I'm just going to keep this portion of the page zoomed in, and I will go ahead and this is going to look really weird right now, but once I go into full screen, we'll be able to access it a little bit easier, and I'll just shrink that back down. And once it's in full screen, we'll be able to actually go back and forth between the device and be able to do a bunch of cool things, answer these questions. So we're looking for logfile.pml, and we're going to open it in Procmon. So let's see if we can do this here. All right, so on the Windows machine, there's a little folder called Process Monitor. So if I open this thing, it will bring these things up for me. I'm just going to open up the basic version right here, the application itself. It says, do you agree? I agree. Open the application for me so I can open up the log file. And it's actually inside of that same location. As you can see inside of this, we actually have the log file, the Procmon log file, etc. I believe that's the one that I'm supposed to be opening. So we will go to Process Monitor, we'll click File, we'll click Open, and then we're going to navigate to that file. It's already here, so there you go, log file. And we're just going to open that. It's a .pml file. And we're going to give it a second, and it will open, and we'll be able to access the data. So there we go. It's loading. All right, cool. So here we go. This is it. So I'm just going to expand some of these things a little bit to make it a little bit easier for us to read through them. The paths are going to be fun. We need to get that information, and the details are most likely very important as well. All right, so what's the first question? It says, what's the process ID of Notepad exe? So you have the process name, right? And then you have the PIDs. So if we click on process name at the top right here, it should technically just organize it for us by name. So let me see if it's actually going to do this. Okay, so we can't click on this thing, but there's a filter option. So let's see if I can filter by something. So architecture is, let me see if I can do name maybe. So if we do process name, boom, there we go. Process name is, and then we will do notepad.exe, and then let's do that and see what we can find. You did not add the item that you were editing. Add it now. Okay, we'll do that. And there you go. Notepad.exe is 5984 is the process ID. So let's see if that's actually the answer. It is. Excellent. What is the parent process ID of the previous process? So we're looking at this, right? So process name is notepad.exe, and we're looking for the parent process ID. So parent process ID, it actually says it right here. Parent, okay, bro. Parent PID is right there. If I hover over it, I'm sure it's going to do that same thing again. Yeah, there you go. That's annoying. So parent PID is 3412, as we can kind of see right here to make it a little bit easier. So it was, what was it? 3412. So let's try that. And that is true as well. What is the integrity level of the process? That's interesting. So let's see if we can find an integrity level here. All right, so here's how I found this one. I just double clicked it. I went to process, and then right here, there's a level called integrity, or a field called integrity, and the value is high. So integrity level of this is high. And that's it. All right, cool. Let's move on to threads. So a thread, as we saw earlier, is inside of the process, right? So it's an executable unit that's inside of the process or employed by the process. And it's scheduled based on the factors of the device. So the factors of the device could be, the CPU and memory specifications, priority and logical factors, and other things. So it's basically an executable inside of the process itself. And we can simplify the definition by saying controlling the execution of a process. That's what it does. So since threads control execution, this is a commonly targeted component, and thread abuse can be used on its own to aid in code execution, or it's most widely used to chain with other API calls as a part of other techniques. Threads share the same details and resources as their parent process, like the code, the global variables, and they also have unique values and data outlined in this table. So you have the stack, which all the data relevant and specific to the thread. So for example, exceptions, procedure calls, etc. I need to slow down a little bit. I'm kind of like overly caffeinated. Thread local storage, pointers for allocating storage to a unique data environment. Stack argument, unique value assigned to each thread, and the context structure holds machine register values maintained by the kernel. They may seem like bare bones and simple components, but their function is critical to processes. So we're going to open the file log file PML in Procmon and answer the following questions. So it's already open, so we're good. What is the thread ID of the first thread created by Notepad exe? So I think we're looking for chronological, right? operation thread is, okay, so it's listed as the operation thread create. So we're looking for an operation called thread create, and we're looking for the first thread, which I'm going to guess that based on just the timestamps here, 721.3, and they're increasing. So this is the very first one. So operation is process start or thread create. There you go. So the first one that has operation thread create, and the question says, what's the thread ID of it? The thread ID is right here, 5908. So we're going to go over there and do that. Very good. What is the stack argument of the previous thread? And this is listed as thread in the event properties. So if we go to this and just open this up, and we're looking for event properties under the stack right here. Whoa, there's a lot of information. And event is available over here as well. And so date thread 6544, let me see, stack argument of the previous thread. So the stack argument, let me see if I can find that. So the only thing that's listed here under thread is 6584. So I wonder if that's what it is. So let's see if we can do 6584. Oh, that is it. So the stack argument is just this number that's listed under thread under 6584. So great, we were able to find that. And now we can move on to virtual memory. Virtual memory is how internals work and interact with each other, and it allows internal components to interact with the memory as if it was actually physical memory without the concept of collision. So without collisions between applications, and we'll be talking about what that is in a little bit. Virtual memory provides each process with a private virtual address space. A memory manager is used to translate virtual addresses to physical addresses. By having a private virtual address space and not directly writing to physical memory, processes have less risk of causing damage. And it probably also will end up getting wiped because it sounds like it's a part of the RAM, the random access memory, which is volatile memory. So if it's not being written directly to physical memory, most likely this is going to be wiped. But let's see if that's actually the case. The memory manager will also use pages or transfers to handle memory. Pages are essentially just chunks of data, so you can think about it that way. Applications may use more virtual memory than physical memory allocated. The memory manager will transfer or page virtual memory to the disk to solve this problem. And we can visualize it like this. So you have virtual memory. So there's virtual memory, we have physical memory, and then we have virtual memory. So, you know, this block is being sent to this chunk of physical memory. This block is being sent to this one. This block is also being sent to this one. This block is being sent to this one, so on and so forth. And then from here, this one is going to go to the disk, and this one is going to go to the disk. And then you have the individual processes that are running inside of these things. So it seems that not everything is going to actually be written to the disk, and not everything is going to be written to the physical memory. So it's kind of selective, right? So the memory manager will transfer or page virtual memory to the disk to solve the problem. The theoretical maximum virtual address space is 4 gigabytes on a 32-bit x86 system. We talked about the x86 architecture in the last 2 videos. The address space is split in half. The lower half, which is these chunks right here, is allocated to processes as mentioned above. The upper half, these chunks right here, is allocated to OS memory utilization. Administrators can alter the allocation layout for applications that require a larger address space through settings, increase user virtual access, or the address window extensions. So what they're talking about right here in the 32-bit system, this is the example that we're talking about. Assuming that it has 4 gigabytes of virtual address space, the top 2 gigabytes are going to be addressed right here. You can 2 processes as mentioned above, and then the upper half is for OS memory utilization, So my bad. So the bottom half will be to the processes that were listed above. The upper half would be the processes for the OS. And then in this particular case, you have a 64-bit system over here that has 128 terabytes, which is insane. I don't even know what system. That's like a massive system. How is that even possible? I mean, I know how it's possible, but it's like that's a really big freaking system. 128 terabytes, dude. That's insane. And that's just one chunk of it. So technically it's 256 terabytes. That's insane. That's a lot of space. Whew, that's massive. It's like probably like a giant data server or something. Administrators can alter this allocation. Okay, we talked about that. The theoretical maximum virtual address space is 256 terabytes on a 64-bit modern system. So theoretically, it's 256 terabytes. The exact address layout ratio from the 32-bit system is allocated to the 64-bit system. Most issues that require settings or the AW are resolved with increased theoretical maximum. You can visualize both of the address space allocation layouts to the right. Although this concept does not directly translate to Windows internals or concepts, it's crucial to understand. If understood correctly, it can be leveraged to aid in abusing Windows internals. So yes, I understand that. What is the total theoretical maximum virtual address space of a 32-bit system? That would be 8 gigabytes. And what is the default setting flag? What default setting flag can be used to reallocate user process address space? And it was the thing that was inside of this right here, increase user VA. That would be the answer, I believe. And open the provided log file in Procmon and answer these questions. All right, so what is the base address of Notepad exe? And it's going to be listed as the operation load image, the base address of Notepad exe. So let's go here. And the operation address image, right? The operation load image, my bad. So the operation load image of Notepad exe. So let's zoom in a little bit and we'll just open the first one here. And we want the load image. So let's see what we can find here. Oh, I see. So this is what it's asking. So this is what it means when they say the operation load image. So inside of the operation load image, the image base is right here. This is what they're saying. Okay, that makes sense. I should have looked at other things. So, okay, this is the location. Now I need to be able to pull that information. So let's see how we can copy that to use for our answer here. Oh, there we go. Image base. Boom. Take that, copy that, and that should be the answer that we're looking for. Excellent, cool. Let's talk about dynamic link libraries. Per Microsoft Docs, a library that contains code and data that can be used by more than one program at the same time is the dynamic link library. So since it can be used by more than one program at the same time, it feeds into the concept of it being dynamic. They're used as one of the core functionalities behind application execution in Windows. From Windows documentation, the use of DLLs helps promote the modularization of code reuse, efficient memory usage, and reduced disk space, so the operating system and the programs load faster, run faster, and take less disk space on the computer. I will let you know right now, though, like most of the freaking computers that I've ever used at my jobs in the past that have been Windows were slow as hell. So it's like, yeah, I guess it's supposed to make things load faster, but like, really though, bro? It does not. It doesn't though. I'm just saying. When a DLL is loaded as a function in a program, the DLL is assigned as a dependency. Since a program is dependent on a DLL, attackers can target the DLL rather than the application to control some aspect of execution or functionality. And these are some techniques: DLL hijacking, side loading, and injection. And if you want to read more about them, you can go to these individual IDs inside of the MITRE attack matrix. DLLs are created no different than any other project application. They only require slight syntax modification to work. Below is an example from Visual C++ Win32. So include this, define this, include this, and bool, I'm guessing is boolean, excuse me. And then we have this, return to. So let's see what it says. It will define the functions as imported as exported. We will discuss the header file's importance or lack of in the next section. These are the header for the DLL file. So is this the actual DLL file? This is the DLL file itself. So this is the DLL file. And then we have the header for the DLL file that we saw, the defined portion of it, etc. So these are the DLL has been created, but that still leaves the question of how are they used in an application, and they can be loaded in a program using load time dynamic linking or runtime dynamic linking. When loaded using load time dynamic linking, explicit calls to the DLL functions are made from the application. You can only achieve this type of linking by providing a header, which is .h, which is what we saw actually right here. So this is what that is. This is the .h for the header. And then what else do we got? And the import library, which is the lib. Below is an example of calling an exported DLL function from an application. So it's been exported from an application. We are now including it or importing it. So that's the header, and this is the DLL, the library. And then we are now going to, I guess, call on it. And I don't know C++, and I don't want to take too much time to try to break this down, but you can definitely take this into something like Gemini AI or GPT or whatever your favorite AI is, and it'll explain it to you like it's nobody's business. So when loaded using runtime dynamic linking, a separate function, the load library or the load library EX, is used to load the DLL at that time. So if we go over here, do we actually see that? We don't see that, so I guess it would be at the bottom right here. And this is essentially what the function is going to do. I think it's just going to call on the hello world function. Once loaded, you need to use the get process address to identify the exported DLL function to call. Below is an example of loading and importing a DLL function into an application. And so this is an example. It's not necessarily necessary to understand what this is. But you have the hello world variable that equals this, and then if hello world is null, meaning it's nothing, then you call it, I guess, or you will call on that as the else portion. So in malicious code, threat actors will often use runtime dynamic linking more than load time dynamic linking. This is because a malicious program may need to transfer files between memory regions, and transferring a single DLL is more manageable than importing using other file requirements. So we're going to look at this in Progmon again and answer the following questions. So what is the base address of ntdll.dll loaded from Notepad? And it says listed in the operation load image of ntdl.dll. So we're going to look at the operation load image that says nt, so load image right here, and we want this one right here, so ntdll.dll. And what is it looking for? They're looking for the base address that would be available here. So the base address is this piece right here. So let's copy that and go over here and paste that. What is the size of the ntdll that's loaded from Notepad and found in the process tab of the event properties? So process tab of the event properties. So this is where we are, process tab. And we're looking for the size of this thing. See if we can find it. It is right here, but I wonder, so can I copy this? How can I copy this? Oh, there you go. That opened up. Do I have the size? I don't have the size. That's unfortunate. So do I have to manually type this? That would suck if I had to manually type that. Okay, fine. It's what is it? 0x1ec000. So let's see if we can do this. 0x1ec000. There you go. How many DLLs were loaded by the Notepad? Filter the operation by load image in Progmon, and we're going to look for DLLs. So we're going to now go here. We're going to filter the operation, and we're going to filter it by load image in the Progmon. So let me see if I can even find that. And if possible, then we will go ahead and see what we can do. So we'll do process name in this case, and we will do notepad.exe and include, okay, so there we go. We filtered the operation. So when you go under filter and you want to list it under this list right here, you want to click on operation and then right here type load image, and then you'll get this right here. And so what is it asking us? It says how many DLLs were loaded by Notepad. And so now we're looking for all of the DLLs that were loaded. And it seems to be a lot of freaking things right here. So if I go from here, and I guess I can just highlight all of them, it seems to be pretty much all of them are DLLs with the exception of just a few. Let's see. So if I highlight all of them, so let's see if we go all over here, does it tell us how many yeah, so 53. So I would say it's either 53 or 52. I just don't know if this one right here is, oh, that is also a DLL. So it's 53 in total. So let's see, 53. The answer is incorrect. What's the hint? It just says load image in Progmon. So it seems like it's 53 though. I mean, the one at the very, very top right here is the Notepad executable itself. So all of these things it's just asking for DLL, right? So am I missing something? Let's see. Okay, so there are two things that, so when you highlight all of the DLLs, there's 53 of them. There's one that is like a D, where was it? You kind of analyze through them and it'll show you, it's a DRV right here. So there's that, we subtract that. And then this one right here, or one of the other ones is a capital, there we go, this capital DLL. I don't think that counts either. I don't know why it wouldn't count, but I believe that's the only other one. So I basically subtracted 2 from 53 and it gave me 51, and that was the right answer. So that is that, and now we can move on to portable executable format. All right, so executables and applications are how Windows internals operate at the higher level. The PE, also known as the portable executable, this is a formatting that defines the information about the executable and its stored data. So the PE format also defines the structure of how the data components are actually stored. It's overarching structure for the executable and object files, and portable executable and COF, so common object file format, make up the actual PE format. So if we look at this right here, the header is the PE format, and this would be the definitions of the things and the file structures, right? And then you have the contents, the actual sections right here, which is the code and the imports and the data itself. And this is what makes up the file executable. So inside of the PE, inside of the header is where the information about the executable and its stored data is defined, and it also defines the structure of the data components and how they are stored. The P is most commonly seen in the hex dump of an executable file, and we will break down what that is for calc. So in the inside of the PE, inside of the portable executable, we're going to look at the calculator executable to see what that looks like. So the structure of PE data is broken up into 7 components. The DOS header defines the type of the file. The MZ DOS header defines the file format as .exe. So let's see right here in hexadecimal, that MZ right there defines it as executable, and the DOS header can be seen in the hex dump section below, so we can see it right there. The DOS stub is a program run by default at the beginning of a file that prints a compatibility message. This doesn't affect any functionality. The DOS stub prints the message. This program cannot run in DOS mode. The DOS stub can be seen in the hex dump section below. So you see it right here. This program cannot be run in that mode. You can see it. The PE file header provides PE header information of the binary, defines the format of the file, contains the signature and the image file header and other information headers, and it's the section with the least human readable output. You can identify the start of it in the section right here. So you can see that right here, and as you can see the rest of it. So this is the header, the PE, and the rest of it on the right hand column right here. You really, I mean, you can't make sense of it. It's literally mostly dots, like the majority of it are dots. The image optional header has a deceiving name and is an important part of the PE file header. The data dictionaries are part of the image optional header. They point to the image data directory structure. The section table will define the available sections and information in the image. As previously discussed, sections store the contents of the file, such as the code, imports, etc. And you can identify each section right here. So you have text right here. And I think it's actually cut off because I'm a little bit zoomed in too much. So let's see if I zoom out a little bit, if we can see that easier. So there you go. You could see text, you could see R data, data again, P data, etc. So it's the codes, imports, and other data that we can see inside of the hex portion. Now that we've defined the format, these sections can actually be seen like this. So .text would be executable code and entry point. .data is containing initialized data, so strings and variables. R data or I data contains imports, which is the Windows API or DLL. So you can actually see it, right? .data, or excuse me, .text. You have .r data right here. Again, more .data. And let's see, .p data is available over here. So we can see all of those things. We have .text, .data, R data or I data. .reloc is the relocation information. .rc or RSRC is the application resources. And then debug is the debug information. So we can actually see most of those here. We have the text, R data, .data, P data, RSRC, and relocation as well. So all of that stuff was there. So what PE component prints the message this program cannot run in DOS mode? And we have that up here. So this is the DOS stub that is available for us. So let's go look at that right there. And we're going to look at the open Notepad.exe in Detected Easy and answer these questions. So let's go here and let's see if we can actually find Detected Easy. I think it's a new, or it's a different software that we're supposed to be using. Okay, so there's die right here is Detected Easy. Goodness, bro. The stuff that these guys do to us. Okay, so all right, so open this in Detected Easy, and what is the entry point? Reported by die. There you go. I should have probably just looked at that first. What's the value of number of sections? What is the virtual address of .data, and what string is located in those sections? So let's see. What's the entry point reported by it? Let's see how long this takes. Okay, cool. Here we go. We have it here. We want to open notepad.exe. So I need to go ahead and find Notepad specifically. I wonder if I can just browse to it, or if it's something that I need to actually find inside of the PC's programs, etc. So let's go and try to just kind of find the program itself. Okay, so I searched for Notepad inside of the search box, and then I right-clicked it and I said open the location of this file. And so we can see the location is this full path that I did right here. So let me click back one more time, and there you go. That gives you the full path. So see users, THM attacker, app data, roaming, etc., etc. So I'm going to just kind of keep this right here, and then we're going to find it using that location. So we're going to go to local disk, we're going to go to users, and then we're going to go to THM attacker, and then we're going to go to, oh, I can't find app data. Brilliant. So maybe I can just do it like this. So I will do app data like that, press enter like that. So we can do it like that. So we'll actually type the whole thing over here. There you go. And we can now click on Notepad and then open Notepad. Okay, so here's some interesting data for this thing. So we're going to expand this and see what we can find. This is a lot of tiny data. Oh my gosh. All right, what's the entry point reported by DIE? So I'm looking for the entry point. And it's right here towards the top right there. So that's the entry point. Let me see if I can right click and copy that. So hopefully that actually copied. Okay, great. What is the value of number of sections? So let's try to find that. It's right here. So it's actually called sections, and the value is 0006. So that would be it. And what is the virtual address of .data? So let's see where that would be. Okay, so this was this was difficult to find. So the hint tells us to look in the PE window, and I was looking for an entirely different application, but there's actually a button right here, the PE button, and it'll open this up right here. So now we can actually look at the section they're talking about, which is the section tab of the PE window that's asking for the virtual address. So section tab of the PE window, which I think I might be here. So let me see if I can find the section tab for sure, and then get the virtual address. All right, so sections is right here on the left menu right here, and a virtual address is right there. And they want it for .data, so we're gonna look right here, and that's the virtual address. So let me see if I can edit this, and there it is. And so there is that. If I can copy that, that would be great. And then paste that and submit it. There we go. And what string is located at the offset of, we'll say 99C, and that's in the strings tab. So let's go to the strings tab, and then we're going to look for 99C. So let's find 99C, and there we go. So if you organize it from smallest to largest, it's line 170. And the string itself here is Microsoft Notepad. All right, here we go. Interacting with Windows internals. To be able to interact with Windows internals, you can do it relatively simply or easily through the Windows API calls and they provide a network native functionality to interact with the Windows OS, and the API contains the Windows 32 API and Windows 64. We'll only provide a brief view of a specific few API calls relevant to Windows internals, and there's the Windows API room. That's exciting. I'm very, very excited to actually learn about that. That's something I know for a fact. Yeah, I have not done this. I would love to learn how to interact with Windows through APIs. Most Windows internal components require interacting with physical hardware and memory. The Windows kernel will control all programs and processes and bridge all software and hardware interactions. This is especially important since many Windows internals require interaction with memory in some form. An application by default normally cannot interact with the kernel or modify physical hardware and requires some kind of an interface. And this is solved through the use of the process modes and access levels. Windows processor has a user and kernel mode. The processor will switch between these modes depending on access and requested mode. The switch between the user and kernel is often facilitated by system and API calls and documentation. This is sometimes referred to as switching point. So the user mode, no direct hardware access. Kernel mode, direct hardware access. Creates a process in a private virtual address space in user mode. Ran in a single shared virtual address space in kernel mode. Access to owned memory locations in user mode. Access to entire physical memory in kernel mode. So obviously kernel mode has a lot more power than user mode does. So we can see it right here. The switching point is basically the point between the user mode, or also known as user land, and kernel mode, which is pretty much the system and the nitty gritty. So you have the user application. I think I should stay out of that. So user application right here, the API, the Windows 32 API that actually interacts with the system calls, or the portion where you can actually start interacting with the kernel, and through the API and the calls of the system, you'll be able to interact with the kernel, which is controlling the physical memory and the hardware. So applications started in user mode or user land will stay in that mode until a system call is made or interfaced through an API. When a system call is made, the application will switch modes. Picture right is the flow chart. When looking at how languages interact with the API, this process can become further warped. The application will go through the language runtime before going through the API. The most common example is C executing through the CLR before interacting with the Windows or Win32 API and making system calls. We're going to inject a message box into the local process and demonstrate proof of concept to interact with it. The steps are as follows. Allocate local process memory for the message box. Write copy the message box to allocated memory. Execute the message box from local process memory. At step 1, we can use open process to obtain the specified process. So we will use, this is C language, this is not C++. So we're going to handle the process, open the process, right? And then at step 2, we can use virtual allocation executable to allocate a region of memory with the payload buffer. So this is where we see right here, this function right here, and the size of the payload right here. At step 3, we can write the process memory to write to the payload allocated region of the memory, and this is the function, and we can see the details right here. So open target process, allocated memory region, data to write, byte size of the data. At step 4, we will use the create remote thread to execute the payload from memory. So this is a variable, and then we're now creating the remote thread function. So open the target process, default size of the stack, pointer to the starting address, and immediately after creation is the value of 0. So we're going to open the command prompt and actually execute the provided file that's inside of our injection folder and answer these questions. So let's go ahead, and I can now close this so I no longer need this. It was an interesting tool though. So we're going to go right here. We will open up a command prompt by going to cmd.exe. I'm already inside of the user's attacker. So what I need to do is I need to go inside of my desktop to be able to get access to the injection. There we go. That's where we need to go to, process injection. So let's do that. I don't know why they spaced it out. Process injection. There we go. And now in here, we can see that we have the executable. So we could basically just do this, I think. So inject-poc.exe. And there you go. it just popped up. There's a little message that popped up. I don't know if I could copy this. Can I copy this? Oh my God, why are they making it so difficult right here? So enter the flag obtained from the executable window. They want me to manually type this. These guys are kidding, dude. I don't want to manually type this. What if I clicked OK? Will it be inside of this? No, it's not. So I have to actually run it and try to capture this somehow. Golly. Okay, manual typing it is. Let's drag this off and we will type it manually. Okay, so the key point here is that this is actually case sensitive and all of these things need to be done correctly. This is a lowercase l, this is an uppercase L. I thought this was an I, like a capital I, but it's not. It's a lowercase l, this is an uppercase L, and the rest of it is exactly as you see right here. It is case sensitive, so keep that part in mind. And yeah, that's it for that last one. So let's go into the conclusion here. So the key point that we take away from this is that Windows internals are the core of how the operating system actually works, and they cannot change without compromising the operating system. And that's why they're so attractive for attackers. So literally they are the building blocks of how the operating system inside of network or inside of a Windows computer works. And so if you can modify them somehow, then you can modify the way that the system works. And if you can actually modify them without stopping the functions of the system, so it appears as if the system is just running normally, but in the background it's actually doing something that you want it to do as the attacker, then you have accomplished your job, your task. The attacker can easily abuse the functionality of Windows internal components for nefarious reasons. For more information, there's the Abusing Networks Internals room. And many of the concepts covered in this room can even translate to Unix counterparts. While specific of the attacks and how they're executed may change, many of the core concepts stay the same. Overall, Windows internals are here to stay. Both red and blue teams need to be aware of their capabilities, including how and why they are used. So this video and the last two videos were very, very detail oriented for me. I followed instructions essentially to be able to get the answers that we needed for them. And this was a learning curve. I went through a learning curve with these videos. So I did my very best to try to kind of like break things down as I understood them. But for the most part, as you saw, I was kind of just reading through everything. So hopefully it made sense to you. Hopefully you were able to get the information and get the answers that we needed and all that good stuff. But for the most part, this was definitely a learning experience for me. It was a learning curve. And I think that's basically what it's going to be like for the rest of the malware analysis module, because it requires very detail-oriented review of very detail-oriented stuff inside of these computers. So we're really looking at the core functions, the building blocks of a computer, not so much the application level stuff. And I mean, I'm enjoying it because I'm learning, but this is stuff that I have to review and re-review to make sure that it actually clicks for me. So if you're having a hard time grasping it, don't worry, we're both in the same boat, basically. That's basically what I'm trying to say. So we're gonna click complete and we'll be done. All right, so congratulations. I hope you got to the same end result that I just got to, and you were able to get all of those answers. And if you want to find more videos like this one, especially as we wrap up the SOC Level 2 pathway of TryHackMe and our just general SOC Level 2 playlist that we have, and as we graduate to PenTest Plus, we have more videos that drop every single week on Fridays for PenTest Plus. And then, of course, there's going to be, right after SOC Level 2 is done, I can now move into the AI for cybersecurity, which is a really big piece. So all of those things, to be able to get access to all those things, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And you will be able to get obviously access to all those things, and you can drop a comment in the comment section below if you have any questions for me, or if you want to just say that you also had a learning curve as you went through it, just so we can kind of be in the same boat. But that's pretty much it for the video today. So just make sure again that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out in SOC Level 2, in PenTest Plus, as well as AI for cybersecurity, and of course everything else that we're going to end up doing for TryHackMe as well. If you're serious about your SysAdmin training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there. Or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comments section. And that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video later. In episode 41 of the SOC Level 2 training series, we're going to go through the Dissecting PE Headers room, which is a part of the malware analysis module that's a part of the SOC Level 2 pathway of TryHackMe. And so we've gone through a lot of cool stuff, or a lot of like really detailed stuff so far in the SOC Level 2 pathway, specifically in the malware analysis module. And today we're going to continue down that same theme, because we're going to be dissecting portable executable files and how their specific headers work and how those headers feed into the actual execution capabilities of those PE files. So we have obviously our introduction, we have the overview of the PE headers, we have the image DOS header and DOS stub. Then we have the image NT header, optional header, image section header, image import descriptor, packing and identifying packed executables, and of course we have our conclusion, and then I'll give you some review and final thoughts, and then you will be dismissed for the day. So that being said, that is our overview of Dissecting PE Headers. If you're serious about your SysAdmin training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there. Or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into Dissecting PE Headers. If you've ever used a Windows operating system, you will probably seen this .exe extension in a variety of different files, and .exe stands for executable. And as the name suggests, it contains code that can be executed, right? You can run it. Therefore, anything that needs to be on a Windows operating system is executed using the executable file, also known as a portable executable file, also known as a PE file. So it can be run on any Windows system, and it's a common object file format, also known as COF. Data structure. The COF consists of PE files, DLLs, which is the dynamic link libraries, shared objects in Linux, ELF files, and for this room we're going to be covering the PE files. So given the background knowledge, it becomes essential to understand what it is and what it does to learn malware analysis, and we're going to go through understanding the different headers in a PE file, learning how to read PE headers, identifying packed executables, and using the information from PE headers to analyze malware. Before we go through this, you should have already seen the intro to malware analysis, which is the very first thing that we did inside of the malware analysis module. So if you haven't seen that already, I would highly recommend you watch that, because there are going to be some core concepts that were covered in that video that we're going to be kind of following along or compiling on as we go through this particular video in this room. So that being said, we are now officially done with our introduction, and we can go to overview of the PE header. When you look at the contents of a PE executable, it basically looks like anything else, really. It has a bunch of bits in it. So if you open it inside the hex editor, you'll see something like this, right? So there's literally just a bunch of bits. And to the naked eye, it's pretty much useless unless you are a super freaking genius and you know what all of this translates to. But you'll also see this in the side right here, which is kind of human readable. There are some elements to it. So it says, this program cannot be run in DOS mode. And then there is some other stuff, which is jargon. And then the rest of it is also jargon. So with the exception of this one little sentence, the rest of it is still pretty much jargon. Or I guess we can call it gibberish, not necessarily jargon. So we're going to try to make sense of all of these things as we just saw them right here. And we're going to use a couple of utilities that will actually help us make sense of it. One of them is called the WX hex editor, and it's inside of the virtual machine that's been given to us inside of this room. And as we view it in the hex editor, we can see that manually interpreting all this becomes super freaking tedious. So we're going to use the PE tree that's also available inside of the virtual machine to help us analyze those PE headers. And this is what you can see. So I've actually used this in some room before. I don't remember which room it was, but I do recognize this specific layout. So you can see it literally is a kind of like a tree format where you have the DOS header, stub, end data, and it just goes and breaks down each individual element of the executable. And then when you click on any one of them, there's more data that's present to us on the right hand side. So the tree structure drop down menu, the left pane is just the shortcuts and to the menus in the right pane. And some of the important headers that we will discuss are going to be the image DOS header, image NT header, file header, optional header, image section, and image import. All of them are under the NT headers. And then you can also, we have this like beautiful little visual, this graphic that kind of helps us understand this. So these are all of the data type struct, and a struct is a user-defined data type that combines several different types of data elements in a single variable. So in one variable, you have a bunch of different types of data elements. So think about it as a dictionary inside of Python, for example. You can store a dictionary inside of one variable. Inside of that dictionary, you can have infinite number of key value pairs. So for each key, there's going to be a value, and you can have as many of them inside of a dictionary as you want, and then you can assign that dictionary to one single variable. So it's user defined. We need to see the documentation to understand the type for each struct variable, and the documentation can be found on the MSDN website, where you can find the data types of these different fields inside of these things. And this is the actual Microsoft Learn website. So we have under these various, there's so many freaking things over here, but it's specifically under Windows, and then Win32 API, and then WinNT, NSWint image, etc., etc. So you can find this if you want to by going to that specific link, which is learn.microsoft.com, and then just type in the rest of the stuff right here. You can also just Google image NT headers 32 structure from Microsoft and then find that. Or if you're using TryHackMe, like I am, you can just click on this link and it'll open it for you. We use the tools mentioned earlier, but there are a lot of other tools that are available that can actually do similar tasks for you as well. So the goal is not necessarily the tool itself, but instead the PE format, so that we can perform the same analysis using any other tool that we come across providing the same functionality. So we're going to move on and actually do some of those things. The question here is, what data type are the PE headers? And they are bits, right? So if we go over here, it actually has it available for us right here. Digital data, I guess we could say it's a combination of bits. Hex editor, we'll see. I think it would be digital data. That's probably the answer that they're looking for. I stand corrected. It is actually the struct data type. So there you go. Struct data type would be the answer. All right, let's go into the very first one, which is that image DOS header and the DOS stub. All right, for this section, we're actually going to use the virtual machine. There's a bunch of instructions that are available to us right here. And instead of reading through them and then doing the exercise, I'm just going to read through them while I do the exercise. So you'll kind of just see the demonstration as we go along with it. I've already started the virtual machine and it was in split screen view. But you can always, if it doesn't show for you, you can just click that and it'll show it to you. I'm just too zoomed into the screen right now, so it won't really look right if I click that button. So I'm going to zoom out and then I'll open the virtual machine and then we'll just move along that way. You can also you can log into it using these credentials if you have access to TryHackMe as a paid subscriber. I want to say this is actually a paid room. It is a free room. That's actually very, very cool. So if you just have a basic free username and password with TryHackMe, you'll be able to use this room as well as the virtual machine that's attached to it. So you can technically use OpenVPN and connect to the IP address that is assigned to this particular room. For me, every single time that you launch it, the IP address is going to be different. So this will not be the IP address that you'll get access to. If you've never done this before, I'm just kind of giving you all those information, but there's chances are that you actually have done this before, so you know what the hell I'm talking about. So once the machine starts, we can see that there's a directory on the desktop named samples. In that, we're going to find the PE files. We're going to open Redline in a hex editor and see what it looks like, and we can use the WX hex editor utility in the attached VM to open it, and then we'll press the menu on the top left corner, search for WX editor, etc., and then we'll be able to find it. So I'm just going to do that. I'm going to open it up, and then we're going to do some of the analysis. The questions that we have over here are, let's see, so it says how many bytes are present in image DOS header, what does MZ stand for, and in what variable of the image DOS header is the address of the image NT header in the attached VM, open the PE desktop, etc. In PE tree, what is the address of image NT header? And that's pretty much it. So what does MZ stand for? That's probably something that's actually inside of the content for us that we can actually kind of run through real quick. So I'm just going to cheat this real quick and see what I can find for the value of Mark Zbikowski. I think that's probably the answer. So Mark Zbikowski. It reminds me of Mike Wazowski from Monsters Inc., but I think it's Mark whatever. I'm gonna destroy his last name. Spikowski. We'll call it Spikowski. Mark Spikowski is what MZ stands for. Now the rest of them we actually have to go through the exercise to find. So now I'm going to zoom out of my screen a little bit, and then we're going to launch our virtual machine in split screen. And what I'm going to do is I'm going to open it up in full screen so that we don't have to kind of worry about just using half of the screen. And then I'll crash that down, and I'm going to open up these instructions in my secondary monitor, and that should be good enough for us to run and gun. So let's do it. Okay, so the first set of instructions is to just click on that button right there in the top left corner, which is the equivalent of the start menu in Windows, and then we're going to look for the WX hex editor by just doing WXH, and then it'll open it up for us. And the instructions are to go ahead and open up the very first thing that we're supposed to be. So I mean, the question asks us to look for the image DOS header of the how many bytes are present in the image DOS header. So I can just click on file and open it in the samples folder that's on my desktop. So let's go into the samples folder, and we can see Redline is actually, yeah, so that's what I was supposed to be opening. The very first one that we're going to use for the analysis is Redline. So now I have Redline. I'm going to open up this, look at this. It's basically, this looks very familiar to the stuff that we see inside of Wireshark, because Wireshark also has a similar, one of the panes, one of the sections of Wireshark looks very much like this, where you actually have the bits and then you have the hex value of everything. So, okay, so here we go. Now, let's read through the instructions from the very top. So we're going to open it up, and this is what we see. So it is let's use the help of PE tree to see what the PE file actually looks like. So if we run the following command in the terminal in the VM, it's going to open up PE tree for us. So if you've ever used the terminal, you know that most things actually require some kind of an argument. So wow, it's a white terminal. Usually it's a black terminal. So if I go here, basically what we need to do is just run PE tree, but then we need to give it the path of the file that we want to use. So in this case, working directory that I'm in, I think desktop is already here, right? So I would do PE tree, and then in the desktop there's going to be the samples folder, and then inside of that was the Redline executable. So that's what we do. And then we run that, and now it's going to open up the Redline executable with PE tree. So PE tree, there you go, error creating runtime, no such file or directory. How is that even possible? Is that supposed to happen? So let's give it a second to see if it'll actually work. I feel like that should not be the case, because I ran it exactly how the instructions tell us to run it. So hopefully this is just kind of one of those things that happens before it opens up PE tree. So I'll give it a couple of seconds and see what happens. Okay, in the notes of the section that we're on right now, it says it'll take approximately 8 minutes for this thing to launch, for the PE tree utility to launch. So in the meantime, we're going to do some of the basic analysis that is available to us inside of the hex viewer, the WX hex editor. So the very first thing that they tell us is to look at the very first 64 bytes of the PE file, which will analyze the valuable information which is inside of the image DOS header. So if we go over here and look at the first 64 bytes. Now, the way that I've expanded this, it actually doesn't show me like that. So if I go and try to kind of narrow this down, because the way that it looks on their screen is that they have, you know, I think it like 16 bytes per section. So it's like a little bit, let's see if I can expand it a little bit more and kind of give us that. So that kind of looks a little bit right, I think. So essentially, the first section that they highlighted was this whole piece right here. What you can see right here, this is pretty much the header. This would be the first 64 bytes, I believe, because that's exactly what I'm looking at over here. Now, at the very first portion of it, we have the 4D5A. So let me kind of zoom in here for you. So this 4D5A is this intro piece right here. So this, when I highlight it right here, we can see that this has actually also been highlighted on the right-hand side. And that's for the MZ, right? So the acronym that we already answered, which is that Mark Spagowski character, that guy. So MZ is the acronym that has been assigned the initials for the architects who created the MS-DOS file format, their identifier of the executable file format. And when they're present at the start of a file, the Windows OS considers it a portable executable file format. So if you can see MZ in the hex right here, that, as we can see right here, if you see that by just looking at the bits, right, or the bytes, excuse me, when you look at that, you can conclude that this is actually a portable executable file, because now we know that MZ is essentially at the very, very beginning of any file that's an executable. Now, if we you know, whenever the PE tree opens up, we're going to be able to get to see some other things that would be available inside of the image DOS header section of it, like, for example, eMagic and what the value of that is. And what happens here, so let me go back into the lecture here for us so that we can kind of read through those, because I do actually need to wait for that thing to load. I didn't realize it was going to take 8 minutes for it to freaking load. So what do we have? So we looked at the 64 bytes, and so this is where we are, right? So this is what it will look like if we looked at the image DOS header section inside of the PE tree utility. Now it says eMagic, which is that specific portion inside of the image DOS header, and it has this value. And this is the same that we saw in the hex editor previously. So the byte order is now reversed because it says MZ, and it has this piece right here, whereas over here you can see that MZ comes first, and then the rest of it comes after that. So it's in reverse order. What happens that because of endianness, it's reversed, and Intel x86 architecture uses the little endian format, while the ARM architecture uses big endian format. The last value in the header is called the ELFA new, and in that screenshot that we see right here, it has a value of this right here, and this denotes the address from where the image NT header starts. Therefore, in this PE file, the image NT header starts from this specific string. And we can see this highlighted in the hex editor. So if we actually go to the very end of this, we can see that this is what's highlighted. And again, it's in reverse view, right? So whatever you see here, it's reversed because of little endianness. So you would actually see 000000D8. So if I go over here and just look for the 000, this piece right here, that's what that piece is right here. So that's where it starts. And then you can see right here, because it's literally empty in all of that section. So this piece right here is where the whole thing starts, as we can see right there. And we can even just highlight the start point of it, and it would highlight it for us in this section as well. So that's where the whole thing starts, right? So we have to remember that the byte order is switched when we compare these in the PE tree utility and those we see in the hex editor due to NDNS. It's generally not much use apart from those fields, especially during malware reverse engineering. The only reason that it's in backward compatibility between MS-DOS and Windows. So the DOS stub in PE tree utility, whenever it does load, we can see that the drop-down menu after image DOS header is the DOS stub. Let's expand it, which it kind of looks like this right here. And it contains the message that we also see in the hex editor. This program cannot run in DOS mode as seen in the screenshot below right here. And we already saw that previously when we were looking at the very first screenshot for this. So the size, hashes, and entropy show by PE tree are not related to the PE file. Instead, it's for the particular section that we're analyzing, meaning the DOS stub section, and they're calculated based on the data in the specific header and are not included. The size value denotes the size of the section in bytes. Then we see different hashes for the section. We learned about hashes in the intro to malware analysis room, so that's why you should have watched that video. But you should also know by now what hashes are, so I hope that this is now your very first introduction to hashes. Entropy is the amount of randomness found in the data. The higher value of entropy, the more random the data is. And we're going to learn about the utility of entropy as we learn more about malware analysis later on. The DOS stub, is a small piece of code that only runs if the PE file is incompatible with the system that it's being run on. It displays the message above. For example, since the PE file we're examining is a Windows executable, if it's run in MS-DOS, the file will exit after showing the message in the DOS stub, which is, this is not runnable. You can't run this program in DOS mode, right? So it only runs basically when the PE file is incompatible with the system that is actually being run on. So how many bytes are present in the image DOS header? So I mean, if I go ahead and try to look at the section right here, maybe we can actually get the information. I wonder if this is, oh, it's already opened. Excellent. So it's already opened for us. So we can now go to the image DOS header, which is where, so I guess it would be right here at the very, very top right here. So it says how many bytes, right? So let me see right here. We can see the specifically that it's asking for. Let's see the question in the image. So how many bytes are present in the image DOS header? So we can go ahead and look at it. I would presume that it's 64 bytes. It's actually part of the lecture notes. So I want to say it's 64 bytes. I think they actually already said that for us. Yeah, so it is 64 bytes. It's not something that will be available to us over here. It was something that they actually gave us in the documentation, in the notes. So in what variable of the image DOS header is the address of the image NT header saved? So if we go over here and try to see, I wonder if this is also a part of the, so inside of the image DOS header, the image NT header, there you go. So we can actually see that here. In what variable it would be the NT headers, I'm guessing, the file header, optional header, section header, etc. So I would say it's inside of the NT underscore header is where it's stored. So let's see if that's actually it. Nope. NT, whoops. Okay, so that's probably not it. So it actually is inside of our lecture notes as well. So the image DOS header is inside of it. There's the E underscore LFA new, and this is the address where the image NT header starts. So it would be in this particular variable that we can say that that has been stored. So if we go over here and try that, it is. So this is the variable of the image DOS header where the image NT header has actually been saved. So if we go to that and try to find that, ELFA new right here, right there, that would be where it actually starts. And that is the last item, as they said in the lecture notes, which denotes where the image NT header actually starts and where it's been saved. And then it says, in this, open this specific file in PE tree. What is the address of the image NT header of this file? Which I hope that I can just run the PE command and not wait another 8 minutes for it to open up. But we're just going to open this up inside of PE tree to see what's the address of the image NT header for that specific file. Okay, so had I known that I needed to load this, I would have loaded it much sooner, and it took, again, some more time to do it. And then for the rest of these tasks, it's going to also ask us to analyze this particular one. And then in the very last task, it asks us to reanalyze the redline video, or the redline executable. And I already had closed PE tree for that. So I had to rerun it, and I'm hoping that it will open up the redline variable or the redline executable for us. This is the analysis of the funky name executable, whatever the hell this is. And in that, we have the variable that they were talking about, which is this piece right here. So I wonder if we could copy that specific element and paste it, and we can. Great. So that was the address of the image NT header for that specific file. Now we can move on to the next one, or the next series of tasks, and keep analyzing this specific file. And from that, I really, really hope that it will actually open up a second instance of PE tree with redline for us. And that's really all I can hope. Unfortunately, I can't find the name of this, so hopefully I'll be able to detect the difference by just looking at some of these bytes over here, just to know what I'm looking at. All right, now let's move on to the image NT header itself. So the rest of this video is essentially going to focus on the rest of this, the rest of the elements of the image NT header, because if you remember, as I expanded it, there were multiple subsections underneath it. So we have NT headers, section header, import descriptor, and resource directory. The NT header, we have the signature itself, the file header, and the optional header that's inside of it, I believe. Yes, so inside of the NT header, we actually have those different subsections, I should say, inside of that. So the starting address of this is found in ELFA new, which we already saw. In the redline binary, we saw that this address was that. So we're going to look at this offset, and we can do that by pressing Control-G in the hex editor window, or going to edit, go to offset from GUI. And then we can see this right here, which will allow us to jump to that specific section, which is this piece right here. Now, if we do this, we got to make sure that we actually click select from beginning, which is what you can see right here, so that it'll go from the very, very beginning of all of this hex to actually be able to find that for you. And then in the type of branch option. And then hex is obviously going to be the one that we're going to choose, because that's what we're analyzing. The first 4 bytes of the NT header consists of the signature, and we can use this as the bytes 50, 45, 0000, which we can see PE in the ASCII that's shown right here. So when we actually go over there, specifically in the hex, we can see in the ASCII where it's PE, so that is portable executable. Signature denotes the start of the NT header. Apart from the signature, the NT header contains the file header and the image optional header. The file header contains vital information. These are some of the screenshots, as we can see right here inside of the file header. So the machine, number of sections, time, date, stamp, etc. The machine mentions the type of architecture. In this example, we have i386, which means that the PE file is compatible with a 32-bit Intel architecture. Number of sections contains the different sections where code variables and other resources are stored. It mentions the number of sections that the PE file has. In this case, we have 5 sections. So we can see that right here, 005. Time date stamp contains the time and date of the binary. Pointer to symbol table and number of symbols are not generally related to PE files. Instead, they are here due to the COF file headers. Size of optional header contains the size of the header, which we will learn about in a little bit. Characteristics are another critical field that mentions the different characteristics of the file. In our case, it tells us that it has stripped relocation information, line numbers, local symbol information, and it's an executable image and compatible with a 32-bit machine. While we look at the file header using the PE tree, we can see that the hex values for each of these are known in the utility, are shown in the utility, and we can see where they are individually located right here. So you could actually see, because they essentially go section by section, bit by bit, right? Or byte by byte, I should say. And we can see they're highlighted over here. But again, it's to the naked eye, this is just gibberish for the most part. So we really do need this PE tree tool, and there we go. So now we have red line over here, and it does say it in the name, which is actually very helpful. So if I go to the other one, it says the name right here as well. So there we go. So we actually have the name of both of them, which is super freaking helpful. I'm super excited that the name is over there. So, okay, so open this in PE tree. Is this file compiled for a 32-bit machine or a 64-bit machine? And if we look at it right here, it'll tell us, which means where. So inside of the machine itself, we're looking at the file header under the NT header itself to see what kind of machine it's under. So if I open this up and basically go inside of the, what is it? If I click on NT header right here, it'll expand it for us, right? So on the left-hand side, we actually have all of these categories that are inside of this overall structure. And when we click on one, it'll just jump to that section for us. So if we click on NT header, it'll actually open up the NT header section for us right here. And then we have file header, optional header, etc. So we can see that it's actually I386 for the machine inside of this as well. So if we go over here to the answer right here, it says this is for da-da-da or 64-bit machine. And we can conclude that it's for a 32-bit machine, right? So what would be the, check the characteristics in file header? Yeah, I mean, it is for a 32-bit machine. So I guess it would be what, 32-bit machine, like that. There you go. Okay, so that's the format of the answer. What is the time date stamp of that file? So we can go over here as well, and then we can see that we have this full piece right here. So I wonder if I could just copy that and paste that whole thing. Cool, that's the answer for that. Excellent. So let's go into the optional header. The optional header is also part of the NT headers. It contains some of the important information we can see. So let's see, this is what it looks like. And then you can see there's a lot of data right here. The bold ones I feel like are like really important. So the image base, address of entry point, etc. It starts right at the end of the file header, and we can see where it would be right here. So this is where the bits themselves start, and then in ASCII, this is what it looks like, which is the male symbol, I think. And then there's like a sad face. I think that's what that is. So this is a lot of stuff. These are some of the key elements of it, I think, that were being pointed out. So the magic number tells us whether the PE file is 32 or 64-bit. If the value is this right here, it denotes 32-bit. If the value is 20B, so 10B is 32-bit, basically 20B would be 64-bit. And we can see that the highlighted bytes, which show this, and it's 10B, so it shows that is a 32-bit. So again, it's backwards, right? So 10B0 instead of 0B01, it's 10B0 because it's little endian, so it's all reversed. So 10B shows us that it is indeed 32-bit. It's significant. So address of entry point is significant from malware analysis reverse engineering. And it's where the Windows will begin execution. So in other words, the first instruction to be executed starts at this point right here. So that's actually very important to know. This is a relative virtual address, so RVA, meaning that it's at an offset relative to the base address of the image once loaded into memory. So it's an offset relative to the base address of the image. Base code and base of data are the addresses of the code and data sections respectively relative to the image base. And image base is the preferred loading address of the PE file in memory. Generally, the image base for .exe files is this, which is also the case for our specific PE file. So if we actually go to this right here, image base is, yeah, exactly that. So base of code, base of data is what we see right here. Address of entry point is what we have right here. The magic, we already saw 10B, which implies 32-bit. So far we have some pretty cool information, or I guess, I don't know if it's cool, but it's useful information. Since Windows can't load all the PE files at this preferred address, some relocations are in order. When the file is loaded into memory, these relocations are then performed relative to the image base. We have subsystem representing the subsystem required to run the image. And it can be Windows native, GUI, which is graphical user interface, CUI, which is command line user interface, interesting, or some other type of subsystem. And from our screenshot, we can see that the subsystem is this 0002 representing Windows GUI subsystem. And we can find the complete list in the Windows documentation to just see which type of code, I guess, would be relevant to each other types of these subsystems. The data directory is a structure that contains import and export information of the PE file, called the import address table and export address table. This information is handy as it gives a glimpse of what the PE file might be trying to do, and we'll expand on this later. So there's obviously more information as you saw in that list. We're not going to go into that, but you can learn more about them inside of the Microsoft documentation. So now, which variable from the optional header indicates whether the file is 32-bit or 64-bit, and that is that very first one, which is magic. Now, what magic value indicates that there is a file in 64-bit? So it was 20B, I remember that, but it's basically 0x, it's, where is it? It was right here. There we go, 0x020b. That's the value that we're looking for here. So let's go there and paste that there. Now, in our specific thing, it says, what is the subsystem of the file for desktop, etc. So let's go and find the subsystem portion of this, which is right here. And it's Windows GUI. So this is the Windows command line user interface. So we'll just copy and paste that into this. Great. So now we are moving along pretty smoothly because I don't have to keep waiting for PE tree to load. I should have done that at the very beginning. So I hope you learned from my mistake. Let's talk about the image section header. In this specific section, there is the data that a executable needs to perform the functions, for example, the code, icons, images, the user interface elements, and all of that stuff. And all of that is inside of the image section header. And we can see this nicely inside of our PE tree outline. So image NT headers, right? NT headers, image section header, and then now we have these various elements like .text, our data, etc. So .text, our data, end data, and RSRC. So .text is a text section, generally the section that contains executable code for the application. We can see for this section, it includes code, execute, and read, meaning that this section contains executable code, which can be read, but it can't be written to. The .data is the initialized data of the application. It has the read-write permissions, but it doesn't have execute permissions. So we can actually see this right here as well, I believe. So .text, it should show us, let's see, what do we have? I really am very curious. There we go. Code, execute, read is under the characteristics of it. And each one of them should have under characteristics the various elements of it. So our data or iData often contain the import information of the PE file. It helps the PE file import functions from other files. End data contains uninitialized data. Reloc is the relocation information. RSRC is the resource section containing icon images and other resources that are required for the application UI. Now that we understand this, we can see what important information the section headers for each section include. So the virtual address is the field that indicates the section's relative virtual address, so the RVA inside of the memory. Virtual size contains the section's size once loaded into memory. Size of raw data represents the size as stored on the disk before the file is loaded into memory. And then characteristics are the stuff that we just saw right now, for example, whether or not it has read, write, or execute permissions. So how many sections does the desktop, this specific executable that we have, so how many sections does that thing have? So let's go into the subsections piece right here. So inside of NT headers, we're going to go into the image section header and expand that. And inside of this, we need to see how many sections exist. So it seems to have 3, because the rest of them, I feel like there's nothing even in here. Or no, there is, but there's no names to them. So I guess these are the ones that actually seem to have, but I mean, so technically it could be 7, because there's 7 of these arrows that I see right here, but only 3 of them have names, like the actual names associated with them. So let's try 7. Okay, 7 is the answer. Even though they don't have names, there is data inside of these different elements here. So that is the right count. Now it says, what are the characteristics of the resource section of that. So if we go to the resource section and then go to characteristics under resource, we can see this full piece. So I'm just going to copy that and just paste that whole thing. And we can see that it has execute, read, and write permissions. And this is the initialized data inside of the characteristics for this piece. Okay, cool. Let's go to image import descriptor. Executable files in general don't have all the code that they need to perform their functions, and Windows OS has a bunch of stuff that can be pulled from the Windows API to help the executable do the things that it needs to do. And all of that information, or all of the calls to the API, are stored inside of the image import descriptor. And it shows the various APIs that the PE file loads when it's executed. So it's handy in identifying the potential activity that the PE, the executable, is trying to perform. So for example, if it imports create file API, it indicates that it's going to try to create a file when it's been executed. So if we look at the image import descriptor, we can see a bunch of stuff. For example, all of these things, right? So original first thunk, characteristics, timestamp, name, first thunk itself. Then these are the things that we see right here. So reg create new, reg enum key, etc. So you can see that there's a lot of stuff that's trying to be done with the registry, and then lookup privileges, open process token. So these are all of the commandlets that this specific executable is going to try to execute. So from the various import functions of this dynamic link library, this DLL, this DLL, this DLL, etc. They're dynamically linked libraries that the export Windows functions or APIs for other PE files. And this shows that the file imports some functions that perform registry actions, as we just saw. To find more information about all of these things, you can go to the Microsoft documentation. For example, this specific link that is available to us, which is the reg key or reg create key function. So this is, again, this is the specific commandlet that calls on this specific winreg.h. And there's breakdowns for all of them. You can see it right here, the create key, and etc. etc. There's a bunch of stuff that obviously interacts with the registry and everything else that goes on. So everything that you would want is available in the Microsoft environment, or at least their Learn website. Now, when you run PE tree on an actual executable and you want to see what it does or what APIs it's going to call on, you can just go ahead and look at whatever the name is right here, and then look at it inside of the Microsoft documentation, and then you'll be able to find out what that specific commandlet does. So the value original first thunk and first thunk, the operating system uses these values to build the import address table, the IAT, and we'll learn more about this in future videos. By studying the import functions of this, we can identify some of the activities that it can do. For example, write a file, create a process, create a directory. And in the red line binary, we can see that the image import descriptor, notable functions like create process, create directory, and write file, which is, I guess, what we see right here in this screenshot. This implies that the PE file intends to create a process, create a directory, and write data to a file. Similarly, by studying the rest of the imports, we can potentially identify other activities that it intends to perform. So looking at this specific see and what the import functions are, from which DLL file does it import this function. So we're trying to find the create window exw inside of the red line portion. So I think this is the red line one. And so if we expand on this, it is inside of the, what is it, image nt header, and then the import descriptor right here. So we need to find where, what is it? The create window exw. I need to find where that is. Okay, so here it is. Create window exw is inside of the, where is it? It's the user32 .dll is where that was. So user32.dll is where the create window exw function was. Cool. So now we can go to the packing and identifying packed executables. And the question on this one, I kind of jumped ahead to look at it. It's asking which of the files in the attached VM in this samples directory seems to be a packed executable. So hopefully I don't have to open up PE tree to find it. Because that would take forever to load again, and it would piss me off. But let's read through this first. Packing is this concept that people will do when they don't want their code to be reverse engineered using a tool like PE tree. So a packer is something that is used to pack that stuff. So let's see if we can actually get some kind of a description, and we don't. So it's a tool to obfuscate the data inside of a PE file so that it can't be read without unpacking it. And packers pack the PE file in a layer of obfuscation to avoid reverse engineering and render a PE file's static analysis useless, which is what we're doing. We're literally statically analyzing these executables using a tool like PE tree. And the other counterpart to static analysis is dynamic analysis, which happens when you actually run the file and then you use a tool or some kind of a sandboxing environment to see what the executable is going to do. So when the PE file is executed, it runs the unpacking routine to extract the original code and then execute it. Legitimate software developers use packing to address piracy concerns, and malware authors use it to avoid detection. So how do we identify packers? From section headers is one way. So we learned that commonly a PE file has a .text section, a .data section, and .resource section, where only the .text section has the execute flag set because it contains the code. Now, the example file, which was this thing that we've been looking at, when we open this in PE tree, we find that it has unconventional section names or no names, which we saw earlier when we were trying to count it right here. So we can think that this has something to do with the tool we use to analyze the file. Therefore, let's check it using another PE analysis tool called PE check. The PE check tool provides the same information that we've been gathering from PE tree, but it's a command line tool, and we can go to that specific directory and run it using the command as such that you can see right here. And then we get the data like what you see here and all the various information that might be relevant to us. So the section name is empty, and it's not a glitch in the tool that we used like PE tree. So another thing that we might notice is that the entropy of the .data section and the 3 of the 4 unnamed sections is higher than 7, and it's approaching 8. As we discussed in a previous task, higher entropy represents a higher level of randomness in data. Random data is generally generated when the original data is obfuscated, indicating that these values might indicate a packed executable. Apart from the section names, another indicator of a packed executable is the permissions of each section. For our PE file, we can see that the section contains initialized data, and it has read, write, and execute permissions. We actually saw that. Similarly, some of the other sections also have read, write, and execute. This is also not found in the ordinary unpacked PE file where there's a bunch of read, write, execute. So in this case, the .text section has execute permissions, as we saw in Redline when we were analyzing Redline. Another valuable piece of information from the section headers to identify that it's packed is the size of the raw data and miscellaneous virtual size. In a packed executable, the size of raw data will always be smaller because it's packed. It's kind of like creating a zip file, for example, and smaller than the miscellaneous virtual size in sections with write and execute permissions. This is because when it unpacks during execution, it writes data to this section, increasing the size in memory compared to the size on the disk, and then it'll execute it. So if it's been packed, the raw data is actually smaller than normal, right? Because raw data should be the larger amount of data. Now we can also actually look at it and try to figure out whether or not it's packed by looking at the import functions. So the import indicator of a packed executable, we can see that it has its import functions by looking at that specific last import. So the Redline file imported lots of functions indicating the activities potentially performs. And in this specific file, we can only see a handful of imports, especially the get proc address, get module handle, load library. And these are often some of the only few imports of a packed PE file because these functions provide functionality to unpack. So for example, load library, right? Or get the process address. These things don't seem to actually be doing things. Like for example, create directory is actually doing something. So if you can see the create directory or registry, etc., like all the various elements that we saw in Redline, if you can see those commandlets being declared, that means that it hasn't been fully packed. But when you see load library, that's kind of like a strong implication that this is actually trying to load some of the things to unpack itself and then use the stuff inside of the library to do the rest of the stuff, etc. So following indications point to a packed executable, unconventional section names or no section names, executing permissions for multiple sections, high entropy approaching 8 for some sections, a significant difference between the size of the raw data and miscellaneous virtual size, and very few import functions. So from here, we can kind of conclude that basically we actually got all of the evidence from the fact that this might be the one that is actually the packed executable. So let's see if that's the answer here. And indeed it is. Okay, so in conclusion, we looked at a bunch of interesting information. Honestly, this was actually more interesting to me than everything else that we have done so far in the malware analysis module. And it's mainly because of the fact that it seems like we aren't just looking at binary code and hex and ASCII, whatever, all these things, because to me, I'm not great at deciphering code with my naked eye. Like, I need some kind of a tool to help me do it. And that PE tree tool is very, very easy to use. Granted that it takes 8 minutes to load a file. Maybe it's because I'm using a virtual machine, and obviously the virtual machine doesn't have that much RAM dedicated to it. So if I was doing it on my Windows PC, for example, which has like a good amount of RAM, I feel like it would be done faster on that machine. So anyways, that being said, we learned what a PE header actually is and what the various subsections inside of the PE header are, how to read the information from it, identifying packed executables, which I think is like one of the key pieces of knowledge that we gathered from this. But there was another one which is inside of the image descriptors, which shows us all of the import commands that are being used and all the different commandlets that are being used, which gives you a really good idea of what the executable is trying to do and what essentially is going to run when you actually run that executable, all the different commands that are going to run. So that actually gives us a really, really good idea of what the executable is trying to do. So very, very useful tool, the PE tree tool. The hex analysis tool, I didn't really use much. I was just going through based on the screenshots that were available for us and the descriptions and the explanations of those screenshots. But the PE header or the PE tree tool was very, very useful. So hopefully you actually got value out of this video and it's helping you get a better understanding of malware analysis. And obviously, if you're like me and you're not great at, breaking down freaking hexadecimal code with your just naked eye, then hopefully this was a little bit motivating because now you get a chance to actually use a tool to help you do malware analysis. And as we go along with this module, we're going to explore more tools and we're going to go deeper into malware analysis, which is going to be very, very useful for us. So I'm going to click on complete and we're going to wrap this thing up. If you found value in this video, then I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel, because there's a lot of videos that will be coming out on this channel, especially now that I'm done moving and now I'm inside my little recording room and I can get back into the recording flow. There was like a good week where the uploads were very slow because I was packing and moving and it was taking a lot of freaking time and energy from me, and I do recognize that I didn't spend as much time and energy as I could have to make sure that you guys get access to information. So I do apologize for that, and I hope that you can bear with me as I get back into the flow of recording and uploading and all of that good stuff. So again, just make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that video comes out. If you have any questions, drop a comment in the comment section below. And that is pretty much it. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section, and that's it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video later. In episode 42 of the SOC Level 2 training series, we are going to go through the basic static analysis room that is a part of the malware analysis module inside of the SOC Level 2 pathway of TryHackMe. And this is where, after this point, we're going to actually start analyzing source code as well as applications or malware, so to speak. And this is where everything that we've talked about so far, all of the nuance, the detailed information that we covered in all of the last videos, the last, I think, like 3 or 4 episodes that we did inside of malware analysis, all of those things are going to come together, and we're going to start analyzing these various malwares that are presented to us, and hopefully we'll be able to find the answers to the questions that we have and everything, and hopefully it'll be a great learning experience for both you and me. And the outline that we have, the overview for this video, is going to obviously be the introduction to the room, the setup of the lab and all the virtual machines that are going to be assigned to us, string search, so searching for strings, fingerprinting malware, signature-based detection, leveraging the PE header, and the conclusion. There'll be some final thoughts, and we'll review everything, and you'll be dismissed for the day. This is a subscriber-only room that's inside of TryHackMe, so you do need a paid membership inside of TryHackMe to be able to access the virtual machines and everything else that's available here. However, you can just follow along with everything that we're talking about, because for the most part, everything that we're doing here is accessible to you. Whether you're running a Mac, a Windows, or a Linux computer, you should be able to, at the very least, follow along with the information and try to do some of these things on your own computer. That being said, if you're going to analyze malware, so you really have to understand that it needs to be inside of a sandbox environment, inside of a controlled environment. You should not be running malware. You shouldn't be downloading and running malware. It's I highly advise against it. So just keep that piece in mind. It's that little piece. Keep that piece in mind, because I don't want you to accidentally go ahead and run malware on your computer, and then you get held up at ransom or something, God forbid, something bad happens, and we just don't want that to take place. So that's pretty much what we have for the overview of this video today, and let's jump into it. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into basic static analysis. In all of the previous rooms of this module, we talked about the basics of computer architecture and the assembly language, and those topics are essential building blocks to learning malware analysis. But now we're going to start analyzing malware starting from this specific video onward. The prerequisites are the Intro to Malware Analysis, the x86 Assembly Crash Course, and the Architecture Overview. These are the 3 episodes prior to this particular episode, or I think it's actually the one right before this one was analyzing PE headers, portable executable headers, and then prior to the portable executable video were these 3 videos. So everything that we talked about so far is basically the build-up to what's going to be happening from now on, which is where the analysis of malware is going to start. The first step in this process is to look at the properties without running the malware, and this is called static analysis. So think of it as staying in its original state. It's static, it's not moving, right? The malware is a static state and it's not running. And then we're going to talk about the basics of this. I've actually done a similar video to static analysis in, I think it was the Secure Software Development Lifecycle, which is a part of the Security Engineering module, which is the Security Engineering playlist. So you can go ahead and find that as well. We're going to be talking about lab setup, everything that we got to do to actually prepare for this, searching for strings in malware, fingerprinting malware through hashes, signature-based detection mechanisms, extracting useful information from the PE header. And without further ado, as I like to say all the time, let's move on to the next task and see what we can do to set up the lab for malware analysis. Before we actually analyze any kind of malware, you really have to understand, as I stated in the beginning in the intro, that malware is destructive, and when you're trying to analyze malware, there's a high chance of damaging the environment in which it is being analyzed, meaning your computer, right? So the damage can be permanent, and it might take more effort to get rid of this damage than the effort that it was made to analyze the malware. Therefore, creating a lab setup that can withstand the destructive nature of the malware is necessary. And the virtual machine concept is why this is so important, and this is why I like TryHackMe so much, because they have a bunch of virtual machines for pretty much every single room that you would go into, that you can use the virtual machine as that controlled environment so that you can go ahead and analyze malware, do hacking exercises, all of those things without really having to worry about ever infecting your own computer. A lab setup for malware analysis requires the ability to save the state of a machine, also known as a snapshot or an image, right? And revert it to that state whenever required. The machine is thus prepared with all the required tools installed, and its state is saved. After analyzing the malware in that machine, it is restored to its clean state with all the tools that were installed. This activity ensures that each malware is analyzed in an otherwise clean environment, and after analysis, the machine can be reverted without any sustained damage. With virtual machines provide an ideal medium for malware analysis. Some famous software used for creating and using virtual machines are the Oracle VirtualBox and, of course, VMware Workstation. And I also I've described various ways that you can download and install Linux images inside of the Linux Plus playlist. I believe it's in the first episode in part 3. Maybe it's it's in the first video in the first episode, part 3 of the overall lecture, where we actually go through the installation of Linux, and you can do the same thing, and you can download an ISO image, use VirtualBox or VMware to install it on top of your current operating system, or you can install it on a USB thumb drive, which is what I prefer to do, and I can launch that USB thumb drive from any computer that supports virtual machines without having to download VirtualBox or VMware or anything like that. These applications, these ones, VirtualBox and VMware, they create snapshots and revert to them whenever it's required, making them well suited for malware analysis. And the following steps portray the usage of this. So create a fresh virtual machine with a new OS install, also known as get an ISO image from your favorite OS, and then install it using VMware or VirtualBox. Set up the machine by installing all of the required analysis tools in it. When you do Kali Linux, for the most part, it has a lot of really good stuff that's already installed in it. And there are different versions of Linux that are designed for different things. So Kali Linux is specifically for penetration testing, so it's for offensive security. And then there's the defensive security of Linux, which I think is actually one of the ones that we're going to be talking about. I think it's called REMNUX, REMNUX, and then there is another one, I forget what the name of it is. I will talk about it in literally just a few seconds. Then you take a snapshot of the machine, copy, download the malware samples inside the virtual machine to analyze it, revert the machine to the snapshot after the analysis completes. So this part is very, very important, right? So once you've installed the machine and you've installed all your tools and everything that you need, you take a snapshot of the machine, an ISO image, right? You take essentially a copy of what the overall machine is before you download the malware and run it, right? And then you save this snapshot so that whenever you run the malware, if anything happens to the machine, you can just revert back to that original snapshot by reinstalling it, right? So following these steps ensures that the virtual machine is not contaminated with remnants of previous malware samples when analyzing the new malware. It also ensures that you don't have to install your tools again and again for each analysis. Selecting the tools to install your malware analysis can also be hectic, and one can use one of the freely available malware analysis virtual machines with pre-installed tools. So there you go. Flare VM was the one that I was talking about. It's a Windows-based virtual machine that's well suited for malware analysis, previously also known as FireEye. It contains some of the community's favorite malware analysis tools. It's customizable. You can install any of your own tools in the VM. It's compatible with Windows 7 and 10. And for a list of the tools that are already installed in it, you can just visit the GitHub page for Flare VM or the Mandiant blog for Flare VM. And since it's Windows-based, it can perform dynamic analysis of the Windows-based malware, which is when you actually run the malware and then you analyze it and you kind of watch to see what the malware does. An instance of this is attached to this room that I'm in right now for performing practical tasks. And if you don't have access to TryHackMe, you can just go download Flare VM and use VirtualBox or VMware to install it. So not hard to do, and you can get access to everything that we're going to be talking about. I've already clicked the start machine, so all of that is going. And there's a directory that's named mal on the desktop, which contains malware samples that we would be analyzing for this room. Another one is Remnux, which is the Linux version of the analysis OS, right? So it's reverse engineering malware Linux. And it's Linux-based malware analysis created by Lenny Zeltzer in 2010. More people joined the team to improve upon that distribution. Like Flare VM, it includes some of the most popular reverse engineering and malware analysis tools pre-installed on it. So when you actually download and install Remnux, you get all of those tools installed on it as well. It helps you save time to what would otherwise be spent in identifying, searching for, and trying to install those tools. And details for those are, of course, on the GitHub and the website for their distribution. The website in this particular case is the Remnux website, remnux.org. So very, very easy to access. And it was previously used in the Intro to Malware Analysis room. We actually have used it already, and we're going to be using it in future rooms, in future videos. So we already have this going. The virtual machine is already running. You can see that my IP address has been assigned to me. This is the administrator username and the password that we have. So in case you do have access to TryHackMe and you want to remote desktop into the virtual machine, these would be your credentials with the exception of the IP address. The IP address is going to be dead essentially by the time that I'm recording this video. When I finish recording, I'm going to crash the machine. I'm going to take it down basically, and that IP address will no longer be accessible. But the username and password for this particular room should exactly be the same. So it's just whenever you launch your virtual machine inside of TryHackMe, you'll get a different IP address that you can connect to should you choose not to use the browser-based virtual machine. I'm going to be using the browser-based virtual machine, so it's going to keep it a little bit simpler for us. Virtual machine is already up and running, so let's go into the next section. Okay, in the Intro to Malware Analysis room, which was the first room, the first video inside of the Malware Analysis module. So if you backtrack, I think it's 4 videos before this particular video, then the title is going to say Intro to Malware Analysis. So that's basically the video that we're referencing. We identified that searching for strings is one of the first steps in malware analysis. A string search provides useful information to malware analysts by identifying important pieces of strings present in a suspected malware sample. To learn more about this, we can look at another room that's dedicated to strings, and let's see if I've already done it. Mal strings. I've actually not done this room before, so that's another thing that we can kind of mark for the future. This is also a subscriber-only room inside of TryHackMe. So, a string search looks at the binary data in the malware sample regardless of the file type and identifies sequences of ASCII or Unicode characters that are followed by a null character, also known as a none character, like a non-existent character. Wherever it finds such a sequence, it reports that as a string. And this might raise the question that not all sequences of binary data that looks like ASCII or Unicode will be actual strings, which is correct. Many sequences of bytes can fulfill the criteria mentioned above, but are not strings of useful value. They might just include memory addresses, assembly instructions. Therefore, a string search leads to many false positives, FPs. These false positives show up as garbage in the output of our string search and should be ignored. It's up to the analyst to identify the useful and ignore the rest. So this is where an eye that has been developed through experience and through practice and all of those things comes in handy, right? So if you've never done this before, if you've never analyzed strings before and you don't know what you're looking for, you're going to have a hard time with this, which is why you want to practice very frequently. There was a comment that came in through the community of somebody saying, how do I go from studying to execution? And this is it. This is it right here. If you're watching this, I forget the username, so I apologize, but you should know that I'm talking about you because you asked specifically on how to go from studying to actually practicing and executing. And this is how you do it. You download Flare VM or you download Remnux, and then you go through the tools that are available and you do something like this inside of TryHackMe, where it's literally a lab environment where you're practicing the theories, practicing the concepts and the philosophies so that you get actual experience in your fingertips, right? So this is how it all plays out, and this is how you develop that eye that can actually identify useful strings and ignore the rest of them. So what to look for? Since you have to identify actual strings of interest and differentiate them from the garbage, it's good to know what to look for when performing a string search. A lot of useful information can be unearthed in a string search, and these artifacts are the indicators of compromise. IOCs, you're going to hear this a lot if you haven't heard of that phrase yet. And indicators of compromise, literally, as they say, they are signs that you've been compromised, right? They're indicators that you've been compromised. Windows functions and APIs like set Windows hook, create process, internet open. These are commandlets that exist inside of PowerShell, inside of the Windows structure. They provide information about the possible functionality of the malware, right? So set a Windows hook, create a process, open internet, right? So IP addresses, URLs, or domains can provide information about possible C2, which is also known as command and control, where there is a remote server that somebody has connected to our local machine from that remote server. Most likely it's like a proxy server because they don't want us to backtrack to their actual location. But that remote server, that C2 connection, is how they are interacting with our local machine, because they have this reverse shell and they can send commands and they're extracting data and doing a bunch of stuff. WannaCry is one of the common stories, the popular examples that is used. It has a kill switch domain that was found using a string search. So that's how they detected WannaCry. Miscellaneous strings like Bitcoin addresses, text used for message boxes. This all helps to set the context for further malware analysis. A basic search that can be done using the strings utility, which is pre-installed in Linux machines, and it can be used for basic string search. Similarly, the Flare VM has the strings.exe. A lot of times what you see, so for example, netcat in Linux is NC for netcat, but then inside of Windows, it's nc.exe. So that's like really the biggest difference for many of these utilities that exist on both of the operating systems. It's just that on Windows, it has an exe at the end because it acts as an executable application. In Linux, it's just a command line utility that you can refer to and you can call on it by just using its name. They do the same task, right? This utility is part of the sysinternals suite, and that's been developed to actually analyze different aspects of Windows machines. We already have a video on sysinternals on this channel, so you can go ahead and check that out if you don't know what that is. Details about the string utility can be found in the Microsoft documentation. The utility comes pre-installed in Flare VM, and the good thing about it is that it can dump strings to a file for further analysis. So it can actually display it onto the screen for you, but it can also dump it into a file for future analysis. Not necessarily further analysis, but if you need to refer back to it without actually running it, or if you need to create a report and send it to your manager, so on and so forth, it can output everything into a file for you. So if you want to refer to the strings utility, you would just do strings, and then you give it the path to the binary, which is essentially the malware, path to the malware that you want to analyze. And there are other tools that can be used for string search, for example, CyberChef, which is amazing. I love it, absolutely. There's a desktop version of it. There's also the website that you can access by just Googling CyberChef, and it's the first one that pops up. It has a recipe. So inside of CyberChef, it's a chef, right? So it has recipes. And there's a recipe inside of CyberChef that can search for strings. And PE Studio is another one that we used in the last video, I want to say. It provides a string search utility. It also provides additional information about the string, like the encoding, the size of the string, offsetting the binary where the string was found, and a hint to guess what the string is related to. It also has a column for blacklisting, which matches the strings against some signatures that previously have been downloaded and configured. So this is what PE Studio, the screenshot, kind of looks like. If you don't know what this is or what it looks like, what it's supposed to do, refer to the last video for the portable executable analysis, the PE analysis, and you'll be able to get some examples of how PE Studio works. But I mean, that's basically it, right? So on the desktop, you can see right here, this is the path to the malware. And then there are indicators inside of it as it's being analyzed, the DOS header, DOS stub, etc., etc. And then there's a strings tab right here that if you click on it, it'll actually show you the value of those strings, for example, whether or not they're on a blacklist, etc. So that is pretty much it. And then these are the values of the strings, right? So query performance frequency, virtual protect, device IO control, terminate process. These are all the things that have been extracted that are not BS jargon. As we talked about a few minutes ago, when you are looking at strings, instead of you having to actually just run strings and then go through everything that's been pulled by the strings utility and try to determine which one is useful, if you use a tool like PU Studio, it literally pulls all the things that would actually be useful to you. Open clipboard, close clipboard, set clipboard data, empty clipboard, send input, all those things. You don't have to use your naked eye to be able to find them. It finds them for you and it lists them. So there are a lot of utilities that make our job easier when we're doing these types of activities, and it would be in your best interest to leverage those utilities. It's not a bad idea to learn how to do it through the naked eye using just a command line. And it's probably actually a good idea to honestly do it so that you can just kind of enhance your experience. But there are tools that can make this easier for you. So this can be done by selecting strings, as we already talked about it. We can learn more about these APIs using resources like Mal API or MSDN. So these are API calls. These are things that you see right here. Those are API calls, and you can learn more about each one of their functionalities by just going through those pages, or you can literally just Google, hey, what does open process do, right? And I mean, that one is kind of a gimme because it tells you that it's opening a process. But just in case you don't know what the other ones do, you can just Google them and then you'll learn. So there's something called an obfuscated string. So searching for strings is one of the most effective ways. And in case of the WannaCry ransomware, effective use of this can often disrupt malware propagation and infection. And the authors know this, so they don't want a simple string search to mess up their activities. Therefore, they will deploy techniques to obfuscate strings. And obfuscation is basically trying to murky it up, right? Trying to disguise it. That's another good way of saying that when you obfuscate something, you're trying to disguise the string so it doesn't look like a basic string that you can actually just read and be like, oh, okay, this guy's trying to open a process, right? Malware authors use several techniques to obfuscate the key parts of their code, and they often render a string search ineffective, meaning you won't be able to find much information when you just search for strings. Mandiant, also known as FireEye, launched Floss to solve this problem. And Floss stands for the FireEye Labs Obfuscated String Solver. I always wonder what came first, the acronym or the value, right? Because it's like, it's so convenient that this ends up being Floss. Like, it has to be the acronym, I feel like. I don't know. Anyways, it uses several techniques to de-obfuscate and extract strings that would not be otherwise found using a simple string search. And the types of strings that it can be extracted and how it works can be found on their blog post on Mandiant's website. And I'll actually open this because I know we're supposed to use Floss in a little bit. So to execute it, you literally open the command prompt, go to the desktop directory. From there, you can use the command Floss. And then if you do -H, it'll bring the help menu, the help page for you. And you can use the following command to search for obfuscated strings in a binary, Floss, no static strings, and then the path to the binary. And the command might take some time to execute. That's always good to know. And you might see what appears to be some error messages before the results are actually generated. So now what we're going to do is we're going to actually open the virtual machine, go to the malware or the mal file on the desktop, and look at which one. We're going to look at the obfuscated strings found in 2, 5, and 6. Which of these contains the string DBG view? So the answer is going to be either 2, 5, or 6, and we're trying to find DBG view exe by running Floss. So let me go ahead and I'm going to zoom out of this, or actually, you know what? I'll do this. I'm going to open up the virtual machine because it makes it easier for you to read if I stay zoomed in like this. So I'm going to open up the virtual machine, but I'm going to open it up inside a new window. And then this way I can now minimize this, and then the new window, there we go. This is going to be our Windows prompt or Windows virtual machine. And now we can actually reference our question here as well. And the command that we're running basically is something like this. But let's see. So we're trying to find obfuscated strings found in that. So that's basically it. What does the hint say? It says use Floss to extract obfuscated strings. It can be executed from CMD after navigating to the desktop. So pretty simple instructions for us. So this is a Windows machine. There are a few different ways that you can open CMD. if you actually have access to keyboard shortcuts, which I don't think I do, because if I do CR, yeah, so usually when you do Control R, it'll open up the run prompt for you, and then from there you can search for CMD. But if you click on the Windows machine or the Windows logo at the bottom left usually, and you can just type in CMD like that, and then it should be able to open it for you, and there it is. So it's actually starting the search. There's the command prompt. So I will open up CMD, and here we go. Now I am inside the user's administrator location. So if I do, I think it's actually dir, because ls doesn't work for CMD, and then there's the desktop. So if I go into desktop, I am now inside of the desktop. CLS is clean screen, so clear doesn't work inside of CMD. And so now if we do dir, we'll see that there is a mal directory right here. So we will go into the mal directory, we'll clear the screen one more time, and now inside the mal directory, we have 1, 2, 3, 4, 5, and 6. Now, what we're going to do is we're just going to run floss, and then the command itself was what? It was floss no static strings, and then give it the path to the binary. So in this case, if I do floss -- no static strings, and then the path to the binary is essentially this, like where we are right here. This is the full path, and then it ends with 1 or 2 or 6 or whatever. And we're supposed to analyze what? We're supposed to analyze 2, 5, and 6 are the ones that we're analyzing. All right, so here we go. Here's the path to the binary. It's going to be C, users, administrator, desktop, and then mal, and then we'll do 2 first. I'm going to press enter, and it says it's going to take some time, so not exactly sure how long it will take. So floss decoded 0 strings, execution after that many seconds. Okay, I mean, that was easy. So we'll do another one. I'm just going to press up on my keyboard to bring the command up. And then now I will do 5 at the end of it. Press enter right there. Let's see if anything comes up for this one. And this might, nope. Okay, so I'm going to guess the answer is 6 because those two didn't give me anything. But let's just run 6 and let's see what, there we go. Now we're getting some information onto the screen here. And we're looking for 5 something. Okay, so this is actually working because the previous ones found nothing for us. So I feel like the answer is going to be 6, but I'm going to wait until the result actually shows up, and then we'll know for sure. But obviously, if the first 2 didn't work, then it's going to be the last one, which is what? Number 6, right? 2, 5, and 6. So let's try 6. The answer should be 6. There we go. That's the answer. It found 1 decoded string, so let's go ahead and zoom in on this a little bit so we can see what's up down here. So far, that's the only decoded string that it's found. We will come back if we find, or when we find, the official answer. Oh, boom, there we go, dbg view exe. So it found it multiple times inside of the binary named 6. So there we go. That was the answer, and we found it using floss. Great. So let's go to fingerprinting malware. When analyzing malware, it's often required to identify unique malware and differentiate them from each other to see which ones do what, basically. And file names don't work because obviously you can very easily change the file name, and you can duplicate things easily, and you can even change hash values really by adding like a very basic addition to the code, which does nothing functionality wise, but then it'll end up changing the hash value. But in this particular case, we're actually going to be looking at hash functions to identify a malware sample, and it takes the file data of arbitrary length as input, and then it creates a fixed length unique output based on the file contents, and it's irreversible, and you can't recreate the file's content using the hash. So this is one of those things that sometimes gets confused with encryption, and a hashing algorithm is not an encryption that can be decrypted, right? So you can't reverse a hash. I've done multiple videos on hash values and hashing algorithms. So if you refer to the cryptography section of, I want to say it's SOC level 1, and you'll get some really, really good descriptions of what hash values are and what they do. And then there's a lot of different demonstrations of hash values and rainbow tables and so on and so forth. So hash values in general, right, can't be reversed because you can't decode the hash. But what you can do is you can try to compare it against a database of stored hashes. So imagine somebody has, 10 million unique hashes stored inside of a database with the plain text equivalent of what that hash means, what the text value of that hash is. And the only thing you can do is you can take your hash value, compare it against those 10 million hashes to see if they exist in that database. And if they do, you'll find the plain text value. That's the only way that you can find it. You can't decode the hash, right? So that's kind of like the key unique feature about hash values. They have a very low probability, which is practically zero, of two files having the different content but the same hash. That's another thing that's very unique about it, is that for the most part, especially when you use SHA-256 and above, SHA-512, when you use these advanced hash algorithms, it's very, very difficult, almost impossible to find the same hash value dedicated to two different plain text values or two different applications, etc. So it remains the same as long as the file's contents remains the same. That piece is very important. Even a slight change in the content will result in a different hash. It might be noted that the file name is not a part of the content. Therefore, changing the file name does not affect the hash of a file. So that's the key element here that we're going to be focusing on, because you can change the file's name so that it doesn't show up in the database of a security tool, right? Let's say the security tool is looking for malware.exe, and then you change it to, I don't know, content.exe, whatever. I couldn't think of a clever name. But you take the same exact malware and you change the name from malware.exe to content.exe. Now, the security appliance is looking for malware.exe if it's just looking for the name. So content.exe won't show up as an alert. But if you set it to search for the hash value instead of the name, then it is more effective, and then you can change the name to whatever you want, but the hash value stays the same, therefore we can detect it. So they're also used to store passwords to authenticate users. In malware analysis, hash files can be used to identify unique malware. Search for this in different malware repositories and databases as an indicator of compromise. And VirusTotal is one of the more popular ones, and I use VirusTotal in my personal life all the time. When I get an email that seems a little bit fishy, or something happens where I'm like, I feel like this might be a bad URL or something. So I'll copy the URL without actually clicking on it. I'll copy the value of a hyperlink without actually clicking on it, and I'll go to VirusTotal and I'll check to see if it's in their database. And sometimes it is, right? And so you're like, oh, well, let me make sure I don't click on this. Methods of calculating file hashes. We have these very common hash algorithms, MD5, SHA-1, and SHA-256. And then when you just do MD5 sum inside of the terminal of a Mac OS, which is Unix-based, or Linux, when you use these commands inside of Linux or Unix-based computers, then you give it the file name or the file path right afterwards, and then it'll give you the hash value for it. Inside of the Windows operating system, you can use a commandlet for PowerShell, which is, I think, get algorithm or something like that, or get file algorithm, if I remember correctly, and then you give it the path to the file, and then at the very end you say algorithm SHA-256 or algorithm SHA-1, and it'll give you that value. These are now considered insecure, these two right here. So you will not find them commonly in modern applications or anything of the sort. One of the examples that I give all the time is that when you go to this little button right next to a URL, click on connection is secure, then click on certificate is valid, and you will end up seeing the SHA-256 fingerprint of the certificate, the asymmetric certificate that's used to encrypt the connection to TryHackMe, and it's a SHA-256 fingerprint. So that is the most I'm not going to say it's the most secure encryption, but it is kind of like the common standard across the board right now, until it becomes very popular to start using quantum encryption, because quantum computers can now decrypt these types of encryption standards fairly easily, but they're not accessible by very many people, because I think there's like a handful of quantum computers across the world right now. So thankfully, your average hacker can't get access to something like that yet, right? So we'll see how the world plays out. So the first two types are now considered insecure or prone to collision, meaning that two or more inputs, two or more files, can have the same hash because there aren't enough variations of MD5, right? There aren't enough variations of SHA-1, therefore SHA-256 is kind of the best common standard right now. A collision attack for these hash functions is not very probable. It's still possible. Therefore, SHA-256 is considered the most secure method of calculating file hash. And we can see that multiple utilities calculate file hashes for us. What we can use is imp hash is one of the big ones. It stands for importing the hash. And imp hash are functions that an executable file imports from other files, or DLLs, dynamic linked libraries. The imp hash is a hash of the function and the calls or libraries that a malware sample imports and the order in which these libraries are present in the malware. And it can identify samples from the same threat groups or performing similar activities. And more information is on the Mandiant blog, available for you at the Google Cloud blog. Actually, yeah, cloud.google.com, threat intelligence, tracking malware, import hashing, etc. So there's that information. So you can use PE Studio to calculate the imp hash of a sample, and there's a little value right here called imp hash that has the imported hash value that's available for you. Any malware samples with the same imports in the same order will have the same import hash. This helps identify the similar samples themselves. And we can see this right here. This is based on Malware Bazaar. The domain is bazaar.abuse.ch. And you can go ahead and search for this imp hash value, right? So this is what we see right here. And then based on that, it'll give you all of the connected executables that would be for that imported hash value. Malware Bazaar, they have the same imp hash. We can see that all these samples are classified as the same malware family. We can see that their SHA-256 is vastly different and doesn't provide any information as to their similarity. However, the same imp hash helps us identify that they might belong to the same family. So the import hash value imports a bunch of different things, and if they fall under the same import hash value, even though they have unique hashes themselves, but they fall under the same imp hash value, which means that they are connected somehow. Fuzzy hashes, SSDeep, another way to identify this is the context triggered piecewise hash, CTPH. This is calculated by dividing a file into pieces and then calculating the hashes of the different pieces. This creates multiple inputs with similar sequences of bytes, even though the whole file might be different, and more information can be found at the website that we have here, which is the ssdeep-project.github, and you can go ahead and read about SSDeep over there. Multiple utilities can be used to calculate SSDeep, like CyberChef. However, this has been placed on the desktop to make it easier, which is the SSDeep utility, and we can just refer to it by using its executable. We do need to actually go either inside of the folder that holds it, or we just need to reference the entire path where it is, and then you can do -H to get the help menu, and it'll give you all of the different usage options that are available for it. And we can calculate the hashes of all of the samples in our mal directory by using this little wildcard character, which says basically run this, right? So run this executable on everything inside of this directory, because the wildcard character could be replaced with A, B, C, D, E, F, G, or it could be replaced with 1, 2, 3, 4, 5, 6, etc. So when you do that, you can now run it against everything inside of the mal directory. Excuse me. And so now you can see all these various hash values for mal1, mal2, mal3, etc. So quite useful. We can try other options that can help the file per the requirements. We have these SSD hashes. We can match these together to identify similar files. This helps us identify similar files if we have a bulk of data. The documentation link is also a good example of this that we just saw right there on the GitHub page for the SSD tool. What we can see below is everything that we have relevant to our use case to match the file. So we can use the -D operator, the -R operator, which runs this recursively, and the L operator to output everything relative to the actual file itself. So you can see now they've used multiple flags here, or multiple options, and we're going to look at everything. What is it? So it literally, I think, is just running it. I don't think it's looking at incoming, outgoing, trash, outgoing corporate espionage, etc., etc. Yeah, I don't think they've attached anything to it. I think they're just running it with these options, and then it's going to search through the entire computer. The results show files that match with each other. The number in the bracket at the end is the percentage of the match along the file. So if we look at the number, yeah, so this is exactly what it is. Maybe actually this is what it is. So incoming, outgoing, and trash are the options that go along with SSDeep right here. And then this is the first line. So this is an outgoing, and then that's what we have right here as the percentage value. This is outgoing, and then this is inside trash. So, okay, that makes a little bit more sense. So in the samples that are located in the mal directory in the attached VM, which of the samples has the same imp hash as file 3? So we'll look at that. And using SSDeep, what is the percentage match of the above mentioned files? The files that we have right here, I'm assuming. So first we're going to run the imp hash or the tool to detect the imp hash for all of the files, which I feel like it should actually be right here, because I think all of these things have been done for us already. It's like I don't need to rerun it because it's already running it against all of these things. So now I just need to try to find the ones that potentially match, but I mean none of these match. So that's another thing that's a little bit concerning here. So let's see what we can find here. Okay, so this is what I believe is the command that we're supposed to be using here. So we're going to be using this command, and then we're going to give it this piece right here. So this is just running SSDeep against the malware contents, and it's going to get us the hash values, etc. But if we want to see which ones match each other, we would use this specific command right here, and then we would just give it the malware location, the malware analysis location. So I'm going to go and see if I can actually do this, right? So if I go back to our desktop, because in the desktop is where the SSDeep location is. Yeah, exactly. So we're going to clear the screen. Let's zoom in a little bit for you here so you can kind of see what's up. So we're going to do this, and then we're going to copy this. Okay, perfect. There you go. There's that. And then now we're going to give it the malware \* so that it analyzes everything inside of that. And there you go. Okay, cool. So it says malware 3 matches malware 1 and at a 93% certainty level. So it says which one of the samples has the same of file 3, and that would be 1. And using the SSDeep utility, what's the percentage match of that, which is 93? Okay, perfect. There you go. That's how we get the answer. So we had to get this specific command right here, and then we were supposed to use it against the contents of the malware folder, because in this case, just to demonstrate it to us, they're running it against incoming, outgoing, etc. But we just needed to run it against the actual malware directory, the contents inside of the malware directory. All right, cool. Let's look at signature-based detection. Now, even though hash values can actually be very useful, they are not the be-all and end-all for trying to figure out whether or not a file is malicious and if it is a file of interest. And the way that we can go ahead and really truly figure this out is by looking at the signature of the file. And the idea here is to find a way to identify some files if they are actually similar, and if a file contains the information that we need, the information that is of interest to us. Therefore, the hashes themselves are not the most ideal way to try to find this. So this is where signatures come in. So this is a way to identify if a particular file has a particular type of content, and we can consider a signature as a pattern that might be found inside of a file. And it's often a sequence of bytes in a file with or without any context regarding where it's been found. So security researchers often use signatures to identify patterns in a file, identify if a file is malicious, and identify suspected behavior and malware family. And then signature-based detection is also known as heuristic detection. And this is one of the more powerful ways that security appliances do the jobs that they need to do. Instead of looking at hash values, which again can be useful, but sometimes they don't tell you the full story, the stuff that you need, because someone could just modify the contents inside of the file without actually changing the functionality of the file. But they can add a comment at the end of the file, and that'll change the hash value of it. And if that changes, then now you have a new hash value, and now you whatever detection mechanism you have in place, it's not going to do anything for you because the hash value has completely changed. Therefore, it can't be used to detect the malware itself. So the rest of the source code, the rest of the contents of that file, even though you added the comment at the end of it, the rest of the source code is not going to be different. And this is where signatures are really helpful. They actually look for the patterns inside of the content of the file to see if it is malicious. Yara rules are one of the more powerful ways of doing this. This is a signature-based rule, and it was called a pattern matching Swiss Army knife for malware researchers. And it can identify information based on binary and textual patterns like hexadecimal and strings that are contained inside of a file. We have a dedicated room for this inside of TryHackMe. I'm pretty sure I've already gone through this because I've done multiple videos on Yara rules. Yep, this is the one that I've already done. So you can actually go ahead and find the Yara videos. There's multiples of them, but that one specifically you can go ahead and find to see how Yara rules work, how you can write them, etc. And there's a repository of open source rules that we can use as per our needs. Essentially, you could literally go ahead and just copy paste the contents of these rule files. There's a lot of them, and you can use these various rules in your own environment to see if anything that you have or if anything that comes in through the network connections or the traffic will trigger any of these rules. And that way it can just make your life honestly much easier to detect something while it happens or before it happens, etc. So when we analyze malware, we can use this repo to dig into the community collective wisdom. However, while using these rules, please keep in mind that some might depend on context. Others might just be used for identification of patterns that can be non-malicious. So just because a rule hits doesn't mean that the file is malicious. So keep that part in mind. For better understanding, you can read the documentation for the particular rule that you want to use to identify the use case, whether or not it will actually be useful to you. Proprietary signatures, also relevant to antivirus scans. These are the ones that can actually be developed for your specific environment. You can create a proprietary signature. And the advantage of this is that since they have to do with and sold commercially, right? So this is one of the things, right? When you buy a proprietary signature or a set of rules that have been designed for proprietary signatures, or signatures that the rules themselves, the rule files, are proprietary, there are lesser chance of false positives, right? So this might lead to a few false negatives, right? So you use the rule, it doesn't detect something, and whatever is happening bypasses the rule, and now you have a false negative, meaning that the detection mechanism, whatever tool you're using, said that, oh no, this is fine, this is not malicious, and it was a false negative, and the malicious file does not hit any signature, right? So antivirus scanning helps identify if a file is malicious with high confidence, and these types of softwares mention the signature that the file has hit, which can hint at the functionality of the file. But we have to note that despite the best efforts, every antivirus product in the market has some false positives and false negatives. So when analyzing malware, it's prudent, right? It's useful, it's a good practice to get a verdict from multiple products. And this is where VirusTotal comes in. This is why I love VirusTotal so much, because they literally have, I don't know how many dozens of different resources. So let's say we go, let's say google.com is the URL that we want to scan. And so we scan URL google.com, and currently as it stands, there are 97 antivirus tools that are used to detect different things, different characteristics or details of the URL. And as you saw on the homepage right here, we can attach a file and it can analyze the file for us, as well as obviously the hash value of the file. We can go ahead and search for a URL, an IP address, a domain name, or a file hash, and then you can obviously just search for the URL itself. So there are a few different ways that you can use VirusTotal to search. You can also sign up for VirusTotal account, get access to an API key, and create automations where the script will run the hash value or the signatures of the files that you're looking at against the VirusTotal database and let you know whether or not that is actually a malicious file or malicious URL. I've developed one of these scripts for our Hackaholics Anonymous members, and they have access to it because of the fact that they're an agent level member or above. So agent, guardians, and masters inside of Hackaholics Anonymous get access to those scripts that I create for them. And one of the ones that I created actually does exactly what I just described. We go ahead and we query the VirusTotal database using an API key that you would get from VirusTotal, and it'll scan your computer for anything that might match any of the database contents of VirusTotal to see if anything comes up as malicious. So we can find verdict about a file from, it says 60 plus antivirus vendors, but as you just saw, it's over 90 right now because they keep adding more and more. And we can always, we've already talked about this in malware analysis. So anyways, when you're analyzing a sensitive file, it's best practice to search for its hash on VirusTotal or some kind of other website, for example, the Bazaar that we looked at earlier. And this is to avoid leaking sensitive information on the internet and letting a sophisticated attacker know that you are analyzing their malware. And we've covered Yara rules in the Yara room and VirusTotal scanning in the intro to malware analysis. And there's different videos that I've done. I've done multiple videos, probably about a dozen by now, that we've used VirusTotal as our reference for whether or not a hash value or a domain name is malicious, whether or not a file is malicious. So Flare VM has another very cool tool that will allow us to do something like this, and it's called Kappa. And this tool helps us identify capabilities found in a portable executable file. It reads the file and tries to identify the behavior of the file based on signatures like the import signatures, or import strings, mutexes. That's new. I've never even heard of that before. And other artifacts that are present in the file. We can go ahead and look at their GitHub page or their blog post. I am so curious what mutexes means. So let's see what that actually is. It is short for mutual exclusion locks, and they're synchronization mechanisms that ensure only one thread or process can access a shared resource at a time. They're used to prevent race conditions where multiple threads try to modify the same data simultaneously, leading to unpredictable results. That's very interesting. I've never heard of that before. It's kind of cool. That's kind of cool where I just learned something new live in real time while I'm recording for you. Using Kappa is as simple as referencing it, calling on the tool, and then giving the location or the path to the malware, the binary, the executable that you're trying to scan. And in this particular case, because we are scanning PE files, they're portable executable files, so we're going to be scanning something that has the exe at the end of it, right? So you can always use the -H to look at the help menu for Kappa, which is a very cool tool. I think I've done a video on Kappa before as well. It sounds really familiar. We can run it against the binaries inside of the mal directory, and it may take some time to complete the analysis, and this is what we have as an example for the very first binary. So we have the hash values here. I've definitely used Kappa before because I recognize this. So the MITRE attack technique that would be relevant to what the actual binary, the malware does. The MBC objectives and the MBC behaviors, definitely have looked at this before. So I definitely recognize this. It has mapped identified capabilities according to the MITRE attack framework and the malware behavior catalog. In this, we saw that the capabilities against the match signatures and the number of signatures that have found hit against these capabilities. And we can see it also tells us if there are obfuscated stack strings in the sample, allowing us to identify if running floss might be helpful. To find out more information about it, we can use -V or VV for verbose or very verbose, which basically gives you a bunch more details, right? So what you see right here is not the verbose version. So all of this information that you see right here is the non-verbose version, and then you can get even more verbose output to be able to get even more details about what you're running. So we're going to run these questions now, and it should be interesting. So let's see. The first one is, how many matches for anti-VM execution techniques were identified in the sample? So I'm assuming that we're talking about, oh no, I see. We're going to be looking at malware 4 to answer the following question. So first, I'm going to run Kappa on malware 4, and then I'll let it finish because it's going to take some time. And then based on that, we'll go ahead and answer the questions that we got. Oh, I hope my virtual machine didn't disconnect because I didn't get any notifications for it. So let's see if we can establish our connection. That would suck if it disconnected. So I'm going to open up our CMD, our command, one more time, and then we're going to run Kappa to make this whole thing work for us and get all the information that we need to answer these questions. So here's our command prompt, and Kappa is obviously a very simple call that we just make by doing Kappa like that. So first I'm going to go into the desktop for the administrator. We are going to list the contents of the desktop, and we have the mal folder, and we want to run it against mal4 that's available for us here. So we're just going to do kappa, and then we're going to do mal\4, and that's basically it. And I'm going to press enter. It's going to take a minute, and then it'll go ahead and generate everything we need for us. I did not do verbose or very verbose. I don't know if that'll make a difference. We'll find out soon enough. Hopefully we'll be able to get all the information that we need by just running it normally without actually running very verbose or verbose. So it's loaded, very good. So now we're just waiting for the analysis portion to finish, and so that's what it's doing right here, right? So it has loading 100%, matching, it needs to also get to 100%. So right now it's still doing its analysis portion. So I will give this a couple of minutes and we will come back when it's done. Okay, so that took maybe 15 minutes, I want to say. So it took a bit of time, and now we have all of our results. Now it says how many matches for anti-VM execution techniques were identified in the sample. So anti-VM execution techniques is what we're looking for, and you can see right here that we have let me see if I can zoom right here, the matches that we have right here for capabilities. So anti-analysis, anti-VM detection, I guess. And so let me see if there's anything else, but anti-VM execution right here, execute anti-VM instructions. It says 86. I wonder if that's the number. So let's try 86 here. Very good. That's the answer. So does the sample have the capability, I guess, to suspend or resume a thread? Answer with Y or no. So to suspend or resume a thread. Let's see if we can find that. Towards the bottom, we have resume thread 2 matches. So we're going to say yes to that one. What MBC behavior is observed against the MBC objective anti-static analysis? So if we go over here to the top right here, so we have MBC objective, and then we have anti-static analysis, and it's looking for the behavior. So disassembler evasion, argument obfuscation, etc. So I think we also need to give it the ID at the very end. So disassembler. Okay, very good. And at what address is the function that has the capability check HTTP status code? The function that has the capability check HTTP status code, and I think it's under capability. So at what address? And the address would be the namespace that they're talking about. So the check HTTP status code is right here, and the address is communication HTTP client. So what do we have here? Okay, so I stand corrected. The namespaces are not the addresses, and the hint that we got right here is to run it with verbose or very verbose and output it into a file and then go ahead and look at the results. So now I have to rerun this, which I'm going to do with just basically using the same command that I had before. And then what we can do is do one of these forward arrows right here and then just give it a name of a file. So we'll just do analysis, I guess, .txt, and that'll be our output file. And oh, you know what am I doing? I literally have to do the, oh, look at that, it happened very quickly. So oh no, it didn't. I thought it did. And I need to do a very verbose option with this. So we're going to do kappa, and then we're going to add the very verbose at the end, or verbose. I guess I'll just do verbose just in case it makes it a little bit faster. And then we're going to do it the analysis.txt. I wonder if, did it happen? That was very quick. Oh no, it barely just started. So it's going to take however many minutes, I guess. And so I have the analysis.txt file over here. I wonder if also, no, it's not. It's not already updating. So we will see how long that whole take. It probably is going to take another like 15 minutes or maybe even longer. So we'll see how this goes. Okay, we are done with the kappa. And so let's now look at the analysis file. And okay, cool. Now we have information here. And what are we looking for? We're looking for check HTTP status code and the address for it. So you can do a few things here. We can actually go through view, what is it, or format, edit, find. There we go. So Control F, but I'm on a virtual machine. Usually it doesn't work for me on Windows machines. So I'm looking for check HTTP, and my keyboard went to sleep because this took so long. So check HTTP status code is what I'm looking for. And there it is. So we have that, and the matches, I guess, would have this right here, namespace, scope, matches, and then encode using data, using etc. So I mean, I guess that would be the one, the matches part, because now it's going used to the different capabilities. So let's see if this is the answer. I hope it is. Let's see if that's the answer. Yep, that is the answer. So the match is right here. That's the address that they're looking for. And we are now done with that one. So now we can move on to leveraging the PE header. For this one, we're going to be using PE Studio, and the PE header and everything inside of the PE header is something that we went in depth for inside of the very last video. PE stands for Portable Executable, which are these executable files, and they consist of a sequence of bits stored on the disk. And the sequence is in a specific format, and initial bits define the characteristics of the file and explain how to read the rest of the data. And this initial part of this PE file is called the header. And inside of the header, there's a series of different information. And this is where like a lot of the nuanced details that I was referring to at the beginning of this video, this is where a lot of it came in, because for the most part, I mean, most of it went over my head because I didn't know what it was. And I was like learning as I was recording. And now I've been exposed to it through multiple videos, so I'm a little bit more familiar with it. So if you don't get it on the first attempt, if this is like your first time watching this or hearing about what PE headers are and everything, don't judge yourself. Don't be too critical of yourself, because it is a concept that requires exposure on multiple instances for you to really get it, for you to really kind of wrap your head around it. So it's not that big of a deal if you don't understand all the details and everything like that. We're going to be trying to find certain information inside of the PE header using PE Studio, and it's one of those tools that can help us analyze PE headers. And PE Tree was another tool that we used, which was a command line tool, and we used that inside of the analyzing or dissecting PE headers video. So the header inside of a portable executable contains information that's useful for malware analysis. And one of the big things was the various commandlets that were inside of it. So it would actually list all of the different elements that are being imported, the linked libraries and imports and functions that are being pulled into the executable file. And it's inside of the header. So all of that stuff that's being imported, I think it was like under the descriptions or something like that, where we actually saw it. The PE file doesn't contain all the code, so it reuses code from libraries and it imports them, right? And a lot of these things are a native part of the Windows operating system, and the functions from these libraries are imported, and the header contains the information about the libraries that the PE is actually using, the executable is using, and the functions that are being imported from those libraries. And this ends up becoming very useful for us because we can tell just from the stuff that's being imported what the executable is trying to do, right? What the functionality of the executable is, what the functionality of the malware is. So for example, if it imports the create a process function, we can assume that it's trying to create a process, right? So there are other functions that provide information about the sample, and it's something that we don't know the context in which these functions are called just by looking at the header. So we need to dig deeper into it to try to see what it actually does, and we'll be doing it in the future videos because this is literally the last main section of this particular video before we get into the wrap up. And so we'll be doing it in future videos. So this is what PE Studio looks like, right? You have the left pane and then you have the right pane. And inside of each individual section right here, you have more information. So if we click on libraries, it'll show us the dynamic link libraries that are being pulled. And then under the description, we'll see what those individual libraries are actually good for or what they try to do. And then there's also functions that will tell us more information about the individual commandlets or the individual functions that this specific malware is trying to call. For example, exit process, get time zone information, get local time. Let's see, terminate process. My dog just hit my my Windows, not my Windows, I wonder if it actually cut the video for a couple of seconds as well, because on my actual screen the video got cut because my dog hit my wires, my HDMI wire. So anyways, these are just some things that are pulled up, right? So exit threat, create threat, fatal app exit, etc., etc. So those are called functions, and these functions are pulled from individual libraries. So if you actually see, it's kind of tough to see right here, but it says kernel 32 DLL. So if we actually look at the library list again, we see that kernel 32 DLL is available over here, and dedicated to this DLL are 153 functions, and in total there are 422 functions that have been imported by this specific executable file. Then there's the concept of the packed executables, which is another thing that we talked about in the last video. And packed executables typically are, or the creator of the malware understands that you can actually find the information about these, what the executable can do through static analysis. So what they do, they try to kind of mitigate or try to evade analysis by packing the original sample inside of a shell type code that, again, obfuscates, right? It disguises the properties of the actual malware, and it's called packing in this particular case because the PE file is now called a packed PE file, which reduces the effectiveness of some of the malware analysis techniques that we've talked about so far. And if we try to search for strings in a packed executable, we probably won't be able to find anything. And searching for similar samples using SSDeep will probably return sampled packs with the same packer instead of the actual samples that behaviorally similar to the sample of interest that we actually have. So signatures might also be evaded due to a malware sample being packed, right? So everything that we've talked about so far can technically be evaded if the malware author packs the contents of the malware. And then if you try to look for hash values or signatures, the only thing that will pull up is signatures of other packed malware instead of actually pulling up signatures of individual functions or commands inside of the malware. And when we go into dissecting PE headers, which is going to be a future video, I think it's the next video that I'm going to end up making, we can identify packed executables by looking at the header of a malware, and then the header contains information like the number of these sections, the permissions of different sections, sizes of the sections, etc. And then you'll end up seeing that like the names of the sections could be blank, or the sizes of the sections would be like noticeably much smaller than anything else because it's been condensed, right? It's been packed. Think of it as turning it into a zip file, right? Like you turn all of the contents of the malware into these packs so that you can't see just off the top what those contents actually include, and it also reduces the size of the various elements of the malware. So it can give us pointers to help identify samples that are packed, and if they are, which type of packer has actually packed the executable. So we're going to open up the malware 4 in PE Studio and to see which library has actually been marked as blacklisted, and then what does that specific library do, which is most likely going to be inside of the description of it. So the PE Studio, I basically searched for PE Studio in File Explorer because I couldn't find the location of it. And the path seems to be that it's in Program Data, Microsoft Windows, Start Menu, Programs, Flare, Utilities, and it seems to be over there. So I'm just going to double click on that, and it'll open up PE Studio for us, and then we'll go ahead and open up the malware 4, the malware sample 4 inside of it, and then we'll be able to look at the contents that we need. So you go to File, Open File. This part is like very simple with any other application that you would use in Microsoft, all of those things work exactly the same. So now I'm going to go in the left section right here. I'm going to go inside of my desktop for the administrator user. Inside of that, I'm going to go inside of the mal folder, and then I'm going to open up for. Now, interestingly, there was also for viv, which was something that I noticed, and I wonder what that was, but we will not be distracted in this particular case. So this is loading, and I think like as we wait, it's going to load more information because it says waiting next to a lot of these things. So I'm going to give it a couple of seconds or minutes or however long it takes for this to fully load, and then based on the final information, we're going to look at the library that's been blacklisted inside of the libraries section, which is currently still waiting to load. And then from that, we're going to also get the description of that library. Okay, cool. So here we go. We have the libraries loaded. Oh no. And the freaking thing started shutting down as soon as I was ready to go. That's insane. Okay, so now I got to give it a second to load. Okay, I had to go through another restart of the virtual machine because it loaded everything and then it crashed on me. So we have the libraries right here, and there they go. And so let's remind ourselves of the question again, which is asking for which library is blacklisted. And this is the only library that has blacklisted, which is RPCRT4DLL. And we would need to try to find the description of that, which is remote procedure call runtime. So first we're going to type the name of it, which is RPCRT4.dll, and then the description is remote procedure call runtime. And with that, my dear friends, we are officially done with all of the questions here. All right, so far we have learned about basic static analysis, that you need obviously a malware analysis lab environment. So Flare VM is the one that we use because it is a Windows based and it has a graphic user interface and it's pretty decent. Remnux, which is the management or the malware, the reverse engineering malware version of Linux, I believe also has a graphical user interface. It just depends on which one you're most comfortable with. And I think, things like PE Studio as well as PE Tree and Kappa and all those things are available inside of Remnux, as well as, obviously, as we just saw, Flare VM. So that would be the lab environment. And you would want to do that for any kind of malware analysis activity because you don't want to put yourself in a situation where you, number one, mess up your main computer. And then number two, it's like you want to have the downloaded version of this thing, or at least the ISO image, and then run it, do whatever you want with the malware analysis, especially when you're doing static analysis, what we just did, because we weren't technically running any of the malware. We were just analyzing each one of those files inside of these different tools. So that technically counts as static analysis. When we go into dynamic analysis and we're going to start running these malwares, it emphasizes the importance of a lab environment even more in that kind of a situation. Searching for strings and obfuscated strings is what we did. Fingerprinting malware using hashes and identifying similar samples of the imp hash and SSDeep is also what we did. Signature-based detection with Kappa, and then of course identifying artifacts from the PE header. We did all of these things using tools, right? We didn't run strings and then just look at all the strings that came out. We looked at string values inside of a tool, and that made it easier for us. So to kind of put you at ease a little bit when you go into malware analysis, even if you don't have a background in malware analysis, as long as you have a decent understanding of what you're looking for, these tools will help you filter and parse through all of the contents of the malware to get you that data. And then from there, you kind of can determine what things might be relevant to malware analysis techniques and your specific investigation in your particular use case. So whatever that may be, whatever it is you might be looking for, these tools make it easier for you to find them. And hopefully that puts you at ease a little bit, because it definitely puts me at ease. I'm not a fan of reading line by line the output of the terminal and these various different tools that are just, they seem very tedious to try to go through line by line of output of a code and things like that. I enjoy doing that on the offensive security side because it actually makes me feel like a hacker to use the terminal and run these different tools. But when you're talking about analysis, there's so much stuff to analyze, and I don't like looking at just line by line by line by line of data. I want to use a tool that will make that process a little bit easier for me. And you just saw that we actually used several of those tools. So what we're going to do in the next video is we're going to continue along with this type of process. I think the next video is actually going to be an exercise that we're going to run for static analysis, and it's kind of like an actual practical exercise. And after that, we're going to go into dynamic analysis, I think, right? Don't quote me on that, but I believe that's what's in our future. So hopefully you found value from this particular video in this particular room. I'm going to click on complete so that we can go ahead and wrap this one up. And then I'll give you a couple of little notes real quick, and then we'll wrap the video officially. If you found value in this video, and if you found any value from this channel, I do encourage you to like, subscribe, and turn on that notification bell so that you get notified the next time that a video comes out on this channel, especially as we wrap up SOC Level 2, as we go further into PenTest Plus, which is drops every Friday. A new episode comes out every Friday for PenTest Plus, and then at the very end of it, I'll do like a bulk upload of all of the episodes so that for the people who like the bigger videos, you'll be able to find those as well. And then we're going to go into AI for cybersecurity, and then CYSA Plus, because I got a request from somebody to do a series on CompTIA CYSA Plus. So there's a lot of content that's going to be coming out, and I don't see it slowing down anytime soon, because this world is constantly evolving, and it's one of those things that I don't think we're ever going to run out of things to talk about. And then we're going to end up doing interviews with other professionals in the industry, other hackers in the industry, which I think is going to be really exciting for people who like the podcast type content, because we get to really look at people who are really deep in the game that are actually doing these kinds of things, and get to see what their situation is like and what their experience has been like, what they can teach us. So it's going to be really exciting. I'm super excited for the future of this channel, and I would love for you to tag along on this journey with us. So make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And of course, if you have any questions or anything, drop a comment, and I will get to your comments as soon as I see them. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section. And that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. Love, peace, and chicken grease. If no one else loves you, Hank loves you, and I will see you in the next video later. In episode 43 of the SOC Level 2 training series, we are going to keep going with our malware analysis module, and we are now officially doing an exercise, a practical exercise, where we're going to use everything that we've learned so far in malware analysis to basically do an investigation and find the answers to over a dozen questions. I think there's a lot of questions on this particular exercise. There isn't much information that we are going to be given. So in this particular case, we have like an introduction that tells us this is the scenario, these are your prerequisites basically to start the virtual machine that's going to have the controlled environment, the lab environment. But that's basically it. You can use Remnux, which is the machine attached to this particular task, or you can use essentially anything else. For example, Flare VM. In the last video, we did Flare VM. In this particular video, we're going to use Remnux, but they have the same software installed on them. So that's essentially what our tool set is going to be. And then we just have a bunch of questions that we got to answer. And that's it. There's really no tutorial breakdown or no instructions left, right? So everything that we've covered so far in the last 5 videos, I want to say, I think we've done 5 videos in malware analysis. We're going to be combining all of that information and using everything that we've learned so far to answer these questions. If you're serious about your SysAdmin education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into MalBuster. This room, this specific exercise, is going to be practice for everything that we've learned for dissecting PE headers and static analysis. And we're going to act as one of the reverse engineers that will analyze malware samples based on detections reported by the SOC team, by the Security Operations Center team. The prerequisites would be intro to malware analysis, dissecting PE headers, basic static analysis, which were basically the last several videos that we did. You don't need to worry about, I would say you don't need to worry about the x86 videos, because there was the x86 architecture as well as assembly. You technically don't need to worry about those. Intro to malware analysis, dissecting PE headers, which is a big one. These two are really big ones. And then basic static analysis, which is the very last video prior to this one. All of those I think would be the most relevant in everything that we're going to be doing today. The scenario is that we're currently working as a malware reverse engineer for the organization. The team acts as a support for the SOC team when detections of unknown binaries occur. One of the SOC analysts triaged an alert triggered by binaries with unusual behavior, and the task is to analyze the binaries detected by the SOC team and provide enough information to assist them in remediating the threat. We are going to be using 2 platforms, Flare VM and Remnux VM, and we can utilize the machines based on our specific preference. I just activated the first machine. I have no idea what loaded, so we'll find that out together. If you prefer Flare VM, you may start the machine attached to this task, else you may start the machine on the task below. So I guess I opened Flare VM because I just clicked this one right here. So I think I'm opening Flare VM, but again, they have the same tools, right? So if the virtual machine is not visible, we're going to do split screen, all of that stuff. And you can find all the malware samples inside the desktop samples location. Don't download the malware samples to your host. That's a big thing right there, because they are actual malware samples. Okay, so just keep that piece in mind. Please do this inside of a controlled environment. This is a subscriber-only room, and this is one of the big benefits for TryHackMe because of the fact that they have these controlled environments, these lab environments that you can basically do whatever you want with this malware and never have to worry about your actual computer hurting or getting affected or infected in any kind of way. And the same thing goes to the attack exercises. When we do hacking exercises and pen testing exercises, we also do those in lab environments so that we don't have to worry about getting arrested for felonies, because hacking is a felony. That being said, let us jump into the actual challenge. In case you use Remnux or you prefer Remnux, you can just use the start machine button in this particular case, or in case you've downloaded Remnux for your VMware or your VirtualBox installation instead of Flare VM, same thing. The malware samples in our particular case are inside of this location, which is the equivalent of what we saw for Flare VM on the desktop of that specific administrator. And that's basically it. So, and then we just jump into the questions here. So first thing I'm going to do is I'm just going to open up this machine inside of full screen in a new window to make it a little bit easier for us to use. And this is one of those things that I hope the Windows machine doesn't crash on me, because in the last video it crashed on me a couple of times and I had to restart the freaking thing all over again. So hopefully it won't crash on me. And we have everything going. So let's jump into question number 1. Okay, so I lied. I had to start the Linux machine because the Windows machine was not a good machine. So I like Linux. I don't know what to tell you. And I think in the TryHackMe environments, the Linux machines just tend to do better than the Windows machine. So we're not using Flare VM. We're actually going to use Remnux. But again, they have same tools, same desktop samples that we're going to be using. None of these things are going to change. So, okay, now we can look at question number 1, which is based on the architecture of the binary, is MalBuster _1 a 32-bit or a 64-bit application? And so in this case, there are several different ways that we can actually do it. And one of the easiest ones is to just look at the file type of MalBuster, and it'll kind of give us some ideas here. So let's go ahead and let's see. I need to see where I am right now. I'm here. So we're going to go to desktop, and we're going to go into samples, and we have MalBusters all here. So the first one is MalBuster 1. And so if we just look at the file type, usually it gives us a decent amount of information about the architecture of the file. And that's what 32-bit and 64-bit is referencing. So if we're trying to find the architecture of the file, we can just use the file command, and it'll usually give you architecture. So MalBuster _1, and it'll give us, you know, PE32 executable. There you go. So 32 executable, Intel 80386 for MS Windows, and I think the 80386 I think is also a hint, but it literally says 32-bit right there. So PE32. And so that's what we want, is 32-bit. There you go. That's the answer. Okay, cool. That was question 1. Question 2 asks, what is the MD5 hash of MalBuster 1? And this is, again, another one of these really, really easy things to get, especially in Linux. This is one of the reasons why I like Linux so much. So there's something called MD5 sum, which is a command that will just get the hash value of it. If you wanted to get the SHA-1 hash, you would do SHA-1 sum. If you wanted to do the SHA-256 hash, you would do SHA-256 sum. So that's the pattern for the commands here. So if we want MD5 sum, we just do that, MD5 sum, and then we give it the name of the file, which is in this case MalBuster _1. And then there you go. That's the hash value, the MD5 hash value of the MalBuster file. So let's see if that actually, there you go, that copied it for us. And cool, moving on. Question 3 says, using the hash, what is the popular threat label of MalBuster according to VirusTotal? So for this, I can actually just use my own computer or my own browser. I can go to VirusTotal, we'll go to search, and then in the search box, we're just going to drop that hash value. And then what does the question say? It says, what's the popular threat label of this? So the popular threat label, I guess, let's see here. Oh, it's right here. It's literally on the, it's like in the middle of the screen. It says popular threat label Trojan.zbot/Razy, I guess. So let's see, we'll do this. Trojan.zbot/Razy. That is the popular threat label of MalBuster. Based on, question 4, based on VirusTotal detection, what is the malware signature of MalBuster 2 according to Avira? Okay, so we need to go back here, and we're going to do the same thing basically to get the hash value, and we're going to do MalBuster 2. So now we have MalBuster 2's hash value, and so we're going to go to VirusTotal, and we're going to do another search right here. I'm just going to drop the hash up there, search for it. And okay, here we go. That is MalBuster 2, and it says, what's the malware signature of MalBuster 2? So let me go ahead and try to find that. And they want the signature based on Avira. So Avira's signature is this right here. So agent heuristic, remember? So I talked about it in the last video. Signature is another way of saying heuristic, and I don't know why that didn't copy. So let's see if I can copy this one more time here. So we're looking for there you go. So heuristic, or I guess Hure is kind of like the short for it, but when you're looking at signatures, usually they're not going to say signature, especially if you actually go to the details tab and try to find something for the signature value, because under the signature info, it says that the file is not signed, which is, I guess technically there's no official signature on the details that have been found for this. So if we want something specific to Avira, this is what they have labeled it, which is this piece right here. So that is that question. So moving on to question 5, I want to say. Question 5 says that MalBuster 2 imports the function core exe main. From which DLL file does it import this function? And we can find this in a few different ways. I used PE tree. Thankfully, it loaded fairly quickly on this particular machine. I thought it was going to take a long time because when we ran it on a Windows machine, when we were doing dissecting PE headers, it took quite a while. It took like 10 minutes to load PE tree, and this is another reason why I like Linux so much. So this actually loaded much faster. And in this particular case, we are looking for the, what is it? It's the importing of the function. So from which DLL does it import that function? And we need to find this inside of the, I think it's inside of the image section header. So basically what happens is that when you click on each one of these, it'll open this up, and then the next one will open up the next piece, and then sorry, my dog is barking in the background. And the next one will open up the next piece, so on and so forth. And so we're trying to see, I think it's inside of the section header specifically. So I'm going to go to this if I remember correctly. And the question again is core exe main. So what we're looking for is core exe main, and then from where that's being imported. Yes, very good. So inside of this particular section, the image section header, there's another piece at the bottom right here, which is the import descriptor. So these are the things that are being imported. So if we expand this piece right here, we'll see that there's going to be this DLL. So the MS core, or Corey, I guess, the MS core DLL. So let's see if that's our answer here. So MS core with an extra E, DLL. Okay, cool. There we go. Question 6. Based on the VS version info header, what's the original name of MalBuster 2? So VS version info header, and what just happened here? Virus total open inside of the machine. So VS version info header. So if we actually go back to the DOS header at the very, very top right here, there is another section under the original information. So VS version info header is what we're trying to look for. To get that original name of this. This also actually exists on the virus total database as well, because it's actually right under the very top of the original information. When you actually run the hash value for it, you'll be able to find it over there as well. But let's see if we can find the VS version info header. It's actually at the very bottom of this whole thing. So we had image NT headers that was open. So if we collapse that, we can get VS version info opened up right here. And the original name, the internal name right here, this is what it is, 7jype.exe. But if we actually go back to virus total for that hash value that we have, you can see right here for that hash, this is the original name of the file as well. So we actually have two different locations that we can pull that information. And there you go, that's the original name of MalBuster 2 based on its hash value. Question 7 says, using the hash of MalBuster 3 now, what's the malware signature based on abuse.ch? So let's go back into our terminal here, and it actually has this open, so I don't want to close that for now. I feel like we won't need it because I think we've moved on to the other one. So let's go into the desktop, and what do we have? Samples, and we want the MD5 sum of MalBuster 3. So there we go. Now we have MD5 of MalBuster 3. And we're going to copy that, and let's go. I think this is what where abuse.ch is right here. I think it's in one of these things right here, unless I stand corrected. I think it maybe not. So abuse.ch, yeah, abuse.ch is not here. So let's see. What abuse.ch might be a website, right? So if I go to abuse.ch, does that exist? Fighting malware, our mission, etc. Is there a way that I can search or query this? Let's see, is there a hint that's available for us? What's the malware signature based on abuse.ch? At the very top of the abuse.ch website, there's this hunting.abuse.ch that has been given to us, and now we have actually a search bar. So we can search for this. Authentication required. You need to log in. Okay, so gosh, now I have to log in. Okay, cool. I was able to use my Google account to just log in. So let's try that one more time. And there we go. Okay, great. So now it's actually doing a search for this hash value for us. And now we are looking for the signature, I guess, for this thing. And it's interesting because it has URL house, malware bazaar, threatfox, Yara, EFI, SandNet. All of these things have actually been pulled. So let's see if I do URL house. Let's see what information I get. And what am I looking for again? I'm looking for malware signature for this thing. So the malware signature is TrickBot is what it says right here. So I think we'll try that as an answer. So TrickBot. Okay, cool. That is the answer. So there you go. So signature right there at the bottom, it says TrickBot, and that's the answer. Okay, cool. Moving on. Question 8, using the hash of MalBuster 4, what is the malware signature based on? Abuse.ch. So we're literally doing the same thing. Now we're just using MalBuster 4. So let's go back here, and then we'll just run our MD5 sum, do MalBuster 4, and there we go. Now we have the hash value of MalBuster 4, and we're going to pull back out, go over here. We'll do a new search right here and paste that in there. And malware bazaar URL house. So let's just go to malware bazaar. Signature is zloader is what it says. So let's go here and let's try zloader. And there you go. That one was pretty easy. Question 9 says, what is the message found in the DOS stub of MalBuster 4? So to be able to pull that up, we actually had to go to PE tree again. And the command, just to kind of show you one more time, is like this. So you do PE-tree and then give it the name of the file and it'll pull it up for you. I don't think I said it the last time that I used PE tree. So now we have DOS stub. So we're just going to click on DOS stub, and the question was, what's the message found in DOS stub? So what is the message? It says, this salfram cannot be run in DOS mode. So let me see if I can copy that real quick, and then let me see if we can go right there. Boom. Okay, very good. Boom, just like that. Easy. Question 10, MalBuster 4 imports the function shell execute A. From which DLL file does it import this function? So we're looking for shell execute A in the import section. So if we go to image section header and then scroll down, and then we can find the image import descriptors. And so we will click on that, and then it has, oh my God, it has a bunch of stuff. Okay, so we got to go through each one of these one by one. I wish there was a way that we could search for the contents of these things, but I don't think we can. So I gotta go through each one and try to find shell execute. So shell execute A is what we're looking for. So let's see inside of which one of these DLLs there is shell execute A. Okay, so here's a little trick for you. Okay, so the DLL itself, the dynamic link library, it kind of gives you a little bit of a hint of what commands or functions could be inside of it. And there's something right here called shell32 DLL. So if we open that up, I'm willing to bet that shell execute is inside of this thing. It says shell execute exw, and I'm looking for shell execute A. There we go, shell execute A. Okay, so great. So that is actually inside of the shell32 DLL. So some of them, if you kind of just look at the name of the DLL, you can kind of guess what it would be inside of it. And obviously it has the name shell in the DLL. So we can assume that anything that might have to do with shells would be inside of that dynamic link library. And thankfully it was. So now we can move on. Oh, and now we're going to be using Kappa. Question 11 says, using Kappa, how many anti-VM instructions were identified in MalBuster 1? And so the command for this, and I guess we can just close this out. The command for this is Kappa, literally, and then we're just going to do MalBuster 1. And we're going to run that, and it usually takes a few minutes, although the last time that I did it was inside of the Windows machine. So let's see how long it actually takes to do it inside of this Remnux machine. And then we'll go ahead and find the anti-VM instructions. Okay, cool. That was significantly faster than the Windows machine. Holy crap, dude. Okay, cool. So anti-VM instructions is what we're looking for here. And anti-behavioral analysis, tactic is evasion. These are the SHA values. So I think it's going to be at the very bottom right here. So we're looking for anti-VM instructions and how many of those actually exist. So it says referencing anti-VM strings, M detection. So what is that? 1, I guess. Check HTTP status is 2 matches, and enumerate. So I think it's 1. I think that's the actual answer for this. So let me see. It's not 1. Okay, so let's see. Okay, so I think I misunderstood the question. So I thought it was like antivirus is what I thought it was asking for, but it's actually asking for anti-virtual machine instructions. And so if we actually go through the objectives and the attack tactics right here, so defense evasion, virtualization, and sandbox evasion. So virtualization counts as virtual machines. And then under MBC objective, there's also anti-behavior analysis, virtual machine detection. So that's 2. And then we have the anti-VM strings, which would be the 3rd. So 3. Okay, great. So 3 is the answer because it's not asking for antivirus. That's for some reason I thought that's what it was trying to ask for, but it's actually asking for anti-virtual machine instructions. So there we go. That's the answer for that one. Now moving on to this one. Question 12 says, using kappa, which binary can log keystrokes? Now, I tried to run kappa on all of the binaries at the same time by using something similar to this command where you do use the asterisk as a wildcard character to try to see if I can run all of them at the same time. But then it has an issue, right? So it says error unrecognized arguments, and then it thinks that the rest of the file names are being served into it as arguments, and then it doesn't allow us to do it. So I think I actually do have to do it one by one. So that's going to be fun. And I'm going to just run it as just one at a time, really. So I should have analyzed the last one because I feel like that was the one that we did, and I didn't see any keystrokes or anything inside of it. So I don't think MalBuster 1 actually has it because I really didn't see any keystroke references inside of it. So I'm just going to cancel this one right now, actually. And then we'll start with MalBuster 2. And so we'll do MalBuster 2, and then I'll grep for keystroke. So let's see if that'll kind of exist. And then we'll do a -I for it to be case insensitive, and then see if we can actually run kappa and see if we can pull anything that has to do with the word keystroke. Okay, so against MalBuster 2, nothing returned. I actually tried keystroke and I did key asterisk just in case it was like keylogger or anything along those lines. So nothing came back for MalBuster 2. So let's do the same thing, but now we'll do it for MalBuster 3, and let's see if anything comes out of that one. Okay, nice. So in MalBuster 3, there were actually several instances referencing key logging. So key logging input capture, polling application hook, and log keystrokes via application hook. Okay, great. So it is MalBuster 3. So let's do MalBuster 3. That should be the answer. Yes, it is the answer. Exciting. Okay, great. Moving on to the next one. I think we're making some decent progress. We have just a handful of questions left. Question 13. Using kappa, what is the MITRE ID of the discovery technique used by MalBuster 4? And that's actually really nice because it does have the MITRE attack section inside of the kappa output results. So hopefully it'll also, I think it also has the ID as well. That is generated for us when it actually generates all of that stuff. So we're going to wait for it to finish analyzing MalBuster. Oh, that was very quick. There we go. Okay, cool. So we have MalBuster 4 analyzed here, and this is it. So under attack technique, you see that attack tactic is discovery, attack technique, file and directory discovery, and then there's T1083. That's the ID. So T1083. Boom. Excellent. Moving on. We're almost done. Let's go. Question 14 is, which binary contains the string God mode? And inside of Linux, we actually have a very useful tool, and it's actually available in Windows as well. It's called strings. So if we know kind of what we're looking for, we can just kind of grep for it. So we have MalBuster 1, grepping for the phrase God. So we'll do like that. Actually, let's do case insensitive all the time. So you just want to make sure that just in case it has capitalization or something. So it does not have God in it. It has reg open key and etc. Okay, so there you go. MalBuster 1 does not have it. So let's do MalBuster 2. And this has God mode. Boom. Get God mode, set God mode. So that would be MalBuster 2. So boom. Excellent. Nice, nice, nice. And last question here. Question 15. Which binary contains the string Mozilla 4.0 yada yada yada? So we're going to do the same exact thing from the top. So we'll do MalBuster _1, and then now we're going to grep for Mozilla in this particular case. And let's see. Okay, I mean there you that was quick. Mozilla 4 compatible. That's what it says, right? Compatible MS. Yeah. Okay, so it's MalBuster 1. That was the very first one, luckily enough. And that should be it. That is it, my dear friends. Congratulations on completing MalBuster. That was not that bad. I thought it was going to be a little bit more difficult, but from now on, just to let you know, as a personal preference for me, I am going to be using Remnux if I have the opportunity to do it. I will not be using the Flare VM because it just worked so much faster. Like the issue with the Flare VM situation wasn't functionality, it was the fact that it was so slow in loading everything. So, and it could be that, you know, the malware files that we were analyzing previously were much larger, so maybe that's why it was taking such a long time to load them. But PE tree inside of Flare VM took forever inside of the Windows machine, essentially, which is what Flare VM is. Inside of Remnux, it was instantaneous. And that's the thing that I'm like, holy cow, it just did not take that long. What, my recording is less than an hour. By the time that I cut out all of the pauses and everything else, it'll probably be around like 30 minutes or something like that. So very, very quick exercise. I loved it. I'm super freaking happy that it took as little time as it did, because now I can go eat something. So that's really, really exciting. So, okay, so we have now terminated our machine. We are officially done. Hopefully you actually got some value out of it. Hopefully you got the same results and everything. If you did get some value out of this video as well as out of this entire channel, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel, because we are wrapping up SOC Level 2. Every Friday, there's a new video that comes out for CompTIA Pentest Plus based on the actual PT0003 test, which is the most recent version of the Pentest Plus that's coming out. And then we have, after that, it's going to be AI for cybersecurity. And then there's going to be CompTIA CYSA Plus and all of the content that there's just so much stuff that's going to be coming out. And I have a feeling if you're interested in cybersecurity and if you're going to take this seriously, I think you want to be a part of that. So in that case, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. And of course, drop a comment if you have any questions or any comments. If you just want to say hi, whatever, I will get to your comment as fast as I possibly can. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section, and that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I will see you in the next video later. In episode 44 of the SOC Level 2 training series, we are going to go through the advanced static analysis room that is inside of the malware analysis module of TryHackMe. And this is the build up, right? So we did basic static analysis, and then we did some exercises that we can use, or that we used everything that we've learned so far for malware analysis, looking at the various tools that we used, etc. And now we're going to go through advanced static analysis, which is, as the name implies, the advanced strategies for doing static analysis, meaning you're not running the malware yet, because we're going to get into dynamic analysis in the very next video, or maybe the video after that one, because I think the next video is going to be the challenge questions for static analysis, for the advanced static analysis. So we're going to go into dynamic analysis where we actually run the malware, but in static analysis, we are still analyzing source code and the contents of the malware without actually running it. And the overview of this content is obviously the intro malware analysis overview, connecting to the virtual machine, which is going to be our controlled environment, Ghidra, a quick review for that, identifying C code constructs in assembly, the overview of Windows API calls, common APIs used by malware, process hollowing, and analyzing process hollowing. And then finally, we have the conclusion where we'll review everything. I'll give you some final thoughts, some final notes, and then we'll wrap it up and then you'll be dismissed for the day. So this is a subscriber only room that's available inside of TryHackMe. However, the virtual machines that we're going to end up using are available for anybody who just wants to get access to those virtual machines. I think in this particular case, it's just giving us a virtual machine specifically, and it might be a Windows machine. Yeah, it is a Windows machine because we're going to, it says that we can RDP into it, and RDP is pretty proprietary. It's native to Windows machines. But you can technically use your own Windows machine to go through exercises like this, because you can always get the tools that we're going to be using to do the exercises yourself. I just wouldn't recommend that you download and run malware on your own computer. So just please be careful with that specific piece. It's like a very small detail, but it's a really, really important detail. So don't download malware just because you want to try the tools, okay? It's very, very important that you understand that. Apart from that, everything else you should be able to get access to, because we're only going to be using open source tools to do everything that we're going to do in this particular video. If you're serious about your SysAdmin education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us dive into advanced static analysis. In the basic analysis video, the basic static analysis video, which was the second video prior to this one. So if you go back one, that was the exercise that we did for practicals, and all we did, we were just answering questions and doing an investigation. The video prior to that one, so I want to say it's episode 42, that was the basic static analysis video. And we looked at characteristics like strings inside of the content of the malware, hashes, import functions, and other key information that was inside of the header, the portable executable header. And that was pretty much it, right, to get an idea of the malware. And in advanced analysis, we're actually going to be looking at the disassembled code and analyzing the assembly instructions to understand the malware's core functionality in a better way. You don't need to necessarily know code, okay? So I just want you to understand that. For a lot of people, including myself, coding is not this really deep skill that we've developed as we got into cybersecurity, and we're kind of learning coding as we go along. And for me, before I got into cybersecurity, the only coding languages that I really understood were HTML, because I used to do web development, and then a little bit of Python because I created some very basic automations using Selenium, which were like web browser automations. And that was basically it. That was the furthest extent of my coding knowledge. I knew nothing about bash scripting. I knew nothing about PHP. I knew nothing about C or C++ or C++, any of those things. So just want to let you know that you don't need to know coding, okay? That's just the key thing. You're going to learn as you go, and I'm going to do my very best to explain the code, and then I will be using tools like the various AIs that are available so that we can get even a better understanding of the code if we need to understand the code. So just want to let you know that. Advanced static analysis is a technique used to analyze the code and structure of malware without executing it, right? So we're still static. And this can help us identify the malware's behavior and weaknesses and develop signatures for antivirus software to detect it. By analyzing the code and structure of the malware, we can get better understanding of how it works and develop new techniques for defending against it. So this is what happens typically, right? So you have the code, it gets compiled, right? And it becomes an executable. And then when you disassemble it or decompile it, you get the actual code itself, the assembly code itself. And it's not, the assembly code, from what I understand, is not the raw code, right? So it gets compiled, it gets disassembled, and it becomes assembly code. So this room is designed to help you acquire the knowledge needed to reverse engineer malware effectively. And we're going to learn assembly instructions more systematically, enabling us to identify important functions more easily instead of getting carried away by each instruction. So that's the key element here, right? So again, as this sentence just implies right here, you just want to be able to identify the important functions instead of getting carried away by each line of code, which can definitely be overwhelming because there are going to be hundreds of lines of code depending on the complexity of the malware. Some of the topics are how advanced static analysis is performed, exploring Ghidra's disassembler functions, and I think this is technically supposed to be pronounced Ghidra, and not very many languages have the Q sound. It's very different from the R sound that is in French. Ghidra, from what I understand, or the Q sound, I think is like 2 or 3 languages that actually have that sound. And Persian, Farsi, is one of them. That's the only reason why I know how to pronounce it. But I think for the most part, most people just say Ghidra. So just keep that in mind. That was my opportunity to flex my language skills a little bit. Understanding and identifying different C constructs in an assembly. And these are the prerequisites, right? So this is actually where we're going to be referencing the architecture videos that we did a little bit, which are a part of malware analysis. So it would be in the last series of videos, and you can see the title. So x86 architecture and assembly are actually in the title of the videos, and then basic static analysis, which we've already done as well. So those are all of the prerequisites. If you have not gone through them, I would encourage you to go through them. These two are very detail oriented. If you've never seen architecture or assembly, you will, for the most part, I think you will be overwhelmed. So I'm just going to set that precedent for you. It's not crazy, right? So it's not like you're not going to be looking absolute nuanced details of everything, but there are some pretty fine details. For example, learning how binary code translates to ASCII or Unicode, etc. Okay, here we go. Let's go on. This is probably as good a time as any to do another overview of what malware analysis is and the different elements or the different steps, phases inside of malware analysis. So we're going to be examining malicious software, also known as malware, to understand how it works and identify the capabilities, behavior, and potential impact. There are 4 steps in this. There's basic static analysis, basic dynamic analysis, then there's advanced static analysis and advanced dynamic analysis. We haven't done any dynamic analysis yet, so we've been so far just talking about static analysis. Basic static analysis is to understand the malware's structure and behavior without executing it, and we would be looking at code, file headers, and other static properties. Basic dynamic analysis is to observe the behavior during execution in a controlled environment. So controlled environment is the key phrase here, also known as a sandbox or some kind of a dedicated virtual machine or something. So hopefully it will not get onto your host machine. A lot of malware, complex, sophisticated malware, have elements in place, functions inside of it that can detect virtual machines and evade running inside of a virtual machine. So if you actually run it inside a virtual machine, then if it's a complicated or like a sophisticated malware, it actually won't do the malicious activities because it's detecting that it's being run inside of a virtual machine. And that's, where malware authors get really clever with these kinds of things, because they know that as a part of analysis, security engineers and security analysts are going to be running the malware in a virtual machine in a controlled environment. So, just kind of pointing that out for you. Running it in a sandbox or a virtual machine and then monitoring the activity, network traffic, and process behavior That's all dynamic analysis. When we get to advanced dynamic analysis, is where to uncover more complex and invasive malware behavior using advanced monitoring techniques. This involves using more sophisticated sandboxes and monitoring tools to capture the malware behavior. And advanced static analysis aims to uncover hidden or obfuscated code, also known as disguised code or filtered code, so to speak, and the functionality within the malware. It involves using more advanced techniques to analyze the malware's code, such as de-obfuscation and code emulation. How advanced static analysis is performed is essentially to discover the capabilities and identify the attack vectors and determine the evasion techniques. And to do this, we use disassemblers like IDA Pro, Binary Ninja, and Radar E2 maybe. I think it's not Radar. I think it's Radar E2. These disassemblers allow the analyst to explore the malware's code and identify its functions and data structures. The steps involved in performing advanced static analysis are: identify the entry point of the malware and the system calls that it makes, identify the malware's code sections and analyze them using available tools like debuggers and hex editors, analyze the malware's control flow graph to identify the execution path, and trace the malware's dynamic behavior by analyzing the system calls it makes during execution, and finally, use the above information to understand the evasion techniques and the potential damage that the malware can cause. So does advanced static analysis require executing the malware in a controlled environment? And that is nay, because that would be a part of dynamic analysis. So if you think about running it, think about dynamic, right? Dynamic requires running. Static, you're not running it. And that's the only question that we have. So let's talk about connecting to our virtual machine. And I'm just going to click that and start the machine. As per usual, if you've never connected to a virtual machine inside of TryHackMe, there are two options to do it. You can run it inside of the browser, which is what I usually default to. And it'll open up in split view. Technically, sometimes the virtual machines are target machines that we would use inside of hacking exercises. And so if you do that, you would also need to launch the attack box as well. But usually inside of defensive exercises or investigations like this one, as soon as you click start machine, the window kind of splits in half, as you just saw. And I had to shrink it because I'm super zoomed in. I'm at 300% view on my browser because I want to make it easy for you to read the content as I read along. But usually I will open it up in a brand new window so that we can look at the full machine as if we're literally inside of the computer. You can also access it via RDP or SSH. Now, when they say RDP, it just automatically implies that we're going to be using a Windows machine. If they say SSH, that means we're using a Linux machine. If you do use RDP, then you would just use whatever the IP address is that's assigned to you. Now, this IP address is going to be taken down as soon as I end this recording. I always say this because sometimes people get, wise ideas and they think that they can go ahead and try to do pen testing against these IP addresses. These IP addresses, number one, are fully protected. They're inside of the virtual private network of TryHackMe. To even be able to get access to them, you need to actually be connected to the VPN of TryHackMe or via VPN to TryHackMe servers, and then you'll be able to run kind of exercises towards that. Apart from that, they're completely blocked off, and they are taken down by the time that the video is finished recording. So just keep that piece in mind. But you can remote desktop into it, and these would be the credentials that you would end up using. So I have successfully launched the VM, and let's see how many files are present in the code constructs folder on our desktop. So here it is. This is the Windows machine. It looks like a Flare VM machine. So this is the VM emblem, the VM logo for Flare VM. This is not my favorite installation of Windows. I'm just going to be honest about this because it tends to kind of run slow, but hopefully it will be fine. So we have a total of 5 files inside of the code constructs folder. So we'll just enter that, and we will now move on to Ghidra or Ghidra. There are many disassemblers in the world of security. We have Cutter, we have Radar E2, Ghidra, IDA Pro, and they can all disassemble malware. We're going to use Ghidra because it's free and it's open source, and it has a lot of features that can be utilized to get proficient in reverse engineering. And the idea is to get comfortable with the main usage of a disassembler and then use that knowledge to use any kind of disassembler, because for the most part, they will be serving the same function. It's in a software in reverse engineering that allows us to analyze compiled code and understand the functionality. And it's designed to help analyst developers understand the workings of the software, right? So how does the software work? By providing a platform to decompile, disassemble, and debug binaries. I absolutely love the logo because I am obsessed with dragons. It's one of the things that I became even more obsessed with as I got into ethical hacking and cybersecurity, because one of the logos for Kali Linux is this gorgeous dragon that they have. So this is just a different dragon. It's not the Kali Linux dragon. Let's not get confused here. But the Kali Linux logo, at least the most recent versions, are also a beautiful, beautiful dragon logo. Okay, so these are the features of Ghidra, okay? We have the decompilation, that it can decompile binaries into readable C code, making it easier for developers to understand how it works. Disassembly, that it can disassemble binaries into assembly languages, allowing us to examine the low-level operations of the code. Debugging, that allows users to step through code and examine the behavior. And analysis, to help us automatically identify functions, variables, and other code to help us understand the structure of the code. When you launch it, this is kind of what it looks like. And I've already launched it, so this is like the full view of, or like the large view of what it is. And then you kind of just open the file, right? So you can first create a project, and all of these things is, I'm just kind of like breeze through this because we're actually going to apply these steps. So you open it up, you create a new project by doing new project. You select a non-shared project so that you're just using it for yourself. You can also do shared project if you want to share it with your coworkers. You name the project and set the directory, or you can just leave the default path for the directory. And then you import the malware executable. So this is where we actually bring in the executable that we want to analyze. And in this particular case, it's the Hello World executable that is on the desktop, and it's actually on this desktop right here as well. That's the executable right there. So you import it, you click OK, and it basically starts running, right? And so it'll show the summary of the program as we see right here, the file name, the read-only, if it is read-only or not, the compiler ID, processor, the number of bytes, the number of instructions, etc. And we can double click on this to open it in the code browser, right? So this is what we have here, where we actually get the import results summary. And then if you double click on it inside of this piece right here, I believe, when we double click on this, it'll actually go inside of the code browser that we have. And when asked to analyze the executable, you want to click on yes. So that's a big piece. The next window that will appear shows us various analysis options. We can check or uncheck them based on the needs. And these are the various options that we have. And I'm not going to read through all of them. You can pause the video if you want to zoom in on it and just read through what they are. But depending on what your use case is and the information that you're trying to find and your skill level, I would say, you would use a variety of these different analysis options. It will take some time to analyze. The bar in the bottom will show the progress. Wait until it hits 100%. Okay. There are many options that we can aid in the analysis. The default layout is as such. So they're going to give us descriptions for this. And so we're going to start like this, right? So we have 1, 2, 3 on the left side pane. And then we have 4, which is the central portion, 5, the right portion right here, and then 6, which is just a toolbar at the very top. So program tree shows the sections of the program. We can click on different sections to see the content within each section. Dissecting PE Headers room, which was one of the videos 2-3 videos ago. It explained the headers and the PE sections in depth, and we used PE tree for the most part to do that. Symbol tree contains important sections like imports, exports, and functions. Each of these provide a wealth of information. The imports contains information about the libraries being imported by the program. Clicking on each one of them shows the assembly code that uses that API. Export contains API or functions that are being exported by the program, and this is useful when we're trying to analyze a dynamic link library because it'll show all the functions that the DLL contains, and then there are the functions themselves that you can find inside the code that will show us the disassembled code of that function and it contains the entry function. Clicking on entry will take us to the start of the program that we're analyzing, essentially where the activity starts, right? So that's the entry of the functions themselves or the program itself. And the stuff with generic names like fun, virtual address are the ones that Ghidra does not give any names to because I guess they're generic. Then you have the data type manager, which is still on the left side. This shows us the various data types found in the program. Then we have the central portion, this large portion in the middle right here. And these are the listings. So this shows the disassembled code of the binary, which includes the virtual address, opcode, assembly instruction like push, pop, add, XOR, etc., operands, and comments. Then we have the decompiled, which was on the right side. That translates the assembly code into a pseudo C code. It's very important to look at during analysis because it gives us an understanding of the assembly code, the toolbar at the very, very top, and that one's fairly self-explanatory. The graph view in the toolbar is an important option because it allows us to see the graph view of the disassembly. And so I guess this is the graph view, kind of. I don't really associate this visual with a graph. I feel like a graph view would be, like a graph. This doesn't really seem like a graph to me. Oh, maybe it's these arrows that they're talking about. Maybe that's what they're referring to. Okay, I guess that's a graph view. Whatever. Memory map option shows the memory mapping of the program. And so if we click on memory map right here, it gives us the memory map and the headers. And these are also things that we, inside of Dissecting PE Headers, we talked about these various types of headers as well. And the various elements, read, write, execute, whether or not it's volatile data, meaning if it's inside the RAM, etc. And the navigation tool shows us different options to navigate through the actual code itself, which I guess is what I think they're talking about, this specific element right here maybe. We can explore strings, so search for strings and click search will give us the strings that Ghidra finds within the program. It can contain very juicy information because strings are actually very useful, as we went through when we were doing the basic static analysis video. And these are a bunch of different strings. So you have the location of them, the label of the string, the actual code unit that they belong to, the string view itself, and I guess the contents inside of the string. So this is technically the contents inside of the string. And analyzing our actual executable, so this is what we're going to be looking at in this particular case. I would say that doing it in in Ghidra, analyzing this specific executable is what we're looking at right here, because there is a separate executable inside of our code constructs that's also called hello world, but it's hello_world. It's not the same as this, I don't think. So I'm just going to say that there are two different executables. To define the assembly code for this, we'll double click on the .text in the program tree section. It will take us to the disassembled code section, and we're going to scroll through it until you see the call for the message box that will display hello world string in the decompile section, and we can see the translated pseudo C code of the function. So the disassembled section shows us how the arguments are being pushed, followed by the message box A, responsible for the message box display, which is what we would see most likely right here. So let me see if I can kind of zoom in a little bit. So we have text. If we click on text, it'll take us to the text section. In this particular case, we have the push functions in the center right here. And then there's a message box A that's highlighted in yellow right here that has the message hello world. And that's kind of the function of the executable, I guess, right? So we can explore the features by examining the simple hello world. In the next task, we're going to do different C constructs. It's trivial to note that the malware's author may have packed or used obfuscation or anti-VM, anti-AV detection techniques, anti-virtual machine, anti-antivirus to make the analysis harder. These techniques will be discussed in future videos. So how many function calls are present in the exports section? So let's see, this is for, what is it? For the hello world executable, I believe. So this is what they're talking about. And so if we want to look at that, I guess what would happen is that, I don't know if it's going to be inside of the screenshots that we have over here. I feel like it's not. So let's see if it is in this case in the exports section. What is that? Export section is inside of the symbol tree, which is this piece right here. And it doesn't show us the answer. So we actually do have to analyze our code here. So let's go ahead and create a new project. And from here, we're just going to be a non-shared project. We're going to click next, and I'll just name it Hello World. My keyboard went to sleep again, so Hello World. There we go. That's going to be the project. And then I'll even do project just so I don't confuse it. And then we're going to finish it, and then there we go. So now we have the Hello World project, and now we're going to go here, and then we're going to import a file inside of our project, and that will be the one on the desktop, which is the Hello World executable, and we're going to import the executable. I could have also dragged and dropped it. And then now we have this various stuff as well that was previously available, and I'm not going to change any of this. I'm just going to click OK on this, and it will now start to import it. And now we're going to wait until this hits 100%, which it did fairly quickly. This is our summary, which is great. The number of functions is actually right on the summary. So it says 16. I wonder what the question was. I think it asks for the number of functions, right? So how many function calls are present in the export section? Okay, that's definitely not the answer that we're looking for. So we want the function calls in the export section. So I will go ahead and double click on this, and it will now load and do all the analysis and everything. And hopefully it will not take too long. It did not take too long. Great. How would you like to analyze it? I do want to analyze it. I'm just going to keep all of the basic default options. And then I want to say, oh, you can't really see it because it's like right below here. But there is a progress bar at the bottom that we're waiting to hit 100%. So maybe I can kind of drag this down a little bit and minimize it, or maybe if we expanded it, let's see if I expanded it fully. Yeah, okay, you can see the progress bar at the bottom right here. So it's analyzing the thing, and it goes to 100% multiple times. So I'm guessing it's doing multiple sections at 100%. So we're just going to wait for that to be fully done and stop running because it's still running. And when that happens, we will then go ahead and see how many functions are inside of the exports section. Okay, cool. So that took, I want to say like maybe 2 minutes. It wasn't really that bad. Now we can click on the exports file right here, or the exports location, and maybe even expand it. And we have entry, and then expand that, and maybe not. There we go. Okay, there we go. So we have the entry point for the exports. I want to say that's what it is, right? That's what we're asking for. It says how many function calls are present in the export section. Is it 1? Okay, I guess it is 1. The function call is entry. That's basically it. There's literally 1 item inside of this exports folder. So, okay, that makes, all right. For a second, I was like, that can't be just 1, but it is just 1. What is the only API call found in the user32 DLL under the imports section? So we are going to click on imports, and we're going to just expand it. And then under user32, there is 1, and it's message box A. That's the only one here. So we'll do message box A. How many times can the hello world string be found in the search for strings utility? So we're going to go up here, click on search, and we're going to search for strings. And what we're going to do is we're going to search for what is the full string? Where is it? Where do I actually type this in? I guess, is it here? No, it can't be. That's the word model. Require minimum lex and all. Okay. What am I searching for, buddy? Oh, maybe that's what it is. So inside of all of these things, now we can try to find hello world inside all of these things, maybe. So let's I'll do a select all here. And then let me see if I can do Control F inside of this environment. It doesn't seem to allow me to do it, but if I click on this little search icon at the top, maybe that's what it is. So show undefined strings. Let me see. Okay, the search function is actually at the bottom right here. So this is the filter where we actually look at it. So first we look for all the strings, we pull all the strings, and then from there we will find whatever we want by doing hello world. It does only show me 1. So I'm going to go ahead and do the search for these strings one more time because there is this minimum length and alignment and all those things. I just wanted to make sure. So I thought this was maximum length and it was at 5 characters, but it's not. So it's the minimum length, which is perfect. So we can even make this a little bit longer, right? So hello world is technically what? HELLO and then space and then WORLD. That would be 11 technically. So if I do 10 as the minimum characters, it should give me a smaller list. And then from here, we can just go ahead and pull up hello world. And it only shows up one time. The length is 12. Oh, it's not. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It is 11. What the hell? Why is it saying 12? Okay, whatever. So one time. It shows one time. Excellent. There we go. What is the virtual address of the call function that displays hello world in a message box? So the virtual address of the call function that displays hello world in a message box. So if we click on the message box right here, it should take me to it. So I think it's this piece and it's this message box right here. And we're looking at the address for the call function. Okay, so inside, when we actually go over here, click on the message box, it brings it to the center of the screen here. And then we have the message box, and this is a call function. So this is what we see right here, the standard call for the message box. And then there are the resemblances of what addresses are. So these things right here that you see right here, these are technically addresses, right? So I tried this one, that was not the answer. And then I tried this chunk, and that was not the answer. And then I tried this chunk. And if you remember, Ghidra, if it can't identify something or if it's generic, it'll give it the fun title at the front of it. And so I tried that one, and that was the answer. So it's the 004073D7. That's the answer for the address of the call function that displays hello world in a message box. So we have officially completed that section. So now let's move into identifying C code constructs in assembly. So as the beginning of this video, I did mention that analyzing assembly code can actually be overwhelming if you've never done it before or if you don't have a background in coding, but it is something that is very important. So what we're going to do in this particular section is to examine the various C constructs and their corresponding assembly code, and it'll help you identify and focus on the key parts of malware during analysis. So you don't have to analyze everything, you just need to find these specific sections, right? So you can load the program present in code constructs as shown below. So what do we have? We have the overall hello world that we see right here. And let me just make sure that it is the same thing, but it says you can load the programs present in code constructs folder in Ghidra as shown below. So they have the project hello world, and then they've loaded all of them into Ghidra. There are different approaches to begin analyzing the disassembled code. So we can look at the main function of the symbol tree section. We can click on the text from the program tree section, and then we can look for interesting strings and locate the code from where those are referenced. Different compilers add their own code for various checks while compiling. Therefore, expect garbage assembly code that does not make sense. So for hello world, this is the very first program that we try out in any programming language, and it's basically to echo hello world or to print hello world onto the screen. This was the very first thing that I did when I was learning Python. It was the very first thing that I did when I was learning shell scripting. It's like the very, very basic, the very first program that anybody ever creates, okay? So this is the example in C code, and it will print hello world on the console. So main, right, print hello world, that's it. And there are two hello world programs. One of them was the desktop that has the hello world message. The other one in code constructs shows the hello world in the terminal, right? So in the assembly, message is hello world, and you can see the code right here. Write the message to std out, which is typically the reference for the terminal display. And this defines the string hello world in the data section and then uses the write system call to print the strings to std out. In Ghidra, if we actually open up the hello world executable found in code constructs, and you know what, while I'm recording this, I'm actually going to, we'll start a new project, right? And then from there, we will go ahead and import all of the other things because, we're going to close all, I guess. So we'll close everything. We don't need to save any of this stuff. And then I'm going to open up a new project, or I'm going to start a new project. And that way, yeah, I feel like I need to just close this out because I don't know how to start a new. Oh, there it is. So this is where we're at. So once you close that out, it actually does that for us. And so we will do a non-shared project in this particular case, and it's going to be the code constructs. I'll name it as code constructs project. That will be our new project. And from here, we will batch import, essentially, the contents of that full folder. So if I do batch import, or I should be able to import like the entire thing, I want to say. So if we do inside of our desktop, we should be able to go and click on code constructs and select all of those files. And it's going to say batch import. Yes, excellent, great. So we're going to import all of that. There we go. And it imported 5 files, perfect. And these are all of our files. And we're going to start analyzing hello world.exe. And while this is going to be analyzed, we're going to read the rest of our information. So now it's analyzing, it's running in the bottom right. Oh, that was super fast. Okay, so I guess that was it. That was not, I thought it was going to take much longer, but that was really fast. Okay, so all right. So this is the main function, examining the assembly and decompiled C code in the main function right here. We can see it right here, and this is the decompiled C code as we can see over here. And so if we look at the disassembled code in the listings view, we can see instructions to push hello world to the stack before calling the print function. There's a for loop concept. So a for loop is something that iterates for the most part, right? So for X, do this. That's basically what it is. It's like for A, do B. For condition, do action. That's essentially what it is. They also call it a conditional statement. Or actually, no, I'm sorry. An if statement is the conditional statement. A for loop is an iterative statement. So the following code shows a simple for loop, right? So it says for integer equaling 1. If the integer is less than or equal to 5, add 1 to it and then print it, essentially, is what it does. And in assembly, let's see. Yeah, so this is going to display a message 10 times, which I don't see the 10 part of it because it says less than or equal to 5. So maybe I am misunderstanding this. So that could very much be the case. But this is the simple for loop displaying the message. The for loop in assembly does the same thing. So loop 5 times as I thought it was supposed to be, but this is what it looks like in assembly. The main function initializes the loop counter ECX to 1 and the loop limit EDX to 5. The loop label is used to mark the beginning of the loop inside the loop. The loop counter is printed to the console using print from the standard library. After printing the loop counter is incremented and the loop limit is checked to see if the loop should continue. The loop continues if the counter is still less than or equal to the loop limit, which in our particular case, it should be 5. I don't know why it said 10 in this other one. That part doesn't make sense to me because it literally says less than or equal to 5. So maybe that's kind of like an issue, or maybe like a misprint or something. But same thing here. We have loop 5 times, right? So it's technically telling us that it's going to loop 5 times. And then if it exceeds the loop limit, the loop terminates. So if it goes greater than 5, it'll stop running. And the control is passed to the end of the program where the program returns 0. For loops in Ghidra. So if we open the for loop executable program that was found in constructs, we can look at the executable. And so this was, I guess, the main section right here. So it makes a, what is it? Let's see, this program demonstrates for loop statements for local 14, etc. And it will go ahead and check it against the local 14 variable. And let's see what the explanation for us says. It says we can see how the for loop is translated into disassembled code. So I guess, yeah, so this is what it is, and it's translated into disassembled code that tells us that the main function does all of those things. Or maybe this is the disassembled code, because when I look at this, yeah, in assembly, this might be, yeah, this is the for loop displaying a message 10 times. So maybe, yeah, this is the disassembled code. So I want to say this is the disassembled code, I think. I'm still not 100% sure on this stuff. So I apologize if I am misinforming you. I do apologize sincerely. A function is a key component of any program language. It's a self-contained block of code that performs it. So this is one version of it. In assembly, this is what it looks like. And the add function starts by saving the current base pointer value to the stack. Then it sets the base pointer to the current stack pointer value. The function then moves the values A and B into the EAX register, adds them, and stores the result in the result variable. So let's see if we can actually look at all of these things and see if we have it. So this is the disassembled version of it. This is the actual function itself. This is like the block of code in C. So you can see integer A, integer B. The result is A plus B, and it's stored inside of the result variable. And then the result variable, the data that's stored inside of it, is returned into our program so that we can use it for future references. So it's very different than this is obviously much simpler than what we can see right here, right? So this is the add function, and it's going to do all of these things inside of 4 lines of code technically. So what else do we have here? The function moves the value of the result into the EAX register, restores the previous base pointer value, and returns to the calling function. A while loop typically says, while this condition is true, I want you to do this. When the condition becomes false, then I want you to stop doing it. So in this case, the integer is 0. If the integer is less than 10, then you're going to print this, and then you're going to add 1 to the integer. And then so it starts at 0, then it's going to be 1, then it's going to be 2, then 3, then 4. And then when it gets to 9, it'll still be true. As soon as it hits 10, it's going to become false, because it's not saying less than or equal to, it's just saying less than 10. So as soon as it hits 10, it will become false. The response here will then be, this is false. This condition is now false, because as long as it's less than 10, the condition is true. So while this condition is true, you're going to do this. As soon as the condition becomes false, you're going to stop doing this. That's basically what a while loop does. And this is what it looks like in assembly. So the move instruction initializes the register ECX to 0. And so we can see it. I think it kind of just gives us everything line by line here, right? So the move instruction initializes the register ECX to 0, representing the variable I. The loop start label marks the beginning of the loop, and we can see it right here. The CMP instruction compares the value of ECX to 10. If ECX exceeds or equals to 10, the loop ends and the program jumps to the loop end label. Otherwise, the value of ECX is pushed onto the stack along with the format string and the value of ECX itself to be printed using printf. The add instruction cleans up the stack after the printf call. Finally, the value of ECX is incremented and the program jumps back to the loop start label to repeat the loop. So all of this says this right here. It's actually very interesting that the disassembled version or the assembly version of the code is so much more complex looking. But I think it's because it's literally saying it's going to compare the integer to 10, and then if it doesn't, or if it exceeds it, it's going to stop it, or if it's still less than 10, it's going to run it again, etc. So it is interesting the way that assembly code actually looks like and the way that it works. It kind of explains this structure for us, right? And if you still don't know exactly how to understand this information, like if you don't know what push means and if you don't know what call means, and push means that it's saving the value of it to the stack, right? It's pushing it to the stack, pushing the format string for the 4, pushing the word, the value for I into the print, and then we're going to call printf to print a value. So we're now calling on this function to do something for us. Now we're adding something, we're incrementing something, and then we're going to jump back to the start of the loop unless this is now either 10 or greater than 10. If it's greater than or equal to 10, it's going to jump to loop end, meaning the loop is going to stop. So this is really the full explanation of the actual 4 or 5 lines of code. It's just that you got to know these very basic pieces right here. The syntax right here, if you just understand what push and call and you can understand what add means. You can hopefully you can understand what increment means. So at the very least, this piece it tells you what the step is that it's trying to do in that specific element. So I like that. That's pretty cool. A while loop in Ghidra. So if we're going to open up the while loop program in Ghidra, go to the functions, and in the symbol tree, locate all the main function. And then we can see that right here. So this is the assembly. Now I fully understand that this is actually the assembly. This is the code itself. And then it's just going to run it, right? In this program, a text is printed 5 times until the value of the counter variable reaches 5. We can observe the assembly instructions on how the counter variable is set, how the loop works, and how the program uses the jump instructions to satisfy the conditions. It's important to note that different compilers would compile the programs differently, adding compiler-related code. To demonstrate, the programs used in this room, in this video, are compiled using different compilers. Therefore, you may find difference in the interpretation of assembly code. We're going to examine the if-else executable and the while loop executable and answer the questions below. So what value gets printed by the while loop in the while loop executable program? So I actually opened up hello world, so I'm just going to close this thing out. I don't want to save it. I will open up the while loop executable, and hopefully this one also will load as quickly as the other one did. It'll be analyzed as quickly as the other one. So let's see how long that one takes. And then the question specifically is asking what value gets printed by the while loop in the program. So we want to see what the value that is going to be printed for us is going to be. So we're going to go through, let's say we're going to go through data, and then let's see if we can file that, or maybe inside of the functions maybe. Let me see what I can find here. Okay, the main function, this was the hardest part for this, was to try to find the actual location of the main function because things are abbreviated here. So if we actually go inside of the functions and then expand the first one right here, which is represented by the underscore. Once we expand that, we have a bunch of other things inside of it. And then if we go down here, there is one that is underscore M. And then inside of underscore M, there's the main function. And then when you click on that, it is automatically highlighted. And then on the right side, we actually see the code itself. And then so it says this program demonstrates the while loop for etc. etc. It's going to print. It's fun to learn at THM. And so we're just going to highlight that portion. And let me see if I can copy that. Okay, great. And we're going to go over here and we're going to print it. And I believe that's going to be the answer here. Very good. All right. So how many times the while loop will run until the condition is met? Okay. So let's see. How many times will the while loop run until the condition is met? So technically, I think it's going to be 4 times because it says less than 5. So if local 14 is equals to local 14 plus 1, so local 14 starts at 1, so that will be the first iteration. Then it'll go to 2, then it'll go to 3, then it'll go to 4, and then it'll stop at 5. So it should run 4 times. That would probably be the answer. Let's see. Yeah, that is the answer. Excellent. Examine the while loop executable in Ghidra. What is the virtual address of the instruction that calls to print the sentence? That's the end of the while loop. So this is it right here. And so we're looking for this piece right there. And what I'm looking for here is the virtual address of this. So what we're going to find right here, this is it. This is the one that says that's the end of the while loop. And the virtual address, I believe, is this piece right here. So let's see if that's actually the right answer. Hopefully it is. Okay, so that was not the answer. And so if we actually right click on this, or not right click, if we actually kind of hover over it, it says on the screen, I can't move the mouse because it'll take it away. But if you look at the bottom right here, it says address. And then it says 00404040. So I'm going to say that that's the address. So we'll do 00404040. And that is also not correct. That is so funny. Why is that not the address? It literally says address. Okay, so here is the answer. And so that makes sense. The way that we find the answer is we're looking for this thing right here. So technically this variable right here is what is being called to print. That's the end of the while loop. So we're looking for underscore puts. And then if we go to find the call to underscore puts, which is this piece right here, this ends up being the address of it. So it's this point, this piece right here. That actually is the address that we're looking for to pull that off. And there you go. That's the answer. So the understanding the syntax, understanding what we're actually looking for is more like 80% of the battle in this particular case. And I did not understand what I was looking for. I was just looking for this phrase, and then when you try to find the phrase, it's right here, and then it literally says it. It's kind of hard to see right here, but it says that's the end of the. So I'm looking at this whole thing. I'm like, oh, that has to be the answer. So I tried that. It didn't work. I tried this address right here. That didn't work. I tried this address. That didn't work. And I was like, okay, well, what the hell am I missing? And then now you can see that there's a call to the puts variable, which is what we actually see right here. So that was the answer for that. Now, in the if-else program, examine the strings and complete the sentence. This program demonstrates, etc. So we're done with the while loop. We're going to move on, and we're going to open up the if-else program here. And let's analyze it, and let's see how long this one will take. Okay, that was actually super quick. It was like literally like 2 seconds, not even. Okay, so we're going to search for strings in this whole thing, and the string itself right here is that this program demonstrates. So here's what I'm going to do just to make my life a little bit easier. I'm going to do a character counter, and then I just want to see how many characters that is. So that is technically 25 characters. So I can at the very least say that the minimum that I'm looking for is 25 characters, and I only want strings of that length. So it should be, and it's literally at the very, very top. This program demonstrates if-else statement. So I guess we'll just put the full thing. This program demonstrates if-else statement. There we go. Excellent. So what is the virtual address of the call to the main function in the if-else executable program? So there we go. So now we know what that means, right? So we first need to go ahead and find the function for the main function. And based on what I saw previously, I wonder if it's the same thing. So under underscore, we're going to go down here. We're going to go to M for the main, and we're actually going to click on the main. And here we go. So this is the main function. And on the right-hand side, we actually also see the integer, etc., etc. So if I click on this, or maybe click on that right there, it should take me to it. And now we can see call on the main function, and we have this number right here. So I really think that this is the answer, and I hope that that is indeed the answer, because I would love to get it right on the first try, and it is the answer. Great. So I learned something today. Or I mean, I'm learning a lot today, but that was cool. Okay, so now we understand what it means when we're calling on something and we're looking at assembly code and what that actually means and how to find those addresses. Super excited. I feel like I'm growing. This is great. All right, let's go to the overview of Windows API calls. The Windows API, if you've never heard of it before, the API stands for the the Application Programming Interface. This applies to very many things, and the concept of an API call is something that you will hear about a lot, and the integration between different applications, right? So when you connect one application to another, for example, Coinbase can pull money from a bunch of different banks so you can fund your Coinbase wallet, your Coinbase account. And to be able to do that, the Coinbase application integrates or connects with the APIs of all of the other banks. So that is one of the biggest uses that is available for API. Now, what happens is that you make a call on the functions within that API. So for example, the Windows API has a bunch of functions that you can call upon, and then each one of those functions does something different, right? So in this particular case, it's the collection of functions that services the Windows operating system, and it provides to enable the developers. This is a very interesting syntax, like the way that this room has been written out. It's a very interesting syntax. And I'm an immigrant, and I have no problem with people who are immigrants that write things out, but this very much feels like it was written by somebody who English is not their first language. And I love that, and I think it's amazing. It's very inspiring because it goes to show that English does not need to be your main language for you to create a freaking room in TryHackMe. You know what I mean? It's pretty amazing. Let's see if we can see who the user is that created this room, because Dex01, this guy right here. So let's see what we can get for Dex01. This guy, I'm sure, oh, it's on the staff, passionate about teaching and learning new things. We love Dex. There we go. Pakistan. See, there we go. My guy. So his streak is at 0 because I guess he hasn't done a lot of things in TryHackMe. I have a higher streak than him, which is 2 right now. David, one of our members inside of Hackaholics Anonymous, has a streak of like 500 or some crazy thing like that. So I'm digressing, obviously. I've also completed more rooms than Dex, so I can confidently say that I feel like I'm a little bit better. Not at all, because Dex literally created the room that we are in, and Dex is teaching us all these things. So just because he hasn't completed many rooms does not mean that Dex does not know what he's talking about. Clearly, he knows what he's talking about. So shout out to Dex. I should probably start doing that, like giving a shout out to the people who created these rooms. I think that would be like a cool little new addition to these things. So I'm going to start doing that. If you're listening to this right now, you're witnessing history. I've decided that I'm going to start giving a shout out to the people who created these rooms for us. So these functions inside of the Windows API includes creating windows, creating menus, creating buttons, and other user interface elements, and performing tasks like file input output and network communication. So we have an example right here, the create process API, which is a really common one that is used all the time by Windows machines, whether or not you know it, right? When you open something, when you open an application, it creates a process. So it creates a new process and its primary thread, right? The function takes several parameters, including the name of the executable, command line arguments, and security attributes. The syntax in C++ looks like this, okay? Just to keep that in mind, you don't necessarily need to know what this is, but this is the create process API call. So this is the C code that uses the create process function to launch a new process. We have this right here, so you can see it right here. Again, I'm not going to go read through this line by line. When compiled, the create process looks like this. So not that complex compared to everything else that we've seen, compared to the loops that we saw where there was like 5 lines of code and it was like a really long assembly description. In this particular case, not that much. So the assembly code pushes the necessary parameters onto the stack in reverse order and then calls the API, the create process function. The create process function then launches a new process and returns a handle to the process and its primary thread. During malware analysis, identifying the API call and examining the code can help understand the malware's purpose. So, when a process is created in suspended state, which hexadecimal value is assigned to DW creation flags parameter? This is interesting. So now I actually have to find some information about that because I don't even know what that is. I have to actually find the answer for that. I don't think it's inside of any of these things right here. So looking at it in a suspended state is what they're telling us. And we were trying to see, okay, so what is the question? And it says, right, read the Microsoft documentation, obviously. So instead of doing that, I'm just going to Google this thing right here because it's basically the same thing as reading through the documentation. So process creation flags, here we go. And we're looking for the suspended state, created in a suspended state. I think it was actually in the basic description right there. So the process, so let me find the answer real quick. Okay, so on the Microsoft documentation, I literally did a Control F or Command F, and I went and found create suspended, and this is it. These are the only 2 references of the word suspended, and then this is what we have for the hexadecimal value. So that is the answer for us over here. Now we're going to explore Introduction to Windows API Room to learn more about Windows API calls, and I want to say I've done this. I'm not sure if I have, but I feel like I have. I have not done it. Okay, great. So this is what we're going to do. We're going to go ahead and pull up the Microsoft documentation page one more time, and we're going to leave this open because I feel like, or maybe not even that, like we should be actually pulling up Windows API calls. So let me just pull up the Windows API calls, and then from there we'll just have that available for us. Programming reference for Windows 32, and then yeah, Win32. So hopefully this will actually be useful for us as we go through the rest of the content here. Now that we understand what these common APIs or what the APIs in general are, we we need to look at the common APIs that are used by malware specifically. And it's an important step in advanced analysis, in advanced static analysis, to examine all of the import functions, which can reveal everything about the malware or a lot about the malware. And it's basically everything that is going to be inside of the import portions right here that we see right here, right? So if I expand on this, we can see that there's the kernel 32 DLL, and then we have the MSV CRT DLL, and inside of them, there's a bunch of different functions that are being pulled in. And same thing for the kernel, and then we can see delete critical section, get current process. These things are they seem like the commandlets, right? So if I go ahead and, for example, open up PowerShell inside of this Windows machine here, and we can literally just do get processes or get process, I think. So let's open up Windows PowerShell just so you can see that these things actually translate into a command, right? So if I do get process, there you go. It just lists all the processes inside of this specific virtual machine that is currently running right now. So that's a commandlet, right? So get process is a commandlet. And in this particular case, it just says get current process. So it's not hyphenated. And usually commandlets inside of PowerShell are typically hyphenated, as you can see right here. If I do get current process, I don't know if that'll actually work for me. It doesn't. So what it gives me right here is that there is no object that has been found. In this particular case, it's not recognized as the name of a commandlet. Script or file, check the spelling of the name. If I do get hyphenated and I do get current process, that also does not work. So maybe that is not an official commandlet, but I do know that get processes is one. And essentially anything that I see like this, I just immediately associate this with some kind of a commandlet. So if there's a get current process API call, we can try to see what the commandlet equivalent of that is, right? So what is the commandlet for the get current process API? Let's see if that gives us anything. And it just says get process. So I guess that is it. That is the one that I found specifically, and I guess I knew one. I knew one off the top of my head, right? So you can do the same thing that I just did if you want to find out what the actual commandlet is for any individual API calls, and you'll advance your knowledge that way. So this is one of the ways that I learn things, is that like as things happen and as I'm exposed to information, I'm like, okay, well, let me see what this means and let me see what that means. And then I just kind of do research individually for each one of these different elements, and I learn as I go. So there are a few different ways that you can learn. That's my preferred method of learning. I just learn as I go. Okay, so moving on, the key logger. There are several API calls for key logging. We can use the set Windows hook X, which installs an application-defined hook procedure into a hook chain. And malware can use this to monitor and intercept system events like keystrokes or mouse clicks. So set Windows hook X is one of them. Get async key state, and it retrieves the status of a virtual key when a function is called. It can use this function to determine if a key is being pressed or released. Get keyboard state retrieves the status of all virtual keys, and this can be used to determine the status of all keys on the keyboard. And get key name text retrieves the name of a key, and malware can use this to determine the name of the pressed key. So these are various API calls that can be used to create a keylogger, right? So malware can intercept and record keystrokes using any of these things, and it allows the malware to capture sensitive information like passwords and credit card numbers and credentials and just the activity of somebody doing something inside of the given computer. Then we have the downloader. The downloader malware is a type of malware designed to download other malware onto a victim system, and it can be disguised as legitimate software or files that are spread through malicious email attachments, software downloads, or exploiting vulnerabilities in software. Downloaders can use various Windows APIs to perform their malicious actions. Some of them are these. So URL download to file. It downloads a file from the internet and saves it to a local file. and it can be used to download additional malicious code or update to the current malware. When HTTP open initializes the when HTTP API, which can be used to establish an HTTP connection to a remote server and download additional malicious code. When HTTP connect establishes a connection to the when HTTP, or excuse me, it connects to a remote server using the when HTTP API. And it can be used to connect to a remote server and download additional malicious code. And then when HTTP open request, which can essentially do all of the same things. There is the invoke web request, which is, I think, invoke web request, which is a lot of times abbreviated to IWR as well. That's another thing that I've seen in previous exercises that makes a web request, an internet request, so to speak, and then that can be used to download data. Then we have the C2 communication, so something known as the command and control server, which is a remote server, and a C2 communication is a method that's used to communicate with the remote server or the attacker or a proxy server, essentially anything that is not in the local network. And now there's a connection that's been established from the local computer to this remote server, and data is going back and forth. Commands are going back and forth via this connection. This can be used to receive commands from the attacker, send stolen data to the attacker, or download additional malware onto the victim system. Internet open is something that initiates a session for connecting to the internet, and it can be used to connect to a remote server and communicate with a C2 server. Internet open URL opens a URL for download, and it can be used to download additional malicious code or steal data from a C2 server. HTTP open request can be used to send HTTP requests to a C2 server and receive commands or additional malicious code. And then, of course, send request that can be used to send data or receive commands from a C2 server. Data exfiltration. So as the name implies, you're just exfiltrating data. You're extracting data, moving data out of the current network into a different location. It could be somebody else's C2 server. It could be a cloud storage location. It just depends how they want to exfiltrate their data. Internet read file reads data from a handle to an open internet resource. And malware can use this to steal data from a compromised system and transmit to a C2 server. FTP for the file transfer protocol. FTP put file is something that uploads a file to an FTP server, and it can use this function to exfiltrate stolen data. Create file creates or opens a file or a device, and it can be used to read or modify files containing sensitive information or system configuration data. Write file writes data to a file or a device. It can be used to write stolen data or to a file and then exfiltrate it to a remote server. And then get clipboard data, which is to pull data from the clipboard. So when you copy and paste something, usually when you copy something, it's copied to your clipboard. And then when you paste it, it pastes from the clipboard. And this can be used to retrieve sensitive data that's copied to the clipboard. A dropper is a malware that's designed to install other malware into a victim system. So it drops other malware, right? It can be disguised as legitimate software or files, and it can spread through the malicious email attachments, software downloads, or exploiting vulnerabilities. Create process is a function that creates a new process. The thing with this is that it can generate so many false positives because all of the legitimate processes on the computer also have a create process commandlet that's running in the background, and it was called at some point to open up all of those legitimate processes. So it is something to keep an eye out for, but this specific search, if you're looking for this, you will most likely find a lot of noise and a lot of data because all of the legitimate processes and applications that have been running also called on the create process API. Malware can also use this function to execute the code in the context of a legitimate process, making it more difficult to detect and analyze, which is why it's so attractive to hackers. Virtual allocation reserves or commits a region of memory, also known as the random access memory, within the virtual address space of the calling process. It can be used to allocate memory to store the code of the malware. Write process memory writes data to an area of memory within the address space of a specified process, and it can be used to write its code to the allocated memory. API hooking is a method that the malware uses to intercept calls to Windows APIs and modify the behavior. So think of it as a man-in-the-middle type of an attack. It allows the malware to avoid detection by security software and perform malicious actions such as stealing data or modifying system settings. And it can be done through get process address, which retrieves the address of an exported function or variable from a specific or specified DLL dynamic link library. And it can be used to locate and hook API calls made by other processes. Load library loads a DLL into a process's address space. Malware can use this to load and execute additional code from a DLL. Set Windows hook X is the, I think that stands for executable, I want to say. And it's used to install a hook procedure that monitors messages sent to a window or system event, and it can be used to intercept calls to other Windows APIs and modify their behavior. Anti-debugging and VM detection. These are some of the key things that we saw in previous rooms and videos as we were investigating these various malwares. Anti-debugging, anti-VM was the one that I saw specifically. And so these are techniques used by malware to evade detection and analysis by security researchers. So we have is debugger present, right? It's checking whether a process is running under a debugger. Malware can use this to determine whether it's being analyzed and take appropriate action to evade detection. Check remote debugger present. Checks whether a remote debugger is debugging a process. Malware can use this function to determine whether it is being analyzed and take appropriate action. NT query information process retrieves information about a specified process, and it can be used whether or not it's being debugged and take appropriate action. Get tick count retrieves the number of milliseconds that have elapsed since the system was started, and it can be used to determine whether it's running in a virtualized environment, which may indicate that it is being analyzed. Get module handle retrieves a handle to a specified module, and it can be used to determine whether it's running under a virtualized environment. Get system metrics retrieves information, system metrics, right? Data and configuration settings, and it can be used to determine whether it's running in a virtualized environment. So details on this are discussed in the anti-reverse engineering room, which is something that I know I have not done. And there's so much stuff inside of TryHackMe that it's just really, really powerful information. And I haven't even scratched the surface, I feel like. There are so many more things that I can do. And they're constantly coming out with more rooms. So that's just really, really cool. So we have a resource here where it says read more on malapi.io to learn about APIs used in different malware families. So this is a malicious API database. Look at that. Wow. This is amazing. This is one of those things that is very, very useful to have access to. Man, I feel like I should be storing all of these things. And you know what? I am going to store this one. This is actually a really useful one. malapi.io. That's very useful. I'm going to keep that one. All right, great. Moving on to the next piece. Now we can add on to the information that we've collected so far to learn about a concept known as process hollowing, which is a part of detection evasion, and it's a process injection technique. So process hollowing is a technique that malware uses to inject malicious code into a legitimate process that's running on the victim computer. The malware creates a suspended process and replaces its memory space with its own code. Then it resumes the process, causing it to execute the injected code. So we actually looked at something, not in this one. I think it was in the previous, in this particular place, where I think we were looking at suspended, right? That was like one of the things that I was looking at for the API calls. Yeah, it is. So creating suspended processes, this is one of those things that is referencing right here. So process hollowing will use the create suspended API call, right? So the technique allows the malware to bypass security measures that may be in place as the malicious code is executed within the context of a legitimate process. Process hollowing is achieved through these steps. So we have creating a new process using create process. This process will act as a legitimate process and it will be hollowed out. So think about the shell of a process being created and then it's suspended, right? So a legitimate process is created. The process is then suspended and then it's hollowed out. And then it will be rewritten, like the content of that process will be rewritten so that it can do what the attacker wants. So first the process is created and it looks legit. Then the process is suspended, and then there's allocated memory to it. So we do virtual allocation. This will be used to hold the malicious code. Then we write the malicious code to the allocated memory using write process. Then we modify the entry point to the set thread index and get thread index APIs. So to the point to the address of the malicious code, right? So we have allocated memory, virtual memory that's been reserved so we can write the code to it. And then inside of that virtual memory, we do whatever we need to. And then we modify the entry point of the legitimate process, right? So we modify the entry point of the legitimate process to the address of the malicious code inside of that virtual memory. And then we resume the process, the suspended process, the suspended legitimate process. We resume it, and it will cause the process to execute all the malicious code. So it's kind of cool when you really think about it. So you have the malware process, right? So this is the actual target process, the legitimate process. We hollow it out, we transfer the malware code into it, and then we resume it, and then it'll just work. It'll work as if it was its normal thing, but it's obviously running the malicious code. So this is a sample C++ code that kind of demonstrates this. So we're going to use namespace std, and then we have the hollow process function that's been created, and essentially it's going to create tools help 32. What is it? This is one API call that's being made, and it's going to take a snapshot as it needs it, and then we are going to start running the individual processes, right? So it's going to open a process, it seems, and then it's going to let's see, read the process memory. It's going to allocate virtual space to it, and then it's going to write to the process memory, then read the process memory again, write to the process memory again. And if this is not available, so if when we put exclamation, typically exclamation means not. So if this is not available, or if it's not functioning, or if it's not useful, I'm kind of trying to call on from my Python knowledge. So if it's not available, it's going to return false, and then it's going to close the handle and break the entire cycle. It's going to break the overall loop that is going on. Apart from that, it will actually go ahead and work, and it's going to, if this is not available either, so if the create process is not available, and if it can't do it, it's going to return as false. If the get thread context is not available, it's going to return as false. If set thread context is not available, it's going to return as false, and everything is going to be closed. Apart from that, if all of those things are not there, so if it's not available, meaning if it is available, then it's going to return as true, and then it's going to go into the main function where it will actually act as the hollow process. The process itself will actually start running, and it's going to tell us that yes, it was successful, and if it wasn't successful, it'll say process hollowing failed. So this main function is going to call on everything else that was created up until this point. Everything else that we've done up until this point is going to be called in that main function. And so we have the hollow process itself. That is the main function. That is all of within this is everything else that you see right here. And there's a bunch of if statements. There's a bunch of, if this is cool, do this, right? If this is cool, do that. If any of these things are not okay, just return false and then ultimately break. But if it is okay, then I want you to go ahead and run the snapshot, do everything that you're supposed to do. And then if that create process can't be run, just return false, etc. So we've already kind of reviewed this. This is actually a pretty lengthy script right here, and for the most part I'm kind of deducing based on what I know from Python, but it is resembling Python in a sense. Usually you don't use these squiggly brackets in Python. You usually use parentheses in Python. Squiggly brackets are mainly used to house data, to house dictionaries of data. So in this particular case, all of the function commands are inside of the squiggly brackets, but for the most part, it is relatively similar to what goes on inside of Python, and then we can just kind of deduce what we know that way. But for the most part, we also know that this is going to do exactly what process hollowing is, which is something that we've already discussed. So we can kind of understand that this entire script is just trying to check for the availability of virtual memory, the availability of certain processes, and if those things are available, it's going to go ahead and hollow them out and then replace them with what the original code is, or what the malicious code is that is supposed to be. So now we're going to analyze the benign.exe in the lab, and we're going to see which API is used to write malicious code to the allocated memory during process hollowing. So let me go ahead in our virtual machine here. I can close malicious API. I'll close that as well. And then we'll go into here, and then we're going to open up benign exe, which is it even in here? Oh, it's not. So I can actually drag and drop it. Let me see if I can drag and drop it into here, and we can just kind of use it as one of our executables. And so we do have that. So we'll just open that up and we will analyze it, and let's see how long this takes. That was actually very quick as well. So, all right, so this one loaded in a few seconds. So we are looking for the import function, right? So we're looking for all of this stuff that is used to allocate memory during process hollowing in this particular specific benign one. And so we know that there are several functions that can be used to allocate memory, right? So virtual alloc ex is one of them. And then when we look at the common APIs that are used by malware, we can actually look at those as well, because there was an entire section for allocation, the virtual memory allocation, or I thought there was, but I guess it's not, or get process address, maybe not. Okay, so I will just go ahead and see what I can find inside of all of the imports that might be relevant to virtual memory allocation. So we're going to go over here, we're going to click on imports, and let's see what we can find here. So in the kernel DLL, so inside of the kernel 32 DLL, towards the bottom, we can see that it has the virtual allocation EX, virtual free, write process memory. So if it's looking for, it says to the allocated, which API is used to write malicious code to the allocation. So I would say write process memory. That might be the one. So write process memory. I think that's it. And that is the answer. Yeah. So there is the specific parentheses that I was supposed to add to the end of it, which I guess I didn't add because I didn't know that I was supposed to add parentheses actually. But the answer is correct. They just added the parentheses for me. So it is write process memory that's used to write malicious code to the memory during the process hollowing. Very good. So now let's go and look at analyzing process hollowing, and then we'll wrap this thing up. All right, now we're going to do a full-on analysis of the benign executable that was on our desktop. I already have it open, so thankfully we will be able to kind of run and gun immediately. An important point to note is that almost all malware comes packed with known or custom packers, and also have employed different anti-debugging or anti-VM detection techniques to hinder the analysis. This will be covered in the next video that we're going to do. This specific sample is not packed, and so now no anti-debugging or VM detection technique is applied either. And the objective is to examine the API calls to find a pattern or suspicious call, look at the suspicious strings, find interesting or malicious functions, and examine the disassembled, decompiled code to find as much info as we can. So once we load the sample, we can go ahead and essentially go after the various functions. Now, Ghidra does not automatically land at the start of the program, and it's up to us to find out where we want to start analyzing. And it's also important to mention that starting to search for create process A is not how an analyst would start analyzing an unknown binary. So that being said, they're going to have us do the very first thing, being create process A. But they did note that, I guess, in a real world, that's not the first thing that you would look at. So I'm kind of confused, but it is what it is. Okay, so we learned in the previous task that the suspicious process creates a victim process in suspended state. So to confirm, we can search for create process A in the tree section, then right click on the show references to display all the program sections where the function is called. So we will go, I'm just gonna literally do this. So I'm gonna go over here because I feel like it might be better to kind of go along with this whole thing. So there's create process A right here. I'm gonna right click on it, and then I'm going to show references to this, and it's gonna show me 2 references right here. Perfect. Okay, great. So we just do this, and then it gives us the same 2 references. Clicking on the first reference will take us to the disassembled code and show the decompiled C code in the decompiled section, as we can see right here. It clearly shows how the parameters on the stack are being pushed in reverse order before calling the function. The value 0x4 is being pushed into the stack. So we can actually see right here, it's right here. 0x4 is the value that's being pushed. And based on the IDs that we gathered, right, that's the create suspended API call that's actually being called upon. That's the create suspended function. Clicking on the display function graph in the toolbar will show the graph view of the disassembled code that we're examining. And then we can see that right here, 0x4 is right here. And it'll take us to this portion right here where it gives us the call, push, etc., all of the various elements of that. And then finally, we will have this section here. So in this case, if the program fails to create a victim process in the suspended state, it will move to block 1. The red arrow represents the failure to meet the condition. So if it fails, it'll move to this, right? If it fails, it'll move to this. If not, it'll move to block 2. It successfully creates the victim process, it'll move to that, and that's what the green arrow represents. So we then open the suspicious file. So the create file A API is used to create and open an existing file, and we can search for this in the symbol tree section and go to the code, what it's referencing to. Hollowing the process. The malware uses this thing, so ZW unmap view of section or NT unmap view of section to unmap the target process's memory. So we can search for those to see if either API is called. In this case, it's NT unmap view of section. And it takes two arguments, the base address, which is the virtual address, and the handle to the process that needs to be hollowed. Then it allocates memory using virtual allocation X. We can find instances of that, and they're passed to the function, including a handle to the process, address to be allocated, size, allocation type, and memory location. And then right down to the memory. So this will actually use the write process memory API to write to the actual memory and write whatever the code is. And so we can do the references again. That would be reference to this. And we can see that the one that's highlighted is the call dword ptr kernel there were 3 calls to write process memory. The last call references the code in the kernel 32 DLL. Therefore, we can ignore that. From the decompiled code, it seems that the program is copying different sections of the suspicious process one by one. Then we do resume thread. So once it's all sorted out, the malware will get a hold of the thread using the set thread context, and then resume the thread using resume thread to execute the code that now has been written on top of the hollowed portion. So we can see right here, set thread context, and then we can see resume thread right here. Now we can see the program sets the thread and then resumes it. So what is the MD5 hash of the benign exe sample? So, I mean, one of the easiest ways that I know to do this is to actually just use PowerShell to do this for me. So let me see. I think it's get algorithm. Let me find out exactly what it was. I just need to remind myself. So this is it. So we're looking for the desktop. That's where benign is located. Excellent. So this is the command itself. So once you're actually in the location that you need to be, it is get file hash, and then the file, or the path, excuse me, is going to be this one right here, which is going to be benign.exe. That's the file itself. And then the algorithm is going to be MD5, I want to say like that. And so there it is. So there's our get file hash of the benign executable. So we got that. So I will just copy that real quick, and then we'll go here and paste that here. Great. So how many API calls are returned if we search for the term create in the symbol section? So in the symbol tree, I actually don't know how to search in here. So I wonder if I just do search right here, and we can go for matching instructions maybe, or let me see what I can find. Okay, I feel very silly because it's literally right at the bottom. Usually it's some things at the top where we can do the search, but the filter is at the bottom of this box right here. So if we just put create at the bottom right there, we can search for it, and there are two API calls that are returned to us. What is the first virtual address where the create process A function is called? So we're going to click on this, and the first virtual address where this is called, I would assume that this is the first one that I have right here. So the first call to this address would most likely, I want to say, is going to be these addresses right here. So let me go ahead and see if I can do that. So this is the call right here. And if I highlight that, all I did was when I clicked on this, I can actually click on this, I guess, and it'll take me to the call of create process A, the very first call to create process A. So that's great. And this is the address that's assigned to it that we can find right here. So we will copy this and cross our fingers to make, hopefully that's the address, and it is great. Which process is being created in suspended state by using the create process A API call? So what is being created in suspended state? So if we're looking at this, I wonder if it is in this portion right here. So let's see if I can expand this a little bit and see what I can find. And it's actually right here. So if we just zoom in on this a little bit, we can see that create process A, it has this program files path, etc., etc., and it has I explore executable. So we can just highlight this piece right here and then copy that and bring that back over here. And that would be the process. So what is the first virtual address where create file A is called? The first virtual address where create file A is called. So this would be the bvar2 right here. So that's the piece that I would be interested in, I want to say. So the call of bvar2, I think, is what we're looking for. I stand corrected. I apologize. This is create process A. We're now looking for create file A, which is this guy right here. So if we look at create file A, we can see the first instance showing up right here. And then this is the address that I have here. So if I call that, we can see, or if I double click that over there, it'll bring us to the first call, which is this address right here. And let me see if I can highlight this guy. Okay, there we go. And so we have this. So we're going to copy that and we're going to go over there, and that would be the address. What is the suspicious process being injected into the victim process? So create file A. Let's see if we can find how this is being referenced here. This is what we got. And evil.exe. That's the injector. So THM attacker desktop injectors evil.exe. Very obvious name. It's not going to be that obvious in the real world. Let's just address that right now. Based on the function graph, what is the virtual address of the code block that will be executed if the program doesn't find the suspicious process? So I guess we're just going to do this right here, and we will go and create, what is it, function graph, I think, display memory map, function graph. There it is. That's the button. So the button, let me close this real quick just so I can show you this one. This is the create function graph. So if I click on this, there it is. And let me see if it'll bring anything for me. Location is not defined or undefined function. Okay, so that's not it. So let's see if I do right click on this, go to show references and try to find this one maybe. So that one, see if we can find that. Okay, wow, that's a lot. And let's zoom in here. And so it's saying what is the, so what's the thing? It says what happens if the program doesn't find the suspicious process. So we're looking for the address of the code block that will be executed if it doesn't find it, which I think is this. So if it doesn't find a suspicious process, it's looking for this. So I'm going to I'm going to venture a guess that this is the portion right here that first is trying to find the suspicious process, because I can't be. Let me read through this a little bit. Okay, once we get past this very first block, so this is the very first block. There's no actual name assigned to it. It just has fun, etc. And then it goes right here. If that one doesn't work, it'll push here. If it does work, it'll move on to this. And if it moves on to this, this is what we have. Can I zoom in a little bit more? I can't. So this is what we have here. So it says created victim process is what it's trying to push in this case. And so if this one fails, it moves to this. And this is what I'm assuming is the one where it's actually trying to find that malicious process, or it's trying to create or find that malicious process. And so if this fails, then it'll move to this piece right here, which will be 401.101. So 00401.101. And that is the correct answer in this case. Which API call is found in the import functions that's used to unmap the process's memory? So we have one of two options that were available to us. It was either the, where is it? The NT unmap, or it is the ZW unmap. And we're looking for either of those. So now that I know that I can actually search through the symbol tree here, I'm just going to search for unmap. And in our particular case, it is NT unmap view of section. That is the one that's been pulled. So I'll just actually copy that and go down here and paste that here. How many calls to the write process memory function are found in the code? And we're going to be looking inside of the text section. So we're going to go inside of this, inside of the text section. Let me see if I can pull that up. Okay, very good. And so we want the calls to write process memory function. Okay, so I tried a few different approaches to try to find this. First of all, I clicked on the text, and then I upload, like literally double click text, and it brings me to the overall thing. And then trying to search through this was a little bit difficult. I went through search and I searched for strings, and inside of the whole thing, I looked for write process memory. And for write process memory, only one string actually showed up. So this was not helpful, I don't think either. And then I obviously went to the symbol tree here, and then I looked for write process memory, and then I clicked on that, and then it brought it up for me here. And then we have the address here, and I double clicked that, and it took me directly to the call that I have here. But then I wasn't able to try to find other instances of it, because it just, every time it just brings me to this specific address. But what happens is that when you double click this and you go over here to the call for the process memory, we have the call to this address right here. There's this X reference to, and I want to say that means that it's referenced twice, if I'm correct. So is 2 the right answer? 2 is the right answer. I am not 100% sure that that's actually what this means right here. So I'm gonna go try to see if I can find out if what this actually means right here. So let me go see if I can find some more explanations for this for us. Okay, so I think it is the correct deduction that we have here. So typically XREF stands for cross-reference, and in disassemblers and analysis tools, cross-reference indicates a location in the code where a particular symbol, like a function or variable, is being referenced or used. To, in this particular case, usually signifies the number of distinct locations in the analyzed code for the cross-reference. So therefore, this strongly suggests that the function is called for twice within the analyzed malware. So there we go. We got that as a little bit of a confirmation for us. Now it says, what is the full path of the suspicious process shown in the strings? So now we need to just go ahead and find the full path of that suspicious process. To try and find that one, because I do remember that there was a path for the evil executable, right? So if we go ahead and reference that piece right there, so let me see if I can go ahead and find that one more time inside of our code. And then this is what we got right here. So create file, right? Inside of the create file, this is the path that we have. Now the double backslashes may not necessarily be necessary, because one of the backslashes is an escape character. So it's not always double backslash. Oh, actually, no, they do want double backslashes. I think that's it. I think that's the path. There you go. So that is the actual path of the evil executable that it was the suspicious process that was shown in our strings. And that's the last question. That was nice. I like that. So that was a bit of a learning curve for me. Anyways, I don't know about you. You're probably where you might be even way better at this stuff than I am. But, you know, we made it to the end, thankfully. And we learned the basics of performing advanced static analysis, common APIs that are used by malware, how process hollowing works. And I think the big piece, the two big takeaways that I have from this was, number one, the APIs, the common APIs that are actually used for malicious malware. And I actually stored that bookmark as well, that malapi.io. That was very, very useful. That's actually very useful database for the common APIs that are used by malware. And we can always just reference that and then try to find their associated IDs to try to look for them inside of malware. So for example, the 0x4, where there's a creating of the suspended process, and then how that actually relates to process hollowing and what that actually means, where you create a normal process, you suspend the process, you assign virtual memory for your malicious code, and then you take the address of the virtual memory and you assign it to the entry point of that normal process. And then when you restart the process, or when you resume the process, it'll now execute the malware, the malicious code. That's very, very useful. That's very, very handy information. So process hollowing was like a really big concept for me, where I was like, wow, that's actually really kind of crazy. And as well as all of the common malicious APIs, or common APIs that are used for malicious purposes. Those two were big takeaways for me from this specific exercise. And I hope that you actually got some value out of it as well. And if you were running along with the exercises that we had here, I hope you actually were able to come to those conclusions and find those answers yourself. So all in all, I hope you got value out of this room and out of this video. If you did indeed get value out of this video, and if you've gotten value out of this channel, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. We are almost done with SOC Level 2. Malware analysis, I think, is actually the last main section in SOC Level 2. So I'm very, very excited about it. I think it's something that has been a long time coming, because I've been trying to get this done. Yeah, malware analysis is the very last one. And we just did advanced static analysis. Then we have basic dynamic analysis. There's dynamic analysis debugging, and then anti-reverse engineering, and the MalDoc static analysis, which is I think it's like the final exercise that's assigned to us for our specific SOC Level 2 pathway inside of TryHackMe. So I'm really, really excited about wrapping this thing up. And then there's going to be obviously a bunch of content that is going to come out, or at least those last segments that are going to come out for SOC Level 2. And then every Friday, we have PenTest Plus, CompTIA PenTest Plus PT0003, which is the most recent version of the PenTest Plus examination certification that is released from CompTIA, and we're going through that, and that's a really, really cool pathway. So every Friday, a new video comes out from that. And then, of course, we're going to go into CYSA, CompTIA Cybersecurity Analyst. And then we're going to have, of course, the AI for cybersecurity and how to train AI to go into security for you and do all those things. So there's so many things that are going to be coming out on this channel. And I think you want to be around for that. So just make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And of course, drop a comment if you have any questions and if you just want to say hi. If you're serious about your SysAdmin education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section, and that is it for today. So boy, Hank Hacker sent it. Hank Hacks Hackers, your favorite network and system attacker / protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I will see you in the next video later. In episode 45 of the SOC Level 2 pathway, we are going to begin dynamic analysis. So far, we talked about the architecture of various operating systems. We've talked about operating with PE headers, the portable executable headers. We've talked about static analysis, and we had a basic and advanced review of static analysis. We've also done a static analysis exercise, a practical examination, so to speak, and we have officially landed at dynamic analysis. And this is the concept where you run the malware to see how it works and how it operates while it's actually running. And this is all a part of the malware analysis module inside of the SOC Level 2 pathway of TryHackMe. And it's a very cool exercise. It's a cool concept. I'm actually very excited about this because I haven't done too much dynamic analysis of malware. So I think this is going to be a good experience for me as I go through it, but hopefully it'll also be a good experience for you as well. We have obviously the introduction, sandboxing, the overall concept of what it is to be a sandbox, or to have a sandbox, not to be a sandbox. To have a sandbox, how to use a sandbox, the procmon, also known as the process monitor, API logger and API monitor, process explorer, regshot, and of course we'll have our conclusion, some final thoughts, some reviews, and then you'll be dismissed for the day. This is a subscriber only room inside of TryHackMe, meaning that you need to have a paid membership to do this. However, you can always just download procmon on your own computer and go through these types of processes. I would highly recommend, if you're going to run malware, to do it inside of a sandbox, as we'll talk about what it means to actually use a sandbox. And do not do this on your own computer. At the very least, make sure you capture a recent backup or an image of your computer to make sure that in case anything does go wrong, you can just reboot and go back to the most recent image of the computer that you have. But again, highly encouraged to not do this on your own computer. Do it inside of a virtual machine, or do it inside of a situation, an environment like TryHackMe. This is one of the reasons why TryHackMe is so powerful, because they give you these virtual machines that you can use for analyzing malware and actually running malware and seeing how it responds. And then of course there's all of the hacking exercises that you can do, where you can hack target machines and victim machines without being subject to felonies, because hacking without permission is actually a felony. So that's my spiel about why TryHackMe is awesome. This specific room has been developed by Myrol Izafar. I have no idea if that's how you pronounce it, but this is one of the staff members of TryHackMe, and they've completed 26 rooms. They've generated a number of rooms for us, including CAPE, investigation with Windows, so on and so forth. So they've done some really good stuff, and they've contributed to the community inside of TryHackMe. Or I'm sorry, these are the rooms that they have completed. The rooms that they have created is the macOS Forensics Artifacts, which is a hard level room, and it's a free room, by the way, so you don't need a paid membership for that. macOS Forensics Basics, which is also free. Advent of Cyber 2024, Linux Logs, and so many other rooms. They've actually created a bunch of different rooms for TryHackMe members, and just a big shout out to Umairul Izafar. I think that's how you pronounce that. I have no idea. This person is from Pakistan, so very great contributors coming in from Pakistan. That being said, we have now completed the overview of the basic dynamic analysis room. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into basic dynamic analysis. All right, so far we have learned techniques to analyze malware without executing it, and that is static analysis. We did basic static analysis. We also did advanced static analysis, and they were both very informative and educational. But you can actually, there are malware that can use techniques to hide their features from a malware analyst. So if you're actually doing static analysis, there are ways that the malware can literally hide itself and hide its true intentions from us and from the various tools that we use. So no matter how well it can hide its features from static analysis, the primary purpose is for it to execute or for it to run. And when it executes or when it runs, it leaves traces that a malware analyst can actually use to identify that this was a malicious piece of software. So we're going to be using basic dynamic analysis to get this done. The objectives are sandboxing and using a sandbox for malware analysis, the components of a sandbox, and how to create one for yourself, using procmon, process monitor, to monitor a process's activity, using API logger and API monitor to identify API calls made by the malware, using exp or process explorer to identify a process is modified maliciously, and of course using regshot to track registry changes made by the malware. The prerequisites are pretty much everything that we've talked about so far. So introduction to Windows API is actually not a room that I think I've done, but it is good to know about the Windows API, and you can always just refer to the Microsoft documentation from the Microsoft website to learn more about API calls and the various commands and processes that launch behind the scenes and the various libraries that Windows uses to support various applications. We have Windows internals, which we've talked about, intro to malware analysis and basic static analysis. All of these things we've talked about in the malware analysis module that we're currently in right now. We just have not done the intro to Windows API. But again, you can refer to the Microsoft documentation and literally just go to Windows API. So let's actually do that. And what you can get is a bunch of descriptions, right? So if you go to the programming reference for Windows API, you will get a bunch of different categories from which that you can go into, and then inside of this you can just find the different API calls that are done, and from there you'll be able to find what each one of these things can actually do and how they can affect the system, and ultimately how these things can be used in malicious activities. Now, there's another website that we talked about in the last video, which is the malapi.io, which is a really, really powerful website as well. And this website is one of those things that shows you the various APIs that can be used from malware or by malware. These are things that can be used by malware to essentially compromise your Windows machine, right? These can be used for exploits inside of malware. So these are really crucial APIs to know about Windows, because these are the ones that can actually be used inside of malware. Now, that being said, let's jump into sandboxing. Anything that has to do with malware analysis, there's an emphasis that it should only be done in a controlled environment, ideally a virtual machine. But then certain malware actually have features inside of them that detect whether or not they're in a virtual machine, and if they are, then they won't do the malicious activities that they've been coded to do. So if it's not inside of a virtual machine, the next best thing is to do it inside of a sandbox. And this is even more important when you're doing dynamic analysis, meaning you're going to execute the malware, you're going to run it, and you can see what it actually does as it's running. So it's very, very important to understand this concept, because during static analysis, accidentally, you can execute the malware. You can accidentally double click on the malware. But if you do it inside of dynamic analysis, you're intentionally executing it. You're intentionally running it because you want to see how it runs and how it responds. And it makes it even more important to use a sandbox environment. So what's required to create a sandbox? The concept here is, number one, you need an isolated machine, ideally a virtual machine that's not connected to live or production systems and is dedicated for malware analysis specifically. The ability of this machine to save its initial clean state and revert to that state once malware analysis is complete, that's very important, which is what I was referencing earlier when I said you need to have an image of your computer. This is why virtual machines are so easy to deal with, because if you download Flare VM, for example, it's been designed for malware analysis. You download the ISO image or the install files essentially, and then you can run it, you can install it, and then go ahead and run the malware analysis, and whatever the malware ends up doing to the virtual machine doesn't really matter, because you can then just tear it down and then launch it again. You can reinstall it using your original install files, and everything should be fine. So this is called creating and reverting a snapshot. and we'll need to revert to the original clean slate before analyzing a new malware so that whatever infection happens from the previous malware doesn't contaminate the analysis of the next one, and so on. Monitoring tools that can help you analyze the malware while it's executing inside of the VM. And these can be automated, as we've seen in automated sandboxes, or they can actually be manual, requiring the analyst to interact with performing analysis. And we'll learn about some of these ones in this particular video. Then we have the file sharing mechanism that can be used to introduce the malware into the virtual machine and send the analysis data or report out to us in our own machine or in a different machine. And shared directories or network drives are used for this purpose frequently, or often I should say, but we can also be careful because the shared directory is unmounted when executing the malware, and the malware could actually infect all of the files inside of the shared directory. So you need to be careful, and you need to make sure that the shared directory is unmounted while you're doing the analysis so that it doesn't go ahead and corrupt the files inside of the share, because that could be one of its intentions. So this is very true of ransomware, because ransomware is designed to encrypt all of your data, which will then require you to pay them a ransom so that they can give you the decryption key. The intro to the malware analysis room, we learned about some automated sandboxes to help perform dynamic analysis. We can also learn about some tools to help create the sandbox, which gives us more analysis control. So virtualization is this concept of a virtual machine, and launching virtual machines either from your current computer, from your host, or doing it on top of what they call a hard metal, I think is what it's called, when you actually do it on top of your core hardware. So these three tools that we have right here are the VirtualBox, the VMware Player, and Workstation. Allow us to create virtual machines isolated from the local machine. VMware Player can't create snapshots, so keep that in mind. For dynamic analysis, snapshot creation is a critical requirement, so you may not want to use VMware Player. I don't even know why they mentioned it. If we can't use it, it kind of seems silly, but whatever. The VMware Workstation and VirtualBox have the snapshot creation option and are therefore suitable for malware analysis. VirtualBox is free, so that makes it the ideal choice. Apart from these, there are server-based virtualization like Zen Server, QEMU, maybe, SXC, and a variety of other ones that help with virtualization on a dedicated server. These types of setup is often used by enterprises for their virtualization. Security research organizations often use similar technologies to create a VM farm for large-scale virtualization. But for this video, we're just going to skip all of those things and install an OS in it. So what we're going to do is that the virtual machine operating system needs to be the same as the malware's target operating system for dynamic analysis. And this is what you would find out ideally during your static analysis. When you're analyzing it, you would find out what type of operating system it wants to run on so that you can use that operating system to actually launch it. So in most cases, it's a Windows operating system. And we're going to be talking about those things in this particular video. We're going to be talking about Windows operating system, and we're going to be launching a malware that is designed for the Windows operating system. So once we have the VM with the OS installed, we have to have some analysis tools on the VM. There's automated analysis tools, and they have built-in tools that analyze malware behavior. For example, the Cuckoo Sandbox, also known as Cuckoomon, is a tool that records malware activity in a Cuckoo Sandbox setup. I really like that name for whatever reason. Obviously, I think the reason is that it's just so silly. You know, cuckoo for Cocoa Puffs or going crazy, whatever. We will learn about some of these tools to perform dynamic analysis. Once we have the required tools installed in the VM, before running any malware on the VM, we must take a snapshot. So just keep this in mind, right? Before you run the freaking malware and after you've installed your tools. So the reason for this is because you don't want to reinstall the operating system and then have to reinstall the tools and again do that again every time you need to analyze another piece of malware. So what you want to do is you want to install the operating system, install all of your required tools, and then take a snapshot. And then once you have that, then you can run the malware. And then after you ran it, you go back to that snapshot, the clean snapshot with all of the tools installed so that you can do it all over again. So file sharing, different platforms provide different options for sharing files. In the most popular tools, Oracle VirtualBox or Workstation, you have the shared folder, creating an ISO in the host and mounting it to the virtual machine, and clipboard copy and paste. These are the most common file sharing options. Apart from them, you can have less common options, for example, running a web server on the guest where the malware samples can be uploaded, or mounting a removable drive to the virtual machine. But make sure that the more isolated the option to share the files, the safer it will be. So if you're going to use a removable drive, or if you're going to use some kind of a web-based server, just make sure that that specific drive or that server is dedicated for this specific activity. There's nothing else on it, and that kind of keeps you the safest as much as possible. File sharing option is also used to extract analysis reports from the VM, so that's another reason why we need it. Once we've created the virtual machine, once we've installed our tools, we've taken the snapshot, and we place the malware inside of the sandbox, we can then start analyzing the malware, and that's what we're going to be talking about. So if an analyst wants to analyze Linux malware, what OS should their Linux, or what OS should the sandbox virtual machine have? And obviously it should be Linux, because they're analyzing a Linux malware. So that makes sense. All right, so let's talk about the process monitor. Process Monitor, also known as Procmon, is a part of the sysinternals suite, which is a suite of utilities that's been created for a variety of different purposes, including security and investigations, as we're going to be going through. This is created by WinInternal software and purchased by Microsoft. Sysinternals consists of many handy utilities that provide advanced functionalities for Windows, and one of those things is Procmon. Now, before moving forward, we're going to start this thing, which I've already done. If you want to remote desktop into it, this will be the username and password, but you would still need to start the machine so that you can actually connect to it. And then from there, you would get an IP address assigned to you. This is the one that's been assigned to me for the length of this video. And then after that, you need to connect via OpenVPN to the TryHackMe server, and then you can remote desktop and connect to it. Once it's started, we can go to the following location to start Procmon, which is Desktop, Tool, Utilities, Procmon EXE. You can always just search for Procmon EXE as well, and then you can launch it. Once you do, these are the key areas of Procmon. 1, 2, 3, and 4, and we're going to get the descriptions right now. So showing and opening the save options. So the open and save options, these are for opening a file that contains Procmon events or saving the events to a supported file. Number 2 shows the clear option, which clears all the events currently being shown by Procmon. It's good to clear the events once we execute a malware of interest to reduce the noise. And then we have the filter option, which gives us further control over the events shown. And then the toggles of turning on and off the registry, these pieces right here, each one of them have a different element. So turn off the registry, turn on and off file system, network, process or threads, and profiling events. Below those controls, you can actually now see time, process, process ID, event name, path, etc., which is all the things that we see right here. So time, process, all these columns that you see right here, these are of the relevant events here. We can observe that these events are shown in chronological order by default. Procmon will show an overwhelming number of events occurring on the system, and for ease of analysis, it's wise to filter them to get the things that you are most interested in. Filtering the events can be done easily from the events window itself. So for example, if you right click on something, you can actually create a filter, right? So you can do include Explorer, exclude Explorer, and include events before or exclude events before, exclude events after, exclude events before, etc. So you can see all those choices. For example, include Explorer, right? Or exclude Explorer. And once you do that, you'll be able to, and this is like right-clicking on Explorer itself. When we actually right-click on Create File, it'll give us the options for that. So include Create File or exclude Create File, so on and so forth. Advanced filtering allows us to look at things, for example, in the menu that was marked as number 3 in the first image, right? You can get that filtering menu. And when we click on this, this is what we're going to see. So we want to look up everything where the process name is something or is not something, then include and then add another one. And then you can add more and more rules or filters to filter things out for you. and select filtering values like process name, the relation, the value, the action. If the checkbox is ticked, the filter is applied. Otherwise, the filter is ignored. We can see that the first two filters are not applied in this particular screenshot right here. And then the third filter states that if the process name is procmon.exe, then exclude that event from reporting. Therefore, we don't see any events related to procmon.exe. It must be noted that an include filter will show events that are related only to that entity. So if we include explorer.exe, only the events with that will show up. I mean, this pretty self-explanatory. There's something also known as the process tree, which is a view essentially, and this is the icon that shows it to us. This will help us identify the parents and children of different processes. As shown, we can see the example below. So a process right here, and then you can see the tree of the child items, for example. So winlogon.exe, it has these things, and it also has CSRSS, and then winlogon.exe in this instance has the font and DWM. Explorer has procmon under it, etc. So you can see the parent as well as the children items. So monitor the sample of this particular case using procmon. This sample makes a few network connections. What is the first URL on which a network connection is made? So now I get a chance to actually open up the virtual machine that we have and open up procmon and look at the first piece. All right, here's our Flare VM Windows machine. I can just do procmon like this, and it should bring up Process Explorer or Process Monitor, excuse me. And so that will actually open up Process Monitor for us. And now from here, we're going to open the sample file. So sample1.exe is the one that we're more interested in. So I'm going to go to my desktop. I'm going to click on samples. And it says there's nothing in here, interestingly enough. So let's see what we can do in this case. Oh, you know what? Completely my bad, because we're supposed to just be running it. We're supposed to run that malware. So that being said, there was an option for us to go ahead and clear everything. So Control X will clear that. Control X should clear all of that as well. And it just keeps bringing more things up, it seems. So let me see if I can just do like a Control All type of a feature and see if I can go ahead and... I don't think so. I think it just keeps adding more, like, because I clear them up and then it just keeps adding more and more and more. So I don't think that will really make that much of a difference for us. So what we can do is we can now launch, because it's so crazy. It's literally goes in the tens of thousands immediately, and it keeps adding more and more events, and there are so many of them. Look at this. Look at how many freaking events there are in this thing. So what I'm going to do is I'm just going to double click this, and we're going to run it, and let's see how it works. And automatically you start seeing the one exe under the process name. So there was like a surge of data that came under that process name, and then it kind of went away. And now it's not really showing up that much anymore. I just saw a few trickles here and there, but for the most part, that was pretty much it. So now what we can do, oh, there you go. We get some more stuff going on as well. So I think it'll, like every maybe 5 to 10 seconds, it'll actually do that. So what we're going to do is we're going to create a filter. And from here, we are going to look for the process name itself. So the process name is going to be 1.exe. That's what I want. So I'm going to click on that, and you do not add the items that you were editing. Added now, yes. And so there we go. Now we have all of the things that are relevant to 1.exe. And everything should be in chronological order. And we can see from here that it actually is in chronological order. And so if I go to the very, very top of this whole thing, it should show me the first connection. So process start happened, operation, etc. And then there needs to be something that we're looking for, which is which URL, which a network connection is made. So what is the first URL for which the network connection is made? Now the operation in itself needs to be something that has to do with a connection to something. So it could be a TCP connect. There we go. This is what I have right here. TCP connect, TCP reconnect. These could be some of the things that could be available for me. So now I can go ahead and I guess add more filtering to this whole thing. And I mean, this thing is still running and is still doing a bunch of things in the background. So obviously this thing is not I mean, I haven't stopped it, and I haven't destroyed, I haven't taken the virtual machine down or anything like that. So all of this stuff is very, very interesting information that's going on with this freaking piece of malware. So let's expand this here. And from here, we are going to add another filter to see what is it, the operation is that I'm trying to look for. So I'm going to go to operation is, or we can say operation, let's see, contains. Let's do that. We can do operation contains TCP, and then click OK, and it's going to say, do you want to add it? And so there we go, TCP reconnect, and this is these are some of the paths, right? So this is the stuff, and there we go. So it has the connection of THM Windows-based compute internal, and then it's going to this domain name, it seems, right here. So let's see if we can open this up and copy that little element right there. This element, I believe, is the piece that we are most interested in. So let me see if I can just highlight that, and then let's see if we can copy that and take that over here. And there we go. So we have the TCP connection for the first URL. Now, what network operation is performed on the above mentioned URL, and is the TCP reconnect is what it says. So there's the TCP disconnect, but then there's also TCP reconnect. So TCP reconnect would be the operation. What is the name with the complete full path of the first process created by this sample? So the name with the complete full path of the first process that's been created. So I need to go to my filters, and I need to reset my filters, and it's going to show me everything now. And what I'm going to do again, I'm going to create a new filter, and the process name again is going to be 1.exe. There we go. And then we're going to add that. And so now that should be applied here. And now I can see everything over here. And what I want is create file, right? So it says what's the complete full path of the first process created. So it might not be create file, it might be create process, might be the operation that we have. So let me see, create query, create file, reg open. There are so many freaking items under this thing right here. So let's see if we can go to the top and see if it says create process, because it does say create file a lot. So I do see that a lot, but I am curious to see if create process will be something that I can go ahead and manage. So what I'll do is I'll just go ahead and in the operation, what I'm going to do is I'm going to say operation will contain the word create, and let's see if that does anything or what it actually kind of narrows it down to. So we do say a bunch of create files, as we can see right here. We see create file, we see thread create, we see create file mapping, create file mapping. Let me see if I can see a reg create and create file. I don't see anything that says create process. So I only see create file or create file mapping. I see some registry creations, and then I see some thread creations. So that being said, the very first one at the very top that says create file is Windows. The next one is the Windows system wow log DLL, which none of those things seem to be the thing. So if we do a create file mapping, still nothing. Then we have this thing that's interesting, which is the create file administrator samples 1.exe. That might be a thing. I'm not sure if that's the case. Let's try that one though. Let's see if that's actually the path that they're looking for. I'm not too sure about it, but we can see that maybe it is. Oh, it is. Okay, so what is the name with the complete full path of the first process created by the sample? So this is the thing, right? So when we run it, there's a bunch of create file operations that exist, and there's create file mappings. But for the most part, they seem like normal dynamic link libraries or normal elements. Then there is this actual file. So this is a DLL. It's not necessarily a file. It's a DLL, dynamic link library, which is a series of functions and commands, API calls, etc. that exist inside of it. And this is the very first one that's actually a file. So the 1.exe is actually a file in this particular case, which happens to be the name of our malware. Now, before we move to the next task, terminate the VM instance and start it again so that we have our VM restarted from the snapshot. That way it's not contaminated with the malware execution. So I'm going to do that now. So I'm going to go ahead at the very, very top here. And this is what it means, right? So this is essentially what we're going to have to do for every single one. We're going to terminate it to terminate the machine so that it is no longer running with that malware, because I would have to go through an entire process to try to remove that malware and all of the signatures and the connections and everything else that is done, which is just way easier to terminate the instance and then restart the instance. So we terminated it. Now we're going to restart the machine. So I'm going to restart it. And obviously it's going to, because I'm super zoomed in, it's telling me that I need to zoom out a little bit. So I will do that. I'm going to give it some time. And once it's fully set up, we will then start with the next section here, which is the API logger and API monitor. Okay, our virtual machine has actually restarted. I opened it up in the new window, so we have access to it. And now we can talk about API logger and API monitor. So the application programmable interface, also known as API, performs a lot of tasks. And so Windows OS abstracts the hardware and provides that element for us. So for example, there's an API for creating files, an API for creating processes, creating and deleting registries, so on. And this is the database of all of the APIs that can be used inside of malware, right? So this is the malapi.io, right? malapi.io. And this is the website that basically outlines all of the things that can be used inside of malware. It's not, I wouldn't say that it's the definitive list. I'm pretty sure that there are other things that can be used inside of malware, because hackers tend to be very creative, and that it's not the full list in my humble opinion, but it is a very good list to get you started. So one way to identify malware behavior is to monitor which API a malware calls. And the name of these things are generally self-explanatory. And you can find also the full list again inside of the Microsoft documentation for programming reference. And this is the one that we saw at the very, very beginning. So we have two resources now. We have MalAPI, and then we have the official documentation from Microsoft as well that lists all of the APIs that can be used in total, right? So now we're going to talk about the API logger and API monitor, which can help us identify what API calls the malware is making. So API logger is basically giving us information about the API calls. So we can start it in the virtual machine that we have, navigate to the path, which is the utilities, or you can just, again, search for it, right? When it opens up, this is kind of what you see right here. And then from here, to open a new process, we can click the highlighted three-dot menu. As we can see, where's the highlight? I think it's this piece right here. That's the highlighted three-dot menu. When you click it, a file browser opens up. It allows you to check the file that you want to monitor the API calls. Once you select it and click inject and log, it'll actually start running it, and it'll actually start running it. And then we can see the log of all of the API calls that have been made in the lower pane right here, the call log. So open process, create tool help, open process, create tool help, open process, exit thread, is debugger present, etc. So we can see all of those things. We can see the PIDs of the process that we're monitoring and all the API calls with basic information about the API in the message field. We can click the PID menu for the API logger to log those calls of a running process. It'll open this thing right here. So the PID menu, I want to say, let's see where it is. I think it's this piece right here. So when we click on that, it'll actually open the PID menu. I think we can confirm that as we run it. This will show the processes with the PIDs, the user that ran the process, and the image path of the process. The rest of it is the same as the case with the starting of the process. Then we have the API monitor, which gives us more advanced information about the API calls. And it has 32-bit and 64-bit versions for 32-bit and 64-bit processes. We can launch API monitor by going to either of those versions inside of the tools utilities portion of our Windows machine. When we open it, as you can see, it has more of an advanced interface, and it can give us a lot of things. So going from 1, 2, 3 here, then we have 4, 5, 6 like that, and then 7 and 8. So starting from 1, this is the filter for the API group that we want to monitor. We have a group for graphics and gaming, another one for internet, and so on. And it'll only show us APIs from the group that we selected. The second tab shows us the process that are being monitored for the API calls, and we can click Monitor New Process to start monitoring a new process. This shows us the API call, the module, the thread, time, return value, and anything else. We can monitor this tab for APIs called by a process. This is tab 3. Then we have tab 4 that shows us the running processes that the API monitor can monitor. Tab 5 shows the parameters of the API call, including the values of the parameters before and after the calls. This tab, which is tab number 6, shows the hex buffer of the selected value. Tab 7 shows the call stack of the process. And finally, we see the output. To understand it, we can open the process in the API monitor. We click Monitor New Process in tab 2, and then you can see this. And then you can click that document button, that file button, and you can most likely select the file. So select the file from a path, any arguments the process takes, the directory from which that we want to start the process, and the method for attaching the API monitor. And we can ignore the arguments and start in options. So process, and that's what we have, right? And then arguments and start in, we can move on. Attach using static import, which seems to be fine. Because we don't have any arguments for the process and we want to start it from the path where it actually is located. Once we open it, you can now see that everything is populated for you, which is very useful. So in tab 1, we have all the values that we can monitor. So all these things right here, you can monitor all of those various values, and by default, everything is selected. In tab 2, we see the path of the process that we're actually monitoring, which is this specific one right here. Tab 3, a summary of the API calls. The highlighted API call can be seen as reg open key, and then hence we know that the process tried to open a registry key. We can see that the API call returns an error, which we can see in the return value field, and the error details can be found in this tabs field. So this is what we see right here, reg open key, and then inside of that, underneath it, you can kind of see that there's this, I think the error I think is inside of it, or maybe not. I think it's actually, this is what they're saying in the return value. In the far hand right, in the return value, you see that there's an error, and then the error itself will actually give us more details as well. So that is some information for that. And then what else do we have? Tab 5 shows the parameters of the API calls from what we had. So this was 1, 2, 3, this is 4 and 5. So this is 4, this is 5. So this is the parameters of the API calls. Tab 6 shows the selected value in hex. Tab 7 shows the call stack of the process. So this is the call stack right here. So we can see that the API monitor provides us with much more information than the API logger. However, we can slow down the analysis process to digest all this information. When analyzing malware, we can decide whether to use API logger or API monitor based on the needs. So we can go to the Windows API room to learn more about API calls, or we can just visit the documentation page from Microsoft, and more like pretty much anything that you need about the API is explained inside of this documentation. So it's not that difficult, and then you can always just Google the name of the API call itself, and you'll get some really good descriptions for the Google AI that's just inside of Google, or you can go to Gemini, you can go to GPT, your favorite AI tool, and you can get even more information that way. So now we can run this. So we can say the sample 1.exe creates a file in the C directory. What is the name with the full path of this file? Then what API is used to create this file? And in question 1 of the previous task, we identified a URL to which a network connection was made. What API call was made to make that connection? We noticed in the previous task, after some time, the sample's activity slowed down such that there was not much being reported against the sample. Can you look at the API calls and see what API call might be responsible for it? And then keep the VM and sample running and move to the next piece. So we're not going to crash it at the end of this one. I'm guessing we're going to be using it again. So let's go ahead and analyze 1.exe one more time. But now we're going to be doing it inside of our API. I'm going to use the API logger, or no, it's not API monitor. I'm going to use API monitor to see what I can get from it, because I think there is a good amount of information that we need from this. So we're going to go to tools, and in this it should already have API monitor, and it does not, so I'm not even going to bother with that. I will just click on the search button at the bottom right here, and we will do API mon, and for that it should get me the API monitor locations, and then I guess the one that's available is the x64. So we'll just run that one. I'm going to give it a couple of seconds. There we go. And thank you for installing. If this is your first time, you might want to check out tutorials. That's fine. Thank you so much. API definition could not be initialized. That's fine too. And monitoring is currently disabled. To monitor new processes, enable monitoring or launch another instance. So I will enable monitor. API definitions could not be installed. Please make sure that the temporary directory is valid, an API monitor is running, and an account that has permissions to write files to the system. Okay. Okay, so I had to tear the machine down and restart it again, and API logger actually works now. That's nice. API monitor I have not tried again, but based on the hint that we received for this specific question, they said that it might be better for us to use API logger, as I have right here. So API logger is easier for this particular purpose, and we're looking for API calls that might be used for creating files and check those specific arguments. So in this particular case, this is what we're going to be doing. So we're going to click on this button right here. We're going to go select our sample from the samples right here, and one exe, open that, and inject and log is what we're going to be doing. And then we're looking for anything that has to do with creating files and check those arguments. So let's go over here and let's see if we can parse through this, because it does actually give us the option to parse. So let's see if I can parse through this, meaning if I can kind of filter through it, I guess. Maybe that's not it. So let's see how I can show that stuff. Okay, so there we go. So this is actually a text document that was created for me. I went through find, and then I did create as the keyword. I pressed enter, and it created this little text document for me. And inside of this we have create file, the create file A, which is the commandlet or the API call that actually creates files. And then we have one exe, my app exe, Windows Explorer exe, and I think that this is the one that they're talking about. So we're going to copy this thing right here and go over here and submit that. Very good. So it creates a file in this C directory, as you can see right there. So what API is used to create this file? That is the create file A. And in question 1 of the previous task, we identified a URL to which network connection was made. What API call was used to make this connection? So what we can do now is we can actually go and search for that specific URL and just find the API call. Although I feel like in the procmon, the API call itself might have actually even been there as well. But what I can do now is I can go ahead and copy this domain and go click on file and then search for the file, or search for that string, that domain name. And okay, so it doesn't give me anything. So interesting. Let's see what else we can do to search for this. I can always just do the first part of it. So if I do 9473155512, let's say, and that's not going to show me anything either. I think what it's doing is that it's pulling up or searching for the individual API calls. I don't think it's actually searching for strings inside of it. Maybe we can search for arguments maybe. So let me see what the hint tells us in this case. So it says the URL in the previous task had an IP address at the start. Check for that IP address in any calls. Okay, so maybe we can do that. So maybe I can, instead of searching for the full thing with dashes, what I can do is I can delete this and then do this. I'll do 94.73.155.12, and then I will delete the first part of it and search for that. Okay, there we go. So now we actually have the internet connect, and then now we have the IP address here. So there it is. So internet connect W is the API call that was used to make that connection. And we noticed in the previous task that after some time the samples activity slowed down such that there was not much being reported against the sample. Can you look at the API calls and see what call might be responsible for it? And we can see that you might need to leverage some knowledge of from one of the previous or prerequisite rooms to identify sandbox evasion techniques. So it could be a variety of different things, really. And what I'm going to do is I'm going to start doing some Googling to see what API calls might be responsible for slowing down activity, or at least the detection of the activity. So interestingly enough, it's actually at the very, very bottom, because I think this is going in order, right? So if we look at the bottom right here, there's this command right here that is actually pretty consistent across most coding languages as well. When you use sleep, it basically kind of stops interacting. It stops doing things, and it'll do it for a number of seconds, and you would tell it to sleep for however many seconds. And in this particular case, it's 1E078, and then so you saw that it actually updated immediately in real time as well. So it slept for that long, it exited thread, and now it ran this thing again, and it'll probably sleep for some other time as well, and it'll do that again. So sleep is actually my best bet in this particular case, without doing any researching or anything of those things, and it happened again. So look at that, sleep again. So yeah, sleep would definitely be my best bet in this case. And there we go. So we got it. So now it says keep the VM running and sample running and move to the next section. So let's do that. And now we can move to Process Explorer. Process Explorer is also from the SysInternals suite, and it's a more advanced form of the Windows Task Manager. It's a very powerful tool that can help us identify process hollowing and masquerading techniques. And we can open this by going to the Utilities folder and just opening a Process Explorer. When you open it up, this is what it looks like. And it shows all the different processes running in the system in a tree format, and we can also see the CPU utilization, memory usage, process IDs, description, company name. We can enable the lower pane from the view menu to find more information about them. And this is what we can see right here. So now you have the lower pane, and it gives you more information about each one of these things. When we select the process in the upper pane, we can see details about it in the lower pane. And we can see the handles of the process that open for different sections, the processes, the threads, the files, the mutexes, and semaphores. That's a new word as well. So I don't know what semaphore is. So let's look at the Google explanation here. Synchronization tools used in concurrent programming to manage access to shared resources by multiple processes or threads, preventing race conditions. Okay, so semaphores, very, very interesting. All right, so this handles inform us about the resources being used in this process. If another process or thread in another process is opened by a process, that's a lot of process. So if another process or a thread in another process is opened by a process, it can indicate code injection into that process. Similarly, we can see DLLs and threads of the process in the other tabs of the lower pane. The word process has lost all meaning to me right now. For some more details about a selected process, we can look at the properties of the process. We can do that by right-clicking the process name in the I don't know why this is so funny to me right now, but like the more I say it, I'm like, dude. Okay, we can do that by right-clicking the process name in the process tree and selecting properties. When we open the properties of a process, we see something like the below image. So here we go. This is what we see here. And process masquerading. So the properties function shows us a lot of information about a process in its different tabs. Malware authors sometimes use process names similar to Windows processes or commonly use software to hide from an analyst's prying eyes. The image tab, as shown in the above screenshot, helps an analyst defeat this technique. By clicking the verify button on this tab, an analyst can identify if the executable for the running process is signed by the relevant organization, which will be Microsoft in the case of Windows binaries. In this particular screenshot, we can see that the verify option has already been clicked. Furthermore, we can see the text no signature was present in the subject. So if we go over here and we can see verify has already been clicked. And then for the signature, let's see if we can see no signature right here. So no signature was present in the subject for Microsoft Corporation, right? So it should say in the image file, it should say Microsoft Corporation as the signature, and it technically has the name here, but that could be something that they manually entered. But when you do verify, it can show you that that actually is not the case. So this means that although the executable claims to be from Microsoft, it's not digitally signed by Microsoft and is masquerading as a Microsoft process. This can be an indication of a malicious process. We must note that this verification process only applies to the image of the process stored on the disk. If a signed process has been hollowed and its code has been replaced with malicious code in the memory, we might still get a verified signature for that process. To identify hollowed processes, we have to look somewhere else. Process hollowing. I don't know why. I'm like, it makes me giddy right now. Like, it makes me giggle. Another technique used by malware to hide in plain sight is process hollowing. In this technique, the malware binary hollows an already running legitimate process by removing all its code from its memory and injecting malicious code in place of the legitimate code. We talked about this in further detail in the last episode. So in the last video where we actually go through advanced static analysis, we do talk about process hollowing quite a bit. So I don't know how in depth we're going to go right now, but if you want more about this about this specific process, then go ahead and check out the last video. So while an analyst sees a legitimate process, that process runs malicious code of the malware author. Process Explorer can help us identify this technique as well. When we open strings in a process's properties, we can see something like the below screenshot. So we're looking at strings here, and we can see these various elements, and this program cannot be run in DOS mode, and then you see other elements in this particular case. And so at the bottom of the screenshot, we can see that the image and memory for the options that we have right here, these two things, when we select image, Process Explorer shows us strings present in the disk image of the process. When memory is selected, it extracts the strings from the process's memory. In normal circumstances, the strings in the image of a process will be similar to those in the memory, as the same process is loaded in the memory. However, if a process has been hollowed, we will see a significant difference between the strings in the image and the process memory, hence showing us that the process loaded in the memory is vastly different from the one stored on the disk. And the big thing about hollowing is that, you start a process, okay? You started normally, and it's a regular, safe process that has been started. And what happens is that it suspends. So when you do process hollowing, you first start it, then you suspend it, meaning you don't close it necessarily. You're just kind of pausing it from running. After you suspend it, you go ahead and allocate some kind of virtual memory for your malicious code. And then you input your malicious code inside of that virtual memory, and you get an address for that malicious code the virtual memory. For that location of the virtual memory that you've allocated, you'll get a little address, and then you take that address and you put it in the normal process's starting address. So the normal process also has a starting address, but it's been paused, and you can now change the details of it. And so you can change the details, namely its starting location, its starting address. You can change it to the address of the virtual memory that you allocated for your malware. And now when you resume that original process, it runs as if it was running. The name of it is the same. Everything is the same, but it's now running malicious code. So when we see inside of the process monitor that the image, right, the stuff that's on the actual operating system, what's supposed to be running for that individual process, it's going to be different from what's in memory, because we are now pulling malicious code from the virtual memory, right? So that's kind of the quick version, the quick explanation of that. Hopefully that made sense for you. So now we are going to answer these questions. What is the name of the first mutex created by the sample in this particular executable? If there are numbers in the name of the mutex, replace them with X. So the hint here, let's see what the hint gives us. It says that enable the lower pane, check handles and mutants in handles, copy and paste the first one. So what we're going to do is we're going to actually open up Process Monitor. First things first, so I'm just going to close the API logger, and I'm going to go ahead and open up Procmon. It's Procmon, right? Or is it Process Explorer? I can't remember. Oh, it's Process Explorer, excuse me. So we're going to open up Process Explorer. There we go. Once we open that up, we can open the pane in the view location. We can look at the lower pane, so lower pane view, and we're going to open up the handles. I want to say, I think that's what it said, right? So let's see what the hint gave us. It said check handles, yeah, and mutants in the handles. So now what we're going to do is we're going to look for the malicious process that we have. I'm just going to open this up in a bigger window. Hopefully it will not crash on me and it'll still work and everything will be fine. Okay, so here we go. This is what we got here. We can expand this now. And now we're looking for that one exe that's been running in the background. So there it is at the very bottom of the left hand side. So now we have this thing, and in this element at the bottom we have a bunch of information that might be interesting. So the specific information that we are interested in is the mutex. So we're looking for mutant categories. So you can actually see that there's mutant categories in this particular case. And now it's looking for that location. And so it says to take the name of the first mutex that was created by the sample, and if there are numbers in it, replace it with an X. So we'll go to the very, very top, and we're going to scroll through this and see what the first mutant instance is that's going to show up for us, which is this thing right here. So let me see if I can copy that. I can't, so let me open it up, and this is what I have. So I can copy that now, and I can go ahead and paste it in here, and then replace the numbers with X's is what they're saying. So X right here, and then we will do an X right there. I mean, this is kind of crazy, but let's see. XXX, X, and then this one right here, 1, 2, 3, and then this last two, 1, 2, and let's see if that's right. That is right. Okay, great. Interesting. Now, is the file signed by a known organization? Answer with yes or a no. So the file being this file in particular, right? So if we're going to go here, we'll right click on this, we'll look at the properties, and we're going to go to the image itself, right? And then click verify. And no signature was present in the subject. So we're going to say no. I mean, I could have guessed no because it is malware. So I can imagine that it would be not signed, but we can just verify that the way that we did. And now we have, is the process in the memory the same as the process on the disk? Answer with yes or no. And I can again tell you that most likely it's not. So if we go look at strings and we look at these things, and we have the process in the memory in the disk itself, which is the image. And if we look at the memory information, we can kind of see that it's not the same, right? So at the very least, we can just look at these initial levels, and then we can see that it's not the same. We can try to look at a lot of other things in here, and we can probably see that it's also not the same. It's clearly not the same. So none of these things are the same, because when you go through these, you can see all these commandlets that are supposed to be running and a variety of L's and etc. And these things have no commandlets or API calls that are in it. There's no series of L's. So all of those things would imply that they are not the same. So we can do N for that as well. And now it says, please move on to the next task and terminate the VM and start it again from scratch. So we're going to now close the window. We're going to terminate it again. I'm going to give it a few minutes just to make sure that it really does reset, because the last time that I started it too early, it gave me some issues. So I'm going to give it a couple of minutes, and then I will restart it so that we can move on to our last piece here, which is RegShot. All right, here we go. I have already restarted the virtual machine, and it should be done in approximately 15 seconds. And we are now going to talk about RegShot, which is a tool that identifies any changes to the registry or the file system. And it can be used to identify what registry keys were created, deleted, or modified during the dynamic analysis by the malware. And it works by taking snapshots of the registry before and after the execution of malware, and then comparing the two snapshots to identify differences between the two. So very simple. To execute this, we would find it inside of our utilities folder, and when we execute it, this is what it looks like. So when we execute it, this thing first pops up, right? The output path that we select in the attach VM might actually be different because every time that you start the virtual machine, the output path most likely will change, which is what you can kind of see right here, but it can stay the same. They said it might be different, right? So it may not necessarily actually be different. In this simple interface, if we select the scan dir 1 option, we can also scan for changes to the file system. However, for the sake of brevity, we will only cover registry changes in this room. To start, we can click on the first shot option. It will ask us whether to take a shot or take a shot and save it. Once the first shot is taken, we see something like this. So first shot, this is what it looks like. Okay, great. And then we have the saved shot of the registry. We can execute the malware. Once we have the executed malware and are confident that it's performed this malicious activity, we can take a second shot. And now we click the second shot option. And right here, I guess they just right-clicked it, maybe. And then you can right-click it. Or I guess when you do click it, it'll say either shot or shot and save. And now that we have both shots, we can compare them to identify the registry changes. We do that by clicking the compare option. And then when you do that, it'll say keys deleted, keys added, values deleted, values added. It'll show you a bunch of things. So it's very, very useful. This is actually very handy. So it shows all of those things, deleted, modified, etc. It also shows changes to the files and folders. We see 0 changes to folders and files because we had disabled the scanning of the directory while taking the shots. So that part makes sense. So if you actually want to see the changes in the files and folders, you would also do scan directory to take that shot as well. If we had enabled this and provided directories to monitor, we would have been able to see details about file system changes. For now, let's move on to the results of the execution. If we save the results by clicking on compare output reg shot, it provides us with the changes in the registry as shown in this particular case. So these are all the ones that were deleted. These are all the ones that were added. There were 20,000 keys that were added. That's insane. We see the date and time of the shots taken, the computer name, the username, version of the reg shot. Below that, we see a list of the changes that were made, starting from the keys that were deleted. One advantage is that it overall, inside of all of the other tools, over all of the other tools, RegShot enjoys that it does not need to be running when we execute the malware. So some malware can check all the running processes and shut down if the analysis tool is running. When analyzing, we might often encounter malware samples that check for proc exp, procmon, or API monitor before performing any malicious activity. So what we can do here is that we can close RegShot. So since it takes a shot before and after the execution of the malware, it doesn't have to actually be running during malware execution, which actually makes it very handy because the malware could be looking for all these things that are required to be running while you're executing the malware, and it won't do all the things that it's supposed to do, right? If it notices that Process Explorer is running, it's not going to do what it needs to do. So this is actually one of those handy tools that you take the shot, close it down, and then run the malware, and then you can come back and look at the second shot, and then you can see if there's a difference or not. So on the flip side, we must ensure that no other process is running in the background while performing analysis with RegShot because there's no filtering mechanism as we saw in the other tools. Hence, any noise created by background processes will also be recorded by RegShot, resulting in false positives, and that can be a bit annoying. So now we can analyze sample number 3 using RegShot. There is a registry value added that contains the path of the sample in this format, HKU, SX, and then yada yada yada. What is the path of that value after the format mentioned here? So what are we going to do? We're going to first open the tool itself, and we're going to go to utilities. We're going to open up RegShot right here, and then we will just take the first shot, and it'll be fairly simple to do. So let's just go ahead and do that. I guess it's going to take some time for it to open up. Okay, so I had to crash the machine one more time and restart it again in order for RegShot to open because for whatever reason, it was not opening. So now that we have this thing going, we can go ahead and follow along with the last series of instructions here. So basically, as soon as we open it, we're going to click the first shot, and we're just going to do shot, and it's going to do its thing. And then once it does that, we're going to run the malware. And then after that, we will take the second shot, and then we'll see what the comparison will be. So no idea how long this is going to take, because I would assume that it's going to take some time. So we will give it a minute, and then we'll come back when it's done, and we'll run the malware, and then we will see what the difference is. All right, cool. So here is our first shot that we took with RegShot, and this is what we have. So 474,000 keys, 921,000 values. Let's just kind of keep that and we'll round it off. So there is that. Okay, so now I'm going to go ahead into my sample folder, and from there we're going to run the sample number 3. So we have sample number 3. We're going to run this thing, and there's a registry value that's added, etc., etc. What is the path of the value after the format that's been mentioned here? So I'm going to assume that sample 3 is running because I double clicked it, and I'm going to give it like, let's say, I don't know, a few seconds or whatever to run. And we will then take shot number 2. It doesn't tell me how long to wait for sample 3 to do what it does and everything else that it does. So hopefully by the time that I'm done saying all of this, the sample 3 will have done everything that it's supposed to do. So now what I can do is I can take the second shot, and then we'll take that, and then we'll let it run, and we're gonna come back to do the comparison. Okay, so I ran RegShot, and I tried to run the malware the first time in my first attempt, and then it was not successful. I wasn't able to run RegShot again, and it just kind of stalled out on me, and then the virtual machine crashed. And then the next several times that I rebooted the virtual machine and I tried to run RegShot, it wasn't working when I went to this folder, so the folder that's on the desktop right here in Tools and then Utilities, and clicked on this. It didn't work because these are technically all links, so soft links, otherwise known as shortcuts, that go to the original files that are installed on this virtual machine. So the only way that I was able to pull it up was actually go to the terminal and go to the original location inside of the C drive, Tools, and then inside of the RegShot folder where it has all of these various versions of RegShot. And then that way I was able to pull off using the RegShot. I think I did X64. Yeah, that is the one that I used, and it's also saying to use X64 for the exercise, so that part was fine. And as soon as I opened it from this location by just calling on the executable like this, as soon as I did that, it opened up instantly and it was able to run. So if you're having problems running RegShot from the tools folder on the desktop, go to this specific folder. Go to C, Tools, and then the RegShot folder. And then inside of that, you can call on the executable, the x64 Unicode version of the executable, and then it should work for you the way that it did for me. And so I did that. I took my first shot, and the first shot completed. And then I came and I ran the 3.exe, inside of the samples folder. I ran this piece of malware, and I've given it, I want to say, a good like 5 minutes, I think, 5 to 10 minutes or something like that. So hopefully now I can actually take the second shot, and then we can get a successful second shot, and then from there we'll be able to do the comparison. So here we go. Fingers crossed. We're going to click on second shot. We're going to take that second shot, and it's running. And so the last time that I did this, I actually did get as far enough, and see, there you go. It just froze right here. And this is also what happened the last time that I did it. And now I am concerned about whether or not this is going to be able to complete its second shot. I'm gonna, I'll give it some time, and we'll see how this whole thing plays out. My goodness, I really, really hope that this works, because I'm trying this on a different day now. I gave up the last time that I was doing this because I tried so many times and it didn't work, and I came back to it on a completely different day, and I'm hoping that this is gonna work. So we'll give it a few minutes, see if it actually works. If not, I will have to troubleshoot yet again and try to figure out how to get this done. Okay, so it actually completed. It looked like it wasn't running because it had that like processing circle that was on the screen, but it actually completed, and it didn't take that long. I think it was like maybe a total of a minute or something like that altogether. So that was not that bad. Now we actually have our second shot that has been completed over here. So let's see if we can now do a comparison. And I'll just do a compare, and hopefully it'll just open up the file for me that we can use as an analysis. There we go. So it's generating the comparison for me between the two shots that it took, and we're looking for something that resembles this. So HKU S.X or S-X dash, and then this whole thing right here. So there we go. There's the comparison. Okay. Oh, am I not going to get a comparison analysis? Is that what's happening? Maybe I should have done compare and output. I think, yeah, it says, oh no, so it says, if we save the results by clicking on compare and output, RegShot provides us with the changes in the registry as shown in the screenshot below. So, okay, I'll do it again. Oh, I see. And then now I can go to output. Now it's error creating a file. Of course, there's an error creating a file. All right, great. So the next time that I run this, I'm going to do compare and output so that I don't have to worry about an error being created in the file. Which means I'm going to go and do this whole thing yet again from the very beginning. I'm going to crash this machine. I'm going to restart the machine. And we're going to run RegShot the first time. We're going to launch the malware. And then we will run RegShot again. And then when I have that second run of RegShot, I will then do a compare output. And all of the steps will be exactly the same. I'm going to run it. I'm going to run the malware. Then I'll run the second shot. And then once that's done, I will do compare output. And then we'll just pick up the recording from that point. Okay, so here we go. We came back. I restarted the machine. I ran RegShot, did the first shot, and then I started the malware, and I ran RegShot on the second shot, and I saved both of those shots just in case. I don't know if that's going to help us or not, but I saved both of those shots, and they're inside of my documents folder. So shot 1 and shot 2 are both inside the documents folder. So now I'm going to open this thing back up, and we're going to do a comparison, and I'm going to do compare and output because last time that's not what I did. And let's see, hopefully I won't get an error and it'll actually display the output for us. Gave me an error message again. So error creating a file, and total changes were 44,754 changes. So we definitely know that the changes were made. There were some keys that were added, keys that were deleted. 20,000 keys were deleted, 33 keys were added. So let me see if I can look at the output one more time. I can't. So here's what we're going to have to do. We're going to have to pull up the registry editor and manually look for that registry change because unfortunately, RegShot is not working for us, and it's something that I wish I had better information for. So we're going to look for HKU, I guess HKU/SX. I'm going to try to see if I can find that because unfortunately it doesn't have anything for me. So let's see what I can find here. Okay, so here's the other attempt. I actually couldn't find anything inside the registry editor. But what I did was I looked at, I closed down RegShot, I reopened it, and then as my first shot, I loaded the shot that I had saved. As the second shot, I loaded the shot that I had saved. I clicked compare, it finished the compare, and now, moment of truth, it still is not creating the file for me, which is now getting to the point that we have a little bit of an issue, it seems. So let's see what we can do here. Okay, so after several approaches, multiple attempts, I have concluded that I need to search for this thing manually. The first time that I tried to do it was through the registry editor, but then I stopped about halfway And I was like, okay, let me see if there are other ways that I can work with RegShot. And I have tried a variety of different attempts. I ran RegShot as an administrator. I opened everything essentially as an administrator, thinking that maybe it was a permission error. But ultimately, I still kept getting the same error over and over and over again, which was the comparison wasn't generating because of, I don't know, whatever reason. The output file just keeps saying error creating file. So that is the main thing that I am now dealing with. So one of the ways that we can do this, knowing that this is the format, right? So this is what we're dealing with right here. The format of the answer is this HKU, etc., etc. And the hint that this gives us is that this is a part of the HKey users registry, and we're looking for a specific hive. So this is a registry hive key. It's specifically going to be under the HKey users, which is abbreviated as HKU, which is that initial part of it, that beginning part of it. And then the rest of the portion that we see right here, this portion right here, has to do with the user's SSID, which means our user SSID is going to be something here. And now it says the answer is the value added that contains the path of the sample in the format of, etc., etc. So I have this right here, right? So this is my user. The administrator user has this SSID, S1, 521, etc., etc., etc. Okay. So this is what I know so far. Now, and what I'm going to do, and this is essentially my last resort here, I'm going to try to find this manually inside of the registry editor. And if I can't find it in reg editor, then I'm literally going to Google the answer because I need to fill in this answer and try to get something done. So it says search for values added, remove HKU numbers from the start, only share the path, not the value. So that's basically it. That's what we're trying to do is find the, what is it? It says remove HKU and the numbers from the start, only share the path, not the value. So that's what we're looking for. So we're going to go and open up the regedit, the registry editor, which is this thing right here. And inside of this, I'm going to go to the HKey users location, which is where that HKU would be. So this is right here. And inside of that, we're going to look for our admin, which is S1 521 1966, ends in 3061, etc., etc., etc. And then we're looking for this one right here. That's the specific one right there. So I'm going to open that one now. And this is where potentially the malware would exist, would be in any of these specific locations. So HKey users, S1, etc., etc. Now I have to do some digging here to see where I can potentially find the answer. Okay. Oh my God. Alrighty then, my dear friends, let me tell you, this was quite a mission. So the way that it all started was this. So obviously I went into my user right here. So my user ID, based on some data that I gathered, it was implied that malware usually is installed in one of the various locations. The first one was inside of software. So we went inside of software, and inside of software, we went inside of Microsoft, and then we went inside of Microsoft Windows NT, which is this location. Let's go down here if we can. So Windows NT, and then under that, we went under the current version. Then we went under app compat flags, then compatibility assistant, and store. Now, once we were inside of store, the rest of it was fairly simple to decipher because there's basically only these are the paths that we can actually share. And the full thing, I typed piece by piece as I kind of deciphered the whole thing, because the answers inside of TryHackMe right here, thankfully, the formatting of the answer kind of helped me a little bit, because they give you the number of spaces that you need to fill in, and then based on that, I did trial and error, and I tried to find the ones that actually filled in these spaces, and I typed in piece by piece. And I'm probably just going to leave that in the edit. I'll kind of like time lapse through it just so you can see how I did it, but I was literally going piece by piece for this whole thing to try to find that answer. And so this is the location, right? This is the ultimate location. HQ users, you go to the actual user itself, and then that's the full location that you have right there, which, let me just open this in full screen so you can kind of see this a little bit better. And it's a very long path, and for the most part, this is what they're looking for. They want everything after software. So that's the full path that they're looking for, which is software, Microsoft, Windows NT, current version, app compat flags, compatibility assistant, store. Windows NT has a space in the between the Windows and the NT. Compatibility assistant has a space between compatibility and assistant. And then when you're inside of store, then you get the rest of the paths that are available here. And then you have to include all of these paths over here as well. And the final answer was C:\users /administrator /desktop /samples /3.exe, which is technically the name of the executable that we launched for the malware anyway. So that was the registry key that was added to our machine. This was more difficult than it had to be, mainly because of the fact that regshot was not working. And I know that if there's a registry that's been added, it's something that we could have tracked down if we just knew where to start looking. And I went to Gemini and I was like, listen, this is the answer this is the question that they're giving me. What can I do to manually search for this? And Gemini said, okay, this is the Hive for the HK users, the local users. And then this is a format that they give you for your user's SID. And so for that, I just literally was like, okay, well, you can just do who am I, and then look for the user, which is exactly what we did here. So I just typed for who am I /user, and then it gave me my username, and then it gave me my SID. And the SID helps us track down which location of the registry we needed to go to try to find our data for our Hive, for our user's Hive. And so that's the SID for my user. And then after that, it was literally kind of just a process of elimination, guessing, trial and error. That's really all it was. And the hint that Gemini gave me was malware is usually installed in software. So I just started with software, and then I typed in software, and it fit. So it fit the number of spaces that it gave me. I was like, okay, maybe I'm on the right path. Then I typed in Microsoft, that fit. I was like, okay, there was a space between these elements right here. And so I was like, okay, so let me see if I can find anything under Microsoft that actually has a space in the name. And so active setup has a space, but it didn't fit. And then I kept scrolling down, and I was like, what else has a space? Okay, Internet Connection Wizard, that doesn't fit. Internet Explorer, that doesn't fit. And I just kept going, and I kept going. And then finally it got to the point that it was Windows NT and Windows kits, where I was like, okay, these are the closest Windows NT actually fit, and then current version fit, and so on and so forth. And I just kept going until I ended up at store. And then inside of store, these were the values that existed. And then again, guesswork and process of elimination, so on and so forth. So that was really the only way that I was able to find it. This should be much, much simpler if regshot actually works for you when you run this exercise, because it should have no problem generating that comparison file. But in my unfortunate situation, it couldn't generate the comparison file. So now it's like, all right, we got to do the manual work. These tools are supposed to help us make our life easier, but it didn't make my life easier, and I had to do manual work. But ultimately, I got the answer without actually going and Googling the answer and being spoon-fed by the internet. And that's actually one of the big thing that I'm really proud of, is that I found a way to find that answer. And now I've worked through the logic with you so that you can find the answer in case you run into something like this, and you know how to come to the conclusion instead of somebody just spoon feeding the answer to you. So there is that, and I can finally terminate this freaking machine. It took a couple of days to do this task, to do this specific task for RegShot. It took a couple of days, but it is now done. It's now over, and we can conclude this video. We are finished with this video. So let's do some final thoughts, some reviews, and we will be out of here. You will be dismissed. Okay, so as it stands, as a review, we covered the concept of sandboxing and what that actually means, and the best way to actually do it is through a virtual machine, which is essentially what I did every single time. Every single thing that I ran, I had to restart the virtual machine, crash it and restart it so that we can start from the beginning, start fresh with a new virtual machine. We looked at the process monitor, we looked at logging APIs and the API monitor, so the API logger and the API monitor. We looked at the process explorer, and then finally we looked at RegShot. And RegShot, in theory, is a good tool. It's a good utility. Unfortunately, it just gave me some problems, and I had to kind of find my way manually, which it is what it is. I feel like I'm better for it. I feel like I learned more as a result of it. So it's kind of like a blessing in disguise. That's the silver lining in the dark cloud. So that's essentially what we went through. And in conclusion, the dynamic analysis, we learned that you can monitor a process using procmon and filter out the processes to focus on the process of interest. You can look at what API calls we're making, figure out if a malware sample is trying to evade detection by performing a process masquerading or process hollowing exercise, and Process Explorer was the tool for that. And then we identified changes in the registry, not using RegShot, using manual search, but RegShot can technically do it for you. And that's pretty much it. That's all I got for this specific room. I can finally click complete and move on from this room to the next room. If you found this video useful and if you've gotten any kind of value from this channel, then I highly encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. Of course, go ahead and check out everything that we have on the channel, because there's a lot of great stuff that's available, especially as we go deeper into SOC Level 2, and then Pentest Plus episodes are coming out every Friday, and then CYSA Plus is going to come out, and then we're going to go into AI for cybersecurity. But I'm going to start AI for cybersecurity before I go into CYSA, because I've been promising that series of content for a long time now, and then I had to move from LA to Vegas and things got delayed, and so I know I've been promising that for a while to you guys, and I promise I will deliver on that. That is my word to you. And yeah, there's a bunch of great stuff that's already on here. There's the members only videos, obviously, that are available here. And then there's SOC Level 1 playlist, SOC Level 2 playlist, Security Engineering playlist, and then all of the popular videos at the top. And then these are all the playlists that I've created so far that have been very, very helpful for people. People have used Network Plus to pass their Network Plus exam. People have used Linux Plus to pass their Linux Plus exam. So these are playlists that I know actually work for people when you go through them and you actually study and go along with the guides. And if you join Hackaholics Anonymous, you get the notes document and the practice questions and everything else as well. So it helps people study. And it's not that expensive to become a member of Hackaholics Anonymous. To actually get access to those is $25 to become a cyber agent, or if you want to go higher, you can go higher. But a cyber supporter is $5. You get access to Discord. I've decided to make the Discord for cyber supporters and everybody else a lifetime membership. So literally, you can sign up for Discord, $5, or sign up, get access to the Discord, come into the Discord server, and then cancel your $5 membership, and you'll still be inside of the Discord server. And you know, at the very least, you get access to that stuff, the early access to the content and the downloads and all of the special stuff that I share in the members community will no longer be accessible to you if you cancel your membership. But at the very least, you can come in, get access to the Discord lifetime, and then bounce if you want to. But I think you should stay, because there's a lot of really amazing stuff that comes out for the members. And One of those things is if you're a cyber agent and above, you get access to all the document downloads, practice questions, and everything. The Python automations that you see right here, I actually write these scripts and give you the scripts, and then I explain, hey, this is why this works the way that it does, in case you want to customize it for yourself, or if you want to go use it at your job or something like that. All of those things. So there's so much value that's inside of this channel. And I'm not just saying that because I'm the creator of the channel. I have compared it against so many other channels, and I know for a fact that we have so much tremendous value on this channel, and I just can't wait for more people to find it and for us to grow as a community. And it's just a very, very exciting thought and an exciting topic. But until then, if you have any questions, drop it in the comment section below. If you had any challenges with the video from today, drop it in the comment section. And if you just want to say hi, drop it in the comment section. Whatever it is, let me know. I am here and I will be as responsive as I possibly can be. I did start an actual day job because of everything that has been going on, so I'm not as available during the days on Monday through Friday, but weekends I'm super available, and I'm still going to be posting regular content, and everything as far as the content schedule is concerned will stay on time and everything will be great. So all of those things are still available to you. It's just that me personally being responsive in the comment section is not going to be as responsive during the week. It's mostly during my lunch hour and like after work, which I really get to respond. And then after that, the weekends I'm fully available. So feel free to comment, feel free to reach out. I will be here at your service. And of course, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you're serious about your SysAdmin training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section. And that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I'll see you in the next video later. In episode 46 of the SOC Level 2 training series, we are going to continue with our malware analysis module, and we're going to be talking about dynamic analysis and debugging, right? So the concept of debugging, and I would assume that this is kind of like a continuation from the last video, obviously, which was the basic dynamic analysis. And sometimes you need to debug the tools that you are using, or you need to debug the results themselves, or something along those lines. Debugging is a concept that will show up frequently when you're using automation tools in general, or when you're creating scripts and things like that. And so this is part of the malware analysis module in the SOC Level 2 pathway of TryHackMe. And we have the intro, obviously, the need for advanced dynamic analysis, and this is the segue to get us into advanced dynamic analysis. The introduction to debugging, familiarization with a debugger, and debugging in practice, bypassing unwanted execution paths. And of course, the conclusion, we'll do some final thoughts, we'll do some review, and then you will be dismissed for the day. This room has been created by Myral Izafar. I constantly mispronounce that. I think this was actually the person who also made the last room that we were in. So obviously it's one of the staff members of TryHackMe, as you can see right here. And this is actually really cool because we can see all the different levels that are available to us over here. And I think I'm like around this area. Maybe might be even higher because I don't know what my individual points are, but for sure I'm up there. This is a developer that we have from Pakistan that works for TryHackMe. Their rank is 30,000. 301,000. So the lower this number is, the higher your rank is. The number of badges that they have, the number of completed rooms that they have, all of those things are kind of irrelevant because this person was good enough to actually get into the staff and start creating rooms for us to view. The created rooms that they've created, the macOS artifacts, forensics, advent of cyber, and very many other ones. So I don't know how to pronounce the username, but if you want to go check out the rest of the stuff that this person has created, Umairalizafar. I want to say Zafar is probably the last name. Ali sounds like the first name. And Umair, so it could be Umair Ali. That's probably the first name. And then Zafar is the last name. So Umair Ali Zafar. That's probably how I'm going to pronounce it. I don't know if I'm right. I don't know if I'm close. I might be right. I might be wrong. Might be kind of close. I feel like I got close that time. But anyways, that's it. That is the room developer for us. This is a subscriber only room, which means you do need a paid subscription to do this, to actually go and access the virtual machine and the content and everything that's inside of this room. However, I will try to make it as easy as possible for you to be able to launch this from your own computer. And the tools that we end up using, more often than not, the tools that we end up using are open source tools that you can just go ahead and find and download and use them in your own environment. So I will say, just be careful when you're dealing with malware analysis, especially dynamic malware analysis, because it requires you to run the malware in order for you to do the analysis. So that's something that you always do inside of a sandbox environment or a virtual machine type of environment. And if you don't know what that means or how to set that up, watch the video prior to this one. So episode 45, where we go into the dynamic analysis basics, and you can understand how to create a virtualized sandbox type of an environment so your actual virtual machine does not get affected. If you're serious about your CySec education and you want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into dynamic analysis debugging. All right, so in the last room, we discussed what it's like to actually launch malware, run the malware executable, and then analyze it as it executes. And malware authors are aware of the fact that we do this. People on the defensive side of security will be doing stuff like this. And for the most part, when you're doing static analysis, you're analyzing the source code and its various elements. When you're doing dynamic analysis, you're actually going to run the code. And so what malware authors will try to do is they'll try to evade your detection techniques. And to do those things, they'll do some kind of control over the execution of it. So for example, there are some API calls that certain malware will make to detect whether or not it's being run inside of a virtual machine. And if it is being run inside of a virtual machine, then it's not going to do what it's designed to do, so that it doesn't, get detected, right? So that's one of the key things that authors of malware try to point out to detect, to see if they're inside of a sandbox environment or if they're inside of a virtualized environment, so that they don't give away their cards. They don't give away what their actual tactics are, so we don't detect it and we don't prevent it from taking place. They only want the malware to run inside of an actual live environment. So that's one way that an author will try to figure out how to evade our detection techniques, right? So we're going to be talking about what these authors are going to do to control their malware execution better to achieve their desired results. And the objectives are to learn the evasion techniques that are used to evade basic dynamic analysis, an introduction to debuggers and how they can help us control the execution flow of malware, manipulating execution flow at runtime by changing registers or other parameters, and patching malware to force it to move past the evasion techniques and onto the actual malicious content. So we're essentially trying to debug the malware so that we can make it do what it was originally designed to do, even though it's inside of a virtualized or a sandbox environment. That's kind of what we want. We want to see what this malware's intentions are. The prerequisites are the two static analysis rooms. So basic and advanced static analysis, and of course the basic dynamic analysis video. And these should be the last like 3 videos, or the last 3 or 4 videos that we did in this specific series for malware detection or malware analysis. The very last video was the basic dynamic analysis. I think prior to that was advanced static analysis, and then there was like a static analysis exercise that we did, and then there was basic static analysis. So you'll definitely see these in the titles of the videos prior to this one, and you can find all of that inside of the SOC Level 2 playlist. It would be the most recent videos that are inside of the SOC Level 2 playlist. So there we go. I've already completed the prerequisite rooms, and I've already recorded all of those videos for your reference. So let's move on. Everything that is done inside of security detection, or really anything that's done inside of the criminal realm, is like a cat and mouse game, right? The mouse would be the person that's trying to evade the detection or evading the arrest, and then the cat would be the people that are trying to hunt them down. And that's basically what it's like inside of analyzing malware as well. So malware analysts, which is us, they devise new techniques. We devise new techniques to analyze the malware, while the malware author, which is the attacker, devises new techniques to evade our detection, right? So we're trying to hunt them down. They're trying to escape getting hunted. That's basically what it is. So what we're going to be talking about in this section is reviewing some of the techniques that hamper our efforts, or they throw a monkey wrench in our efforts to analyze malware using static or basic dynamic analysis. When they want to evade static analysis, and in static analysis videos, we actually learned the techniques that we can use to analyze malware without running it. And malware a lot of times tries to look like a legitimate piece of software to evade the eyes of a malware analyst. And because we're not executing it during static analysis, the main focus of static analysis is to obfuscate the true functionality of the program. And the main focus being the focus of the person who's creating their malware. So their main focus when they create their malware is to evade our static analysis by obfuscating, by disguising the true functionality of the program until we actually execute the program. And these are some of the common techniques. So changing the hash values, when we've learned that we can just check on the hash value of a file against some kind of a database, and then we'll see that, oh, okay, this actually is previously a malware. They just renamed the file. And so now we can detect that that hash value, the old hash value, the same hash value is the hash value of the malware. So what they would try to do is they would try to change the hash value by somehow editing the contents of the source code. And a lot of times this can be done by adding a simple comment to the source code, and now the hash value completely changes. So when the malware's hash changes, bypassing the hash-based detection mechanism is the goal. And hashes can change even if one bit of the malware is changed, unless we're talking about context-triggered piecewise hashes or fuzzy hashes. So just adding a NOP instruction, which is a non-operation instruction, which is, it could again be a comment, right? A comment has no operation value, and that it can actually change and defeat the hash-based detection techniques because the hash value now changes. Defeating antivirus signatures. So places like VirusTotal have a bunch of different antivirus vendors, and the antivirus signature and other signature-based detection often depends on the static patterns found inside of the malware, and the authors can change those patterns to try to evade those detection signatures from antivirus. And this is accomplished by general obfuscation of the malware code, and then obfuscation of the strings. So some of the strings, as you saw inside the basic analysis room, the static analysis rooms, and those videos, we see that the strings actually hold a lot of value for us if we can see them. So if they haven't been disguised or blocked out, we can actually see what the intentions of the malware are by just looking at some of the strings, because in those strings we have the API calls that the malware is trying to make. So when they obfuscate them, they disguise them, right? And then we can make sure that the authors that obfuscate the strings by decoding them at runtime, when we search for them, we may not find anything useful. So when it actually runs, it decodes those strings during the execution, the stuff that's been obfuscated. And the author might obfuscate important things like the URLs, the C2 command and control domains, and the API calls, any of those things, to avoid burning the infrastructure based on a single string search, which is a very basic search that we can do. Runtime loading of dynamic link libraries. We can identify what the malware imports while analyzing the PE headers, the portable executable headers. Malware authors often use Windows libraries the loaded libraries or loaded library EX to load a DLL at runtime, so they don't have to actually hard code it inside of their malware. They'll just call on those libraries to pull the functionalities of them so that their malware can still do what it needs to do inside of a Windows computer. When analyzing this malware statically, we might not see all the functions that it's linked to while analyzing the headers. So that's another thing that they can use to avoid static detection. And then there's packing and obfuscation. So packing is very popular because it's literally like packing the present. So think about all of the chunks of the malware that if you looked at it through static analysis, you could actually read line by line what it's doing. When they pack it, they usually pack it inside of a section that doesn't have a name, or the name is like, it might seem like a very common name. And so those names will, if it doesn't have a name, that's kind of like one of the loudest signs that, oh, this malware has been packed or this software has been packed. And if it has been packed, then it's a sign that it's malware. So when we look at a packed present, we can't say what we can't actually see what might be inside it unless we unpack the wrapper and take out the present. And packers pack the malware in a wrapper by writing code that decodes the malware at runtime. So when you look at it through static analysis, you can't see what's going on unless you actually run it. So we can execute the malware, unpack the code, and load the actual malicious code into the memory and then execute it. And that's one of the ways that we can get past the packed malware sections. So most of these techniques are suitable for hiding in plain sight, but they can be defeated when the malware is executed while performing dynamic analysis, which brings us to the evasion of dynamic analysis. And so dynamic analysis, again, as a reminder, is when we run it, right? When we run the malware. And there are a lot of different tools that we can use to run malware and to look at what happens before and after running the malware. And it helps us identify whether the malware runs in a controlled analysis environment or not. So identification of virtual machines is one of the key elements. So they might backfire nowadays since a lot of enterprise infrastructure is hosted on VMs. And one of the favorite malware authors has been to identify that the malware is running inside of a VM. So it checks the registry keys or device drivers associated with popular virtualization software like VMware or VirtualBox, and such as the single CPU or limited RAM. These are other resources that can hint that the malware is being run inside of a virtual machine. And then if it notices that, then it's going to do a different execution, and it's not going to actually do anything malicious so that we can fool the analyst. The timing of the attack, so the malware will actually try to time out automated analysis systems. So for example, when we execute it, it will try to sleep for a day using the Windows sleep library. After a few minutes, the automated analysis system will shut down, right? If there's no traces of malicious activity. Newer malware analysis systems can identify these attacks and try to mitigate them by shortening the time that the malware sleeps. However, malware can identify those mitigations by performing targeted timing checks to see if the time is being manipulated. And this can be done by noting the time of the execution and then comparing it with the current time after the execution of the sleep call. So this is actually very clever. It's basic. It's like a really, really basic piece, but it's very, very clever. So if they know that they're going to, the malware analyst is going to run the malware, and they're going to check to see what it's doing inside of the live environment. So they're going to stop the malware. So it's like you launch the malware, you run it, and then it doesn't do anything that it's supposed to do for a day, right? For a couple of days, let's say. It won't do anything that it's supposed to do, and it's under the assumption that we're going to run some kind of a analysis software, some kind of a dynamic analysis software, and then we're going to run the malware. And so if nothing happens during the next 5 to 10 to 15 minutes, during the next hour that we've ran the malware, if nothing happens, then we're going to be like, oh, okay, so this is not malware because we did dynamic analysis and nothing changed. And then you can kind of rest assured that it's fine, and then you release it into the production environment, and that's when you no longer are analyzing it, and then it can do whatever it needs to do after a few hours or a few days or whatever it is. So that's actually very clever, and it's not a complicated thing to do because you're just using the sleep library, the Windows sleep library, to pull it off. There are traces of user activity. So the malware will actually try to identify if there are traces of a user in the machine. So if very few traces are found, then the malware will decide that it is being executed inside a controlled system and take a different benign execution path. Traces of user activity can include no mouse or clipboard movement or keyboard movement, lack of browser history, no recently opened files, little system uptime, etc. So all of these things can hint that there's no actual user on this machine, and we're literally just using this machine to run the malware to see what it's going to do. It's very, very clever. These things are so freaking clever. Identification of analysis tools. So it can actually ask the Windows OS for a running process list using process 32, process 32 next, also process 32 first, process 32 next, or anything similar to that. And if popular monitoring tools are identified among the list of running processes, malware can take a benign execution path. So if procmon or procxp, so process monitor or process explorer, if either of those things are running, the malware can identify and switch to benign activities. Another way to identify this is by looking at the names of the different windows open inside of a system. So if the malware finds that olidbg or procmon is open in the windows, then it can switch to a different execution path, which is again very clever. These things are not complicated ways of avoiding detection. They're actually very simple ways of avoiding detection. It's just they're super creative and very clever. So by employing these, malware authors can make it difficult for malware analysts to perform static analysis or dynamic analysis. And malware analysts can use some tools and techniques to take greater control over the execution of the malware, helping them defeat evasion techniques. So malware sometimes checks the time before and after the execution of certain instructions to find out if it's being analyzed. What type of analysis technique is bypassed by this attack? Oh, they're asking for the analysis technique. So this would be, oh, my keyboard fell asleep again. I want to say this is dynamic analysis. So this would be basic, if I can type, dynamic analysis. Yeah, so they're checking to the time before and after the execution, and that would be done if we're talking about execution, that means that would be done inside of dynamic analysis. What's a popular technique used by malware authors to obfuscate malware code from static analysis and unwrap it at a certain time? And the keyword there is unwrap, so packing would be the answer to that. And cool, now we can move to debugging. The concept of debugging is usually associated with software programming and software developing, and it's basically what we do to fix a program and debug certain elements of the program that prevent the program from running like they're supposed to. And so the malware sample that's trying to evade detection or reverse engineering can also be considered a program that has a bug, right? So malware is malicious software, right? So it's a program basically, but it has malicious intentions. So if it's not doing what it's supposed to, technically that's considered a bug inside of that malicious software. It's not doing the thing that it was supposed to do. And so when we're looking at that malware as a reverse engineer, as an analyst, we need to debug it so that we can make it do what it's supposed to do. And interactive debugging becomes an essential part of advanced malware analysis. And the debugger tool is what provides us the control that's desired to monitor a running program more closely, looking at the changes in different registers, variables, memory regions, etc. And it also allows us to change the variable values to control the program's flow at runtime. For example, if it detects that it's being analyzed or whatever and it goes to sleep for a day, we can change that variable value to actually make it run immediately, right? Which again provides us more control over what it's supposed to do. So we have different types of debuggers. There's the source level debugger that works on the source code, as the name implies. Most software programmers will use source level debuggers while writing the code to check the code for bugs. And it's a high level debugger compared to the other two options that we have. When we use this, we see the local variables and their values. And this is, again, something that's actually done by software programmers. So a source code debugger will actually look at your source code and try to detect errors or issues inside of your source code and help you debug those before you move into the later stages in the development lifecycle. So These are actually used inside of regular development and inside of regular software programming. It's just that, again, malware is malicious software. So we're going to use it as well to analyze malware. There's the assembly level debugger. So when you have source code, you assemble it for various sections or blocks of code, and there's assembly languages and there's the assembly code itself. So when a program has been compiled, the source code is lost and it can't be recovered. So you have source code, you compile it, and now it looks very, very different. You can't find the source code. And in the case with malware analysis, literally the same thing. So we don't have the malware's source code, and then we have a compiled binary. So the assembly level debugger can help us debug compiled programs at the assembly level. And when we use this type of debugger, we often see the CPU register values and the debuggee's memory. And this is the most common type of debugger used for malware reverse engineering. And the debugger attaches to the program that has to be debugged and then executes it as per the analyst's desire. And then we have the kernel level debugger that are often a step lower than assembly level debuggers because they debug a program at the kernel level. So for this level of debugging, there are two systems that are actually required. One of them is the code running that's on the other system, one system is used for debugging, So one system is used for debugging the code running on the other system, and this is because the kernel stopped using a breakpoint. And then we can look at the next few sections to actually see what they're debugging, or how to debug the actual malware that we would be looking at. So how can we recover the pre-compilation code of a compiled binary for debugging purposes, right? Yes, or it's not how, my bad. So can we recover the pre-compilation code of a compiled binary for debugging? And the answer is no. So once the source code is gone, you no longer have access to the source code. Which type of debugger is used for debugging compiled binaries? And that is the assembly level. So this is it right here. So I'm just going to copy this whole thing. It's the assembly level debugger that is used for compiled binaries. And which debugger works at the lowest level among the discussed debuggers? And that would be the source level. So the source level debugger, I want to say that's the one that it's the lowest level, right? Work on the source code level, which would be, oh no, this is the highest level. So, okay, I see the direction is the reverse. So kernel level debugger would be the lowest level of debuggers that are available. And there we go. So let's talk about the actual debugger. And now we have a virtual machine that we're also going to launch here. Some of our options for debuggers would be the WinDBG, or I guess WinDBG, OllyDBG, IDA, Ghidra. We've actually used Ghidra previously. We're going to be using the X32DBG and X64DBG. I've already started the virtual machine. We can also connect to it via RDP. If you had access to TryHackMe as a paid member, you would be able to do this, but unfortunately, this is not available to people who are not paid members. And if you have a paid membership and you want to connect to it from your own machine, you would need to connect via OpenVPN to the TryHackMe servers, and then you can go ahead and connect to the machine itself. It's a Flare VM machine, which is not my favorite type of virtual machine, but this is actually designed for reverse engineering of malware, and it's the version of the malware analysis operating system that is native to Windows. My thoughts just stopped running for a second. I was like, why am I speaking so slow? Okay, so it includes all the tools required for analysis. To start, we can just go to Desktop, Tools, Debuggers, and then just open this thing up, and then we'll see something like this. And so to open a file, you can navigate to File Open, just like any other application. And this is what it will look like when you actually have an malware that's opened. We're currently seeing the CPU tab in the interface, and we have to use X32 for 32-bit samples, X64 for 64-bit samples. So we are currently on this tab, the CPU tab on the far left that you can see right here. And this is what we're seeing right here, right? So this is basically what the debugger itself looks like. So in the bottom left corner, the execution of the program is paused because a system breakpoint has been reached. So system breakpoint reached, that's what it says right here, and the status is paused right there. We can control whether to execute one instruction at a time or the whole program. And that's kind of the key feature of a debugger, or the key feature of debugging in general. When you run the program one step at a time, one instruction at a time, just to see which instruction gives you the problem, right? And that's kind of the overall concept behind debugging, because you want to just see at which step of the whole process the thing breaks down. So the screenshot, we can see that there's disassembly in the middle pane with the instruction pointer pointing to the next instruction executed if we start the program. So disassembly would be the middle pane, I'm assuming. And then it's right here. And if we click on it, it would move to this next line to keep running the program. In the right pane, we can see the registers and their values. We can note that the value in EIP is the address EIP is pointing to in the disassembly pane. So in the right hand, we can see right here, these are addresses, as you can see right here. So we can see that it's pointing to the address of it as if we were going there. Oh, I think this is what they're talking about right here, is the address that it's talking about, I believe. Yeah, so anyways, similarly on the bottom pane, we can see the stack view on the right side and the dump view on the left side. Okay, so I stood corrected. So this is the part that they're talking about when they say the address that is pointing to. And so 147F would be the address that's right here. And so we're trying to find 147F, which is right here, the F147. That's the address that is pointing to right here. So this is the address on the right-hand side register, and then this is where we're actually at right now. And then it would move to F150, not like the Ford truck. And the timer showing the time we spent debugging on the right corner, which is what we have right here. Time wasted debugging. Let's look at some of the other tabs. So the breakpoints shows the current status of the breakpoints. Breakpoints are points where the execution of the program is paused for us to analyze the registers and the memory. A breakpoint on a specific instruction can be enabled by clicking the dot in front of that instruction in the CPU tab, and then it'll take you into the breakpoint. And this is the breakpoint tab right here inside of the upper menu. The memory map shows the memory of the program, and so that's the next step that we see right here. We can also see the call stack of the program, which would be the next button right here. The threads running the program are shown in the threads tab, which is right here. And then any handles to files, processes, or other sources that the process creates are shown in the handles tab, which is what we can see by clicking right there. So in the next section, we're going to talk about how to utilize this information for analysis. So in which tab is the disassembly view shown in that? And that would be the CPU tab. If a process opens a file or a process, where can we see this information regarding the opened file or process? So any other handles to files or are shown in the handles tab that we can see right at the very end right there. All right, so let's talk about debugging in practice. For this section, we're actually going to run the software, and we're going to use the, CrackMe Arabel, or CrackMe a Rebel. There we go. Sometimes I have no idea what I'm reading. So crackmearebel.exe is the file that we're going to be debugging. So you click on open, and then you select the file itself. So we see the file that we need to open. It attaches itself to the process and pauses before it starts. We can see that a blank command window opens in the background. This shows that the process has started out but was stopped by the debugger. Then this window might not open with all the processes, so just keep that in mind, because not all processes might require a terminal to open up, a command line to open up. It'll depend on the user interface of the process. In the debugger window, we can see the familiar disassembly, the registers, the stack, and the other useful information, and the address might not always be shown as it is in the images as well. So what we can see right here, it may not always be shown necessarily. So in the debugger window, we have some features that can help us control the execution, and this is what we can see. So these are some of the things that can actually help us. So this would be restart, that would be stop, this would be the next step, this would be pause, and then this I think this will just continue to play. This would be paused. This will take us to the next breakpoint, I want to say. I wonder if they actually show it to us. So let's see. So it says among these from left to right, we have the feature for opening a new file, which is that piece right there, restarting the execution of the open file from the start, and stopping the execution. The arrow key will execute the program until it is stopped or paused by some other program. Please do not press this button because it might freeze the program. If you did, kindly restart the program by terminating it through the task manager. So that's a really good thing to keep in mind. When you click on this, it's just going to run. Okay, so just keep that in mind. This is not the one that we want to click. And usually you don't want to do that anyways. You just want to go step by step. Maybe you'll run it on the first run through. In this case, we're not going to do that on the first run through. We're just going to go step by step. So then we have the pause option. The last two options are for stepping into and stepping over. Okay, that makes sense. The rest of the options are also useful, but for the scope of this, we're not going to be talking about it. So now that we know how to control it, we are going to execute the program using the arrow key. Only press it once. When we do that, we can see in the bottom right corner that the program status changes to running, then paused. Along with the status, we have the reason for pausing the execution. It says int3 breakpoint TLS callback. This means that we have hit a TLS callback and the debugger was programmed to break execution on TLS callbacks. So that's the piece that has stopped it from running. So int3 breakpoint TLS callback at this particular location. And so they pressed the arrow button. This is the piece that they're talking about here. And it ran, and then it just automatically stopped because it's designed to stop, right? The debugger was programmed to break the execution as a TLS callback. In the debugger, we can set where to put automatic breakpoints on a program by going to the options preferences menu. And this is what the screenshot would look like when we choose different points as breakpoints. We can see that TLS callback and system TLS callbacks are checked. So we can see right here, TLS callback and system TLS callbacks in the settings options for the automatic breakpoints. So since these are often used as an anti-reverse engineering technique, we should be careful when navigating this TLS callback. Therefore, it will be prudent to single step each instruction while we are in the callback. We can do that by clicking the step into option that we discussed. After stepping into every instruction, we see the EIP moving to the next instruction, and the values in the registers and the stacks change accordingly. After stepping in a few instructions, we reach a conditional jump instruction. In the pane, we can see that the debugger tells us that the jump is not taken. The registers pane shows that the ZF is set, so the jump is not taken. So right here, we can see right here. And so the jump that's supposed to be taken, let's see, it says jump is not taken right here. So the jump to D116E is the jump that's supposed to be taken because we're technically here. And we're supposed to be taken into this jump, and it says that the jump was not taken to D116E, which is this kind of like grayed out portion that we can see right there. So that jump was not taken. So if we analyze both of those paths, we can see if the jump is taken, it goes to the address D116E, which pops the EBP and returns. On the contrary, the current execution path where the jump is not taken takes us to address D1000. So if the jump is not taken, going to D1000 is something that I'm actually very curious about. Where would we see that? Oh, it's actually right here. So it's literally in the center right here. That doesn't zoom in. So this would be the section where it actually shows us. So on this line, this is the location that it's supposed to be at. It's supposed to go to D116E, which would be this piece right here. But if this jump is not taken, then this line will take us to D1000 right here. So that is where we can actually see that element. We can see what is on this address by double clicking on the address. So let's go there. Alternatively, we can hover over the address to get a glimpse of the instructions. The below screenshot shows the code where we follow the address, and we can see a few API calls like create tool help 32 snapshot, load library, get proc address or process address. If we follow it down further, if we are sure that this function call was intended and we wanted to return after the function was executed, we could step over, which will bring us back after the function has been executed. However, the function seems too important to bypass straight away. So this is what we can see right here. So if we actually double click on it, it'll take us to D1000. This is the address that we see right here. And then from here, we can see what it would look like and what the rest of the calls would be if it continued down this specific path. And so in this particular case, I can't see all of the API calls that they're talking about unless they're in here, and they're not. So the API calls themselves, text-wise, are not here. It could be that the specific codes for them are here, because API calls do have numerical codes essentially that are assigned to them, so we can kind of decipher them like that. And just to make the script itself, or the software itself, a little bit more lightweight, they use codes instead of the full API call. So the libraries can be used to evade detection for legitimate purposes, but we don't know that for now. So we can move along this path, and if we see a red flag, we just restart it again using the restart execution option. Moving forward, we see that the library being loaded is suspend thread. So where do we see that? Oh, right here, suspend thread. Right here, suspend thread, kernel. Oh, interesting. So maybe if we go over here, maybe that's what it shows us here. I don't think so. I was trying to see maybe we actually have that going vertically for us over here as well, but that doesn't seem to be the case. It's actually interesting that it has it right here vertically going down. So kernel 32 DLL and suspend thread. That's so interesting that it looks like that. Okay, very cool. So the suspend thread API is being loaded. This TLS callback will suspend the thread based on detecting a running process like a debugger. The create tool help 32 snapshot helps identify running processes. This is why the program will freeze if we proceed with the execution. We can verify this hypothesis by moving forward along the code path. On verification, we find that it's an evasion code path. Therefore, we would like to bypass it. For that, we would like to take the jump in the start of the TLS callback. Let's start the execution and get to the TLS callback in the next piece. So the attached VM has a crack me in the directory. Now I actually have to run the software. So we are now going to come out of this fully zoomed in version that we have here, so I can actually go into that split screen and load our malware that we have over here. So the one that we're supposed to be loading, from what I understand, is which one? The CrackMe A Rebel is the one that we're supposed to be loading inside of our little tool, which is going to be the, what are we using? The X32DBG is the one that we're using. All right, so here's X32DBG. I opened it by just clicking on tools and then going inside of the debuggers inside of the tools folder, and then I opened up X32DBG. For the intensive purposes of our exercise, I'm just going to open this up in a full screen so that we can get to see it a little bit easier, and then I'll zoom back in on this so we can look at the content a little bit easier. And then what I'm going to do is I'm going to also open this up in a separate window on my other monitor so that I can look at the content and be able to navigate this whole thing without having to just go back and forth between the content. Okay, so now that we are here, the question says to obviously load the, what's the name of the file again? It is the A Rebel just by itself. So I'm going to do file and I'm going to do open, and we're going to look for A Rebel. So this should be inside of CrackMe A Rebel, and that's what it is. Desktop CrackMe A Rebel. That's all it is. So this is the executable right here, and then there's A Rebel 1. So we're going to just do A Rebel, and we're going to open this one right here. And there it is. It is now officially opened, and we can even kind of make this a little bit full screen to make that easier. So the first question says, in this CrackMe, there is a TLS callback with a conditional jump. Is this conditional jump taken? Write yes for yes or no for no. So what we're going to do is we're just going to press play. So system breakpoint reached is what it says at the bottom left right here, which is the pause status that we're in. So I'm going to press play and see if it's going to stop at that TLS callback. There we go. So TLS callback at CrackMe, Rebel, etc., etc. And so this is what it is right here at 1160. This is the TLS callback, and there's a jump that's supposed to be taken at 1160, and this would be the jump, I would say. And it says, is the TLS callback taken. So I would assume we press play again, right? And let's see if that actually does anything for us. Okay, so I had to use Task Manager to end it because it did freeze up on me, and then I restarted it, and I restarted the X32DBG, and then I uploaded the CrackMe A Rebel into it again, and then I pressed play again, and now we have reached the TLS callback one more time. So instead of pressing this button, I'm just going to do the next one where it says step into. So let's see if we'd actually do it. So there's step 1, there's step 2. TLS callback is going to be at the, where was it? It was at 11,160, right? So let's see if it's actually going to take this hop that it's supposed to take right here. So we will click on that and then click one more time, and it does not take the hop. It actually went into the portion and then it skipped past it completely. So it didn't take the hop. So the answer for this question right here would be a big fat N or no. Let's get to the actual question. So there we go. That's a no. Now the question is, what is the value of the 0 flag in the above mentioned conditional jump? So I need to restart it again. So I'm going to go over here and we're going to restart the whole thing, and I'll go from the very, very top. System breakpoint reached. Great. So now we're going to press play again, and it will read that TLS callback at CrackMe, etc., etc. So now it says, what is the value of the 0 flag in the above mentioned conditional jump? Well, we can see on the right hand pane on the far right are all of our E flags. So the 0 flag, I'm assuming, is this piece right here. Yeah, so it says Z flag, right? 0 flag, set if the result is 0, cleared otherwise. And the value of that is 1. So we can just go ahead and do that right here. And which API call in the mentioned sample is used for enumerating running processes? So now we need to find the API call for enumerating running processes. So there's a call that's being made right in the middle of the screen right here, get window thread process ID, and I wonder if that's it. So get window thread process ID. And that is not the answer. Okay, so it's used for enumerating running processes. This one retrieves the process ID. So I'm curious as to, was that get window thread process ID? Okay, I did spell it right. So at least that's not the issue. Okay, so let's see what it might actually be. Okay, so the other thing I can think of is to just kind of keep clicking forward to see if we can find anything. So we're going to get to the point where we had the hop. Let me kind of zoom in a little bit here so we can see it. So we're going to go to the point where the hop existed, which is right here, and then we're not going to obviously take that hop. So when we click it, it'll take us here. We have another call that's being made, create tool help 32 snapshot. So let's see what that does. So what does create tool help 32 snapshot do? And that takes a snapshot of the specified processes, the system processes, threads, modules, and heaps at a specific point in time. This allows us to examine the state of the system resources without interfering with their operation. Okay, so it looks at the processes. So let's see if that's actually the answer here. So create tool help 32 snapshot. Okay, that is it. Okay, so it is used for enumerating running processes, right? Because it takes a snapshot of the system's processes, as it says right here. From which Windows DLL is the API suspend thread being called? So from which Windows DLL? Now, from the screenshot that we have right here is the kernel 32 DLL. So that would kind of be my assumption that I would make. Create tool help 32 snapshot is also on this screen point, and so it is actually on our screen right here as well. So we do see suspend thread, that's right here, and then right before it we actually see the kernel 32 DLL, that's right there. So we can pretty confidently say kernel 32.dll would be that answer. Excellent. So that is the answer. Great. So now we can move on to bypassing unwanted execution paths. So this, it's been restarted. The execution has been restarted, brought back to the branch of code where we identified a detection invasion and the TLS callback breakpoint, which is this whole piece right here. So we are now back at the breakpoint TLS callback. Stepping a few instructions to reach the conditional jump, we get to the following point. So if we click on this piece right here, so stepping forward a few pieces, right, we get to the conditional jump right here. And so it does say that the jump is not taken. That's actually another way to find it right at the bottom right here inside of this little pane. So we see that the jump is not being taken at this point. In the previous task, we identified that the 0 flag was the reason for the jump not being taken. By double clicking ZF in the right pane, we can change the ZF to 0 because the 0 flag right here, right? So this is it right here. That was 1 originally. And so we can actually double click that and change it to 0. And now we can see that it's 0 and the jump is taken. This way we can bypass the unwanted execution path. If we step further or execute the program, it will take the jump and move to address D116E. What we did here is change the execution path on runtime by manipulating the registers. However, if we execute the sample again, it will again go to the evasion path unless we change the register. So if we wish to defang the binary, we will have to change it so that the evasion path is not an option if it is just run through double clicking. This is called patching. This way, after being defanged, we can perform dynamic analysis to reach our desired conclusion. So let's see how we can do that. We can right click on the instruction we want to edit to find the options related to that instruction. So we are still at the hop point right here, okay? So among these is the option to edit as seen in the following screenshot. So I can right click on this. I'm assuming that's where they right clicked on. And then you can go to binary and then you can go to edit, okay? So when we press edit, we see the following window. We have the ASCII, Unicode, UTF-8, and then you have the hexadecimal portion right here. And that's pretty much it. So in the lowermost pane, we see 7505 in hex, the opcode for conditional jump instruction. We can change this, change the JNE to JE. So where do I have that? It just says J right here. JNE to JE. This way the jump will be taken without us changing the 0 flag. Change the conditional jump to an unconditional jump. This way the jump will be always taken regardless of the condition. So among those two options, the second one is better as it gives us surety for the jump. However, there is one more way we can edit the binary, and that is by filling the call instruction at address D1169 with non-operating, and as discussed in a previous, these are instructions that actually don't do anything. The screenshot below shows that we can fill the instruction with NOP by right-clicking, going to binary, and fill with NOPs. So instead of doing an edit, we can actually do fill with NOPs, and then it will take that piece, which is which one? Oh, it's the step, right? It's the step that is supposed to be taken because they're on this line. So they're not on the one with D116E. They're on the other one. So the instruction at D1169 with NOPs, which is this piece right here. So those have been filled with NOPs. Once done, we can go to File, Patch File to write this file to a disk, and we can see something like this, that we can see a rebel, etc. And those are the patches. And then by clicking patch file in this window, the debugger, so this is the patch file button, the debugger will ask us whether to save the patch file. This is how it will look once we have filled it with NOPs. Notice that a single instruction has been replaced with 5 NOP instructions. This is because the size of the single instruction was equal to 5 NOP instructions. This is more visible in the above screenshot, which is what we can actually see right here. Where each NOP is mapped against its equal size opcode, and then we'll actually see it right here. So this would be the patched version of it, where we actually see that instead of that single line, now we actually have 5 lines that say NOP. We can see that CrackMe A Rebel 1 is patched, and this is how the same file looks when patched and saved. So that's what that one was. So now we've used the debugger to patch a file evading debuggers. What is it called when a binary's assembly code is permanently altered to get the desired execution path? And that is called patching. And that's the only answer that we actually had to do in this thing, so I didn't even need to go do that whole piece. But technically we can just try it. So I'm going to restart again from the very top, And then this is the portion right here. So actually now I'm going to press play so that we can get to the TLS, and there we go. So this is the portion right here, and this is the one that they were editing. This is the one that they were just going to replace with NOPs. And so if I do that, then it should say, okay, is this what you want to do? And I'm just going to do that. And then there you go. Now it's been replaced with NOPs. And now technically, I guess if we actually ran it, it would probably, or we would need to save it, right? So this is the debugger. That's actually basically all it's doing. So what we would need to do is save it and then run it using a dynamic analysis technique. And then we would actually see what it's going to do as it's intended to do, right? So that was kind of the whole piece of this. So if I click this, it's going to say it's still running. It's going to be terminated. Do you really want to exit? I'm going to say yes. I'm going to close the debugger, and we're going to close this window. And I believe we are officially done. So are there any? No. Yeah, we're pretty much done. So this was cool for me because I have not done debugging specifically on malware, but I have done debugging on Python scripts because I write a lot of Python scripts for our community, for Hackaholics Anonymous. So if you are not a member, go check that out. But for the most part, I have not done any debugging on malware specifically. And that was actually very cool, that X32DBG, which is designed for debugging malware specifically. Is the one that I think it's open source, and it is something that you can just easily get access to, and it's a very fun little tool, or depending on your definition of fun, I'll say that, but it is a cool little tool, and it is something that thankfully we actually got a chance to kind of get an introduction to, and we're going to be doing more of this stuff when we go along to advanced dynamic analysis, which is going to be the next room after this one. So we've talked about the common techniques to evade static and basic dynamic analysis, the use of debuggers, using debuggers for changing the environment at runtime, and using debuggers to patch malware. And this is obviously not it. So we're going to go to anti-reverse engineering to learn more about these things. And I think that's going to be the next step inside of our SOC level 2, malware analysis. So this should be the next step inside of our SOC level 2 malware analysis, because we just did advanced or basic dynamic analysis. We've also done dynamic analysis debugging, and anti-reverse engineering is going to be the next element. And then we have MalDoc static analysis, which is an actual exercise, like a practical exercise that we're going to use to wrap up the malware analysis module. And by doing that, by actually wrapping up the malware analysis module, we have officially wrapped up the SOC level 2 pathway of TryHackMe. So we have literally 2 more videos left to finish SOC level 2 in TryHackMe, which is very cool. I'm very excited. This is a big point for us. So thank you for hanging out, and thank you for going through this process with me. I really hope that this is actually serving useful to you. And hopefully you were able to kind of follow along with me and learn some cool things from this video. If you did get value from this video, and if you've gotten any kind of value from this channel, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel, especially as we wrap up SOC level 2. And then we're gonna keep launching Pentest Plus videos every single Friday. I give away Python automations, obviously, and I do Python automation videos that will be coming out. What else do we have? We have the CYSA Plus that's going to be coming out. We have AI for cybersecurity that's going to be coming out, how to train AI to do your work for you, and how to use AI, how to manipulate AI to do a lot of crazy things, which is actually very, very cool. That's going to be happening. There's a lot of crazy stuff that's on the horizon. There's a lot of amazing content as we advance further into this world. I'm super excited about it. So I don't know about you, but I geek out and I nerd out over these kinds of things. So very, very excited about it. And I think you will also get a lot of value out of it. So if you have any questions on the video that we did today, or if you have any questions in general, feel free to drop it in the comment section below. There is, of course, the Discord chats that are available. So even if you join as a cyber supporter in Hackaholics Anonymous, it's $5. You get lifetime access to the Discord chats. And then at the very least, you'll be inside of the community. And then if you have any questions or anything like that, you can drop it in the community. And then either I will answer or some of our more advanced members will answer. And that's kind of what my goal is to build this thing out and get a really solid community available for people who are interested in cybersecurity, ethical hacking, pen testing, so on and so forth. So at the very least, drop a comment in the comment section below. But if you want, I would highly recommend you check out Hackaholics Anonymous and see which tier of membership is more relevant to you. And then based on that, you can go ahead and join Hackaholics Anonymous as well. So if nothing else, like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. And of course, drop a comment in the comment section below. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server, as well as early access to content, and the agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@hankhackshackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comments section. And that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker / protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I'll see you in the next video later. In episode 47 of the SOC Level 2 training series, we are going to go through the anti-reverse engineering room, which is a part of the malware analysis module inside of the SOC Level 2 pathway of TryHackMe. And this is the second to last video that is going to be, or at least for now, that will be inside of the SOC Level 2 playlist, because we are just about to wrap up malware analysis, and we're essentially going to be done after we do that. So I'm very, very excited about this. Reverse engineering is one of those things that we do as security professionals, as security engineers, security analysts, when we go through looking at malware and trying to reverse engineer, trying to backtrack and kind of see what the malware is supposed to do. And then there is anti-reverse engineering, which is what the hacker does, what the attacker does to prevent us from being able to reverse engineer, right? From being able to see the things that they're intending for their malware to do. So what they are going to do is anti-reverse engineering techniques, and then that's the malware author's job, and our job is to notice this and then get around this. And so the concept here, or the overview, excuse me, is we have the intro, obviously, anti-debugging, and so we did debugging in the last video, and we're going to talk about anti-debugging using suspend thread, the VM detection, virtual machine detection, and then virtual machine detection by checking the temperature, packers, and identifying and unpacking. And then we have the conclusion, and we're going to wrap it up for this video, and you will be dismissed. So very, very excited about this specific one. Our creator for this is a rebel. That is the user or the developer that developed this room for us to be able to use. This is somebody on the staff of TryHackMe. Obviously, they're based out of the UK. They're based out of Great Britain, the United Kingdom. There we go. And so they've done a lot of great stuff, and their rooms that they have created is also pretty extensive. So they've created a lot of rooms that we can use. So shout out to a rebel from TryHackMe. Very, very grateful for you doing everything that you've done for us so that we can learn and develop our skill sets. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@hankhackshackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into anti-reverse engineering. Our job as security professionals, and a lot of times, is going to be reverse engineering, which is the process of studying a technology product or a software or hardware, learning how it works, and extracting the functionality or design information. Basically, when you do engineering is when you build something. Reverse engineering is trying to see how that thing actually works by kind of breaking it down into its parts, right? And so the same thing applies to malware. When we do reverse engineering against malware, we're trying to see how the malware was engineered, how it works. And malware authors, the people who created these things, are trying everything they possibly can to prevent us from figuring out their tricks and figuring out what their malware is trying to do, so on and so forth. So they deploy anti-reverse engineering tactics as they developed their malware. And that's the whole concept behind this specific video, is what is it that they do, what are the tactics that they do for anti-reverse engineering, and then how can we bypass those tactics so that we can actually figure out what the malware is trying to do. And that's the whole goal here. And this is the closest thing that we will get to advanced dynamic analysis, because this is technically a part of dynamic analysis of malware. So in this particular room, in this video, we're going to go through the various reverse engineering techniques that malware uses, and this includes virtual machine detection. So if a virtual machine is something that we would do, or what we would use as an isolated environment when we run the malware, so that it doesn't infect the rest of our computer. It only infects the virtual machine, and then we can just crash the virtual machine, right? And then we don't have to worry about the rest of our computer, and then we can just restart the virtual machine to try to analyze a different piece of malware. So virtual machine counts as a sandbox type of an environment, and that is something that a malware author is trying to detect. So they will try to detect whether or not their malware is being run inside of a sandbox or inside of a virtual machine. And if it is being run inside of the virtual machine, then it shouldn't do its malicious activities, because that would give us a clue as to what it is they're trying to do. Another way to do this is to obfuscate using packers. And we'll talk about this when we actually go into it, but packers essentially, or packing malware, is essentially disguising the various elements of the malware so that we can't see it with the naked eye when we do static analysis, and therefore we don't know what it's actually intending to do. And then there's debugging, which is what we did in the last video, where we ran through the malware activity step by step, literally line by line inside of the code. And we were like, oh, okay, this line does this and this line does this. And so that's called the debugging process. And they do this inside of software development in general. When you debug something, you go through the software line by line to see what each element of the code does. And then from there, if there is a bug inside of the software, then you can find out exactly what line that bug starts at and what the problem is, so you can fix it. So there is anti-debugging that is done for malware, because they don't want us to debug their malware. Malware is technically malicious software, so we can run the same type of strategies to debug malware, and an anti-debugging means that they don't want us to be able to do that. So the objectives are to learn why malware authors use anti-reverse engineering techniques, learn about the different anti-reverse engineering techniques, learn the techniques on how to circumvent anti-reverse engineering using various tools, and how anti-reverse engineering techniques are implemented by reading the source code. It's good to know basic and advanced dynamic analysis. So these are the things that we've done already inside of this module. So the last series of videos, you should already see, the debugger, reading assembly code, patching, all of those things have been covered in the last series of videos inside malware analysis. Basic knowledge of assembly, what it actually is, what it does, what it means, and the understanding of C programming concepts like conditions, like if-else statements, and the flow of a program. You don't need to know advanced C programming, it's just understanding what it is. And my recommendation is, if you don't know C programming code, one of the things that you can leverage is an AI tool. So Gemini, Meta AI, ChatGPT, Claude AI, whatever your favorite AI tool is, you can use one of those tools to go ahead and analyze code, and then it'll tell you, okay, this code does this, or this is what it's trying to do. So those are some of the tools and some of the prerequisites. And then of course we have a virtual machine that has been assigned to us that I've already started. And this virtual machine is a Flare VM. So Flare VM is a Windows-based operating system that is designed for malware analysis specifically. It comes pre-installed with a bunch of different tools that you can use to analyze malware either statically or dynamically. Statically means without running the malware. Dynamically means you actually run the malware and then you try to see what it's doing. So now that we have gotten all of that out of the way, let us go ahead and look at anti-debugging. As I mentioned already, debugging is essentially the concept of looking at software line by line to try to see which line of code is where the bug is, right? So if a software has a bug, that means it's not running properly. And if that is indeed the case, then we're trying to find out exactly what part of the source code that bug exists in. And so the same thing applies to malware. So when we're analyzing malware, we're trying to essentially find out where that bug is, especially if the malware is not doing what it should be doing. Meaning, if it's detecting that we're in a virtual machine, it's going to stop running the way that it should be running, and it's not going to do all of the malicious activities that it was designed to do, which means if it's not doing what it was designed to do, it has a bug in it. So we need to debug it. Now, that whole process is what we do as security engineers. Now, the malware author, the person who created the malware, is going to deploy anti-debugging techniques so that we can't debug their malware. Now, these are some of the commonly used debuggers, and we use the x64DBG in the last video. There's OllyDBG, there's IdaPro, and then of course there's Ghidra, and then we also have used Ghidra before as well. And the techniques are as such. So checking for the presence of a debugger. So the malware code looks for processes or files associated with debugging tools or hardware-based techniques like detecting hardware breakpoints. For example, a common anti-debugging technique uses the API function is debugger present to check to see if a debugger is running. And then that basically is what we did in advanced dynamic analysis. And so if the debugger is present, then the malware isn't going to do what it's supposed to do. Tampering with the debug register. So malware may try to modify or corrupt the debug logs, which debuggers use to control the execution of the code, which prevents the debugger from functioning correctly. So if the debugger is present, one of the ways that the malware can mess with it is to just modify the debug logs so that the debugger can't actually do what it's supposed to do. And then using self-modifying code, which is sophisticated, where the malware modifies itself while it's running, making it difficult for a debugger to follow the code flow. So those are very, very interesting series of tactics. This last one specifically because it's like AI, basically. The malware is looking at conditional statements, right? So if a debugger is running, do this series of things instead of you doing what the other things are supposed to do, and it modifies itself while it's actually running, which is kind of crazy. So we're going to look at anti-debugging techniques in the next session. What is the name of the Windows API function used in common anti-debugging techniques? And that was the one that said, is debugger present? So let me make sure my keyboard wakes up. So is debugger present is the name of the Windows API function. So now let's look at anti-debugging using suspend thread, which we actually touched on in the last video. Suspend thread is a Windows API function that's actually legitimate. It's a real function that's used to pause the execution of a thread in a running process. And you, again, can use this legitimately, right? But it's also something that can be used by malware to suspend any threads attempting to debug or analyze it. And that's one of the big things that it can do to just make the debugger not work, right? So if you can just stop the debugger from working, what better way is there to actually do this to get past the debugger, right? So the program that does this specific technique exists in our Flare VM. So you can run the 32DBG tool, which then you can run the opening the suspend thread executable, and then press F9 twice to continue the execution of the malware. And then x64DBG will now become unresponsive, and you can confirm the suspended process by opening the task manager, and then you can see that the process's status would be suspended. So we can actually run that, and then we can completely terminate it by doing end task to terminate the x64DBG. The code snippet below shows how the malware works under the hood. So this is our code snippet, and this is, I believe, the C language code. So I'm not that great at C, so I'm not going to even pretend to understand what this is. So what I'm going to do is I'm just going to copy this whole thing, because this is actually a very large piece of code. So I'm going to copy this whole thing, and I'm going to ask Gemini to give us a quick little high-level description of what it's supposed to do. Okay, so first there's a global variable, the D word, this element right here at the very, very beginning. This global variable is used to store the process ID of a detected debugger process, and it's initialized to -1 to indicate no debugger has been found yet. So that's what it starts at, and then if it is found, then this value changes. So our D word is going to be the global variable. And then we have the enumerate windows processes, the callback function. And this is a callback that will be called by enum windows for each top level window on the desktop. Its job is to check to see if any of these windows belong to a process with a title that suggests it's a debugger. And then it will get the process ID, so it gets the process ID associated with the current window. And if that process ID, so it'll check to see if the window process or the window belongs to a specific process ID that enum windows was called, which in this case will be the PID of the potential debugger. And then it will check the title of the windows as well. So get window text length and get window text W, all of these elements right here, this line of code right here, retrieves the title of the window. W suffix indicates wide character Unicode functions. If, so this is our first conditional right here. So the core detection mechanism, it checks if the window title contains the substring DBG in it or debugger in it, case sensitive due to the WCS-STR. This is a very common, albeit easily passable way to detect debuggers like OllyDBG, WinDBG, etc., which have a debugger or DBG in their actual window titles and their names. If the match is found, the process ID is set to the PID of the detected debugger, and false is returned, which stops the enumeration of windows. MalLoc, mallocation, dynamically allocates memory for the window title. It's crucial to remember that free this memory to prevent leaks, which is not done in specific function. This is a potential memory leak. Is the debugger process function takes the process ID as an input and use the enum windows to iterate through all top level windows, calling enum windows process for each one. And then this is the Windows API call that initiates the window enumeration, passing the process ID as a parameter to the callback. And then this return function right here, it checks if the debugger process ID that we had, which would have been set by enum windows processes, if the debugger window was found for that PID, it matches the input of DW process ID. So this is going to check to see if that global variable matches the input variable. Suspend debugger thread function. So the purpose is to anti-debug, right? So it enumerates all the running threads and attempts to suspend any thread belonging to a detected debugger process. So this is where that suspend thread element comes in, and it creates a snapshot of all threads running on the system, then iterates through all those threads inside of the snapshot, opens a handle to each thread with permissions to query its information and suspend or resume it. It gets the PID of the process to which the current thread belongs to, calls the previously defined isDebugger process function to check if the process owning the current thread is a detected debugger, prints a message if the debugger is found, so debugger found with PID, etc., suspending. And then this is the critical anti-debugging function, this piece right here, the D word that we went and looked at the very beginning, the global variable. If a debugger is found, it attempts to suspend the debugger's thread. Suspending a debugger's main thread can cause it to hang, become unresponsive, or crash, making it difficult for an analyst to continue debugging the malware. Used to print the last error, closes the handle to prevent, and then the main function calls the anti-debugging function, and basically just kind of runs the overall debugger, right? So this is a full script that has multiple functions inside of it. It'll enumerate the Windows processes. It'll look to see if the debugger process, if it has the word debugger or DBG or anything in it, or if the PID matches anything. And then if it does, it'll actually suspend that thread. And then finally, just like many other script syntaxes or many other script processes formats, we always create a main function at the very end that will just call on all of the previous functions. So that is what this chunk of code does. And so now we have a description right here. So if you don't want to be bothered with reading the source code, here's the short explanation, which is basically what we just actually looked at. So it can effectively stop an analysis from continuing the investigation. So fortunately, we have a way of dealing with this. Patching is one of the most critical skills required. And this is basically when we patch the software, right? So when you patch a software, you're fixing its debug, or if you're fixing its bug, excuse me. So we've already talked about this. So if there's an element of the source code that detects us using a debugger and then it stops running, we need to patch that element so that we can actually run the software. We can run the malware. So we want to patch the function suspend thread so that the debugger won't get suspended. And we open this by double clicking on the icon, press F3 to show the open dialog window, look for the sample file called suspend thread, etc. Press the F9 key to jump execution to the entry point as shown below. Right click anywhere on the main screen, highlight search for current module, then search intermodular calls. On the search field at the bottom, type suspend thread. This will filter the list and then it'll show us the element itself, the suspend thread portion. And then now we're at the part of the code calls the suspend thread API. To skip the function, right click on the suspend thread line and select binary filled with non-operating protocols or non-operating procedures. Don't change anything, just press OK. And so what happens is that it'll replace that chunk with NOP elements that will stop it from running. So previously, the piece that was suspending a thread will now be replaced with non-operational chunks. And then this is what happens, and press 9 to continue execution, and we'll see that the debugger continues at the very end without crashing our debugger. While the console prints out the lines debugger found with PID suspending, it's not actually doing anything because we've skipped the function that does the suspending. And so this is great. However, if you try debugging again, you'll discover that it will start crashing again because our patches are reset and now gone. To avoid reapplying patches, we can export and import the patches for future use. So stop the debugging by pressing Alt F2, go through the patching steps in the previous section, but do not do the last step. So once the patches that you want are in place, you go to the top bar, click View Patch File to open the patch dialog window. The list of the patches will appear in the right panel, and then we can see that there are 6 entries to replace this one element, and this refers to the 6 memory locations, the NOPs. We're going to click on Export and then basically save the file, then stop the debugger and debug the file again. Because debugging has restarted, the previous patches have now been erased. We can restore it by importing the file that we made. So go to the View Patch File. By this time, press the Import button, and then you'll be able to import the previous patch, and then press F9 to continue it. So exporting and importing are very helpful in reverse engineering, as it allows to save your work, to save the hassle of doing them all over again. And then we're going to look at it in the next section where we can do another reverse engineering technique and other ways to circumvent them. So what is the Windows API function that enumerates windows on the screen so that the malware can check the window name? And that was the API function that we had right here. I think it's called enum windows. Its job is to check if any of these windows belong to a process that the process title that suggests it's a debugger. Yeah, so it's enum windows that has that element. What is the hex value of a non-operational instruction, which is that 90 that we see right here? So if we go up here, right here, you see that these are all NOPs, so the hex value is 90. And if we also look at the source code that was changed right here, you can also see the hex values are all 90. So that would be the value. And what is the instruction found at memory location 004011CB? So let me see if it exists over here in our screenshots. If not, we actually have to run the whole thing. So CB, oh, it's right here. Literally, the instruction is add ESP, 8. That's the memory instruction. So we actually have that. So I was able to answer all of these things, ESP, 8. I was able to get all of these answers by looking at the screenshots. But basically, if you wanted to run this, if you have access to this virtual machine, because it is subscriber only for the TryHackMe users, if you wanted to run this, you would basically just do everything that we just did, right? So the very first time was to just open the debug tool, open the suspend thread executable, and then F9 twice to continue the execution of it. And then you'll see that it's suspended. You'll see that the debugger tool is suspended because the malware detected it, therefore it stopped it. And this is the code that we just saw that would actually do those things. And it calls enum windows to detect the DBG in the title, because that's literally what it's called, right? It has DBG inside the title. And so because of that, it does what it's supposed to do. So what we're going to do is what we would do is to patch it. So then you would open the debugger again, open the suspend thread executable again, and run it. And it'll jump to the execution entry point as we just see right here. And so you can see it calls suspend thread, right? So that's the element that you run, but you don't run it twice, right? So this is the piece right here where it says press F9 twice to continue the execution. And in this particular case, you're only going to press it once because we want to jump to the location that the suspend thread call is made. And so this is the element where we're going to replace it, right? So you will right click, anywhere on the main screen, highlight search for current module, then select intermodular calls, and then type suspend thread to actually find it, which is this piece right here. And then we'll be able to find that call function that actually is calling on the suspend thread. And then we can now be on that actual element that has the call to the suspend thread API. And then so what we're going to do is right click on it. So we're going to right click essentially on that line right there, right? Or right click on this element right here. And then you're going to go to binary filled with NOPs, don't change anything, etc. So why don't I actually do this? Instead of just doing the explanation, I'm just going to run it. And then instead of doing F9 twice, I'm only going to click F9 once. So we'll do file. We're going to open the suspend thread executable, and then we're going to run it. So let's go to the desktop. We're going to open up malware, and then we're going to add the suspend thread executable. And there it is. So now we're here. So now we can just do F9 is basically another way of saying we'll press this run button right here, and then you can also press the step into to get to the next element. So if I press run, it'll run, and then it immediately, that's the equivalent of doing F9. So this is the button that I ran. Because I'm using a virtual machine, I feel like F9 might not work, so I just pressed this run button. So it'll go to the first spot right here, this piece where you actually see suspend thread. And this is the piece that we're trying to fill with the NOPs, right? So click on this, and automatically I can just do binary fill with NOPs, and then that's it. So it's kind of, they gave us a few extra steps right here, but I can just right click on that and fill with NOPs, right? And then so what would happen ideally is that the next element should be replaced with NOPs. Now we can see right here that 4011B1 is not the piece that I'm on. So I think I shouldn't be filling that piece with NOP. So maybe I should be actually following the instructions that they're talking about. So it says search for current module and then select intermodular. So we'll right click, and then we will do search for, so this is at the bottom right here, and then we're going to do current module, and then we're going to do intermodular calls. So this is where it is, right? So search for current module, intermodular calls. We're going to do that. And then we get a chance to search through these elements right here. On the search field at the bottom, which is right here, we're going to type suspend thread. And there it is. So that, not threat, thread. There you go. So there it is. So now I have the suspend thread that's pulled up. And then from here, we can go ahead and right click on this function and then do the binary fill in. Or actually, no, it says skip this, right click on it, select binary fill with whatever. So I mean, I think I see it, but it says, so maybe I need to double click on this and it'll take me to that element. Okay, there you go. Okay, there you go. Now we're at the place that if I replace it, it'll actually show me the same thing. 411B1 would be the next step right here. And I see right here, 4011B1. So this is actually the element that we want to fill with NOPs. So we'll do binary, fill with NOPs, and then click OK. And now it'll fill that with these non-operating elements, right? So boom, now we have it, 411AB to 411B0, so 411, there you go, AB2411B0, it's all been filled in, and now we have the next step, etc. So now it says to continue the execution, so I'm gonna press continue and continue again, right? So run it, show it to me, buddy. Let's see how it works. Do we have it in the background? Oh, there you go, it's actually running. So it's running in the background, debugger found with da-da-da, but it's not actually suspending anything, because if I go to the task manager, X32 right here is not suspended, right? So it's actually detecting what it's supposed to do. And then the exporting element of it was just something you can go review those things. I'm not going to export the patches because we're going to move on to a different element. But that was it. That was essentially us running through the instructions just so we can kind of see how the whole thing plays out. And you just saw that. So now we can move on to the next part, which is the virtual machine detection. Okay, so in case you don't know what a virtual machine is, it's basically a computer that you can run virtually, right? So it's a software version of the computer itself. You can run it on top of your actual current host, meaning you can have used something like VMware, or you can have something like VirtualBox, right? And then you can get an ISO image, which is basically the image of the operating system that you can then run from your current computer, and it will act as a separate computer on top of your actual computer. So it's essentially another computer that's running. And so when you open up the malware inside of the virtual machine, it's not going to infect the rest of your computer because it's running in its own isolated environment. This is also known as a sandbox. So when we do this, this is the approach, this is the strategy to try to have an isolated environment within which we can actually run the malware so it doesn't affect the rest of the stuff. Now, technically, what I'm on right here, this piece right here, this is also a virtual machine that is now being hosted on my browser, and it is originally installed on the TryHackMe servers, and so I'm just launching that instance from TryHackMe, and now I have this virtual machine running, and so I can run a malware on this virtual machine and it won't affect my actual computer. So that's kind of the one of the big draws of virtual machines, especially when we're talking about malware analysis, dynamic malware analysis, right? So when malware identifies that it's running inside of a virtual machine, it can respond differently, meaning it can choose not to do its malicious activity. So it can execute only a minimal subset of its original functionality. It can self-destruct and delete itself, or overwrite parts of its code. It can cause damage to the system by deleting or encrypting files, meaning the virtual machine itself, or just not run, right? So this is kind of probably the most clever thing that can happen, because any of these other things, either this one or this one, these are the best things that the malware can do, because if it self-destructs, then we're like, oh, it's definitely malware. If it causes damage to the system, we're like, oh, it's definitely malware. So these are the two things that if you're a malware author, you kind of want to do those, because you don't want to give away that you had the malware. Because if I am aware, if you self-destruct or if you cause damage to my virtual machine, then I'm like, oh, so definitely it was malware. Now we need to take even a more careful approach to everything that we're doing. But if it doesn't run, or if it's doing a basic subset of its functionality, then we're like, oh, maybe it isn't malware. We got to like dig a little bit deeper, but we still don't have our guards all the way up. I mean, we should at the very beginning of this because we suspect that it's malware, but you know, you're not as on high alert as if the self-destruction takes place or there's damage taking place. So these are some of the techniques that it can run, the malware can run to see if it's inside of a virtual machine. So it'll check running processes, very similar to what we did for the anti-debugger, right? So VMs have easily identifiable processes. So VMware, for example, runs a process called VM tools, and VirtualBox has VBox service. And the malware can use enum process, the way that we did, to call all the processes that are running on the machine and then look for those names, right? It can check installed software. So it can look at the Windows registry, the software Microsoft Windows current version uninstall registry key, and then from here it can check the installed programs like debuggers, decompilers, forensic tools, etc. Network fingerprinting. It can look for specific MAC and network addresses unique to virtual machines. For example, VMs auto-generate MAC addresses that start with any of these number sets right here. So these numbers are unique and are specifically designed to a VM vendor called the organizationally unique identifier. So if the MAC address has any of these things as the starting point, you can rest assured that it's a virtual machine. Checking the machine resources, so we can look at a machine's resources like the RAM and the CPU utilization, and a machine with RAM amounting to less than 8 gigabytes indicates a virtual machine, because pretty much all laptops and computers these days especially start at a bare minimum of 8 gigabytes. I think now it's like probably even 16 gigabytes is like the bare minimum. So all of those things indicate it's a virtual machine, as they are typically not assigned to a significant amount. Like a virtual machine typically gets, let's say, 4 gigabytes of RAM or something like that. And then detecting peripherals. So the malware can check for connected printers, because it's rarely configured properly on VMs and sometimes not even configured at all, which is really not that big of a deal because I don't have a printer configured on my laptop right now. So that doesn't necessarily mean I'm on a virtual machine. Checking for domain membership. So corporate networks are usually target for malware, so we can determine whether or not we're on a corporate network by checking if the current machine is part of an Active Directory domain. And it can quickly be done by using logon server or computer name as an API call to get the environment variables. Then we can look at the timing of the base account. So it can measure the time that it takes to execute specific instructions or access particular machine resources. So some instructions can be faster on a physical machine compared to a virtual machine. So these are not foolproof techniques, but it's not uncommon to see malware using a combination of one or more of these things just to verify whether or not it's actually on a virtual machine. And to prevent malware from using some of these techniques, we can apply several changes to the system that will remove VM-related artifacts, like making the virtual machine look less like a virtual machine. Meaning we can remove or modify registry entries that the malware checks for installed programs, to hide the debugger, change the MAC addresses, configure the VM to appear connected to a printer. And you can see how tedious that can become. So it can be something that we can easily do, for example, using a script like VMware Cloak or VBox Cloak to help automate that process. And even in that situation, if all the techniques are addressed, minor architectural checks can still be made by the malware, as we'll see, that will determine whether or not we're actually running VM or not. So what's the name of the identifiable process used by malware to check if the machine is running inside a virtual box? And we have this at the top right here, which is the identifiable malware. It's the VBox service. There you go. So if it's running inside VirtualBox, it's most likely going to check for that process. What is the OUI automatically assigned specifically to VMware? So let's see if we can actually find the OUI to VMware. And it says MAC addresses da-da-da, for example, VMs da-da-da-da. Okay, so what is the OUI for VMware? Let's see if we can find that. A simple Google query will show us that this is the OUI that's been assigned to VMware. So let's go ahead and get that. And I wonder if it's actually a list, it's on the list that we had above. The 5056 is on this list. Yeah, this is actually the last one that's on this list. So that's the one assigned to VMware. Using Task Manager, what process indicates that the machine for this room is an Amazon EC2 virtual machine? So we're going to open Task Manager back up, and then we want to see what is the one. So I think it's Amazon SSM agent. That would be the background process most likely that will indicate that we're running on a virtual machine. Let's see if there's anything else that might be useful to us, but I think it's that first one, the Amazon SSM. Yeah, so I think it's the Amazon SSM agent.exe. So let me see if that is indeed the case. Amazon -ssm-agent.exe. That is it. There you go. So that indicates that we are running an Amazon EC2 virtual machine. So now that we know that these are some of the techniques for VM detection, we need to look at a way that we can kind of bypass this. A version of checking for a VM or virtual machine is by looking at the temperature of the machine itself. So there's something called the Win32 temperature probe, and it's a WMI class that contains real-time temperature readings through the SM BIOS, the system management BIOS data structure. In a virtualized environment, the value will return not supported because typically virtual machines don't have that inside of the hardware, the basic input-output system. There are some other machines also that may return not supported because it doesn't necessarily exist on every single machine's SM BIOS feature. So just keep that part in mind. It doesn't necessarily mean that this thing is an actual virtual machine if it says not supported, okay? But there is a version of this that we can just test on our machine, which is basically the VM detection executable. I'm not going to run it because it's not going to do anything. We're going to open it in the debugger because we want to fix it and we want to patch it to make sure that we can actually get the result that we want. But essentially, when we run it without the patching, right, when you just run it regularly, it's going to say proceeding with non-malicious activities. I guess I can run it because it shouldn't be that complicated to run. But basically, this is the code in the background that's going to check to see if there is some kind of a temperature probe on the virtual machine. And if there is, it's going to just say, hey, you know what? There we go. So proceeding with non-malicious activities because VM was detected, right? So that's basically what it says. And so this is the full code right here. If you, and the idea that they've given us is that you can compile it and run it on your physical machine to see how it changes its behavior, meaning I should run it on my actual laptop, which I'm not going to do. No actual malicious execution is inside the code, so it's safe to run. And the only thing that it's going to do is if it detects that it's on a physical machine, is that it's going to have this pop up. But I'm not going to run it because it would require that it would compile the code and run the code and do all that stuff. So I'm not trying to do all that. It's, I'm just going to take it for their on their word that this is going to happen. Plus, we're also going to change this, right? We're going to change it inside of the debugger that we just have right now, and then we're going to be able to see what it looks like inside of our virtual machine anyways, because as long as it gives us this response, that means that we've properly patched it and we've debugged it. So the architectural check, like checking temperatures, can be challenging. Fortunately, there are ways around this. For example, we learned that we can patch a function with NOPs to prevent it from executing, and we can do the same thing over here. So we'll be covering two other approaches: manipulating memory directly and changing the execution flow with EIP. So opening this again, go to the file, open this again, press F9 to start running, and then it will halt at the code that's marked as entry point. And then we're going to press Control G on the keyboard to bring up the enter expression to follow, and then enter this value, and it'll take us to the memory address. F2 to set up a breakpoint, and F9 to halt the execution. Now we're at the memory location here, and the block of instructions from this location corresponds to part of the C code snippet, the enumerator that will go ahead and essentially, I would say, probably enumerate what it would as far as the elements of the virtual machine, or the elements of the virtual machine that would help the malware detect whether or not it's actually on a virtual machine. So these are the comments that have been added to the right side to highlight the values to pass the function. And so let's just start with that element right there. So we'll just do these chunks of exercises. So this is fine. That's what the malware did. So I'm just going to go ahead and open the VM detection inside of our piece right here. There we go. So press F9 to start the running. Or I could just, let me see if F9 will actually work here. So if I press F9, no, it doesn't work. So I'm just going to do the forward button and it starts running. So now let's see. So it says debugging will halt at the point called entry point. And for me, it does not say that. So if I actually click on this, it says call VM detection, and that's all good. So if I run it again, or if I do, let's try run one more time. Maybe it'll do it and get to the entry point. Proceeding with non-malicious activities, VM detected. Okay, so that's actually running, and that ended up closing itself. So I'm gonna run that one more time because it closed itself after it was done. It just did proceeding with non-malicious activities. So start running the program in the debugger. Debugging will halt at the code marked at the entry point. So press play, and it should stop at the entry point, but I don't see entry point on my screen right here. So maybe if we go to full screen so we can actually see the full piece. So I will exit split view right here. I will allow this. I will maximize this, and let's see if we can see entry point in here. Oh, we do. Okay, there you go. So there it is. So it was previously hidden, but it's right there. So it stopped at entry point. Excellent. So now what we can do is go and do the enter expression to follow and enter this value to follow it, and then press F2 to set up a breakpoint at this memory location, then F9 to halt the execution. So what I need to do is, I wonder if Control G will work, right? Because hopefully it does. So if I do Control G, okay, there you go. That worked. Enter execution expression to follow. So I will paste that expression, and then there it is. So press OK. And so I have this now. So there we go. And then F2 to set up a breakpoint at this memory location. So we should be at the 10E0, which is exactly where we are. And then breakpoint, I guess, is something that I want to do. So I should be pressing F2 to set up a breakpoint. But I wonder if this button right here, this breakpoint button, I wonder if that does the same thing. But I will try F2. And F2 does not do anything for me because it is just increasing my my display brightness on my computer. So I will need to find out how to set a breakpoint through the actual menu. So give me a quick second. Okay, so if we actually just right click on that item and go to breakpoint, F2 is toggle, I guess, so I can just click on that and it'll turn that piece into a breakpoint. So there you go. That's how we can do that. And then F9 wants to halt the execution here. And again, so halt the execution might be something that I don't know if I can do with my F buttons. So I need to see if there is a version of this that will allow me to do it. So let's see what I can do here. So as I anticipated previously, as I guessed, this button right here is the F9 button, because if we go to debug and then we look at what the value for run is, it is F9. So I'm just going to do that. And so I guess that would be our halt right there. So so we have now officially halted the execution right there. Now we're at the memory location. This and the block of instructions from this location corresponds to the part of the C code. To help us visualize this, there are comments on this. So presumably the comments would be something that I could actually see. And so let's see what the comments would be. You know, what is it? U return, WBM infinite, PM enumerator. So let me see if I can find any of those things. Okay, so there are no comments, because I think the comments that he's referring to, the creator of the room, is comments that he added to the screenshot specifically. So these elements right here don't show up in the analysis that I'm making, but just looking at the data right here, these elements right here, I know that we're in the right space. So it says 10 E0 8D45E8 LEA-EAX, so 10 E0 8D45E8 LEA-EAX. So I know I'm in the right place. And then the next one is 10 E3, 10 E4, 10 E7, etc. And so 10 E3, E4, E7, etc. So I know we're in the right place. So now we're going to press F8 a few times to step through the code until you reach the memory location 10FD. And step through the code is accomplished by this button right here. So it says step into. And if we click on debug, we can actually see that as well. So step over, it says F8 right here. So that's technically it. So there we go. And then we want to get to which location? It says you want to get to the 10FD. So 4010FD, which is going to be down here. So we're just going to press this a few times until we get to that location, which is right there. So 4010FD, and that's the one that they're telling us to do right there. Here we can see that the value of EPB18 or uReturn is being compared to 0, and this goes to the C code, which if uReturn is 0. So this piece right here, we're trying to see if it actually compares to 0, and this is the part that I would love to actually see inside of the code right here. So what we can see right here is if it's comparing the EBP18 to 0. So I want to see if I can actually find that, to see if I can see EBP18 to 0, because that would be great. Unfortunately, because I don't have those comments, I can't see the stuff that he's talking about in this piece, where it's like, if you return equals 0, because we can technically see it right here. But again, I don't have those actual comments for myself right here. So I am on this line, and then I do see the EBP 18 comparing to 0. So this piece, CMP, D word, etc., I'm assuming that is comparing the D word variable, the global variable, to see if that this element equals to 18, and that's essentially it, right? So if it does, then it's going to do something, and if it doesn't, it's going to do something. So we want this if condition to evaluate to false. What we can do is edit the memory location pointed to by this, so that it will contain the value of 1 instead of 0. And what did I just do here? I just shrunk out of that. So we want to change it so that it'll contain the value of 1 instead of 0. And to do this, we're going to right click on the line that has EBP18 and click follow in dump, then select EBP18. So right here on FD, we're going to right click it, and then we're going to follow and dump EBP18. So here it is, goodness gracious. And then we're going to do follow and dump, and then address EBP18. And so let's see if that actually is the case. So when we do that, we'll see the bottom of the screen at the dump 1 window tab that the current memory location is FF08. So we have this right here. So in dump 1, let's make sure we're actually here. Okay, great. And so if that is indeed the case, the memory location should be at FF08, and I don't see a highlight. It does say that the dump is FF08, so that piece I see, but I don't see anything highlighted. Oh, I see. So FF08 would be the thing in the, yeah, so there it is. There it is. There's the actual highlight, and it's on FF08. Okay, great. Excellent. Double click on the rightmost 00 values. This will open up a modify value window. Enter 01 in the expression field and click the OK button. So on FF08, on the rightmost 00 values right here, so FF08, we see that on the rightmost 00 right there. We're going to double click on that, and it should bring this for me. There you go. It has the pop-up. And so what I want to do here is that put 01 in the expression field, which is right here, and then click the OK button. And it should change the value down here to 01, FF08. There you go. We have 01. Excellent. Very good. So to turn the attention back to the main window, CPU tab, press F8 a few times. You'll notice that the code will not exit anymore, as it skips the execution from 1101 to 1100A. And what we've done is that we've manipulated the bits of memory location to direct da-da-da-da. However, the program will now crash if you continue running the program. And it was supposed to exit at the previous function, but we've introduced a bug since we intentionally skipped this. Don't worry, this always happens when messing around in debugger. So for us to continue to investigate, there's one other method that we can use that would allow us to jump around and continue. Okay, so I guess, so if I do this a few more times, yeah, so it skipped from this and it just went directly to this. And I would assume that that's not the ideal result, because that's what we didn't want to happen. And last chance exception bug, etc. I keep getting the same thing at the bottom where it pauses it. So I guess it's not the ideal situation. So if we continue to run the program, it will crash. So if I press play, it would, yeah, it seems to not be working. So that is unfortunate for us, because technically we want it to continue working, I guess. So the program was supposed to exit at the previous location, but we introduced a bug. Okay, this always happens when messing around. Okay, so for us to continue to investigate, there's one other method that we can use that would allow us to jump around. And let's say we want to skip everything and jump to this part of the code, this piece where it says thermal zone temperature, etc. in the assembly code. The instructions would be 401130 and 401139. So between those elements right here. So we want to get to the 401130 and 401139, which is right here. So this from here to 39. So these 4 lines right here is where we have this temporal zone temperature, that piece right there. Okay. So the great thing about debuggers is that we can change every value related to the program. We can change the values in the memory locations, the values on the stack, and even the values of the registers. The EIP register is the register that holds the memory address that tells the debugger what next instruction to execute next, and this can be edited. So going from the last step, on the registers panel on the right side of the screen, look for something that says EIP and then modify value. So this is what we have right here. And I think it's 40110A is what it's supposed to look like. So continuing from the last step, so 40110A, which is what I believe that is right here. And we're looking for the EIP value that says 40110A. So I need to go back, it seems. So let me see if I can actually do that. Okay, so to be able to achieve the rest of the stuff right here, because continue from the last step, I had skipped over this element. So we're supposed to end up at 40110A. So I literally restarted the program, or restarted this whole debugger by clicking this restart button right here. And I started from the very top of the instructions, meaning I came here and I first pressed play, right? Or pressed this part right here that I think it's like F8 or F9. F9, there we go. So I pressed F9 and then it took me to the entry point. And then from here, I did the Control G to actually search for the expression, and then it took me to the element where I could set up the breakpoint. So this piece right here, and 4010E0, this piece right here. Then I clicked the right click and I put an entry point, or excuse me, a breakpoint, and then I did the play button one more time, or the F9, to halt the execution. And everything that you see right here is as it is. So this is what you see right here, right? So E0, that's where it started, and I got the execution. And I pressed this button, the step over, a few times until we got to 10FD. And then I right clicked on this, I went to follow and dump, and then I looked at the location, which took us down here to this portion, the F08, and then I changed this last value from 00 to 01. So literally repeated every step of this process, and now we have ended up at where we are right here. So right here, we have changed it to 01, and now we can press the F8 a few times so that we can move from 1101, and we can see that it was going to skip 1101 and end up at 110A, and this is where we want to stop. Okay, so we want to stop on 1108. That's where we are right now. So this is where I am, and so I want to stop right here, and essentially what we want to see is that it's going to skip this and it's going to end up here, right? So if I press this, let me make sure it's actually clicking. There we go. There it is. So it goes from there, and then it'll jump to 110A. So we see that it skips these other executions, and then it just stops at that location. So that's where we want to be for this next element to work. So it says we want to skip everything and jump to the part of the code that happens in the assembly code. This is where it's located, right? So from 110A, it would end up in this location where we have right here. So the great thing about it is that we can change the value, etc. So continuing from the last step, on the registers panel on the right side, we can see that EIP, and then we should be able to change that value. So you see that EIP right here is 110A, right? So now I'm actually here where the EIP value is 110A, and then this is what EIP is right here, the execution, right? The entry point or execution point, I think. So now what I want to do is I want to modify that value and enter this as the new value, which would be the line that this thing starts from. So it is this piece. I'm just going to copy this to make sure I don't make any kind of a mistake here. We're going to go here, modify the value, and then we're going to paste the expression, right? It says as the new value for the expression, I think. So it says modify value as the new value. I guess, yeah, that's what it is. So I'm going to paste that. Okay. And it takes me automatically to this location. Very good. Now we press F8 to step through the code. You'll notice that we'll jump directly to that instruction. Notice how the EIP marker now points to the location that we wanted. So, okay. F9 again would continue running the program, resulting in proceeding with malicious activities. And that would be the final piece of this. So this is where I'm at right here. And so this is the location as it says. So if I press play, let's see, it's running. So I guess there should be a pop-up that says, there we go, proceeding with malicious activities. So we did everything that we're supposed to do. Good job. You successfully prevented the malware from detecting that it was running. Okay, great. So in the C code snippet, what is the full WQL query used to get the temperature from that? So we want the C code entry. So let me just zoom out a little bit and go find the WQL query that's going to pull the temperature for us. And it's right here. So this is the execution query, this piece right here. So I think they want that full thing. If not, it might just be the select part. So let's see. Okay, that is not it. So to temperature from the Win32 temperature probe class. I'm pretty sure that was it, but I think they're looking for maybe this piece, the select from. I think that's the piece that they're looking for. So we'll go here and we'll try that again. Okay, great. There you go. That's the one. What register holds the memory address that tells the debugger what instruction to execute next? What register holds the memory address? I want to say, is that EIP? Yeah, that is it. So EIP is the piece right here. This thing that you see, that's the thing that tells what to execute next. Before U-turn is complete compared to 0, before U-turn is compared to 0, what is the memory location pointed by EBP04? So before it turns to 0, what is the memory location by 04, right? EBP04. Okay, in order to pull this off, the hint tells us that we need to run through the steps one more time. So I restarted the malware. I ended up at the entry point. I did Control G. I pasted the value that would take us to the location that we wanted. So Control G, and then pasting this value right here, and it took us to that address. And then I did the breakpoint. I did the F9 to halt the execution. And now we're at the E0, and we want to end up at this location. The 10FD is the location that they're talking about. So the function will da-da-da-da, and it will write value da-da-da-da. So what we're going to do is press F8 a few times to actually get to FD. So essentially what that means is just getting to this location again. So just going to press this until I get to FD. And there it is. So now the value is supposed to be EBP, right? So the location now, it says before U return is compared to 0, what is the memory location pointed to by EBP04? So if I right click this, I think this is where I can go and do the follow and dump, and then EBP, but that says EBP18. So EBP04, the memory value, that's the one that I think they want. So if I do follow and dump, there you go. So address EBP04, there it is. So this is the one that has EBP18 on FD, and then we want the one that's EBP04. So if I right click this and then follow and dump and do that, it should take me to that location, which is right here. So the FF1C, I want to say, is the value that they're looking for. So FF1C, it could also be the 10FA, so 004010FA. So let's try that, 004010FA. So that's not it. So the location then would be this piece right here. So 0019FF1C. So let's try that. So 0019FF1C. Yeah, that's the actual location. So we had to just right click on the one that says EBP04 and then do follow and dump EBP04, and then it will bring us to the bottom right here, and this is the one that they're talking about. All right, cool. So now we can talk about packers, and we'll do an overview of packers, and then we'll go through identifying and unpacking, and then we will be officially done. Obfuscation is a technique that aims to intentionally obscure data, right? So to disguise data, to make it undecipherable by the naked eye, and it's harder to understand or analyze. So the most common obfuscation technique is using encoding techniques. So command line strings or domain names is encoded using popular encoding techniques like XOR or base64. And when you see something like this, right, that's basically a base64 string. So let's see what this actually means by going to our favorite tool, which is CyberChef, and then basically you just drop in whatever the input is, and then usually you can automatically detect it. And so in this particular case, it did not automatically detect it. So from base64 would be my recipe. And then this is the response. This is a base64 encoded string. That's basically all it says. So nothing fancy. So using encryption techniques, this involves encrypting data such as communications to a command and control server, file formats, and network traffic. The most common types are symmetric key and public key encryption. Symmetric is private key, public key is asymmetric. So these are encryption techniques that would encrypt the strings and the value so that you can't even decipher it. So this is encoding. And as you saw, it's very easy to decode encoded string, not so easy to decrypt encrypted strings. And code obfuscation involves various techniques like manipulating the code to alter the syntax and structure, renaming functions, splitting code across multiple files or segments. And there's a lot that can be done. So we don't go really crazy in this particular video. We just want to know about the wide use of packers in malware. And that technique can be considered to fall under obfuscation. So packers are tools that compress and encrypt executable files. It compresses the target executable and embeds it within a new executable file that serves as a wrapper or container. This dramatically reduces the size of the file, making it ideal for easy distribution and installation. Also, it has code obfuscation, runtime packing, and anti-debugging techniques. And because of these features, they are a popular tool for malware authors. So there are a lot of packers available. These are the list of them. Each of them are unique and they can have different algorithm for packing. And these are some of the most common ones that have been outlined here. If you're actually inside of this room, you can literally click on any of these and it'll just take you to the given website for it. So for example, this is the website for AutoHotkey. And you can go and I guess it's called Impress, but the website itself was AutoHotkey, Themida, VM Protect, all these things could be packers. If you don't have access to this room, you can just Google these names and you'll be able to find the websites. So not all programs are malicious because as we just talked about, it can just condense or compress the program to make it easier to transfer and easier to use. So protecting the intellectual property from theft is one of the big things as well when you do something like packing, because you don't want the source code to be exposed. And Themida is widely used to prevent video game cheating. It's one of the packers that's available. So packers encrypt an obfuscated program. It would be impossible to know that malware capabilities without actually running the type of malware that has been packed. Because of this, we can't reliably depend on static analysis and signature-based detection to determine the capabilities. The only thing that we can glean from malware sample at this state is the packer tool that was used, meaning when it's packed and you're doing static analysis, the only thing that you can really learn about the malware, is what packer tool was actually used. And it's a good starting point because we'll be able to kind of figure out what that packer does to be able to decipher it. So what is this base64 encoded string? So we already have our CyberChef running, so we will just go ahead and do that. I mean, it literally says the same thing. So this is a base64 encoded string. Was that? Oh no, the other one said this is n base64 encoded string. This one says this is a base64 encoded string. Okay, so identifying and unpacking. Let's get into it. So we have a packed malware piece that is on our virtual machine. We can use it inside of Detected Easy, also known as DIE, and it'll show us the identification. So if it's actually been packed, it'll display it as best guess under this section. And so from this particular screenshot, I want to say that this is the element, the Microsoft linker, Visual Studio, etc., under the best guess right here, the packer, or excuse me, the packer here, my bad. So packer is UPX, there you go. And the linker is Microsoft linker, but the packer itself is UPX, as we can see. So we can also click on the entropy button on the right side of the screen to open the entropy window. The entropy window looks and determines how much entropy each section has. As you can see, it has been determined that section 1 is packed. as we can see that right here. Excellent. So entropy measures the level of disorder or uncertainty in a system. Packed malware tends to have high entropy due to the randomness of the packing process. Another tool is PE Studio, which lists information on PE files. It's important because there are specific packers that will still leave clues. We can click on PE Studio, go to the menu and open it. On the list of items on the left panel, click on Sections Self-Modifying. So let's go here. I already have PE Studio open, so I can do File, and I can open the file and then open up the packed malware that we have here. And it says, where is it? It's on the list of the items on the left. We have the Sections Self-Modifying that can bring our element to us. So there we go. I have Sections Self-Modifying. There we go. And so it has UPX0, UPX1, and UPX2. And I do know that we need the value of entropy for UPX2 for one of our questions. So it's 2.006. That's one of the answers that we need. And then the other question at the bottom asked for the Microsoft version, which is 14.16. So that one is available here. So where is it? Right here. So 14.16 is the Microsoft linker. And the PE Studio, what's the entropy of UPX2? And we have 2.006, 2.006, and that's that answer. And that's basically all the questions that we have for this section, but we're going to read through everything else as well. So what do we have here? We have the section names of standard PE file are text, data, resources, but in the output above, we can see that this section names have been changed. The strings PX1, PX0, 1, and 2 are some of those identifiable pieces of information that packers like UPX leave behind. Not all packers change this value, but usually this is the most accessible first place to look. Because different packer tools use various methodologies in packing executables, sometimes tools like Detected Easy could not identify all types of packers. So we can do automated unpacking. Once the packer for packed malware is identified, it's possible to see an unpacker, to use an unpacker to get the original file. Some are readily available, like in the case of UPX, where you can use the same packing program for unpacking. For other commercial tools like Themida, you might have to rely on unpacker scripts made by third parties. These are some of the scripts. If you chance upon malware packed with an obscure tool or modified to thwart available scripts, things might get more difficult. There are services like UnpackMe, where you can upload a sample and it will try to identify and unpack the malware for you using custom unpacking and artifact extraction. This is still not perfect. So this is UnpackMe, available at unpack.me, and you would sign up and you would upload your malware sample. Manual unpacking and dumping is probably the best way to execute it and then try to unpack it. So when a packed malware is executed, the wrapper or container code performs decryption and deobfuscation. Once fully unpacked, the malware can proceed. At this point, the packer is useless, and we can thoroughly analyze the malware by debugging it using a debugger. So we can use our X32DBG and continue with this. So packed exe, I'm going to open it and do Control G, and then we're going to jump to this spot. So I already have, let me see, where is it? It's right here. No, that's Task Manager. Where's DBG? There's DBG. Great. So we're going to open our packed exe right here, and then we're going to click G and just go to that element. So G, and then we're going to go to that location, press OK, and it'll take us automatically there. Now we're at this location. This is before the entry point. So press F2 to set a breakpoint, then F9 twice to move execution to this location. So we're going to go right here, and we're going to do right click, breakpoint, because I don't have F2 really accessible. And then I'm going to press F9 once, F9 twice, and now I'm at that specific breakpoint, which is the 2D4 element. Great. So now we have jump packed, and that is it. Jump packed. There you go. So press F7 to jump to the memory location 401262. This location is the starting location of the legitimate program. And so we're going to go right here, and under debug, we're looking for the F7 option, which is step into. So I will press that, and it will take me to the call packed location. Very good. So 262 is what we're looking for. There we go, 262. By now, you may be curious about the memory location 2D4 and 262 and their relevance to what we're doing. When this UPX-packed malware is executed and the execution location reaches this, the 2D4, it indicates that the legitimate part of the program has already been successfully unpacked and is now copied in memory 401.262. As outlined in the next steps, we can now begin dumping from this location. Other packers have different approaches to unpacking, so the steps above would not work for them. To start dumping, go to the top bar menu, click Plugins and Sila. So we're going to do Plugins and we're going to do Sila. I think that's how you pronounce it. It's a tool that dump process memory to disk and fix and rebuild the import address table. We'll use this to unpack legitimate parts of the program, so it will have updated memory locations. Once the Sila plugin is open, click the dump button. So we'll just click dump. Where is it? Right there. Dump button. And then we're just gonna, I guess, save it. So I'll just do the save in the malware location. There it is. There you go. To the exact location as the original file. Okay, so that's good. If you try to run this, an error will appear. This is because we have not fixed the import address table yet. So back in Sila, click the IAT auto search button to start. This scans the memory of the process to locate it. So we're going to do IAT auto search. Result of the da-da-da is different. Do you want to use ISH? Yes, I do want to do it. And so IAT was found. Oh, let me make sure that my machine does not expire on me, because that would really suck. So we're going to add an hour to our machine. Hopefully that will be fine. All right, so where are we? We are here, right here. Okay, great. So if you try to run it, this is what happens. Back in Sila, we're going to click auto search. This scans the memory to import the address table. If a pop-up asks you if you want to use it, click. Oh, I see. If a pop-up window asks if you want to use AAT, select no, then press OK. And I clicked yes. So there's the IAT. So let me do auto search one more time, and then no, and then OK. I guess I'm not sure if I did that wrong. At this point, the appropriate values are related to the IT are now computed. We can now click on the Get Imports button to this selection. I wonder if I actually did this wrong or right. So I will now do Get Imports, and we should have these values. So user DLL, okay, D00, D108, and D110. Let's see if that's what we got. D00, 108, and 110. Okay, that seems right. The list will show all the DLLs. This is short because the program is simple, and actual malware will have a longer list. Sila will find invalid entries. This is marked with the X icon next to it, so we can see that right there. To delete these, go through each invalid entry, right-click, and select Cut Thunk. Once deleted, you should be left with valid entries with checkmark icons. Click on the Fix Dump button, then select the previously generated dump file, and a new file will be created in the same directory as the dump file with the SCY appended to its file name. If you executed this, the program will now work correctly. So first, let's go and see if we need to remove anything here. So both of these are done. So we're just going to, what is it? I'm going to click on this, right? And then we're going to do, where's the, not, I guess if I right click on it, it says cut thunk, but it's not there. So if I'll right click, I see. So I have to right click on the individual ones, and then we cut thunk. Okay, great. So there you go. So now we have cut the thunks. That's so funny. And so since we've done that, we can do fix dump. So now we're going to click on fix dump. There you go. And so I have this now. A new file will be created in the same directory as the dump file with the string appended to its file name. So I don't have anything. Oh, I see. I need to do select the previously generated dump file. So this is my previously generated dump file. Open that. And once I do that, a new file will be created in the same directory. I guess there's already a file created. Yeah, there you go. So dump SCY. It's already there. Okay, so great. So now it says if you executed this, the program will now work correctly. You can confirm it if the unpacking was successful by inspecting the generated file using PE Studio or Detected Easy. Here's the output of Detected Easy. You'll notice that it's not packed anymore. So let me see if I can just click on this and see if I can use Detected Easy, because it said I could just right click it and open Detected Easy. There you go. So Detected Easy was one of the options. So it'll open, and I guess, yeah, so there's no packer or best guess or whatever. It just says compiler, Microsoft Visual C+, and linker, which is that. So that is all good. And same thing that we have over here. And we already have the answers to these questions, and we are officially wrapped. So as a conclusion, as a final thought here, we did anti-debugging, we did VM detection, and we looked at packers. And I will say that I don't think that these are the fully inclusive, like all-inclusive list of everything that is done with anti-debugging, right? So, or anti-reverse engineering, I should say. I don't think these are all of the tactics, because hackers are constantly working and they're constantly learning and they're constantly developing new methods to do this. So this was just kind of an introduction to anti-reverse engineering. We used PE Studio, we used the DBG32, we also looked at DIE, Detected Easy. So these were some of the tools that we used. We looked at a few different approaches to anti-reverse engineering, and hopefully it sheds a little bit of light for you and you kind of understand what the process is like and what can be done. This is not the be-all and end-all of this particular education. Very similar to everything else on this channel. So most of the stuff that we've done is an introduction to things, and it's up to you to dig deeper into it if it's something that interests you, right? There is a handful of playlists, for example, the CompTIA Security Plus, Network Plus, Linux Plus, and then I'm going through PenTest Plus. Like those things, I would say are pretty comprehensive as far as those categories are concerned. But even within Linux Plus or within PenTest Plus, as we're going through it, there are so many tools that are introduced during those studies, and we don't specialize in any of the tools. We say, hey, this is the tool, this is what it does, this is what you can do with it, here are some examples of what you can do with it, and then we move on to the next one. Probably the one where I did like the most in-depth introduction or in-depth overview of it was the packet tracer from Cisco when we were doing Network Plus. But even with that, there are so many other things that you can do with the packet tracer that it would just take an entire course to try to teach you just that one software. It would take hours upon hours, dozens of hours to try to share with you what exactly you can do with that one software. So all of these things need to be considered as you're looking at everything that we're going through, including anti-reverse engineering. We did one module on malware analysis, but this does not mean that you are now a malware analysis expert. And the only thing that we're going to be doing after this is done is going and looking at an actual exercise where we run malware analysis on something. So we're no longer going to be talking about any ideas or strategies for doing malware analysis. We're just going to implement everything that we've learned so far so that we can go ahead and get those final points and wrap up the SOC level 2 pathway that's inside of TryHackMe. But that, I mean, for the most part though, like considering everything, considering all the different resources, this was a great security education where we went through SOC level 1, we did CYSA plus, we did all those things, and now we have finished SOC level 2. So I can tell you from my own personal experience, I feel much more competent than I did a year ago when I started all of this stuff, right? So just, take it with a grain of salt. I think there's a lot of other things that can be learned. We can always learn more, we can always practice more and advance more. And I encourage you to do that. I encourage you to do independent study and download some of these tools or download the virtual machines and do some of these exercises just so you can really understand what's going on instead of just watching videos and following along click by click. You won't learn everything that you need to learn by simply just doing that. So that's my 2 cents on it. If you found this video useful and if you've gotten any value from this channel, I do encourage you to like, subscribe, and turn on that notification bell so that you get notified the next time that a video comes out, because we are constantly uploading videos. We are at 355 videos as it stands right now. I have some really popular ones that are on the home page here. We have the created playlists, we have members only videos, we have and these are reserved for Hackaholics Anonymous, and you'll find out how you can join Hackaholics Anonymous if you want to. SOC level 1, SOC level 2, security engineering, and then there's these individual ones that are pretty popular. So CompTIA PenTest Plus right now is what we're working on right now. This is the 2025 version of the PenTest Plus. Network Plus is already done, and this is the 2025 version of Network Plus. Python for Hackaholics Anonymous, CompTIA Security Plus Examination, Linux Plus Exam Prep, Cybersecurity 101. These are some of the most popular playlists that I have right now. Linux Plus is very, very popular. A lot of people are using it. I think Network Plus is probably the next one that was like really popular. And again, there's just more stuff that's going to be coming out. There's going to be CompTIA CYSA Plus that's going to come out. There's going to be AI for cybersecurity, where we learn how to program AI, essentially how to train AI to create our own security analysts, our own automated security engineer agents, So there's a lot of stuff. We're not going to be slowing down on content anytime soon on this particular channel. And if you're interested in anything with cybersecurity, ethical hacking, pen testing, or system administration, because this is also kind of goes into system administration. If you're interested in any of this stuff, then you definitely want to be a member of this community, and I think you will get a lot out of it. So if you haven't done so already, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section. And then that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I'll see you in the next video. Later. Welcome to the 48th and final episode inside of the malware analysis, which is inside of the SOC level 2 pathway in TryHackMe. And this is literally the last episode until they upload more rooms and more content for us to review and study together. And in this last episode, for now, we're going to go through the MalDoc static analysis, and we're going to be looking at malicious documents. And malicious documents are a lot of times used in phishing campaigns where you send this really curious and exciting type of an email, and you have an attachment, and you entice the user to click on it. And then when they click on that document, then there's a bunch of malware or macros that are launched from the document itself, and then next thing you know, you're inside of the computer and then inside the network, and you're doing a bunch of crazy things. So this is what we're going to be talking about in this particular episode today. And we have an overview here. So we have the introduction, connecting with the lab, initial access for spear phishing attachments. This is what these things are: documents and their malicious use, PDF document structure, analyzing a PDF document, analyzing malicious JavaScript, Office doc analysis, OneNote, and then of course we have a conclusion. This room was developed by multiple people. It's actually very, very cool to see. So TryHackMe, obviously, we have CM Natick, we have Dex01, and Dr. Gonzo. So these are the creators of this particular room. Very, very grateful to them because without them, we would not be where we are today. And I'm super excited to actually be here with you today to be able to wrap up, as it stands for now, the SOC Level 2 pathway of TryHackMe, and of course the malware analysis module. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us get into MalDoc static analysis. If you're watching this video and you have no idea what documents are, then we are in a lot of trouble, let me tell you. Documents are very commonly used. There is documents that can be created with Adobe Acrobat. There are documents that can be created with the Microsoft suite of software. There's the Google suite of software that you can use to create documents. So there's a lot of different sources that you can use to create documents, to read documents, to modify documents, etc. Therefore, this is a great attack vector for malicious actors to use to be able to mess with us and to try to exploit us and, deliver malware, steal sensitive information, carry out phishing attacks, etc. So malicious documents, therefore, is an essential part of cybersecurity strategy to be able to analyze them. And we can identify potential threats by analyzing the structure and content of a document and taking steps to mitigate it. This is particularly important today when more businesses rely on digital documents to share and source sensitive information than anything else. So we're going to be learning about the presence of malicious URLs, references to file names and API functions, IP addresses, domains, malicious scripts like PowerShell, JavaScript, VB script macros, etc. And we're going to understand the different variants of malicious documents, their structure, and how they are used in different phishing attacks. Then we're going to look at the tools and concepts required to analyze a malicious document. The objectives are the different document types like OneNote, DOTM, Docs, XLS, PDF, etc. Analyzing complex JavaScript, importance of malicious document analysis, PDF structure, and key components like objects, keywords, and filtering. And I want to make a quick note, if you are not good at JavaScript and you don't know how to read JavaScript, it's not that big of a deal because you will have a tool like Google Gemini, which is a great analysis tool that you can go ahead and just drop the JavaScript in it, and then you can say, hey, what does this do, right? Can you explain what this block of code is trying to do? So that being said, let us first connect to our lab, and then from there we'll dive into the content. If you're not familiar with the TryHackMe environment, virtual machines and attack boxes are a very, very big piece of why TryHackMe is so amazing. And these are basically virtual machines that you can use to run a variety of different practical exercises, including security analysis, and of course hacking and penetration testing. And these are one of those things that you don't want to do in the real world because it's a felony. So it's great to do it in a controlled environment like TryHackMe. So I've already launched this virtual machine and it opened up in a split screen, but I'm super zoomed in onto my screen right now, so you can't really see it. If I wanted to connect to it via OpenVPN, I could connect from my specific computer. So once you're connected to OpenVPN, then you can go ahead and launch the virtual machine, and then you can secure shell into it. So we have username remnux, password is malware, and this is the IP address. So it would be remnux at this IP address, and then you would be prompted for the password, and then you would go ahead and enter the password. And that's basically it. That's like the only thing that we need to do to set up the lab environment. Now I'm going to click split view because it should already be done. And there it is. This is my machine here. So I'm going to open this up in full screen just so it's a little bit easier for us to use it. I will remove that piece, and then I'm going to zoom back in onto the screen right here to help read easier for you, and then we are ready to run. So first, let's talk about the spear phishing attachment. To understand what spear phishing attachments are, we need to first understand what spear phishing is, and then obviously who would use a spear phishing campaign to get what they need. And then of course an attachment. Hopefully you understand what an attachment is. It's basically a file that is attached to an email. Now spear phishing is a variation of phishing. Phishing in general is when you send out emails trying to get people to click on a link or to open a malicious document. When you do spear phishing, you do the phishing campaign against a specific person or a specific group of people, because that person might have elevated privileges or they might be somebody important. So instead of fishing with a net, so to speak, and trying to catch a bunch of people, you're trying to go after a specific person or a specific handful of people that have what you need, essentially. So these are very common cyber attacks that target specific individuals or organizations through carefully crafted and personalized phishing emails. And the personalization part of it is very important because the person that you're targeting should feel like it's directed to them for their company, etc. Now, this is something that is an attack vector that has been used by a lot of APT groups, and APT stands for an advanced persistent threat. And these are either an individual person or usually a nation state or a state-sponsored group, which is basically a group of hackers and attackers that have an advanced persistent agenda in mind to be able to attack you, your company, your country, etc. And the idea is to trick the recipient into opening a malicious attachment that contains malware, ransomware, or something else. And by doing that, the attacker gets unauthorized access to the target system, allowing them to steal sensitive information, compromise systems, and achieve other nefarious goals. This is the screenshot from the MITRE attack framework for phishing and spear phishing attachments. And so there's a lot of sub-IDs underneath this, and there's a lot of campaigns that are associated with this because this is very popular, because the key element here is the human error element. So these systems usually are pretty secure. And the big thing that we're trying to focus on here, the big thing that we're trying to target is a human being, because human beings are emotional and they can be distracted and they could have a bad day and not pay attention, etc. There are so many reasons why a human being has flaws. And so the idea is to take advantage of those flaws, right? So APTs, APT groups, are highly organized cybercrime groups or state-sponsored entities known to use spear phishing to infiltrate the target, and they employ spear phishing with attachments as an effective way to bypass security measures and gain a foothold in the target environment. So APT-28, also known as Fancy Bear, is a Russian state-sponsored group that's been responsible for high-profile attacks like the 2016 Democratic National Committee hack. APT-28 used spear phishing emails with malicious attachments. Once the attachment was opened, the malware installed and allowed the attacker to exfiltrate sensitive information. APT-34 was known as, or is known as, Oil Rig, and it's an Iranian cyber espionage group that has targeted industries primarily focused in the Middle East. One of their tactics include spear phishing, and when the victim opens the attachment, a macro initiates and the download installation of malware, which then establishes a connection with the attacker's command and control server. Cozy Bear, APT-29, is another Russian state-sponsored group. They've targeted governments and organizations worldwide, and against the Norwegian parliament in 2020, they sent spear phishing emails with malicious attachments, and the attack resulted in unauthorized access to sensitive data. And then we have Menu Pass Group, APT-10, a Chinese cyber espionage group that has targeted organizations in various sectors, including government, aerospace, and healthcare. They have used spear phishing with malicious attachments, and when the attachment is opened, the malware contained within it compromises the target system, allowing them to exfiltrate sensitive data. So it's mostly about either encrypting their data to hold them at ransom, exfiltrating sensitive data, or establishing a remote connection so that you can essentially run commands and do a variety of different things. These are kind of the end results for a lot of these campaigns in general. So the malware families that are associated with these documents are Emotet, that is a banking Trojan that is often distributed through malicious email attachments, typically in the form of Microsoft Word documents. Once installed, Emotet can steal sensitive information like banking credentials and email addresses, and it can also be used to download additional malware. The MITRE reference includes a reference for Emotet, which can be found at this specific link. So you can just go to MITRE or attack.mitre.org and then look for Emotet. Just search for Emotet and you'll be able to find it. TrickBot is a banking Trojan, again, that is often distributed through malicious email attachments and is known for modular design, which allows attackers to add a new functionality to the malware as needed. And it has been used to deliver ransomware, exfiltrate data, and perform other types of malicious activity. And again, you can find it on the MITRE website by searching for it. Then we have the Quackbot. I want to say that's how you pronounce that. It's not Cackbot. I think it's called Quackbot. And it's a banking Trojan that is often distributed through malicious email attachments, known to steal banking credentials and other sensitive information. It's also capable of downloading and executing additional malware and can be used to create backdoors on infected systems. And of course, there's a MITRE reference for that. Then you have Drydex, again, banking Trojan, steal banking credentials and other sensitive information. It's been active since 2014 and one of the most prevalent banking Trojans in recent years. you can search for it in MITRE. Locky is a ransomware family that is often spread through malicious email attachments, typically in the form of Microsoft Word documents. It can encrypt the victim's files and demand a ransom payment. Zeus, another banking Trojan, and it's through malicious email attachments. It's known for ability to steal banking credentials and other sensitive information and used in numerous high-profile attacks. And then there's Petya, a ransomware family that's often spread through malicious attachments, and it's been active since 2016. Encrypt the victim's entire hard drive, making it much more difficult to recover from than other types of ransomware. So from which family does the Locky malware belong to? And so we have it. It's a ransomware family that often spread through malicious email attachments, typically in the form of Microsoft Word documents. So I guess we can say Microsoft. Nope. So from which family does the malware belong to? Okay, so ransomware is the family that they're looking for. So Locky malware is a ransomware. What is the sub-technique ID assigned to spear phishing attachments? So we can actually find it right here. So the sub-technique ID is T1566. It's right here, T1566.001. So it's a sub-technique of the initial access, T1506001. Or not, what is it? I can't believe I forgot it already. 1566001, my bad. So 1566001, there it is. Okay, great. So let's talk about documents and their malicious use. I'm not going to read too much into this because you should know what these various document types are, but obviously these are content, or these are assets that are used to deliver malware or execute code on a user system. And it's very important, and it's important to be cautious, when you're opening these documents from unknown sources. So if you don't recognize the source, or if you don't recognize the conversation or anything like that, do not open the document. If you want to do something where you can analyze the document, download it. Don't click on it to actually open it. Download it and then go to VirusTotal and connect it as an attachment to see if it is malicious, but do not open the document. It's very important. You can right click on a document and download it. There's usually an arrow, like a drop down arrow that's available for an attachment where you can click on the arrow and download it. But as long as you don't open it, you are not running the document. Therefore, whatever is installed in it, whatever malware is installed in it, won't run. So PDF, the common one, portable document format is widely used, that can be opened on different devices. The attacker can also use this to deliver malware or launch attacks. They can embed a malicious code or link in the file that, when opened, can exploit vulnerabilities in the system. It can be used for phishing attacks, including links that redirect users to fake websites where they are prompted to enter personal information. So that's another thing. Inside of the PDF contents, there can be instructions, and then inside of that, there would be a link that they can click, and then they would go to the website, enter personal information. DocX is the Microsoft Word document, and Google Drive also allows you to do this. So Google Docs also allow you to download a DocX type of a format that you can open in Microsoft Word. And again, they can be used to deliver malware using macros, which are a series of commands that automate tasks within the document. Attackers embed malicious macros in the Word document that can execute code on the system. They can create a Word document that prompts users to enable macros to view the contents of the document, which then executes the malicious code that can steal personal information. So it can prompt the user to enable macros to view the document, and then by enabling macros, that's where the code exists, and then they can go ahead and run their code. Excel SX is an Excel spreadsheet, also known as Google Sheets or Microsoft Excel, that can be used to deliver malware by using macros. So they can embed malicious macros in the Excel sheet, and that can execute code. An attacker can create a sheet that prompts them to enable macros, very similar to what previously happened. PPTX is PowerPoint presentations, and it can be used to deliver malware or phishing attacks that can enable malicious code or links in the presentation that, when opened, can exploit vulnerabilities in the user system or redirect users to fake websites where they're prompted to enter the personal information. So inside the PowerPoint, there would be either malicious code or links in the presentation that they can actually run or click on. XML is the kind of like the advanced version of HTML. So XML is inside the same family as HTML. and it stands for Extensible Markup Language. And it's used to store and transport data. Attackers can use XML documents to exploit vulnerabilities in a user's system. For example, attackers can inject malicious code into an application by uploading an XML file that contains code designed to exploit vulnerabilities in the application. And OneNote is a digital note-taking application that allows users to organize and share their notes across devices, hence the name OneNote. So you're using OneNote to share with a bunch of different users. And in itself, it's not typically used to deliver malicious content because attackers can abuse OneNote to deliver phishing attacks. They can also use OneNote to store and share malware. For example, they can create a OneNote notebook that appears to contain legitimate information, but it includes a link to a malware download. When the user clicks on the link, the malware is downloaded and executed on the system. So with that one click, they download and execute the malware. So we've learned about some very common types. And now we can see how we can look at the details of them to explore the malware and essentially prevent from them launching. So let's look at the structure of a PDF document. Before we start analyzing them, we need to know what they actually look like and how they look like kind of behind the scenes, so to speak, under the hood. So it consists of a series of objects that are organized into a specific structure, and understanding the structure is important for analyzing and working with the PDF. So this is the overview of the structure. We have the PDF header, and this is the first line in the PDF that contains the signature and the version number. And it's a sequence of characters that identifies the file as a PDF. So this is what the PDF header looks like. And so it's the PDF, and then of course version 1.7. Then you have the PDF body, which contains a series of objects that are organized in a specific structure. Each object is identified by an object number and generation number, which are used to uniquely identify the object within the document. So you have object 1, type catalog, object 2, type pages, object 3 right here, page, object 4, page, etc., right? The PDF cross-reference table is a table that provides a map of the locations of all of the objects in the PDF file. And this is used to quickly locate the objects within the file. And so XREF is the cross-reference keyword right there. And then you can see these are the cross-reference, this is the cross-reference table essentially. And these are the locations that you would find various pieces of data. PDF trailer is the last section of the file that provides information about the document, like the location of the cross-reference table, the size of the file, and any encryption or security settings. And then you can identify it by looking for the trailer, start cross-reference, 788, end of file, right? So now we understand these, we can explore the keywords that have usage within the PDF. So JavaScript or JS points to JavaScript that will run when the document is opened. Names is the file names that will most likely be referenced or referred to by the PDF itself. Open action or additional action, AA, is the element function to carry out an action like running a script. Embedded file shows other files embedded within the PDF. URI or submit form are links to other URLs on the internet, and launch is a keyword used to run embedded scripts within the PDF file itself or run new additional files that have been downloaded by the PDF. Analyzing the simple PDF document, which is what's available inside of our virtual machine here. So we're just going to open the terminal, go to the desktop, and do Notepad Simple PDF, and it will open it in text format, and it will be able to recognize the PDF structure and the components as we can see right here. So you can see that if it's opened inside of a text editor instead of being opened inside of a PDF reader like Adobe Acrobat, it looks very different than what it would look like if you actually opened it up inside the PDF, meaning you can actually see PDF version up here, you can see the object, and you can see another object, so on and so forth. And so we can see that there's a catalog object here, and then we have another one that actually has an author, creator, creation date, etc. So we want to find the author of the simple PDF document. So I'm just going to open up my terminal. This is like a really interesting version of Linux here. And what I want to do is I want to find the PDF document. So where is it? It would be inside the desktop, I think they said. So if we're going to go here, there you go, simple PDF. So we'll do Notepad, and then we'll do simple PDF. And then it'll open it up in the Notepad. There you go. So this is, we can see the structure, and the author here is Ben. So we're looking for the author of the simple PDF document, and that would be Ben. All right, cool. So let's do the analysis. Now we can understand what the structure is, right? So we have the PDF structure. Now we're going to do some analysis. When we want to analyze a PDF document, we could do it using a variety of different tools. So one of the simple ones that we just saw was the Notepad version, right? So we just did Notepad, gave it the name of the PDF, and then it opened it for us, and then we can analyze its contents. And this is kind of the least sophisticated way, because we have to manually sift and sort through this to try to find what we want. If we examine it, we can get PDF version, author name, objects, keywords like JavaScript, encode, action. We can find the trailer. And similar kind of information is obtained using the strings command to extract the strings from the document. But then there are tools, right? So there's PDF id.py. So this is a Python script used to summarize the objects or keywords found within the document. So objects 18, stream 3, JavaScript, what is it, 1 and 2, I guess. So there's JS and there's JavaScript. So 1, 2. Open action is 1, etc. So objects, this document contains 18 objects. It contains 3 streams. It contains 1 JavaScript and 1 JS instance. So I wonder if that would count as 2 technically. Open action indicates that an action will be performed when the document is open. So it could be running a JavaScript or downloading a payload. Therefore, the object is worth examining. Then we have the PDF parser Python script, and it's used to parse the PDF, search objects, filter, etc. So you can look at the help menu, just like many other things inside of Linux or even Windows. If you're inside the command line, you can always either do -H or you can do --help, and it'll pull up the help menu, as you can see right here. So getting the version, filters, etc. So the command simple PDF, just combined with the PDF parser Python, it will bring the information up for you, right? So we have there's an actual comment here. We have object 1, the object action is what it is right here, object 7, and then object actions essentially. So the tool returns all the objects it finds with the PDF document. We can look at the search option to return only the objects that contain open action. So you do PDF parser Python, PDF parser.py, excuse me, and then you do search, and then you do open action as the keyword that you're looking for, and then you give it the file name, and then it only pulls the objects that actually have open action in them. So for example, object 1, we saw that it had open action, but now we're only pulling the one that actually has open action. So it shows object 1, and it includes open action, which is referring to object 6. So that's the other piece, right? So then we can use the object option to retrieve object 6. So PDF parser object 6, simple PDF, right? And then it pulls object 6 for us. And now we can see that there's the JavaScript reference. So there's an action here, and it's a JavaScript reference. And then there's this whole instance ID right here. So that's the last 2 results that conclude when the PDF form document is open, the open action will be triggered, resulting in the execution of the JavaScript code. And the JavaScript code is what we found right here. So we can also search for JavaScript as the search key term, and then it will of course pull up the element for us that has the JavaScript, and then it feels like it's an encoded version of the code. So that's the one that only object that points to an actual JavaScript code. Then we have PBDF, or what am I saying? PEEPDF. Maybe that's probably the way that we can pronounce it. I looked at it as PPDF, but it's probably PEEPDF. It's another analysis tool used to determine if any malicious element in the document. It also has an interactive option to interact with these objects. So we can use PEEPDF, simple PDF, to retrieve important information. For example, the hash values, right? These are very, very crucial a lot of times, because you can actually search for hash values on VirusTotal to see if it's malicious. The number of streams that we have here. We have the open action element that's inside of here as well. So it says suspicious elements. There's an open action element. JavaScript right here. Now this one actually has, I think it says 6. No, it should say 1. So I think the stuff inside the parentheses is the number of open action calls, and then the stuff inside the square brackets is the name of the object or the number of the object. So you can see right here. So objects, and it goes through 18, and then open action is inside the first object, JS and JavaScript are inside the 6th object, so on and so forth, right? We can see the interactive interface using peepdf-i, which will give us an interactive interface, and then you can do help command and you'll get things like that, right? So peepdf-i simple PDF, and then it'll open up a new command line. You can see ppdf right here, and then you can do help, and it'll give you a bunch of different things that you can actually pull. So some of the things, like for example, using object and then doing object 6, which will actually pull the information. So for example, we need one of the answers that we need is the flag value here. So we can actually pull the object 6 value and then get that, right? So there you go, you see it right here. We can also extract JS to view the JavaScript code, and the extract URI option can be used to extract URLs within the document. So we can do extract, and then it'll do usage extract URI or JS version. So then you can do extract JS, and then it'll go ahead and extract it. And again, that's the flag that's inside of the app alert JavaScript line, right? So we're able to look at the PDF and extract indicators of compromise from it, and we're going to look at a more complex JavaScript and see how to extract IOCs from the embedded JavaScript. So now we need to get that flag that's inside the JavaScript code. How many open action objects were found within the document? What is it? I think it was 1, right? Right? How many encoded objects were found in the document? That's also a really good idea. So let's see if we can actually find the encoded objects that are here. Let me see if I could see it here. Objects 18, technically. I don't know if it's actually encoded objects. Let's see. Is it encoded objects? Is 18? No. It's actually a single digit number. And what are the numbers of the encoded objects? Separate with a comma. So let's see if it's inside of these screenshots. If not, I mean, no big deal, because we could literally just go ahead and run them. And I will just go ahead and do peepdf and do it in interactive mode, because I also need to get the flag in here. And then from there, we'll be able to get our encoded documents as well. So let's go ahead here. I'm just going to close the text editor here, and we'll go to our screen right here. So we'll do peepdf like that. We'll do -i, and then we'll do simple PDF. And then it should open inside of the interactive format of this piece right here. Let me see if anything else is going to open. There you go. Okay, great. So now it opened. It actually gives us the hash value, right? Size, version, binary, objects are 18, streams are 3, URIs, comments, errors, nothing like that. Catalog 1, info 7, objects 18, streams 3, encoded 2. There we go. So we see the encoded value right there that we can actually pull. So encoded, boom. And then what are the numbers of the encoded objects? That's actually very good too. So 15 and 18 are the numbers of the encoded objects. So we'll go ahead and input that over here. Great. So now finally we need to get the JavaScript code. So that can be done with a few different things. So I can just do extract JS, for example. And since I'm inside of an interactive menu, I can just literally type extract JS, and that'll bring it up, and there it is. So luckily, this isn't harmful. That's what the code says. So Control C usually copies it, but I think I just closed out of it. Yeah, so that's not what I was intending to do. So right click and copy is what I wanted to do. All right, there we go. Now we can paste it. No way. Why can't I copy and paste? That's insane. Okay, so I can't copy paste for whatever reason. So luckily, this isn't harmful. That is the flag. Cool. Let's go to analyzing malicious JavaScript. Now we have a scenario. So there is a malicious PDF document. A junior SOC analyst has extracted the embedded JavaScript and handed it over to you to have a detailed look at the code. And as a SOC level 2 analyst, we need to examine the JavaScript code, deobfuscate if possible, and extract the indicators of compromise. So in the remnux JavaScript code directory, there's a code in a text editor using that's basically it. We're going to open it, and this is what we see right here. So this is the JavaScript code. It does not necessarily look malicious, I guess. We have remarkable library pool manner, growing slightly, gas outside, share page window. So that sounds like a piece of code. Inflation creation, derived behavior. That's also a piece of code. What else do we have? Feed, bus, commercial, bother. That's also a piece of code. So these things, it's complex and time consuming, contains randomly generated variable names which don't make any sense, contains obfuscated code that needs to be de-obfuscated. So Box.js is the tool that we're going to be using to de-obfuscate this thing. So Box.js, embedded code.js. That's basically it. And then it's going to de-obfuscate. It's going to pull things for us, right? So we can see that there's a bunch of GET requests, and all of the indicators of compromise are saying that it fetched a URL, right? And so, you know, the WP admin is a WordPress link that takes you to the admin of the WordPress website. There's the uploads, there's the files, app, etc. So a controlled environment returns all the IOCs. It creates a subfolder that contains useful files like what we see right here. So we actually have the results of the analysis that we have. And then inside of it, so if we do the ls al to show us everything, including the permissions to it, we can see that there's actually a new file, it seems to be, that is available inside of the results, because this is a directory. And inside of the results, there is another JSON file that I guess is probably important for us to use. So what's the name of the dumped file that contains information about URLs? I'm going to take a guess. And I'm going to say it's urls.json. And this is probably what they blurred out for us, but that was just so easy. How many URLs were extracted from the JavaScript? What is the full URL, which contains the keyword slideshow? And we need to defang it using CyberChef. And that's basically it. So how many URLs were extracted? And let me see. So it says 10 seconds, specify another timeout. It doesn't say how many unless we actually run it. So let's go ahead and run the thing. So Box.js is the name of the tool that we're going to end up using. So I'm going to kind of zoom in on this a little bit. Let's clear the screen. And we want to go to not this location. We want to go to the, what is it, JavaScript code? I think that's what it was, right? So what's my working directory? Remnux. Yeah, so I'm going to go to JavaScript code and embedded code.js. I think that's what it was, right? Is that where it's located? Yeah, embedded code.js. Okay, that's what we want. So then we are going to do box-js, and then we're going to do embedded code.js, and then we're going to press enter. And then it's going to pull the information. It's going to create a directory that holds all of the URLs for us. And then we're going to try to see how many URLs are extracted. So now I can see that there is the results. So I will do embedded, cd embedded code.js embedded. There we go. Results. And then now we have the URLs. There we go. So urls.json. So let's see if I can just do a cat of this and see what's inside of it. And there it is. So there isn't too many. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That seems to be the count here. So there we go. 9 is the answer. And what's the full URL of the keyword slideshow inside of it? So we got slideshow, and then we want this full URL right here. Hopefully I can actually copy this and paste it. Let's see if this will allow me to paste it. It still doesn't allow me to paste. That's pretty annoying. So what if we do this, do copy link? Let's see if we can do that. It still doesn't allow. That is obnoxious that I can't copy this thing. That's so freaking annoying. Why am I not allowed to copy it? Copy as HTML maybe? No. That is annoying. Okay, so manual typing it is. Okay, so I typed it onto into my note, and we need to go ahead and defang it now. And what did I just do here? There it is. So let's just delete that. So defanging a URL is actually very easy using a beautiful tool like CyberChef. So we're going to do defang URL as our recipe, and then we're just going to do that. And so there you go. It automatically goes and defangs it for us. So there we go. We got that. We're going to copy that. We're going to go over here and we're going to paste it here. And that is the defanged URL. Now, it says that this is not the answer. So I'm guessing, what? Am I missing the last? I think I'm missing the last / right there. So we'll do that as well. And then we'll copy that one. And let's see if that's the answer. It's not. What the hell? Okay, this is the final format of the answer. So as you can see, it's a little bit different from what we got from CyberChef, because CyberChef did put the square brackets around this section right here. And the rest of it pretty much is exactly the same as we got from CyberChef. It's just that initial square brackets have been removed, as you can see. The rest of it is pretty much identical, and that's it. So it's aristonbentrey.com, slideshow, etc., etc. And there we go. All right, cool. So now let's analyze Office documents. Word documents, also known as doc or docs extension files, are essentially created by Microsoft Word, or they're created by Google Docs. They typically have the doc or docs extension. They contain text, images, tables, charts, a bunch of other types of content. So there are two Word formats. There's the structured storage format. It's a binary format used by Microsoft Word versions 97 to 2003, and they have extensions of .doc, .ppt, XML, etc. And an Office Open XML format is XML, XML, used by Microsoft Word versions 2007 and later. It's actually a zipped file containing all related data within the document. We can unzip this to see the content just by replacing the extension with .zip before unzipping, and they have extensions as .docx, .docm, etc. So what makes these things malicious are the macros. It's like a very big piece that can be done. They're small VBA scripts that can be embedded in the Word document. They can be used to automate tasks, but they can also be used to execute malicious code. And malicious macros can be used to download and install malware on the user system. So the code essentially could be a GET request, for example, from some domain that the hacker controls, and then on that domain they have another file that can be downloaded, and then they can also use the macros to steal information or perform other malicious actions. So they could basically just put code inside of the macros of the document, and then from there whatever the code is would end up running, and then it would do whatever the actions are that the hacker wanted them to do. Embedded objects are objects that have actually been embedded into the document. So for example, an image or an audio video file or any type of other file that's actually been embedded into the document is considered an embedded object. And they can contain these objects that are designed to exploit vulnerabilities in the software used to open the file. Links, just like URLs, basically anything along those lines. Links to websites that host malware or phishing pages designed to steal credentials. Exploits, which is code that exploits vulnerabilities in the software that are used to open the file. They can be used to download and install malware on the system, gain unauthorized access, etc. Hidden content. So malicious Word documents can also contain hidden content that is not visible to the user but can be used to execute malicious code. That's also something that when I saw, I was like, that actually sounds really simple, but it's kind of powerful how effective it is. So analyzing a malicious doc. So we have suspicious.doc inside of our Word doc folder. TRID or TRID, TRID maybe, that might be the thing. I think it's TRID, so I'm just going to call it that. This is what it looks like. So TRID suspicious doc, we can see that it's a Microsoft document. We can see the older version potentially. Then there's the OLEID, so OLEID, used to extract basic information to gain an understanding of the structure. So this is what we can see right here. So the indicator, OLE format, application name, VBA macros, true, meaning that they actually do have macros in there. The document is suspicious. It's not encrypted. It does contain VBA macros, and it's a Word document. Then we have OL meta, OLE meta. And this is again what it looks like. So it actually gives us more details. So the code page, title, subject, the author, keywords, template, the creation time, the last saved time, creating application, the code page doc property, and then the values itself. So lines, paragraph, scale, crop, etc., etc., etc. So these are all key information. Creation and last save, the author's name, OLE time, the creation modification time of different stream objects that are present in the document. And these are the things that we can see right here. So these seem to be actually very, very important as well, because you can see the root information. What is it? There's macros, macro project, macros, VBA. All of those things are available. OL map that gives us details about the different sectors of the file, and you can see those here. OLEVBA, used for extracting the VBA objects that it finds within the file, and shares the summary of the suspicious elements that it finds. So we can see the VBA objects themselves. So macro disk document CLS, suspicious doc, this is the stream, new macro BAS, that's the stream, auto open, document open. Auto open itself has all of these things in here, and so we can see that there is PowerShell being launched, and then we have in a hidden window, so you don't actually get to see that it was launched. And then in the background, in the PowerShell, in the hidden PowerShell window, this whole thing is going to be ran. And so this looks like an encoded string. So it looks like a base64 encoded string, basically. It shows the macros found within the document. The summary of the elements are here. So we have auto open, we have a suspicious shell, we have the run, PowerShell executable. These are all indicators of compromise, essentially. So it contains code that will auto execute when the user opens the document. It contains suspicious base64 encoded strings, contains PowerShell code. Then we have the Python script for OL dump, I guess. It can be used to check if there are any macros embedded in the document. The MM, so uppercase M / lowercase m, will be mentioned against the object stream, indicating that the stream is a macro which needs to be checked. So we can see this right here, MM, this piece right here, uppercase M, lowercase m, on lines 7 and 8. We can see that right here. Or I guess objects 7 and 8 contain the macros that we need to investigate further. We can also use metadata or -m to display the information. So for example, the reference of the Python file, -M, suspicious doc, and then it'll give you again the author name, creation time, last save time, and various other data as well. We can use the -s, so for the object 7, using the -s to see what macro is enabled in the document. So we can see under, and then -v I guess would be for verbose. That's usually what it's like. And so again, we can see the string that is embedded inside of it, create object wscript.shell.run. So those things are all done. And then the basic 64 encoded string, which will execute when the document opens. So Viper Monkey is another one that can be used to analyze and emulate the behavior of the macros inside this document. We can run it and we can see these things right here. So suspicious document, starting emulation, traceback, and then we can see that what is it? No module, running export, all Excel, this document, OLV stream, this document. So it runs and emulates the embedded macro in an isolated environment, trying to extract IOCs and useful information. Okay, so this is kind of like a sandbox, essentially, that would run it in a controlled environment. And then we can see what it's trying to do, founding the possible URL right here, schemas, open XML formats, auto open, found possible intermediate IOC base64 PowerShell. That's the string right there. And another parameter for the PowerShell, which is this massive string right here. Okay, so very good. The URL it extracted is indeed a false positive. It also extracted PowerShell script that will execute. And we can use CyberChef to go ahead and look at the decoded version of it. So very, very important. It's now evident that the document will try to connect to the C2 server on port 4444 to access the malware called stage2exe. And we can use CyberChef to look at that the URL as well. And that's also very, very useful. So from a SOC analyst perspective, we will move on to creating a detection rule that outbound traffic to detect if any host has communicated to that server in the past or if there's any connection in the future. So very, very useful. So what is the author name of the document? How many macros are embedded in the document? What's the URL extracted from the suspicious doc file? And to be able to do that, I think I'm going to use the Viper Monkey, assuming that we actually have it on our Remnux machine. So I'm going to go inside of the Word doc location and I'm going to do vmonkey and I'm going to see if I can access it, right? It's vmonkey suspicious doc. Okay, so let's go ahead and kind of organize this piece a little bit. Okay, great. So now we can do clear. We will go back to, and then there should be a doc folder. Let's go back one more, excuse me. And then go back one more. And what do we have? Is it the OneNote? No, Word doc. So we're going to go into the Word doc location. And there we go. So vmonkey, right? vmonkey. My God. Spell that right. There we go. And then suspicious document. So let's see if we have, I hope we do actually, because it seems to be the best tool to be able to use. Okay, great. So there it is. And then it has the strings for us. Okay, great, awesome, very, very exciting. The issue that I have is that I can't seem to copy and paste any of these things, which is it's very inconvenient, and I can't do this without the copy paste element, because this is going to be impossible to type without copy paste. So that's the piece that I'm like, oh my God. So please, Lord, please let me be able to copy and paste this string right here, because I would be screwed if I wasn't able to do this. And let's see. Oh my God, please, 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 please. I wonder if I can access the internet inside of this thing. If it's connected to the internet, that might make it a little bit more useful, but if it's not connected to the internet, I am in trouble. Okay, so this is very useful. I don't know if it's connected to the internet or not, but there is a saved link right here from base64 that opens up CyberChef. So hopefully I can now paste it, but no, it didn't even save anything. It didn't copy anything. There you go. Okay, great. Okay, cool. So there we go. That's the thm.redteam.thm. And so that's the domain, right? So HTTP, yeah, that's the domain. So we're going to, hopefully now we can copy this. I feel like it's Remnux that just won't let me, oh, no, it's not, you see? So URL extracted from the suspicious file, it didn't let me copy it. So thmredteam.thm stage2.exe. That's the domain that we're gonna get. thmredteam.thm stage2.exe. Well, close enough. Okay, great. At least that worked. So how many macros are embedded in the document, and what's the author name of the document? So let's just minimize this real quick. And we need to find the author name, and we need to find the number of macros embedded in it. So let's see if we can find that here. Looking at the top of our results here, we have macro and then macro. So it seems that there are 2 macros. So I wonder if that is the answer. Great. And now the author name of the document. I couldn't find the author name inside of that output, but there is one of the other tools that we were able to use that gave us the author name. So it's not the, so let's see, which one is it? This is the olddump.py, and then getting the dash capital M. So let's see if I can just reference olddump.py like that, dash capital M, and then do suspicious doc, and then let's see if it'll run, and it did. Okay, great. The author is CMNatic, which I think is one of the creators of this room, right? Is that? Yeah, it is. It's CMNatic, the creator of the room. Okay. All right, CMNatic, I see you. Cool. There we go. Now we're going to go through OneNote. As we mentioned earlier, this is a note-taking tool that can be used in collaboration with other people, and it's a part of Microsoft's suite of tools. and allows the user to create and organize digital notebooks containing various types of content like text, images, audio recordings, etc. And it ends with a .1 or .OneNote extension. So we can look at the various entities. So for example, Malware Bazaar, and we can look through their database to see what different APT groups have actually started using OneNote documents in their campaigns. And so if we actually go to Malware Bazaar and we just search for file type 1 to display all the OneNote documents, and then you can see a bunch of entries, right? You see the SHA-256 hash values, the file type, signature, metastealer, tags, etc., the reporter or the person, the entity, the computer, not the computer, the company that reported it. So we're going to use one of the documents to practice analyzing and see if we can extract some obfuscated code. And it's inside of course, the OneNote docs where we can see invoice.1. And we can use TRID to look at it. As we can see, it's a Microsoft OneNote. We can pull strings and look at the top 20 strings as we can see. And you can see iec.ch show up a few times. There's an ID of something that seems to be coded here. Some references to some suspicious domains and some embedded code. And another utility, OneDump, to get the objects inside the document. So Python 3 OneDump-H. And this is what we can see here for the help menu for OneDump. And so if we do the invoice.1 just to kind of look at it, we can see that it has these elements here. So .png files, right? And so the document contains 6 objects. We can look at each object one by one. By the looks of it, we can confirm that objects 5 and 6 seem to have HTML files. And the S flag to select the 5th object to dump it onto the screen. So S flag select number 5 and then the invoice 1, and then you can see that this is the contents of it. And now we can see there's JavaScript in here, there is a variable hello, variable content, etc. So containing obfuscated JavaScript and VB script, we'll save it by using the command Python 3 and then -d invoice, and then just use this element right here, that kind of arrow that points to object 5, and open it in Notepad. And then this is what we can see again right here. And then you can also see these pieces right here, the right reg, and then we see variable body, variable function, and inside of the variable function there seems to be this right here. So it says body.replace this string, and then it's replacing it inside of this. All of these things is being replaced by that string, and then the registry delete is actually deleting that registry. So the code clearly uses a replace function to remove the string 5 and from the obfuscated. We'll use CyberChef to replace and clear the code. So we can do find and replace 5 and then we're going to replace what? I guess nothing. It seems to be it just seems to be that we're just going to find and replace it with nothing. And then there's going to be a global match, and then we're going to do generate code beautifully to actually organize the code for us so that we can see what the code is trying to do. It's placed on the desktop, as they say. The code makes more sense, and it contains some important IOCs, so we can see that the document contains 2 suspicious HTML objects, contains the obfuscated code and the cleared out by removing the 5 and. It's writing the obfuscated script to the registry, runs the script, C2 domain is this domain, downloads the payload using the curl command right here, and outputs it into index 1, sleeps for 15,000 milliseconds using sleep right here, runs the payload using the run DLL2 inside of shell right here, and then deletes the registry. So what's the value used in the sleep function? We have 15,000. The curl command is being used to download from a URL and is saving the payload in a PNG file. What is being saved inside the PNG? So this is what seems to be being saved, I think. Or no, actually it outputs the payload into this right here. So that's the PNG file that is being outputted. There we go. And how many objects are found in the invoice.document? And we saw that answer over here as well, because it said there are 6 objects. So I don't think I even need to run it. So maybe, let's see. Yeah, there you go. So I didn't even need to run the exercise manually. We see that they already did it for us and they pulled all the information for us. So that part, I mean, there's no other questions that we need to answer. So we're done. This was a cool room. I've always liked the idea of macros inside of documents. And so looking at malicious documents and what the various elements of the malicious documents are and how we can pull that data from them, and how everything falls under the object, and inside of the object you can embed these various codes, and of course you can base 64 encode something so it doesn't visually, you can't see what it's being said, but it still runs the code, which is very, very important to kind of wrap the head around. So obviously we looked at different document types, the PDF structure, how to perform static analysis on documents like PDF, Doc, and OneNote documents, and dynamic analysis on malicious documents, and deobfuscation for these various script codes will be covered in future videos. And you can always follow TryHackMe on Discord. I also have a Discord channel that's a part of the Hackaholics Anonymous community that it's literally $4.99 and you'll get lifetime access to it. So if you want to continue to be a supporter, it would be amazing if you just stayed a supporter, but technically just to add like really a lot of value for $4.99, you can become a member of the Discord community forever. You'll get lifetime access to it. So there's a bunch of other tiers of memberships that you'll find out in a little bit, and you'll find out what extra benefits those tiers of memberships get. But for the most part, that's all we got. And I hope you actually found value from this video. If you did indeed find value from this video and from this channel, I do encourage you to like, subscribe, and turn on that notification bell so that you get notified the next time that a video comes out on this channel, because there's a lot of videos coming out on this channel all the time. There's also the videos that already exist on the channel. If you have not checked them out, I would recommend you go check those out. So there's a few playlists that I'm working on right now. This is actually the very last episode so far of SOC Level 2, because TryHackMe has been known to add rooms later on, and they add more content to each individual playlist. So we may end up coming back and adding more videos to SOC Level 2, but as it stands, we are officially done with SOC Level 2. So the next playlist that we want to work on finishing is the CompTIA Pentest Plus, which is what you actually see right here. And the CompTIA Pentest Plus currently has 12 videos on it already. Every Friday, there's a new episode that comes out for that. I finished the Network Plus from CompTIA. I finished the Security Plus, Linux Plus, and a variety of other playlists. And these are like really robust playlists. A lot of people have used them to pass their certification exams. So that's something that I'm really excited about. It says 6 videos in here, but it's literally, I think, like probably 25-30 hours of content that's inside of each of these playlists. So they're very in-depth, they're comprehensive playlists. And the same thing is going to apply to the Pentest Plus. And then we're going to get into AI for cybersecurity, where you can integrate the API of AI with a variety of different security software so that you can create an agent, an automatic agent that will do a variety of things for you. We have the members only playlist for Hackaholics Anonymous that has the Python descriptions and the code by like line by line of code that we use to create Python scripts, so that you can go ahead and create your own scripts for either your own computer or for your job and things like that. And then there's SOC Level 1, SOC Level 2, security engineering. There's a lot of stuff, right? So you will never, I don't think you will run out of content when you join this channel. So if you're interested in cybersecurity, if you're interested in hacking, if you're interested in security analysis in general, or system administration in general, I really feel like you will get a lot of value out of this channel. So if you haven't done so already, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section, and that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video later.